Hi there, you're in the lab with your mate JJ. Today is New Book Teardown Day. Haven't done a new book teardown for a while, so thought I might do one of those. The particular book that we'll be looking at is this tome. This is called God Created the Integers, and it was edited with commentary by Stephen Hawking. This claims to be the new edition, so I'm not sure what other editions there were. This book was published in 2007, so since we call anything published since the year 2000 a new book, this meets our criteria as a new book, but none of the actual content of it is particularly new. It's actually just a collection of famous papers that Hawking has put together, all the way from Euclid through to Gödel and Turing. So it's how many pages? 1,355 pages. 1,300 pages. Wow. So, look, we're just going to have a look through this thing. It's going to take ages. This is... Hopefully you've got some time for a long video, because I think this is going to be a long video. But we'll pop over to the bench and we'll have a look at this thing. We'll have a look at the front and the back, and then we'll go through it and see what's on the inside. So let's do it. Here we are on the bench. Here's our book. God Created the Integers. The Mathematical Breakthroughs That Changed History. Edited with commentary by Stephen Hawking. New edition. Now includes selections from Euler, Bolyai, Lobachevsky, and Galois. Now, I'm suddenly reminded that I don't know how to pronounce any of these names, so I'm probably going to embarrass myself when I talk about these mathematicians, because I've only got book learning, and the books don't teach you how to pronounce the words. Alright. Obviously the quote of the book, oh, there we go, Leopold Kronecker. Okay. I didn't know that was him who said that, but the full quote is, God created the integers, all the rest is the work of man, by the 19th century mathematician Leopold Kronecker. So that's a really great quote, and that's what the title of the book is taken from. Best-selling author and physicist Stephen Hawking explores the masterpieces of mathematics through 31 landmark works spanning 2,500 years and representing 17 mathematicians. From the geometry of Euclid through to the calculus of Newton, the probabilities of Laplace to the thought of Boole, this extraordinary volume allows readers to peer into the mind of genius by providing them with excerpts from the original mathematical proofs and results. It also charts the progression of mathematical thought, granting the reader a solid understanding of the very foundations of some of our current technologies. Praise for On the Shoulders of Giants, the great works of physics and astronomy, edited with commentary by Stephen Hawking. Alright, so he obviously has some other book out there similar to this, except it's physics and astronomy papers that he's put together. I didn't know about that. I'll have to check it out. Might get myself a copy and we'll have a look at that one as well. Anyway, let's see how we go with this one first, huh? Now, the nice things that people had to say about his work, Publishers Weekly said, Hawking gives these works a setting that is elegantly simple and in its simplicity effectively broadening. And then this is from To the Letters, this year's Best Reads column. Neil Gladstone and Michelle McCready of the Newspaper Enterprise Association recommended On the Shoulders of Giants as a great gift for anyone enamored with scientific history. At 1,264 pages, this book is heavy in a lot of ways, but it's also an eminently authoritative and readable text for anyone with an interest in the universe around us. There you go. So his other book was 1,264 pages. This one got into 1,300. Fascinating. So you could get this for $30 in the USA or $37.50 in Canada. Published by Running Press. Printed in the USA. Cool. And this is not a hard-covered version. It's a soft copy. A paperback. Paperback, not a soft copy. That's different. Alright. So, Running Press, Philadelphia and London. As we said before, published 2007. Can you see that? I'm just going to check the video quality. I'll be back in a second. I'm back. So I just checked and it seems to be okay. So hopefully you can see the text as well as is possible. It seemed to be working okay on my check, so that's all good. Now, okay. So here we go. There's some notes. A note on the text. On the texts, plural. The texts in this book are based on translation of the original printed editions. We have made no attempt to modernize the author's own distinct usage, spelling, or punctuation, or to make the text consistent with each other in this regard, the editors. Text and picture credits. Text permissions. Selections from Euclid's Elements by Thomas L. Heath, courtesy of Dover Publications. Selections from The Works of Archimedes by Thomas L. Heath, courtesy of Dover Publications. By the way, Dover, they're a venerable publisher. I mean, they do some really high quality and high tech, just heavy duty stuff. Dover, yeah, they've done some really great stuff. Most of it's beyond my pay grade. So we won't go on reading all the credits. So obviously they've taken a lot of text and pictures from other volumes, which they've catalogued there. And as you can see, they come all the way through to Kurt Gödel and Alan Turing. Wow. And this is the table of contents, so we'll certainly flip through that. We'll look at that in detail in just a second. And then once we've gone through the contents, we'll go through the introduction. And then we'll be away, kicking off with Euclid at 325 BC. Wow. And then we'll be away. Then it's just chapter until we get to the end. I think there's a index. I don't know if there's any... appendices. I don't think there are. There's the index beginning on page 1327. Wow. Yeah, right. Okay. Well, let's go and have a look at the table of contents. Then we'll read the introduction and then we'll flip through the book. Okay, here we are. So the introduction is on page 13 in the Roman numerals part of the book, and then we're off. Euclid, circa 325 BC to 265 BC. His life and work. So his life and work. That section is from the editor. Stephen Hawking, presumably, and then there's his actual work. So, okay, great. So we're going to get an introduction to the life and work of our various mathematicians. Cool. And I do believe that this work is presented roughly in chronological order. So it starts with Euclid and it goes through to Gödel and Turing. Wow. All right, so we've got, looking at Euclid, we've got selections from Euclid's Elements, Book 1, Basic Geometry, Definitions, Postulates, Common Notions, and Proposition 47, leading up to the Pythagorean Theorem. Book 5, the Eudoxian Theory of Proportion, Definitions and Propositions. Book 7, Elementary Number Theory, Definitions and Propositions. Book 9, Proposition 20, the Infinitude of Prime Numbers. Book 9, Proposition 36, Even Perfect Numbers. And then Book 10, Commensurable and Incommensurable Magnitudes. Wow. And then we've got Archimedes, 287 BC to 212 BC. His life and work. Selections from the works of Archimedes. On the Sphere and Cylinder, books 1 and 2. Measurement of a Circle. The Sand Reckoner. The Methods. There you go. Archimedes. And then we've got Diophantus, circa 200 to 284. Okay. Selections from Diophantus of Alexandria, a study in the history of Greek algebra. Book 2, problems 8 to 35. Book 3, problems 5 to 21. Book 5, problems 1 to 29. René Descartes. Wow, we really skipped ahead a bit there, didn't we? So we had Euclid, BC, Archimedes, BC, and then we had Diophantus in the third century, 200 to 284, and then skip what, like, I don't know, 1,300 years to René Descartes. There you go. So René Descartes lived 1596 to 1650. His life and work. Then the geometry of René Descartes. Very interesting. So of course he gave us the Cartesian plane, didn't he? So perhaps that's got something to do with it. Isaac Newton, 1642 to 1727. His life and work. And then selections from Principia. I think that's how you pronounce it, Principia. But I don't know much about Latin. On first and last ratios of quantities. Wow. Okay. Then we've got Leonhard Euler, 1707 to 1783. His life and work. Then on the sums of series of reciprocals. De summis serium reciprocarum. I don't know how to pronounce all that Latin. The Seven Bridges of Königsberg. Proof that every integer is a sum of 4 squares. Okay, wow. And then we've got Pierre-Simon Laplace, 1749 to 1827, his life and work, and then a philosophical essay on probabilities. I think I've read this actually in a separate book. There you go. So Jean-Baptiste Joseph Fourier, or is it Fourier? Fourier? I should know. We call it the Fourier transform, so presumably that's the correct pronunciation. 1768 to 1830, his life and work. A selection from the Analytical Theory of Heat. Wow, that's cool. Chapter 3, Propagation of Heat in an Infinite Rectangular Solid. The Fourier series. Cool. Carl Friedrich Gauss, 1777 to 1855. His life and work. Selections from Disquisitiones Arithmeticae. Arithmetic Disquisitions. Section 3, Residues of Powers. Section 4, Congruences of the Second Degree. Okay. Augustin Louis Cauchy, 1789 to 1857. His life and work. Selections from Ove Completas de Augustin Cauchy. Resume des Lecons don... Oh, I really shouldn't. I don't know how to pronounce this. This is making me feel ignorant. Alright, so it's from Royal Polytechnique sur le calcul infinitesimal. I don't know what that means. Lessons, something to do with infinitesimal calculations. I don't know. Resume, I don't know. Lesson 3 to 4 on differential calculus. Okay. And lesson 21 to 24 on the integral. Okay. And then we've got Nikolai Ivanovich Lobachevsky, 1792 to 1856, his life and work. Geometrical researches on the theory of parallels. Okay. And then Janos Bollier, I don't know how to pronounce these names, 1802 to 1860. Gee, he didn't live long, did he? 58. His life and work. The Science of Absolute Space. Whoa, gee, that sounds cool. Wow. Okay. Évariste Galois. Okay. 1811 to 1832. That almost can't be right. Wow, he didn't live long at all. 21 years. Wow. His life and work. That'll be interesting to read about his life and work. On the conditions that an equation be soluble by radicals of the primitive equations which are soluble by radicals, on groups and equations and abelian integrals. George Boole, 1815 to 1864, his life and work. An investigation of the laws of thought. Hey, that's cool. This book's great. I'm really looking forward to it. It's too bad I can't pronounce everything correctly. Bernard Ryman, 1826 to 1866. Gee, he didn't live long either, did he? 40 years. His life and work. On the representability of a function by means of a trigonometric series. And then they've got it in German. Do you think I could have a go? Über die Daltonbarkeit ein Function durch eine trigonometrische Reihe. Who knows? Germans are out there laughing at me. On the hypotheses which lie at the bases of geometry. Okay. Cool. And then on the number of prime numbers less than a given quantity. There you go. So those were all published in German by the looks of it. Now, here's a name that I don't know how to pronounce. So Karl Weierstrass, I don't know, 1815 to 1897. At least he had a good innings. He lived for much longer compared to the rest of the guys we've seen. So then we've got his life and work, and then we've got selected chapters on the theory of functions. Lecture given in Berlin in 1886 with the inaugural academic speech in Berlin 1857. Section 7, uniform continuity. And then we've got Richard Dedekind, 1831 to 1916, his life and work. And then essays on the theory of numbers. Wow. Then we've got George Cantor, 1848 to 1818, his life and work. And then selections from contributions to the founding of the theory of transfinite numbers, articles 1 and 2. Oh, now here's a name I don't know how to pronounce. Henry Lebesgue, I don't know how to pronounce his name. 1875 to 1941, his life and work. And then we've got selections from integral longueur, integral length area, preliminaries and integral. Then we've got Kurt Gödel, 1906 to 1978, his life and work. And then on formally undecidable propositions of Principia Mathematica and related systems. And then we've got Alan Turing, 1912 to 1954, his life and work. And then On Computable Numbers, with an application to the Einstein's problem, Proceedings of the London Mathematical Society. Wonderful. All right. So we've got an introduction here. Presumably this is from the editor. And then we're straight into it with Euclid. So the introduction's not long at all, just 3 pages. So it begins with a quote from Richard Feynman, spoken in 1964. It says here, American physicist Richard Feynman. In case you didn't know, I think everyone knows Richard Feynman, don't they? Even I know Richard Feynman. Okay, introduction. We are lucky to live in an age in which we are still making discoveries. It is like the discovery of America. You only discover it once. The age in which we live is the age in which we are discovering the fundamental laws of nature. Isn't that cool? Spoken in 1964. So that's what, 40, 50, 60 years ago. 60 years ago. I don't know if they had any string theory theories back in 1964. Richard Feynman, of course, was a quantum physicist. He might be thoroughly unimpressed by string theory. I don't know. Showcasing excerpts from 31 of the most important works in the history of mathematics, 4 of which have been translated into English for the very first time. This book is a celebration of the mathematicians who helped move us forward in our understanding of the world and who paved the way for our current age of science and technology. Over the centuries, the efforts of these mathematicians have helped the human race to achieve great insight into nature, such as the realization that the Earth is round, that the same force that causes an apple to fall here on Earth is also responsible for the motions of the heavenly bodies, that space is finite and not eternal, that time and space are intertwined and warped by matter and energy, and that the future can only be determined probabilistically. Such revolutions in the way we perceive the world have always gone hand in hand with revolutions in mathematical thought. Isaac Newton could never have formulated his laws without the analytic geometry of René Descartes and Newton's own invention of calculus. It is hard to imagine the development of either electrodynamics or quantum theory without the methods of Jean-Baptiste Joseph Fourier, or the work on calculus and the theory of complex functions pioneered by Carl Friedrich Gauss and Augustin Louis Cauchy. And it was Henry Lebesgue's work on the theory of measure that enabled John von Neumann to formulate the rigorous understanding of quantum theory that we have today. Albert Einstein could not have completed his general theory of relativity had it not been for the geometric ideas of Bernard Riemann. And practically all of modern science would be far less potent, if it existed at all, without the concepts of probability and statistics pioneered by Pierre-Simon Laplace. All through the ages, no intellectual endeavour has been more important to those studying physical sciences than has the field of mathematics. But mathematics is more than a tool and language for science. It is also an end in itself, and as such, it has, over the centuries, affected our worldview in its own right. Karl Weierstrass provided a new idea of what it means for a function to be continuous, and George Cantor's work revolutionized people's idea of infinity. George Boole's laws of thought revealed logic as a system of processes subject to laws identical to the laws of algebra, thus eliminating the very nature of thought and eventually enabling to some degree its mechanization. That is modern digital computing. Alan Turing eliminated the power and the limits of digital computing long before sophisticated computations were even possible. Kurt Gödel proved a theorem troubling so many philosophers, as well as troubling too many philosophers, as well as anyone else believing in absolute truth, that in any sufficiently complex logical system, such as arithmetic, there must exist statements that can neither be proven nor disproven. And if that weren't bad enough, he also showed that the question of whether the system itself is logically consistent cannot be proven within the system. This fascinating volume presents all these and other groundbreaking developments, the central ideas in 25 centuries of mathematics, employing the original texts to trace the evolution and sometimes revolution in mathematical thinking from its beginnings to today. Though the first work presented here is that of Euclid, circa 300 BC, the Egyptians and Babylonians had developed an impressive ability to perform mathematical calculations as early as 3500 BC. The Egyptians employed this skill to build the Great Pyramids and to accomplish other impressive ends, but their computations lacked one quality considered essential to mathematics ever since: rigor. For example, the ancient Egyptians equated the area of a circle to the area of a square whose sides were 8/9 the diameter of the circle. This method amounts to employing a value of the mathematical constant pi that is equal to 256 divided by 81. In one sense, this is impressive. It is only about 1/2 of 1% off of the exact answer, but in another sense, it is completely wrong. Why worry about an error of 1/2 of 1%? Because the Egyptian approximation overlooks one of the deep and fundamental mathematical properties of the true number pi, that it cannot be written as any fraction. That is a matter of principle, unrelated to any issue of mere quantitative accuracy. Though the irrationality of pi wasn't proven until the late 18th century, the early Greeks did discover that numbers existed which could not be written as fractions, and this was both puzzling and shocking to them. This was the brilliance of the Greeks, to recognize the importance of principle plura in mathematics, and that in its essence mathematics is a subject in which one begins with a set of concepts and rules and then rigorously works out their precise consequences. Euclid detailed the Greek understanding of geometry in his Elements in Alexandria about 300 BC. In the ensuing centuries, the Greeks made great strides in both algebra and geometry. Archimedes, the greatest mathematician of antiquity, studied the properties of geometric shapes and created ingenious methods of finding areas and volumes and new approximations for pi. Another Alexandrian, Diophantus, looking over the clutter of words and numbers in algebraic problems, saw that an abstraction could be a great simplification, and so Diophantus took the first step towards reducing symbolism into algebra. Over a millennium later, Frenchman René Descartes united the two fields, geometry and algebra, with his creation of analytic geometry. His work paved the way for Isaac Newton to invent calculus, and with it, a new way of doing science. Since Newton's day, the pace of mathematical innovation has been almost frenetic, as the fundamental mathematical fields of algebra, geometry, and calculus, or function theory, have fed on and in turn nourished one another, yielding insights into applications as diverse as probability, numbers, and the theory of heat. And as mathematics matured, so did the range of questions it addresses. Kurt Gödel and Alan Turing, the last two thinkers represented in this volume, address perhaps the deepest issue, the question of what is knowable. Like those of the past, future developments in mathematics are sure to affect, directly or indirectly, our ways of living and thinking. Pardon me. The wonders of the ancient world were... Sorry, I've lost my place. Excuse me for a second. And as mathematics matured, so did the range of questions it addresses. Kurt Gödel and Alan Turing, the last two thinkers represented in this volume, address perhaps the deepest issue, the question of what is knowable. Like those of the past, future developments in mathematics are sure to affect, directly or indirectly, our ways of living and thinking. The wonders of the ancient world were physical, like the pyramids in Egypt. As this volume illustrates, the greatest wonder of the modern world is our own understanding. Alright, so here we go. Page 1, Euclid, circa 325 BC to 265 BC. His life and work. With the possible exception of Isaac Newton, Euclid is the best known mathematician of all time. Until sometime in the 20th century, his one and only surviving work, The Elements, was the second best-selling book of all time, surpassed only by the Bible. Yet there is no reason to believe that Euclid was anything other than a compiler of the mathematics known in his times, akin to Noah Webster, the great 19th century lexicographer who gave his name to the leading American dictionary. There is very little known about Euclid. He taught at an academy in Alexandria, the Hellenic city that Alexander the Great founded at the mouth of the Nile in Egypt. Because of his work as a compiler, Euclid was familiar with all of the Greek mathematics that had preceded him, and especially familiar with the first crisis in mathematics, the crisis of the irrational. Pythagoras died circa 475 BC, is a mysterious figure from early Greek mathematics. If we know little of Euclid, we know even less of Pythagoras. We do, however, know something about the Pythagorean school. The Pythagoreans thought that the whole of the cosmos could be described in terms of the whole numbers, 1, 2, 3, etc. As Aristotle wrote, the Pythagoreans have been brought up in the study of mathematics, thought that things are numbers, and that the whole cosmos is a scale and a number. The Pythagorean theorem, presented in this chapter, demonstrated this. Small whole numbers like 3, 4, and 5 could be found that not only describe the lengths of a right triangle, but also had the property that when the areas of the squares erected on the two smaller sides were added together, they equaled the area of the square erected on the longer side, the hypotenuse, the side opposite the right angle. Notice how the ancient Greeks phrased the Pythagorean theorem in terms of geometric objects and not in terms of numbers. Then someone asked an interesting question. If there were, I know this one. This is great. Okay. Then someone asked an interesting question. If there were a square with each side a unit in length and a second square with double the area of the first square, how would the side of the second square compare to the side of the first square? This was how the question of the square root of 2 was originally proposed. The ancient Egyptians found a good approximation to the answer. The side of the second square was the side of the second square was to the side of the first square, almost as 7 is to 5. This should certainly be no surprise to us, since we know 7 on 5 can be expressed as 1.4, which is very close to what we know to be the decimal expansion of root 2. But close wasn't good enough for the Pythagoreans. After all, the Pythagorean theorem didn't assert that the areas of squares were close to being equal. It asserted that they were, in fact, equal. Then, someone whose name we don't know hit upon a deep insight. Suppose that the square root of 2 can be expressed as the ratio of two whole numbers, and that these two whole numbers share no common divisors except 1, their common unit. Call these whole numbers p and q, with the property that the square p erected on a side of length p is exactly twice the area of a square q erected on a side of length q. Now, if p contains twice the number of units than q, then p must contain an even number of units. The Pythagoreans already knew that if a square contains an even number of units, the number of units the square contains must be a multiple of 4 units of area, and its side must contain an even number of whole units of length. Still, everyone knew how, given one square, you could find another one with fourth the area. Just erect a square on a side equal to half of that side. In this case, erect a square T whose side T is 1/2 of the side P. Because P contains an even number of whole units of length, the side T must still contain some number of whole units of length. But then, if the square T has 1/4 of the area of square P, the square Q must contain twice the number of units of area as the square T. So because the square T contains an even number of units of area, then, just like the square P, the square Q must also contain a multiple of 4 units of area. So its side Q has to contain an even number of units of length. So far, this mathematical argument has been like a tennis match, going back and forth between the players. Eventually, the argument reaches its climax. It began by supposing that the sides P and Q had no divisor in common except 1, and it ended up with a contradiction that they shared the divisor 2. Try as they might, the Pythagoreans could not find a flaw with the argument. Knowing that no one had in fact ever found a way to express the square root of 2 as the ratio of 2 whole numbers, the Pythagoreans faced up to the reality that they had proven that the square of 2 could not be expressed as the ratio of 2 whole numbers. Thus were born the irrational numbers, mathematical objects that could not be expressed by means of whole numbers, at least not for 2 millennia, the first of what Kronecker called the works of man. The Pythagoreans carefully guarded this great discovery because it created a crisis that reached to the very roots of their cosmology. When the Pythagoreans learned that one of their members had divulged the secret to someone outside their circle, they quickly made plans to throw the betrayer overboard and drown him while on the high seas. Whoever he was, this man was the first martyr for mathematics. The crisis of the irrational also instructed the ancient Greeks that they could not look at arithmetic to form the foundation for the rest of mathematics, and with it an explanation for the structure of the cosmos. They had to look elsewhere. They turned to geometry. Euclid's Elements is most remembered for its geometry, and especially remembered for its treatment of parallel lines in the definition of parallel lines. Parallel straight lines are straight lines which, being in the same plane and produced indefinitely in both directions, do not meet one another in either direction. And in the fifth postulate, the parallel postulate, that if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the straight lines, if produced indefinitely, meet on that side on which the angles are less than the 2 right angles. Fair enough. This is very different from the form in which it is often presented. Given a line and a point not on the line, it is possible to draw exactly one line through the given point parallel to the line. This is an equivalent but different form given by the Scottish mathematician John Playfair in 1795. During the height of the Newtonian era, philosophers such as Immanuel Kant never doubted the truth of Euclid's parallel postulate. They merely inquired about the nature of its truth. Was the parallel postulate necessarily true of the cosmos, or only contingently true? Of course, since the advent of the Einsteinian revolution, we know that parallel postulate isn't true at all about the cosmos. The Einsteinian spacetime cosmos that we inhabit is curved. Euclidean geometry and Newtonian physics are only approximations. So, we may ask, what did the Greeks think about the nature of the parallel postulate? I believe that a brief consideration of the ancient Greek conception of the world will explain that they too viewed the parallel postulate as a useful fiction rather than as a true description of the physical world. After all, the Greeks believed that we inhabited what the historian of science Alexander Koya, has called a closed world, a spherical cosmos in which there were no straight lines actually extending to infinity. Below the moon's orbits, bodies moved in straight lines neither towards the center of the Earth nor away from it. Above the moon's orbit, bodies orbited in perfect circles around the center of the Earth. In this cosmos, there weren't actually any straight lines at all. But the Greeks had a problem. They needed to find a foundation for their mathematics. The Pythagoreans had pursued arithmetic as a foundation and reached a crisis. Needing to find an alternative, another school descending from Thales. I don't know how to pronounce that. Give me a second. I'm back. So the correct pronunciation is Thales. Thales. I suppose I might as well look up the pronunciation for the other one as well. Hang on. Alright, I'm back, and I've looked up the pronunciation. So it's Alexander Poiré. Alexander Poiré has called the closed world spherical cosmos in which there was no straight lines, and then needing to find an alternative, another school descending from Thales. Thales. Yeah, Thales. Okay, Thales. So, needing to find an alternative, another school descending from Thales died circa 547 BC, sought to base mathematics on geometry. This school found that they could achieve very little without the parallel postulate. They couldn't prove the Pythagorean theorem, for example. In fact, they couldn't prove much geometry at all. This should come as no surprise to us moderns who have the benefit of 2,500 years of hindsight and know that the Pythagorean theorem is false in non-Euclidean geometries. I believe that the ancient Greeks knew that the parallel postulate was only a useful, no, let me say very useful, approximation. If the proof of the irrationality of the square root gave us the first crisis in mathematics, it also gave us the first example of the form of argument known since ancient times as reductio ad absurdum, reduction to absurdity. A second example of this form of argument can be seen in Euclid's proof, the infinitude of prime numbers, another proof that certainly originated with someone else. A prime number is a positive integer, such as 3 or 23, whose only positive integer divisors are 1 and itself. Proving the infinitude of prime numbers is stunningly simple. Suppose there is a largest prime number, p. Multiply all of the prime numbers up to and including p. Now add 1. The result is not divisible by p, nor is it divisible by any of the numbers less than p, because p and all of the prime numbers less than it evenly divides into their product before 1 is added to it. Suppose that there is a largest prime number. Supposing that there is a largest prime number leads to a contradiction. Reductio ad absurdum. The Greeks noticed that many prime numbers come together in pairs. 11 and 13, 17 and 19, 29 and 31, for example. These are called twin primes. Some have believes that the Greeks... I haven't heard that word before, hang on. Okay, so this says, some have believes. It must just be a typo, and they're talking about some have believed that the Greeks speculated that there were not only an infinitude of prime numbers, but also an infinitude of twin primes. But they weren't able to prove that, nor has any mathematician since. Neither has any mathematician been able to disprove the existence of an odd perfect number. A perfect number? That sounds quite odd indeed. What is a perfect number? A perfect number is the sum of its integer divisors greater than or equal to 1, but less than itself, what are called its proper divisors. The ancient Greeks found all of the even perfect numbers as follows. Notice that the sum of the powers of 2 from 1, which is 2 to the power of 0, to 2 to the power of n minus 1, is equal to 2 to the power of n minus 1. In a very simple case for n equals 3, 1 plus 2 plus 4 equals 7 equals 8 minus 1. Now let's do some simple arithmetic. 7 equals 1 plus 2 plus 4 is 2 to the 0 plus 2 to the 1 plus 2 to the 2. 7 equals 8 minus 1 equals 2 to the power of 3 minus 2 to the power of 0. 14 equals 16 minus 2 equals 2 to the power of 4 minus 2 to the power of 1. These columns all add up to 28. Writing that sum in yet another, we see that 28 equals 1 plus 2 plus 4 plus 7 plus 14 equals 2 to the power of 2, 2 to the power of 3 plus 2 to the power of 4 equals 2 to the power of 2 times 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 equals 2 to the power of 2 times 2 to the power of 3 minus 1. 28 is the sum of its divisors. Notice how these divisors are first all the powers of 2 up to a given exponent, then 1 less than the next power of 2. Call this the turning point divisor. And then the turning point divisor times all of the powers of 2 up to that given exponent. And notice that if 7 were not a prime number, then 28 would not be equal to the sum of its proper divisors. If the turning divisor had just one prime aliquot divisor, that would cause the sum of all the proper divisors to overflow. With these observations, the Greek had proven that if 2 to the power of n minus 1 is a prime number, then 2 to the power of n minus 1 times 2 to the power of n minus 1 is a perfect number, and that even perfect numbers must have this form. More than 2 millennia later, no one has ever discovered an odd perfect number. No mathematician believes that an odd perfect number exists, but none has been able to prove that no odd perfect number exists. The Pythagoreans tried and failed to found all of mathematics on arithmetic. Refounding mathematics on geometry meant founding arithmetic on geometry. Quick, which is larger, 7 over 5 or 10 over 7? That may be too easy for you. Try this one instead. Without a calculator, which is larger, 19 over 12 or 30 over 19? Try doing it just using multiplication and not division. The Euclidean theory of proportion, presented in Book 5 of Euclid's Elements, provides the tools, namely multiplication, for arriving at an answer. Following Eudoxus, who died circa 355 BC, Euclid posed the problem as follows. Consider 4 magnitudes of length, A, B, C, and D. How can one determine whether the ratio of A to B is greater than, less than, or equal to the ratio of C to D? Exodus began by asserting that magnitudes are said to have a ratio to one another which is capable when a multiple of either may exceed the other. He recognized that if the ratio of A to B is greater than the ratio of C to D, all multitudes of the ratio of A to B are greater than the same number of multitudes of the ratio C to D. Recognizing this fact, Eudoxus realized that all he had to do was to find one multiple to use, and he could solve the problem. The multiple he chose was the product of B and D. Multiply the ratio of A to B by the product of B to D, gave the ratio of the product of A, B, and D to B, or the area of the rectangle with sides of length A and D. Similarly, multiplying the ratio of C to D by the product of B and D gave the ratio of the product of C, B, and D to D, or the area of a rectangle with sides of C and B. Thus, the area of the rectangle with side A and D is greater than the area of the rectangle with sides of length C and B, if and only if the ratio of A to B is greater than the ratio of C to D. Whereas the Pythagoreans had tried to arithmetize geometry and failed, when Eudoxus tried to geometrize arithmetic, he succeeded. By the way, since 19 times 19 is greater than 30 times 12, 19 on 12 is greater than 30 on 19. Euclid is the greatest mathematician. Euclid is the greatest mathematical encyclopedist of all times. Today, when mathematicians from different specialities have difficulty understanding work at the frontiers of each other's speciality, no one mathematician could hope to edit a compendium of all known mathematics. Yet it remains an ideal in the mathematical community. In the second half of the 20th century, the French mathematical community offered a pale imitation of Euclid in the person of Nicolas Bourbaki. In fact, Nicolas Bourbaki wasn't even a person. He was the fictitious nom de plume of a collective of more than 20 French mathematicians working in diverse branches of mathematics. Euclid remains, to this day, our model for mathematical texts. Cool. Now here's selections from Euclid's Elements, Book 1. Basic Geometry, definitions, postulates, common notions, and proposition 47, leading up to the Pythagorean theorem. All right. Man, it's going to take us a long time to get through this book. I might have to do it one chapter at a time. I'm not sure. Wow. This looks like it's going to be pretty heavy. That's what's like 17 pages for Euclid. All right. Definitions. 1. A point is that which has no part. This is kind of old school, isn't it? It's already dated. Anyway, this is where we began. This is Euclid. Come on. All right. 1. A point is that which has no part. 2. A line is breadthless length. 3. The extremities of a line are points. 4. A straight line is a line which lies evenly with the points on itself. 5. A surface is that which has length and breadth only. 6. The extremities of a surface are lines. 7. A plane surface is a surface which lies evenly with the straight lines on itself. 8. A plane angle is the inclination to one another of two lines in a plane which meet one another and do not lie in a straight line. 9. And when the lines containing the angle are straight, the angle is called rectilineal. 10. When a straight line set up on a straight line makes the adjacent angles equal to one another, each of the equal angles is right, and the straight line standing on the other is called a perpendicular to that on which it stands. An obtuse angle is an angle greater than a right angle. 12. An acute angle is an angle less than a right angle. 13. A boundary is that which is an extremity of anything. 14. A figure is that which is contained by any boundary or boundaries. 15. A circle is a plane figure contained by one line such that all the straight lines falling upon it from one point among those lying within the figure are equal to one another. 16. And the point is called the center of the circle. 17. A diameter of the circle is any straight line drawn through the center and terminated in both directions by the circumference of the circle, and such a straight line also bisects the circle. 18. A semicircle is the figure contained by the diameter of the circumference cut off by it, and the center of the semicircle is the same as that of the circle. Okay. Then we'd go on rectilineal figures, trilateral, quadrilateral, multilateral, equilateral triangle, isosceles triangle, scalene triangle, right angled triangle, obtuse angled triangle, acute angled triangle, square, oblong, rhombus, rhomboid, trapezia. Parallel straight lines are straight lines which, being in the same plane and being produced indefinitely in both directions, do not meet one another in either direction. Okay, so what did he call those? Those were the definitions. Then there was some postulates, some common notions. Then proposition 47. In right-angled triangles, the square on the side subtending the right angle is equal to the squares on the sides containing the right angle. And there's a note here for 1. Okay. Oh, I see. These are translators' notes, and they've got some Greek here in the small print. So, right. Okay. So yeah, obviously, translation is tricky. Let's try and read this slowly, though. This is proposition 47. In right-angled triangles, the square on the side subtending the right angle is equal to the squares on the sides containing the right angle. That's Pythagoras' theorem. There you go. Oh, here we go. We've got a drawing of it over here. Very good. So, okay, cool. Okay. So basically they're going to go through and presumably they're going to prove Pythagoras' theorem. I'm not sure what's happened here. We've gone from this. Oh, there's QED. So that was the end of proposition 47. And on we go. So the print here got really small. If we listen, says Proclus, to those who wish to recount ancient history, we may find some of them referring this theorem to Pythagoras and saying that he sacrificed an ox in honor of his discovery. But for my part, while I admire those who first observed the truth of this theorem, I marvel more at the writer of the Elements, not only because he made it fast by a most lucid demonstration, but because he compelled assent to the still more general theorem by the irrefragable arguments of science in the 6th book. For in that book he proves generally that in right-angled triangles the figure on the side subtending the right angle is equal to the similar and similarly situated figures described on the sides about the right angle. I don't understand. It's just a bit out of context there. I don't know if it was the following on from these notes. I don't know. Did we want to go through the proof? Why not? I mean, we won't do all of them, but let's do the first one. This proposition 47, Pythagoras theorem. Let ABC be a right-angled triangle. And we've got a picture of it up there in the corner, if you can see. Having the angle BAC right. I say that the square on BC is equal to the squares on BA and AC. For let there be described on BC the square BDEC, BDEC, and on BA, AC, the squares GB, HC, through A, through A, let AL be drawn parallel to either BD or CE, and let AD, FC, okay, be joined. Then, since each of the angles BAC, BAG is right, it follows that with a straight line BA and at the point A on it, the two straight lines AC, AG, not lying on the same side, make the adjacent angles equal to two right angles. Therefore, CA is a straight line with AG. For the same reason, BA is also in a straight line with AH. And since the angle DBC is equal to the angle FBA, for each is right, let the angle ABC be added to each. Therefore, the whole angle DBA is equal to the whole angle FBC. And since DB is equal to BC, and FB to BA, the two sides AB and BD are equal to the two sides FB and BC respectively, and the angle ABD is equal to the angle FBC. Therefore, the base AD is equal to the base FC. And the triangle ABD is equal to the triangle FBC. Now, the parallelogram BL is double of the triangle ABD. for they have the same base BD and are in the same parallels BDAL. And the square GB is double of the triangle FBC. Now the parallelogram BL, did I already do that bit? Double of, they have the same and are in the same blah blah. And the square GB is double of the triangle FBC, for they have the same base FB, are in the same parallels FBGC. But the doubles of equals are equal to one another. Therefore, the parallelogram BL is also equal to the square GB. Similarly, if AE BK be joined, the parallelogram CL can also be proved equal to the square HC. Therefore, the whole square BDEC is equal to the two squares GBHC. And the square BDEC is described on BC, and the squares GBHC on BA and AC. Therefore, the square on the side BC is equal to the squares on the sides BA and AC. Yes, QED, baby. There you go. So that's the proof for Pythagoras' theorem from Euclid in his Proposition 47, a few hundred years BC. Probably not by him, probably from Pythagoras. Shall we read on a bit? The print seems to have got really small here. I don't quite understand why the font got smaller suddenly. I don't know. It starts in addition, but in addition to what exactly? I don't understand. Anyway, let's read it. Maybe it'll make it clear. In addition, Plutarch, Diogenes, Laterius, Athenaeus agree in attributing this proposition to Pythagoras. It is easy to point out, as does G. Jung, one haben die Gretchen das Irrationale, that these are late witnesses, and that the Greek literature which we possess belonging to the first 5 centuries after Pythagoras contains no statement specifying this or any other particular great geometrical discovery as due to him. Yet the distich of Apollodorus, the calculator, whose date, though it cannot be fixed, is at least earlier than that of Plutarch and presumably of Cicero, is quite definite as to the existence of one famous proposition discovered by Pythagoras, whatever it was. Nor does Cicero, in commenting apparently on the verses DNAT Door, page 3, C36, section 88, seem to dispute the fact that the geometrical discovery, but only the story of the sacrifice. Okay, so these seem to be all notes on the translation. Okay, so skipping ahead a bit here. On this assumption, how was Pythagoras led to this discovery? It has been suggested and commonly assumed that the Egyptians were aware that a triangle with its sides in the ratio 3:4:5 was right-angled. Cantor inferred this from the fact that this was precisely the triangle with which Pythagoras began. If we may accept the testimony of Vitruvius that Pythagoras taught how to make a right angle by means of 3 lengths, measured by the numbers 3, 4, 5. If then he took from the Egyptians the triangle 3, 4, 5, he presumably learnt its property from them also. Now the Egyptians must certainly be credited from a period at least as far back as 2000 BC with the knowledge that 4 squared plus 3 squared equals 5 squared. Cantor finds proof of this in a fragment. When they talk about Cantor, are they talking about George Cantor? I don't know. finds proof of this in a fragment of papyrus belonging to the time of the 12th dynasty newly discovered at Kahun. In this papyrus, we have extractions of square roots. For example, that of 16 is 4, that of 1 9/16 is 1 1/4, that of 6 1/4 is 2 1/2, and the following equations can be traced. Okay, it can be seen that 4 squared plus 3 squared equals 5 squared can be derived from each of these by multiplying or dividing out by one and the same factor. We may therefore admit that the Egyptians knew that 3 squared plus 4 squared equals 5 squared. But there seems to be no evidence that they knew that the triangle 3, 4, 5 is right-angled. Indeed, according to the latest authority, T. Eric Peat, the Rhind Mathematical Papyrus, 1923, nothing in Egyptian mathematics suggests the Egyptians were acquainted with this or any special cases of the Pythagorean theorem. How then did Pythagoras discover the general theorem? Observing that 3, 4, 5 was a right-angled triangle, while 3 squared plus 4 squared equals 5 squared, he was probably led to consider whether a similar relation was true of the sides of right-angled triangles other than the particular one. The simplest case, geometrically, is to investigate was that of the isosceles right-angled triangle, and the truth of the theorem in this particular case would easily appear from the mere construction of a figure. Cantor and Ullmann, Greek geometry from Thales to Euclid, illustrate by a figure in which the squares are drawn outwards, as in I-47. Okay. So this is just all about whether we can really... we're trying to figure out what Pythagoras actually did. Okay. Rational right-angled triangles from an arithmetical standpoint. Pythagoras investigated the arithmetical problem of finding rational numbers which could be made the sides of right-angled triangles, or of finding square numbers which are the sum of two squares, and herein we find the beginning of the indeterminate analysis which reached so high a stage of development in Diophantus. Fortunately, Proclus has preserved Pythagoras' method for solution in the following passage. Certain methods for the discovery of triangles of this kind are handed down, one of which they refer to Plato and another to Pythagoras. The latter starts from odd numbers, for it makes the odd number the smaller of the sides about the right angle. Then it takes the square of it, subtracts unity, and makes half the difference the greater of the sides about the right angle. Lastly, it adds unity to this, and so forms the remaining side, the hypotenuse. For example, taking 3, squaring it, and subtracting unity from the 9, the method makes half of the 8, namely 4. Then, adding unity to it again, it makes 5, and a right-angled triangle has been found, with one side 3, another 4, another 5. But the method of Plato argues from even numbers, for it takes the given even number and makes it one of the sides about the right angle. Then, bisecting this number and squaring the half, it adds unity to the square to form the hypotenuse, and subtracts unity from the square to form the other side about the right angle. For example, taking 4, blah, 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 blah. Okay. The theorem of Pythagoras in India. The question has been discussed anew in the last few years as the result of the publication of two important papers by Albert Burke on Das Apos blah 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 German 1901 and 1902. The first of the two papers contains the introduction and the text. The second, the translation with notes. A selection of the most important parts of the material was made and issued by G. Thibault in the Journal of the Asiatic Society of Bengal. Okay. The general effect of the criticism is, I think, to show the necessity for the greatest caution, to say the least, in accepting Burke's conclusions. I proceed to give a short summary of the portions of the contents of the document which are important to the present connection. It may be premised that the general object of the book is to show how to construct altars of certain shapes, and to vary the dimensions of altars without altering the form. It is a collection of rules for carrying out certain constructions. There are no proofs, the nearest approach to a proof being in the rule for obtaining the area of an isosceles trapezium, which is done by drawing a perpendicular from one extremity of the smaller of the two parallel sides to the greater, and then taking away the triangle, so cut off, and placing it the other side up adjacent to the other side equal to the blah 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 blah. Okay. Alternative proofs. So these are some other proofs of Pythagoras' theorem. The well-known proof of I-47, obtained by putting two squares side by side with their bases continuous and cutting off the right-angled triangles, which can be put on again in different positions, is attributed by Al-Nazizi. Okay. Around about 1000 AD. 802 to 901 AD. Okay. So this is Euclid's section, but it's obviously looking at the Pythagoras. This has nothing to do with Euclid. I'm a bit confused. Anyway. But it is all about the Pythagorean theorem. Okay. Okay. So that concludes our investigation of the Pythagorean theorem, and now we're on to the Eudoxian theory of proportion. Okay. Wow. I wasn't expecting this to go on so long as it does. Alright, so that's 25, it's like 37 pages. Wow. This is Book 5, The Eudoxian Theory of Proportion, Definitions and Propositions. Okay. A magnitude is a part of a magnitude, the less of the greater, when it measures the greater. The greater is a multiple of the less when it is measured by the less. A ratio, have a ratio, be in the same ratio, proportional, have a greater ratio, duplicate ratio, triplicate ratio, corresponding magnitudes. Alternate ratio, inverse ratio. My friends would get upset about this, alternate ratio, because they say alternate is actually a verb, alternate, and if you want the alternative ratio, that's what you should say. But I'm not going to die on that hill because that horse bolted a long time ago. Okay, we've got inverse ratio, we've got composition of a ratio, we've got separation of a ratio, conversion of a ratio. A ratio ex equali arises when, there being several magnitudes and another set equal to them in multitude, which taken 2 and 2 are in the same proportion as the first to the last among the first magnitudes, so is the first to the last among the second magnitudes. Ex equali. Or, in other words, it means taking the extreme terms by virtue of the removal of the intermediate terms. Perturbed proportion. Proposition 1. If there be any number of magnitudes whatever which are respectively equimultiples of any magnitudes equal in multitude, then whatever multiple one of the magnitudes is of one, that multiple also will be of all. Man. This is the history of careful thinking, isn't it? Proposition 3. If a first magnitude be the same multiple of a second that a third is of a fourth, and if equimultiples be taken of the first and third, then also ex equali the magnitudes taken will be equimultiples respectively, the one of the second and the other of the fourth. Man, I am not going to think that hard about this. Proposition 5. If a magnitude may be the same multiple of a magnitude that a part subtracted is of a part subtracted, the remainder will also be the same multiple of the remainder that the whole is of the whole. Wow. And then before we finish our Euclid section, we're looking at Book 7, Elementary Number Theory, Definitions and Propositions. So we've got a unit, a number, part, parts, multiple, even number, odd number, even times odd number, odd times odd number, prime to one another, composite number, composite to one another, multiply, plane, sides, solid sides, a square number, cube, proportional, similar plane, solid, perfect number. Okay, proposition 1. Two unequal numbers being set out and the less being continually subtracted in turn from the greater. If the number which is left over measures the one before it until a unit is left, the original numbers will be prime to one another. Proposition 7. If a number be that part of a number which a number subtracted is of a number subtracted, the remainder will also be the same part of the remainder that the whole is of the whole. For let the number AB be that part of the number CD which AE subtracted is CF subtracted. I say that the remainder EB is also the same part of the remainder FD, that the whole AB is of the whole CD. Well, dear me, I'm not going to think carefully about that. Wow. And on we go. Proposition 12. If there be as many numbers as we please in proportion, then, as one of the antecedents is to be one of the consequents, so are all the antecedents to all the consequents. Proposition 20. The least numbers of those which have the same ratio with them measure those which have the same ratio the same number of times, the greater and the less the less. Proposition 22. The least numbers of those which have the same ratio with them are prime to one another. Proposition 23. If two numbers be prime to one another, the number which measures the one of them will be prime to the remaining number. Prime numbers do my head in. They really do. And already in this book they mentioned there was a proof, didn't they? That the proof that reductio ad absurdum, that there can't be a greatest prime number. I'm going to go make coffee. I'll be back. I got myself a new coffee. I'm still in Euclid. This is still the first chapter and we're already up to page 86. Okay, proposition 26. If two numbers be prime to two numbers, both to each, their products will also be prime to one another. So we've been looking at primes as far back as Euclid. Interesting. There is something mysterious about the primes. The integers are such a regular idea, and primes are such an irregular phenomenon. It's quite bizarre. Oh, this is the fourth book from Euclid that we're going to look at, starting on page 101. This is book 9, The Infinitude of Prime Numbers, proposition 20. They discussed this earlier. Prime numbers are more than any assigned multitude of prime numbers. There you go. They gave that to us in simple language earlier. Book 9, Even Perfect Numbers, Proposition 36. If as many numbers as we please, beginning from an unit, be set out continuously in double proportion until the sum of all becomes prime, and if the sum multiplied into the last make some number, the product will be perfect. Book 10, Commensurable and Incommensurable Magnitudes. Definitions. 1. Those magnitudes are said to be commensurable, which are measured by the same measure, and those incommensurable, which cannot have any common measure. Commensurable in square, incommensurable in square, rational, irrational. Okay. Proposition 2. If, when the less of two unequal magnitudes is continually subtracted in turn from the greater, that which is left never measures the one before it, the magnitudes will be incommensurable. Proposition 4. Given three commensurable magnitudes, to find their greatest common measure. Proposition 5. Commensurable magnitudes have to one another the ratio which a number has to a number. Proposition 6. If two magnitudes have to one another the ratio which a number has to a number, the magnitudes will be commensurable. Alright, and that brings us to the end of Euclid. And we're up to Archimedes. There was Plato and Aristotle and Archimedes, I believe. There we go. Yeah, Archimedes. I think it was Archimedes who got stabbed by a Roman soldier. Anyway, it might say. Let's read what Hawking had to say about Archimedes. Archimedes lived 287 to 212 BC. His life and work. Archimedes is best remembered for jumping out of his bath and running naked through the streets shouting, "Eureka, Eureka, I have found it," when he discovered how to distinguish a genuine gold crown from a counterfeit crown. Less well known is that he devised a test to distinguish the greatest mathematician of antiquity, himself, from impostors. In the Greek world of mathematics, it was common for mathematicians to send out announcements of their newly discovered mathematical theorems without accompanying proofs. When Archimedes suspected others of claiming his results as their own, he inserted into his own announcements 2 or 3 propositions that required all of his mathematical talent to demonstrate to be false. When the impostors claimed the false statements as their own newly discovered truths, he exposed them by sending counterexamples. We know little of Archimedes' life. The Roman general Marcellus wrote that one of his soldiers killed Archimedes in 212 BC during the Second Punic War. There you go. So I was right about that. Isn't that awful? Some fucking dumb, soldier stabbed Archimedes. I wonder how much that set back humanity. Anyway. Tradition says that he worked at geometry until the very end of his life in his 75th year, which would place his birth in 287 BC. Archimedes' father was an astronomer named Phidias, who lived and worked in the Greek city of Syracuse, I don't know how to pronounce it, sorry, on the island of Sicily. Their family may have been related to the royal house of Syracuse. Archimedes was on intimate terms with King Hiram II. Although, like Euclid, we know very little of Archimedes' life, the comparison ends there. Although Euclid was a compiler who may have achieved few, if any, new mathematical results on his own, Archimedes was a pioneer, many centuries ahead of his time, in both mathematics and engineering. In fact, Archimedes was best known in antiquity for his engineering accomplishments on behalf of the royal house of Syracuse. When King Hiron challenged him to move a great weight from a small force, Archimedes conceived the idea of the compound pulley and showed how he could easily pull into shore a three-masted ship that 100 men could only pull in with much difficulty. According to the ancient Roman biographer Plutarch, it is in connection with this story that Archimedes uttered his famous remark, "Give me a place to stand on, and I will move the earth." Plutarch and other ancient commentators, such as Polybius and Livy, mention the fantastic ballistic war engines Archimedes devised for the defense of Syracuse against the Roman army led by General Marcellus. Plutarch wrote, "When Archimedes began to ply his engines, he at once shot against the land forces all sorts of missile weapons, and immense masses of stone that came down with incredible noise and violence, against which no man could stand, for they knocked down those upon whom they fell in heaps, breaking all their ranks and files. In the meantime, huge poles thrust out from the walls over the ships and sunk some by the great weights which they let down from on high upon them. Others they lifted up into the air by an iron hand or a beak like a crane's neck, and when they had drawn them up by the prow and set them on end upon the poop, they plunged them to the bottom of the sea, or else the ships, drawn by engines within and whirled about, were dashed against steep rocks that stood jutting out under the walls, with great destruction of the soldiers that were aboard them. The ship was frequently lifted up to a great height in the air, a dreadful thing to behold, and was rolled to and fro, and kept swinging, until the mariners were all thrown out, when at length it was dashed against the rocks, or let fall." Archimedes could completely immerse himself in a problem and stay unaware of his surroundings, as Plutarch wrote. Oftentimes Archimedes' servants got him against his will to the baths to wash and anoint him, and yet being there, he would ever be drawing out of the geometrical figures, even in the very embers of the chimney. And while they were anointing of him with oils and sweet savours, with his fingers he drew lines upon his naked body. So far was he taken from himself, and brought into ecstasy or trance, with the delight he had in the study of geometry. His habit of ignoring his surroundings would end up costing him his life. Archimedes' engineering accomplishments, building war engines, made him a prime target of the Roman army that invaded Sicily in 287 BC during the Second Punic War. Legend records that the Roman soldier found Archimedes drawing figures in the sand. The soldier commanded Archimedes to stop what he was doing and leave immediately. Archimedes asked for more time to work out a problem in the sand. Enraged, the soldier ruined Archimedes' figures in the sand and ran him through with his sword. Archimedes' mathematical works fall into three groups. 1. Those that prove theorems concerning areas and solids bounded by curves and surfaces. These include on the sphere and the circle, on the measurement of the circle, and the method. 2. Works that geometrically analyze problems in statistics and hydrostatics. It's not statistics, statics. Okay. Works that geometrically analyze problems in statics and hydrostatics. 3. Miscellaneous works, especially ones that emphasize counting, such as the Sand Reckoner. This volume includes the Sand Reckoner, on the sphere and the circle, on the measurement of the circle, and the method. The version of On the Measurement of the Circle, known to us, may be a far cry from the work written by Archimedes. It contains just 3 propositions, and the second one in order, which compares the area of a circle to a square on its diameter, depends on the third proposition, which states that the ratio of the circle's circumference to its diameter is greater than 3 1/7 but less than 3 10/71. A fairly good approximation of pi. It is the first proposition that holds the most interest for us. It states that the area of a circle is equal to the area of the right triangle, in which one of the sides about the right angle is equal to the radius and the other is equal to the circumference. Notice the interesting way in which Archimedes' statement of the theorem equates an area bounded by a curve, the circle, with an area bounded by straight lines, the right triangle. We moderns express the area of the circle as pi r squared. In modern notation, Archimedes would express it as half 2 pi r r. Yeah, right. When proving theorems about the area or volume of a figure bounded by curves or surfaces, Archimedes employs the method of exhaustion, sometimes called indirect passage to the limit, along with the eponymous Archimedes lemma. The lemma states, by the way, that word which I'm having trouble pronouncing, eponymous, it means named after the person. So the Archimedes lemma is named after Archimedes. That's why it's eponymous. But of course you knew that, and you probably know how to pronounce it as well, which makes me feel a bit silly. The lemma states, given two unequal lines, surfaces, or solids, the greater exceeds the lesser by an amount such that, when added to itself, it may exceed any assigned magnitude of the type of magnitudes compared with one another. Archimedes generally employs these tools in a reductio ad absurdum proof. Archimedes begins his proof by recognizing that if the circle A, B, C, A, I'm not seeing B, oh there it is, A, B, C, D, okay, is not equal to the right triangle K, whose legs are the radius and the circumference of the circle, then it must be larger or smaller than K. There you go. Okay. The first half of the proof supposes the area of the circle to be greater than the area of the right triangle K. He begins his proof by inscribing the square A, B, C, D inside the circle. He continues by bisecting the arcs AB, BC, CD, and DA, and then bisecting these halves again and again until the sides of the inscribed polygon, whose vertices are the points of the continued bisection, are so close to the circle that the area remaining between the circle and the inscribed polygon is less than the supposed difference between the areas of the circle and K. Therefore, he reasons, the area of the inscribed polygon must be greater than the area of K. He continues by considering the perpendicular ON from the center of the circle O to the side AE. Because AE is part of a polygon inscribed inside the circle, the segment ON must be less than the circle's radius, and the perimeter of the polygon must be less than the circle's circumference, the other side of the right triangle K. Therefore, the area of the inscribed polygon must be less than the area of the right triangle K, contrary to what has just been proven. The other half of the proof demonstrates that the area of the circle cannot be less than the area of K. Many of the theorems Archimedes proved had been stated and proved inadequately prior to him. However, he also discovered many remarkable new results. The method gives us a glimpse at how Archimedes discovered new theorems to be proven. In his preface to On the Sphere and the Cylinder, Archimedes wrote, "Since then, certain theorems not hitherto demonstrated have occurred to me, and I have worked out the proofs of them. They are these. First, that the surface of any sphere is 4 times its greatest circle, 4 pi r squared in modern terms. Now, these properties were all along naturally inherent in the figures referred to, but remained unknown to those who were before my time engaged in the study of geometry. Having, however, now discovered that the properties are true of these figures, I cannot feel any hesitation in setting them side by side, both with my former investigations and with those theorems of Eudoxus on solids, which are held to be most irrefragably established, namely, that any pyramid is 1/3 part of the cylinder which has the same base with the cone and equal height. For though these properties were naturally inherent in the figures all along, yet they were in fact unknown to all the many able geometers who lived before Eudoxus, and had not been observed by anyone. Now, however, it will be open to those who possess the requisite ability to examine these discoveries of mine." Nice one, Archimedes. The method has the most interesting history of all of Archimedes' known works. For many centuries, it was only known by an obscure reference made by the 10th century encyclopedist Suidas, who mentioned a commentary written by Theodosius of Bithynia about a century after Archimedes' death, mathematicians were tantalized by the prospect of finding a universal method for finding their results. Descartes, in fact, suspected Archimedes of suppressing the method so that no one else would be able to benefit from it. In 1899, the Greek scholar Papadopoulos Kerameus reported the discovery of a mathematical palimpsest. I don't know what that is. He had found in a library in Istanbul, Turkey. Palimpsest is an ancient document that has had its original contents washed off so that new contents could be written on it. Upon reading the few lines of the manuscript published by Kerameus, the Danish classic scholar John Ludvig Heiberg recognized characteristic Archimedean traits. He suspected that the underlying manuscript must be a work of Archimedes. Heiberg must have been amazed when he examined the palimpsest firsthand. Kerameus had found the long-lost treatise, The Method, which begins, Archimedes to Eratosthenes greeting. The presence of another Archimedean works in the palimpsest only confirmed its authorship. The Kerameus-Heiberg palimpsest was originally written in the 10th century. In the 13th century, a monk had washed away the original ink so that he could write a book of devotional prayers. Dear me. The monk must have had no idea of what he had washed away. Dear me. Nor could he have imagined the palimpsest's future value. In 1998, Christie's auction house sold it for $2 million. Archimedes' technique in The Method supposes that solids are composed of planar elements of uniform density. Okay. The volume of a given solid X can be discovered by placing it on an axis with one or two other figures, B and C. Archimedes supposes that all of the figures are cut by parallel lines, all perpendicular to the axis. He has chosen the figures B and C so that 1. Their centers of gravity and the centers of gravity of their planar elements all lie on the chosen axis. 2. Their volumes are known. 3. The planar elements of B can be compared to the planar elements of X, possibly together with C. The last requirement requires the investigator to discover figures B and C appropriate for computing the volume of X. Once Archimedes establishes the relationship between the corresponding planar elements, he produces the axis to a point tau so that the length tau phi is appropriate to the problem, another demand on the investigator's ingenuity, and it is taken to act as a lever about the function phi, the fulcrum phi. All right. Given the right lever, Archimedes could not only move the Earth, he could also discover new mathematical truths. Okay. So that was the life and work of Archimedes. I suppose we should finish reading this bit. We discussed all that. For each planar element X of X, and possibly C of C, if C is needed for the problem, he places a corresponding element Y of equal area so its center of gravity is at tau, so that Y acting at tau balances the corresponding planar element B acting where it is beta, that is YB equals phi beta to phi tau. For his next step, Archimedes takes the composition. Okay, blah, 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 blah. So I don't know why they went into all that detail in the life and times of Archimedes, life and work, but it did. Okay. The full title of this work, The Method of Archimedes' Treating of Mechanical Problems, underscores Archimedes' view that the proofs contained in the works did not qualify as mathematical proofs. The proofs in the method depend on physical assumptions about the figures involved and the principle of the lever, a mechanical principle. Given the right lever, Archimedes could not only move the Earth, he could also discover new mathematical truths. And this is this is the work of Archimedes called On the Sphere and Cylinder, Book 1. Archimedes to Diothesius greeting. On a former occasion, I sent you the investigations which I had up to that time completed, including the proofs, showing that any segment bounded by a straight line and a section of a right-angled cone, a parabola, is 4/3 of the triangle which has the same base with the segment and equal height. Since then, certain theorems not hitherto demonstrated have occurred to me, and I have worked out the proofs of them. They are these. First, that the surface of any sphere is 4 times its greatest circle. Next, that the surface of any segment of a sphere is equal to the circle whose radius is equal to the straight line drawn from the vertex of the segment to the circumference of the circle, which is the base of the segment, and further, that any cylinder having its base equal to the greatest circle of those in the sphere and height equal to the diameter of the sphere is itself, that is, a content half as large again as the sphere, and its surface, including its bases, is half as large again as the surface of the sphere. Now, these properties were all along naturally inherent in the figures referred to, but remained unknown to those who were before my time engaged in the study of geometry. Having, however, now discovered that the properties are true of these figures, I cannot feel any hesitation in setting them side by side, both with my former investigations and with those of the theorems of Eudoxus on solids, which are held to be most irrefragably established, namely, that any pyramid is 1/3 part of the prism, which has the same base with the pyramid and equal height, and that any cone is 1/3 part of the cylinder, which has the same base with the cone and equal height. For, though these properties also were naturally inherent in the figures all along, yet they were in fact unknown to all the many able geometers who lived before Eudoxus, and had not been observed by anyone. This is the same that they quoted earlier. Now, however, it will be open to those who possess the requisite ability to examine those discoveries of mine. They ought to have been published while Conan was still alive, for I should conceive that he would best have been able to grasp them and to pronounce upon them the appropriate verdict, but as I judge it well to communicate them to those who are conversant with mathematics, I send them to you with the proofs written out, which it will be open to mathematicians to examine. Farewell. Awesome. Then we've got some definitions. Concave in the same direction, concave in the same direction, solid sector, solid rhombus, assumptions. Proposition 1. If a polygon be circumscribed about a circle, the perimeter of the circumscribed polygon is greater than the perimeter of the circle. Okay. Proposition 2. Given two unequal magnitudes, it is possible to find two unequal straight lines such that the greater straight line has to the less a ratio less than the greater magnitude has to the less. And on we go with propositions and proofs from our mate Archimedes. Proposition 11. If a plane parallel to the axis of a right cylinder cut the cylinder, the part of the surface of the cylinder cut off by the plane is greater than the area of the parallelogram in which the plane cuts it. Wow. Proposition 20. If one of the two isosceles cones forming a rhombus be cut by a plane parallel to the base, and on the resulting circular section a cone be described having the same apex as the second cone, and if the resulting rhombus be taken from the whole rhombus, the remainder will be equal to the cone with the base equal to the surface of the portion of the cone between the parallel planes, and with height equal to the perpendicular drawn from the apex of the second cone to the side of the first cone. I think it's so cool that this stuff has reached us from antiquity. I mean, this is really old. So still more from Archimedes. On the Sphere and Cylinder, Book 2. So we've just finished Book 1, and this is Book 2. To the same person, Dositheus. I don't know who Dositheus is. It was someone that Archimedes was corresponding with, I guess. So, on a former occasion, you asked me to write out the proofs of the problems, the enunciations of which I had myself sent to Conan. In point of fact, they depend for the most part on the theorems of which I have already sent you the demonstrations, namely 1, that the surface of any sphere is 4 times the greatest circle in the sphere, 2, that the surface of any segment of a sphere is equal to a circle whose radius is equal to the straight line drawn from the vertex of the segment to the circumference of its base, 3, that the cylinder whose base is the greatest circle in any sphere and whose height is equal to the diameter of the sphere is itself in magnitude half as large again as the sphere, while its surface, including the 2 bases, is half as large again as the surface of the sphere, and 4, that any solid sector is equal to a cone whose base is the circle, which is equal to the surface of the segment of the sphere included in the sector, and whose height is equal to the radius of the sphere. Such then of the theorems and problems as depend on these theorems I have written out in the book which I send herewith, those which are discovered by means of a different sort of investigation, those namely which relate to spirals and the conoids, I will endeavour to send you soon. The first of the problems was as follows. Given a sphere, to find a plane area equal to the surface of the sphere. The solution of this is obvious from the theorems aforesaid. For 4 times the greatest circle in the sphere is both a plane area and equal to the surface of the sphere. The second problem was the following. Okay. Proposition 1. Given a cone or a cylinder, to find a sphere equal to the cone or to the cylinder. Here, presumably they're talking about volume. Proposition 4. To cut a given sphere by a plane so that the volumes of the segments are to one another in a given ratio. Oh. Proposition 6. Given 2 segments of spheres, to find a third segment of a sphere similar to one of the given segments and having its surface equal to that of the other. Measurement of a circle. Proposition 1. The area of any circle is equal to a right-angled triangle in which one of the sides about the right angle is equal to the radius and the other to the circumference of the circle. Didn't we see this earlier? The sand reckoner. So we're still we're 200 pages in and we've done Euclid and we're still in Archimedes. The sand reckoner. Might just pop that up a bit. How's that? There are some, King Gilon, I don't know how to pronounce Gilon. There are some, King Gilon, who think that the number of the sand is infinite in multitude. And I mean by the sand not only that which exists about Syracuse and the rest of Sicily, but also that which is found in every region, whether inhabited or uninhabited. Again, there are some who, without regarding it as infinite, yet think that no number has been named which is great enough to exceed its multitude. And it is clear that they who hold this view, if they imagined a mass made up of sand in other respects as large as the mass of the earth, including in it all the seas and the hollows of the earth, filled up to a height equal to that of the highest of the mountains, would be many times further still from recognizing that any number could be expressed which exceeded the multitude of the sand so taken. But I will try to show you by means of geometrical proofs, which you will be able to follow, that Of the numbers named by me and given in the work which I sent to Zeuxippus, some exceed not only the number of the mass of sand equal in magnitude to the earth filled up in the way described, but also that of a mass equal in magnitude to the universe. Now, you are aware that universe is the name given by most astronomers to the sphere whose center is the center of the earth and whose radius is equal to the straight line between the center of the sun and the center of the earth. Pardon me. This is the common account, as you have heard from astronomers. But Aristarchus of Samos brought out a book consisting of some hypotheses in which the premise led to the result that the universe is many times greater than now so called. His hypotheses are that the fixed stars and the sun remain unmoved, that the earth revolves about the sun in the circumference of a circle, the sun lying in the middle of the orbit, and that the sphere of the fixed stars situated about the same center as the sun is so great that the circle in which he supposes the earth to revolve bears such a proportion to the distance of the fixed stars as the center of the sphere bears to its surface. Now it is easy to see that this is impossible, for since the center of the sphere has no magnitude, we cannot conceive it to bear any ratio whatever to the surface of the sphere. We must, however, take Aristarchus to mean this: since we conceive the earth to be, as it were, the center of the universe, the ratio which the earth bears to what we describe as the universe is the same as the ratio which the sphere containing the circle in which he supposes the earth revolves bears to the sphere of the fixed stars. For he adapts the proof of his results to hypothesis of this kind, and in particular he appears to suppose the magnitude of the sphere in which he represents the earth as moving to be equal to what we call the universe. I say then that even if a sphere were made up of the sand as great as Aristarchus supposes the sphere of the fixed stars to be, I shall still prove that, if the numbers named in the principles and some exceed in multitude the number of the sand which is equal in magnitude to the sphere referred to, provided that the following assumptions be made. One, the perimeter of the earth is about 3 million stadia and not greater. It is true that some have tried, as you are of course aware, to prove that the said perimeter is about 300,000 stadia. But I go further, and putting the magnitude of the earth at 10 times the size that my predecessors thought it, I suppose its perimeter to be about 3 million stadia and not greater. 2. The diameter of the earth is greater than the diameter of the moon, and the diameter of the sun is greater than the diameter of the earth. In this assumption, I follow most of the earlier astronomers. The diameter of the sun is about 30 times the diameter of the moon and not greater. It is true that, of the earlier astronomers, Eudoxus declared it to be about 9 times as great, and Phaedius, my father, 12 times, while Aristarchus tried to prove that the diameter of the sun is greater than 18 times, but less than 20 times the diameter of the moon. But I go even further than Aristarchus, in order that the truth of my proposition may be established beyond dispute, and I suppose the diameter of the sun to be about 30 times that of the moon, and not greater. 4. The diameter of the sun is greater than the side of the chiliagon inscribed in the greatest circle in the sphere of the universe. I make this assumption because Aristarchus discovered that the sun appeared to be about 1/720th part of the circle of the zodiac, and I myself tried, by a method which I will now describe, to find experimentally the angle subtended by the sun and having its vertex at the eye. Up to this point, the treatise has literally has been literally translated because of the historical interest attaching to the Epistema Verba of Archimedes on such a subject. The rest of the work can now be more freely reproduced, and before proceeding to the mathematical contents of it, it is only necessary to remark that Archimedes next describes how he arrived at a higher and lower limit for the angle subtended by the sun. This he did by taking a long rod or ruler, fastening on the end of it a small cylinder or disc, pointing the rod in the direction of the sun after its rising, so that it was possible to look directly at it, then putting the cylinder at such a distance that it just concealed and just failed to conceal the sun. And lastly, measuring the angles subtended by the cylinder. He explains also the correction which he thought it necessary to make because the eye does not see from one point but from a certain area. Cool. The result of the experiment was to show that the angle subtended by the diameter of the sun was less than 1/164th part and greater than 1/200th part of a right angle. To prove that, on this assumption, the diameter of the sun is greater than the side of the chiliagon, or figure with 1,000 equal sides, inscribed in a great circle of the universe. So he's basically just trying to figure out how much sand there is in the universe. I don't know, does he count the sun and the moon and the earth, or what about the stars? I don't know. Orders and periods of numbers. 1. We have traditional names for numbers up to a myriad, which is 10,000. We can therefore express numbers up to a myriad, which is 100 million. Let these numbers be called numbers of the first order. Suppose the 100 million to be the unit of the second order, and the second order consists of numbers from that unit up to 100 million squared. Let this again be the unit of the third order of numbers, ending with 100 million cubed, and so on, until we reach the 1 millionth order of numbers, ending with 100 million to the power of 100 million, which we will call P. 2. Suppose the numbers from 1 to P just described to form the first period. Let P be the unit of the first order of the second period, and let this consist of the numbers from P up to 1 million P. Let the last number be the unit of the second order of the second period, and let this end with 100 million squared times P. We can go on in this way till we have reached the 100 millionth order of the second period, ending with 100 million to the power of 100 million P, or P squared. 3. Taking P squared as the unit of the first order of the third period, we proceed in the same way till we reach the 100 millionth order of the third period, ending with P cubed. 4. Taking P cubed as the unit of the first order of the fourth period, we continue the same process until we arrive at the 100 millionth order of the 100 millionth period, ending with P to the power of 100 million. This last number is expressed by Archimedes as a myriad units of the myriadth order of the myriadth period, which is easily seen to be 100 million times the product of 100 million to the power of 99,999,999 and P to the power of blah blah blah. Okay. The scheme of numbers thus described can be exhibited more clearly by means of indices as follows. Okay. The prodigious extent of this scheme will be appreciated when it is considered that the last number in the first period would be represented now by 1 followed by 800 million ciphers, while the last number of the 10 to the power of 8th period would require 100 million times as many ciphers. That is 80,000 millions of ciphers. Okay, I'm not sure why he's gone to the trouble of defining all that. Octads. Consider the series of terms in continued proportion, of which the first is 1 and the second 10, i.e. the geometrical procession 1, 10 to the 1, 10 to the 2, 10 to the 3. The first octad of these terms fall accordingly under the first order of the first period. The second under the second octad, Okay. So then he finally gets around to how those numbers apply to the sand. And then he says the results in the 8th order, 10 to the 7. Conclusion. I conceive that these things, King Gelon, will appear incredible to the great majority of people who have not studied mathematics, but that to those who are conversant therewith, and have given thought to the question of the distances and sizes of the earth, the sun, and the moon, and the whole universe, the proof will carry conviction. And it was for this reason that I thought the subject would be not inappropriate for your consideration. Archimedes, were you an ass kisser? It sounded like he was kissing ass, didn't it? Or maybe he was just being polite. The method of Archimedes' treating of mechanical problems to Eratosthenes. Archimedes to Eratosthenes greeting. I sent you on a former occasion some of the theorems discovered by me, merely writing out the enunciations and inviting you to discover the proofs, which at the moment I did not give. The enunciations of the theorems which I sent were as follows. 1. If in a right prism with a parallelogramic base a cylinder be inscribed which has its base in the opposite parallelograms, and its sides, that is 4 generators, on the remaining planes or faces of the prism, and if the center of the circle, which is the base of the cylinder, and through one side of the square in the plane opposite to it a plane be drawn, the plane so drawn will cut off from the cylinder a segment which is bounded by 2 planes, and the surface of the cylinder, one of the 2 planes being the plane which has been drawn, and the other the plane in which the base of the cylinder is, and the surface being that which is between the said planes, and the segment cut off from the cylinder is 1/6 part of the whole prism. Okay. 2. If in a cube a cylinder be inscribed which has its bases in the opposite parallelograms and touches with its surface the remaining 4 planes, faces, and if there also be inscribed in the same cube another cylinder which has its bases in other parallelograms and touches with its surface the remaining 4 planes or faces, then the figure bounded by the surfaces of the cylinders, which is within both cylinders, is 2/3 of the whole cube. Now these theorems differ in character from those communicated before, for we compared the figures then in question, conoids and spheroids and segments of them, in respect of size, with figures of cones and cylinders, but none of those figures have yet been found to be equal to a solid figure bounded by planes, whereas each of the present figures bounded by 2 planes and surfaces of cylinders is found to be equal to one of the solid figures which are bounded by planes. The proof then of these theorems I have written in this book and now send to you. Seeing moreover in you, as I say, an earnest student, a man of considerable eminence in philosophy, and an admirer of mathematical inquiry, I thought fit to write out for you and explain in detail in the same book the peculiarity of a certain method by which it will be possible for you to get a start to enable you to investigate some of the problems in mathematics by means of mechanics. This procedure is, I am persuaded, no less useful even for the proof of the theorems themselves, for certain things first become clear to me by a mechanical method, although they had to be demonstrated by geometry afterwards, because their investigation by the said method did not furnish an actual demonstration. But it is of course easier when we have previously acquired, by the method, some knowledge of the questions, to supply the proof than it is to find it without any previous knowledge. So Archimedes was an empiricist, wasn't he? I'm a bit of an empiricist. I'm also a hack. This is a reason why, in the case of the theorems, the proof of which Eudoxus was the first to discover, namely that the cone is a 1/3 part of the cylinder and the pyramid of the prism having the same base and equal height, we should give no small share of the credit to Democritus, who was the first to make the assertion with regard to the said figure, though he did not prove it. I am myself in the position of having first made the discovery of the theorem now to be published by the method indicated, and I deem it necessary to expound the method partly because I have already spoken of it, and I do not want to be thought to have uttered vain words, but equally because I am persuaded that it will be of no little service to mathematics, for I apprehend that some, either of my contemporaries or of my successors, will, by means of the method when once established, be able to discover other theorems in addition which have not yet occurred to me. First, then, I will set out the very theorem which became known to me by means of mechanics, namely that any segment of a circuit of a right angled cone, i.e. a parabola, is 4/3 of the triangle which has the same base and equal height. And after this, I will give each of the other theorems investigated by the same method. Then at the end of the book, I will give geometrical proofs of the propositions. I premise the following propositions, which I shall use in the course of the work. And on we go. Proposition 3. A cylinder with base equal to the greatest circle in a spheroid and height equal to the axis of the spheroid is 1.5 times the spheroid. It's so much fun that these guys were into this, hey? I mean, these guys were highly nerdy, weren't they? Good work, Archimedes. Proposition 5. The center of gravity of a segment of a right-angled conoid, i.e. a paraboloid of revolution, cut off by a plane at right angles to the axis on the straight line, which is the axis of the segment, and divides the said straight line in such a way that the proportion of it adjacent to the vertex is double of the remaining portion. This is the sort of stuff he was thinking about when that soldier stabbed him to death when he was 75. Proposition 8. The enunciation, the setting out, and a few words of the construction are missing. Oh, I see. The enunciation, however, can be supplied from that of Proposition 10, with which it must be identical except that it cannot refer to any segment, and the presumption, therefore, is that the proposition was enunciated with reference to one kind of segment only, that is, either a segment greater than the hemisphere or a segment less than a hemisphere. Heiberg's figure corresponds to the case of a segment greater than a hemisphere. The segment investigated is, of course, the segment BAD. That's great, segment BAD, bad. The setting out and construction are self-evident from the figure. Okay. Proposition 9. The center of gravity of any segment of a sphere is on the straight line which is the axis of the segment and divides this straight line in such a way that the part of it adjacent to the vertex of the segment has to the remaining part the ratio which the sum of the axis of the segment and 4 times the axis of the complementary segment has to the sum of the axis of the segment and double the axis of the complementary segment. It looks like they've got some parts that that weren't quite clear. Consequently, ... not greater ... It's cool that he tried to count all of the grains of sand. He talked about the perimeter, didn't he? Did they think that the Earth was flat? There is no doubt that Archimedes proceeded to and completed the rigorous geometrical proof by the method of exhaustion. As observed by Professor C. Joule, the solid in the present proposition is made up of 8 pieces of cylinders of the type of that treated in the preceding proposition. As, however, the 2 propositions are separately stated, there is no doubt that Archimedes' proof of them were distinct. In this case, AC would be divided into a very large number of equal parts, and planes would be drawn through the points of division perpendicular to AC. These planes cut the solid and also the cube in square sections. Thus we can inscribe, and circumscribe to the solid the requisite solid figures made up of element prisms and differing by less than any assigned solid magnitude. Alright, that's it for Archimedes. Now we're up to Diophantus, which is our third mathematician, here on page 241. So, 3rd century AD. Yeah, okay. His life and work. Although historians can only date Diophantus to the 3rd century AD with some uncertainty, we do know something of his life. We know this from a word problem left by a friend of his shortly after his death. His boyhood lasted 1/6 of his life. He grew a beard after another 1/12. After 1/7 more he married, and had a son 5 years later. The son lived to half the father's age, and the father died 4 years later. This is a typical example of Diophantus's great work, the Arithmetica, which is excerpted here. See if you can solve the riddle of Diophantus's life history. The answer can be found at the end of this introduction. The best evidence for his dates comes from the works he cites and the works that cite him. In his book on polygonal numbers, Diophantus presents the definition given by the Greek mathematician Hypsicles in the middle of the 2nd century BC. At the other end of the range, the Alexandrian mathematician Theon mentions Diophantus in a work from the middle of the 4th century AD. Historians date Diophantus to the middle of the 3rd century AD based on a letter of Michael Psellus, an 11th century Byzantine scholar and statesman, which states that Antolius, bishop of Laodicea around 270, had dedicated a treatise on ancient Egyptian computation to his friend Diophantus of Alexandria. This is consistent with the dedication Diophantus makes at the opening of the Arithmetica. Knowing, my most esteemed friend Dionysius, that you are anxious to learn how to investigate problems in numbers, I have tried, beginning from the foundations on which the science is built up, to set forth to you the nature and power subsiding in numbers. All right. Most likely, Diophantus made this dedication to the Dionysius, who was Bishop of Alexandria between 247 and 264. Alexandria had become the center of Hellenistic culture shortly after Alexander the Great founded it in 331 BC. By the 3rd century AD, it was often the scene of conflict between the growing Christian community and the established Roman and Greek communities. By the early 2060s, persecution of the Christian community was an everyday event in Alexandria. The great road through the city was usually clogged with the bodies of Christian martyrs. Famine and pestilence often beset the city. Given the environment, we can only wonder if the friendship between Diophantus and Dionysius meant that Diophantus was a Christian. The Arithmetica is not a theoretical work in the tradition of Pythagoreans. Euclid's proof that there is no largest prime number would have been completely out of place in the Arithmetica. Instead, the Arithmetica is a work of logistic or computational arithmetic. Its roots lie more in the mathematics of ancient Egypt, Babylonia, and India than in those of ancient Greece. In his introduction, Diophantus promises a work comprised of 13 books. However, only 6 books were known until very recently. The other books must have been separated very early. The first female mathematician known in the Western world, Hypatia, the daughter of Theon of Alexandria, wrote the earliest commentary on the Arithmetica. We know little of Hypatia beyond the fact that she was murdered by a mob of Christian fanatics in 415 as they burned Alexandria's great library to the ground, destroying the greatest repository of classical thought. According to the 10th century encyclopedist Suidas, she wrote commentaries on the Arithmetica, Ptolemy's astronomy, and Apollonius's conics. In the Western world, The Arithmetica may have survived the destruction of the Great Library of Alexandria in the form of the manuscript in Constantinople seen by Michael Psellos. This one manuscript is the progenitor of all the copies of the Arithmetica known to the West until very recently. A little more than 30 years ago, scholars found an Arabic manuscript containing 4 previously unknown books from the Arithmetica at the shrine of Imam Riza in the holy Islamic city of Mashhad in northeastern Iran. It had been translated in Lucca by Quasta, a Christian of Greek origins, born in the city of Heliopolis in Syria. In the introduction, Diophantus begins by defining the different species of numbers from the second through to the sixth powers of a variable. That is, x squared, a square, and its sign is a d with a y superimposed, thus dy. X cubed, a cubed, and its sign is ky. X to the power 4, a square, and its origin is dyd. X to the power 5, a square cube, and its sign is dky. And then x to the power of 6, a cube, and its sign is kyk. He continues. But the number which has none of these characteristics, but merely has in it an indeterminate magnitude of units, is called arithmos, and its sign is that. I'm not sure what that sign is. This symbol, something like the Greek letter sigma, as found at the end of words, is how Diophantus represents the unknown quantity, which he literally described as the number. So this is algebra. We will use x in conformance with contemporary convention. Okay, that's great. I need some more coffee. I'll be back. Diophantus was the first mathematician to introduce a sign for subtraction. It looked something like this, perhaps representing an abbreviation for the Greek verb lipian, to want, which begins with the Greek letters lambda and iota. Diophantus did not employ signs for either addition or multiplication. He represented addition simply by juxtaposing numbers or variables next to each other. He never needs a symbol for multiplication because his coefficients are always definite integers or fractions. To Diophantus, positive terms represent a forthcoming and negative terms a wanting. Positive terms always come before negative terms in his problems. The 2 general rules he gives concern multiplication. A wanting times a wanting yields a forthcoming. A forthcoming times a wanting yields a wanting. For Diophantus, a negative quantity simply could not exist without some positive quantity from which it would be subtracted. He regarded as useless any equation leading to a negative solution, much less an irrational or imaginary solution. Diophantus's commentators have all despaired at their inability to provide any real categorization of the problems in the Arithmetica. The first book consists of determinate algebraic equations. Books 2 through 5 mostly contain indeterminate problems consisting of expressions in 2 or more variables to the first or second power that are to be made equal to a square or a cube. Book 6 focuses on right triangles considered arithmetically with some linear or quadratic function of their sides to be made into a square or a cube. Because every problem requires its own special method, I will analyze one of the problems for you. Book 5, Problem 9. The problem is to divide unity, that is 1, into 2 parts such that if the same given number be added to either part, the result will be a square. The given number will be an integer, and tantalizingly, Diophantus tells us the given number must not be odd, and the double of it, plus 1, must not be divisible by any prime number, which, when increased by 1, is divisible by 4. This condition indicates that Diophantus knew that the square of an integer cannot leave a remainder of 3 when divided by 4. You can easily prove this by squaring 0, 1, 2, and 3 and taking the remainders after dividing by 4. Without any further conditions, Diophantus takes 6 as the given number. Therefore, 13 must be divided into 2 squares, each of which is greater than 6. If we then divide 13 into 2 squares, the difference of which is less than 1, we solve the problem. Take half of 13, or 6.5, and we have to add 6.5, a small fraction which we will make a square, or multiplying by 4 we have to make 1 on x squared plus 26 a square. 26x squared plus 1 is a square equals 5x plus 1 squared. Say whence x equals 10. Multiplying by 2 would have eliminated the fraction. However, 2 is not a square, therefore Diophantus multiplies by 4, a square number. The step changing 1 on x squared plus 26 to 26x squared plus 1 is ordinary, straightforward algebra. However, the step re-expressing 26x squared plus 1 as the square 5x plus 1 squared is pure Diophantus, a step to get a term in x squared near to 26x squared because he is solving for 2 numbers summing to 1. Having done this, he continues. That is, in order to make 26 a square, we must add 1 100th, or to make 6.5 a square, we must add 1 400th, and 1 400th plus 6.5 equals 51 on 20 squared. Therefore, we must divide 13 into 2 squares such that their sides may be as nearly as possible equal to 51 on 20. This becomes a bit more understandable if we rewrite this inequality as this. Okay, Diophantus continues. Now 13 equals 2 squared plus 3 squared. Therefore, we seek 2 numbers such that 3 minus the first equals 51 on 20, so that the first equals 9 on 20, and 2 plus the second equals 51 on 20, so that the second equals 11 on 20. Diophantus next substitutes for x for 1/20th. He continues. We write accordingly 11x plus 2 squared, 3 minus 9x squared for the required squares. Recall from basic algebra that these expand to 121x squared plus 4, 44x plus 4, and 9 minus 54x plus 81x squared respectively. So the sum equals 13. Therefore x equals 5 on 101, and the sides are as given. Subtracting 6 from each, we have pairs of unity. Have you been able to solve the problem at the beginning of this sketch? In modern notation, it resolves to solving the equation. There you go. The solution is x equals 84. Oh, there you go. So 84. So that was the end of Diophantus, wasn't it? Oh no, there's more from Diophantus. I'm going to take a quick break and we'll continue. I'm back. So now we're going to continue with selections from Diophantus of Alexandria, a study in the history of Greek algebra, Book 2, Problems 8-35. Okay, well let's have a look at problem 8. To divide a given square number into 2 squares, given square number 16, x squared is one of the required squares, therefore 16 minus x squared must be equal to a square. Take a square of the form, why is there a note? Mx minus 4 squared, m being any integer, and 4 the number which is the square root of 16. E.g. take 2x minus 4 squared and equate it to 16 minus x squared. Therefore 4x squared minus 16x plus 16 equals 16 minus x squared, or 5x squared equals 16x, and x equals 16 on 5. The required squares are therefore 256 on 25 and 144 on 25. Okay, so I mean, I'm not a professional, but it seems to me like Diophantus, did he pioneer algebra? I don't know. Book 3, Problems 5-21. Problem 5. To find 3 numbers such that their sum is a square and the sum of any pair exceeds the third by a square. The numbers are 8.5, 32.5, and 40. Book 5, problems 1 to 29. Problem 1. To find three numbers in geometrical progression such that each of them minus a given number gives a square. And here's a solution. That's great. 130,321 on 10,816. There we go. So up to Rene Descartes, which is, like 1,300 years later. So we didn't get much done for 1,000 years. Anyway, here we are. Rene Descartes, 1596 to 1650. Okay, his life and work. Rene Descartes was born into prominent families known for making significant contributions to French culture. His father, Joachim, came from a long line of medical doctors and was a councillor to the provincial parliament of Brittany. His mother, Jeanne Brocard, came from a wealthy family with property in Pitot. I don't know how to pronounce that. They married in 1589 and already had a son named Pierre. Oh, that's a bit naughty. And daughter named Jeanne. When their third child, Rene, was born in 1596. They named him after his maternal grandfather, who had died in 1596. There you go. Descartes never knew his mother. She died in childbirth 13 months after he was born. His father left the children in the care of Madame Jeanne Sain, who became Descartes' surrogate mother and remained so even when Descartes' father remarried in 1600. If Jeanne Sain was Descartes' mother figure, then Father Etienne Charlotte, the rector of the Jesuit college in La Flèche, I'm sorry about the pronunciation, was his father figure. Descartes entered the college at La Flèche in 1606 and remained there for the next 8 years. It had just opened 2 years earlier. In contrast to the municipally run colleges in France, which were explicitly based on a humanist model, the Catholic colleges, such as La Flèche, continued to provide a thorough grounding in traditional Catholic thought and the classics of antiquity. Like most French colleges, La Flèche was I wish I knew how to pronounce that, was a combination. Actually, I'm going to go find out. Hang on a sec. Alright, I'm back. And so the correct pronunciation apparently is La Flèche, like the word flesh. There we go. Like most French colleges, La Flèche was a combination of a secondary school and a university. At La Flèche, the first year was devoted to preparatory classes, the next 3 years to grammar in Latin and Greek, and the 5th year to rhetoric. All instruction was in Latin. Although the Jesuit fathers were very demanding of their students' academic work, they could have soft spots in their heart. The fathers at La Flèche often allowed Descartes to stay in bed all morning because of his poor health. Many students left Jesuit colleges like La Flèche after these first 5 years to enroll at a university and pursue a degree in one of the 3 major professions: law, medicine, and theology. In fact, many of the secular universities refused to take students with more than 5 years at a Jesuit college, fearing that they would be too indoctrinated with the radical teaching of the relatively new Jesuit order. Descartes was not one of these students. He was very pleased to learn that his father wished for him to stay at La Flèche for an additional 3 years. At the beginning of these 4 years, Descartes began his study of metaphysics, ethics, natural philosophy, and dialectic. The curriculum in natural philosophy included the study of Euclid, Archimedes, and Diophantus, as well as contemporary mathematics. While at La Flèche, Descartes may have made a personal contact that proved to be just as valuable as the mathematical foundation he gained. One of Descartes' later correspondents, Marin Mersenne, was also a student at La Flèche. From the 1620s to the 1640s, Mersenne acted as the hub of French scientific activity, corresponding with anyone and everyone of any importance. His correspondence alone runs to more than 10,000 pages. Descartes left the college at La Flèche in 1614 and enrolled at the nearby University of Poitiers to study law. He earned his law degree in 2 years. However, law seemed to hold little interest for him. There is no record of Descartes ever practicing law, as his father probably wished. His real interest at Poitiers was medicine, and he developed a keen interest in dissection. Having lived in one region of France for the first 20 years of his life, Descartes must have been eager to see other parts of Europe. Upon receiving his law degree, he joined the army of Prince Maurice of Nassau as a gentleman officer. After 2.5 years of the Netherlands, Descartes left the service of Prince Maurice and joined the army of Maximilian Bavaria. Shortly after joining Maximilian, Descartes travelled to Frankfurt, where he witnessed preparations for the coronation of Ferdinand II as Holy Roman Emperor. Descartes continued his military career until the age of 30. He spent the first half of 1620s travelling through Europe as the 30 Years' War raged. His correspondence records that he visited Bavaria, Bohemia, Germany, Italy, and Hungary, as well as Holland and France during these years. Although these were years of constant travel, Descartes found the time to lay the groundwork for his work in metaphysics, epistemology, and natural philosophy. In 1618, while in the service of Maurice of Orange, Descartes met with Dutchman Isaac Beckman, 7 years his senior. Beckman shared Descartes' interests in philosophy and mathematics. Beckman, or is it Beekman? Beekman became another father figure to Descartes, and Descartes became Beekman's intellectual apprentice. Most importantly, Beekman became a confidant to Descartes. Shortly before his 23rd birthday in 1619, Descartes outlined a scheme for a new mathematics in a letter to Beekman. What I would like to present to the public is a science with wholly new foundations, which will enable us to answer every question that can be put about any kind of quantity whatsoever, whether continuous or discontinuous, each according to its nature. In arithmetic, certain quantities can be solved by means of rational numbers, others by using irrationals, and finally others can be imagined but not solved. In this way, I hope to demonstrate that in the case of continuous quantity, certain problems can be solved with straight lines and circles alone, that others can be solved only with curves other than circles, but which can be generated by a single motion, and which can therefore be drawn using a new compass, which I do not believe to be any less accurate than, and just as geometrical as, the ordinary compass which is used to draw circles. And finally, other problems can be solved only with curves generated but motions not subordinated to one another, curves which are certainly only imaginary, such as the quadratics, which is well known. I do not believe one can imagine anything which could not be solved along similar lines. Indeed, I hope to show that particular kinds of questions can be resolved in one way and not another, and so that there will remain almost nothing else to discover in geometry. The task is infinite and could not be accomplished by one person. It is as incredible as it is ambitious, but I have seen a certain light in the dark chaos of this science, thanks to which the thickest clouds can be dispelled. This served as a first draft for what would turn into part of Descartes' fourth rule for the direction of the mind. It is evident to anyone with the most minimal education what pertains to mathematics and what does not in any context. When I attended to the matter more closely, I came to see that the exclusive concern of mathematics is with questions of order or measure, and that it does not matter whether the measure in question involves numbers, shapes, stars, sounds, or any other object whatsoever. This made me realize that there must be a general science that explains everything that can be raised concerning order and measure irrespective of the subject matter, and that this science should be termed Mathesis Universalis. Mathesis Universalis. A venerable term with a well-established meaning. for it covers everything that entitles these other sciences to be called branches of mathematics. How superior it is to these subordinate sciences, both in usefulness and simplicity, is clear from the fact that it covers all they deal with. Up to now, I have devoted all my energies to this Mathesis Universalis, so that I might be able to tackle the more advanced sciences in due course. Nice one. It would be nearly 20 decades until Descartes actually had the time to develop his mathematics. Did I say 20 years? It would be nearly 20 years until Descartes actually had the time to develop his mathematics. After his military career, Descartes lived in Paris between 1625 and 1628. He found himself in a circle of thinkers who, like himself, rejected much of the Aristotelian orthodoxy still ascendant in the early 17th century. From time to time, he and his circle argued the merits of the heliocentric astronomy of Copernicus. However, they needed to couch their discussions in hypothetical terms. In 1624, the theology faculty at the Sorbonne in Paris had issued an edict threatening anyone with death for advocating views contrary to the approved teachings of the ancient authors. Although he remained an ardent Catholic his entire life, Descartes found the clerically influenced intellectual atmosphere in Paris to be too threatening, and in 1628 left for the more liberal environment in Protestant Holland. His decision to leave Paris may have also been hastened by a duel he fought over the honour of a lady. We know nothing of this lady except that Descartes compared her beauty to the beauty of truth. He must have left Paris in a great hurry. Descartes' correspondence records that he took nothing with him except for the Bible and the Summa Theologia of Thomas Aquinas. Descartes settled in Amsterdam and soon made himself prominent in its intellectual circles. During the winter of 1634-35, Descartes became a fixture at the house of Elizabeth Stuart, Electress of the Palatine and Queen of Bohemia. She was the widow of the Frederick V of Bohemia, whose armies had been routed at the Battle of the White Mountain in 1630, and was forced into exile of poverty in the Netherlands. When Frederick died in 1632, his widow remained in the Netherlands on a pension provided by her brother, King Charles of England. Descartes had a close intellectual relationship with the Dowager Queen Elizabeth, and later on with her daughter, Princess Elizabeth of Bohemia. While in Amsterdam, Descartes became friendly with Constantine Huygens, secretary to Frederick Henry, Prince of Orange. Huygens came from a family of diplomats, and he became an ardent supporter of Descartes. However, the Huygens family is best known for Constantine's eldest son, Christian, 1629 to 1695, a contemporary of Newton, who the English philosopher John Locke would describe as the Eugenius. Descartes took an active interest in the education of the young Christian Huygens, and Huygens developed Descartes' theory of vortices. In the mid-1630s, Descartes had the only significant romantic relationship of his life with a woman named Helen, a maid in the house where he was lodging. In July 1635, she gave birth to Descartes' daughter, and they named the child Francine. The child was baptized as a Protestant and had only occasional contact with her father during her short life. She died of a fever that swept through Holland in 1640, just after her 5th birthday. Her death left Descartes greatly shaken. Only with her death could Descartes begin to understand what she really meant to him. True to form, he had no contact with Helene following their child's death. The Netherlands was also the birthplace of Descartes' greatest works: the Discourse on Method, the Meditations on First Philosophy, and Principles of Philosophy, and the Geometry, the work presented here. We can easily see the power of Descartes' mathematical methods with his exposition of two very basic mathematical operations, determining products and square roots. Recall that to Euclid and his Greek successors all the way up through the 16th century, arithmetic propositions are stated in terms of geometrical figures such as line lengths, not because line lengths provide a good method for representing numbers, but because that is what numbers are. Thus, determining the product of two abstract values x and y meant constructing a rectangle whose sides had length x and y and realizing that their product in the area of the rectangle. Similarly, the ancients would take the square root of an abstract value x by representing x as a two-dimensional figure and finding a square of equal area. The side of that square realized the square root of x. The crisis of the irrational forced the Greeks to resort to these geometric interpretations. Descartes would have none of these geometrical restrictions. We should also note those proportions that form a continuing sequence are to be understood in terms of a number of relations. Others try to express these proportions in ordinary algebraic terms by means of several different dimensions and shapes. The first they call the root, the second the square, the third the cube, the fourth the biquadratic, and so on. These expressions have, I confess, long misled me. All such names should be abandoned, as they are liable to cause confusion in our thinking. For though a magnitude may be termed a cube or a biquadratic, it should never be represented to the imagination otherwise than as a line or a surface. What, above all, requires to be noted is that the root, the square, the cube are merely magnitudes in continued proportion, which always implies the freely chose unit that we spoke of in the preceding rule. And that didn't sound grammatical to me, but it is what it said. Thus, the cube of a quantity x, for example, is designated as x cubed, not because it represents a geometric cube, a three-dimensional figure, but because it represents a series of proportions with three relations. 1x, x to x squared to x cubed. Instead of requiring geometric constructions for every one of the objects being considered, Descartes supposed that all of the given objects exist and shows how to construct the value sought as a line segment. Here is how he determines the product of two quantities at the very beginning of his geometry. He supposes that unity, that is 1, is given by the line segment AB, and proceeds to multiply the values represented by the line segment BD, collinear with AB, and BC. He connects the points A and C, and then constructs through D the line parallel to AC that intercepts BC at E. In doing so, Descartes has created two triangles, ABC and DBE, that are similar to each other. Consequently, their sides are in proportion. So BE to BC is BD to BA. But since BA equals 1, he has BE to BC equals BD, or BE equals BC times BD, the sought for solution. Taking square roots is just as straightforward. He lets the line segment GH represent the quantity whose square root is to be determined, and extends it from G to F, so that FG equals unity. Having done that, Descartes bisects the line segment FH at the point K and constructs the semicircle centered on K, having KH equals KF as its radius. At the point G, he erects the perpendicular to FH that intersects the circle at point I. This time, Descartes has actually constructed three similar right triangles, IGF, HGI, and HIF. The angles IGF, HGI, and HIF are all right angles. Since IGF and HGI are similar, we have GH to GI equals GI to FG. By supposition, we have FG equals 1. Therefore, GH equals GI squared, demonstrating that GI is the square root of GH. Descartes continued to live in the Netherlands until 1648, when Queen Christina of Sweden offered him a position at her court in Stockholm to establish an academy for scholars and give her lessons in ethics and theology. When Descartes accepted her offer, Christina sent a warship to take him to Sweden. Descartes had never been treated so royally, and he probably expected to be treated just as royally at the Swedish court. Although his surroundings may have been royal, Descartes had not bothered to inquire about the hours he would be expected to keep. Owing to his lifelong mediocre health, Descartes often remained in bed all morning. Much to his chagrin, he learned that this was not the style of the Swedish court. Queen Christina insisted that her lessons begin at 5 in the morning, regardless of the weather. This required Descartes to leave his residence at 4:30 in the morning and brave the often inclement northern climate. The weather of 1649 to 1650 was exceptionally harsh, and Descartes soon became ill with pneumonia. Preferring his own treatments to anything Christina's documents might prescribe, Descartes tried to cure himself with a concoction of wine-flavoured tobacco designed to make him vomit up the phlegm. He soon got worse, falling into a delirium and dying 2 days later on February 11th, 1650. There. That's the end of Descartes. So here's the geometry of René Descartes. Book 1. Problems, the construction of which requires only straight lines and circles. Any problem in geometry can easily be reduced to such terms that a knowledge of the lengths of certain straight lines is sufficient for its construction. Just as arithmetic consists of only 4 or 5 operations, namely addition, subtraction, multiplication, division, and the extraction of roots, which may be considered a kind of division, so in geometry, to find the required lines, it is merely necessary to add or subtract other lines, or else, taking one line which I shall call unity in order to relate it as closely as possible to numbers, and which can in general be chosen arbitrarily, and having given 2 other lines, to find a 4th line, which shall be to one of the given lines as the other is to unity, for which which is the same as multiplication, or again to find a 4th line, which is to one of the given lines as unity is to the other, which is equivalent to division, or finally to find 1, 2, or several mean proportionals between unity and some other line, which is the same as extracting the square root, cube root, etc. of the given line. And I shall not hesitate to introduce these arithmetical terms into geometry for the sake of greater clearness. For example, let AB be taken as unity. This is the same thing that they had in his life and work. Thus, all the unknown quantities can be expressed in terms of a single quantity, whenever the problem can be constructed by means of circles and straight lines, or by conic sections, or even by some other curve of degree not greater than the 3rd or 4th. But I shall not stop to explain this in more detail, because I should deprive you of the pleasure of mastering it yourself, as well as of the advantage of training your mind by working over it, which is in my opinion the principal benefit to be derived from this science, because I find nothing here so difficult that it cannot be worked out by anyone at all familiar with ordinary geometry and with algebra, and who will consider carefully all that is set forth in this treaty. I shall therefore content myself with the statement that if the student, in solving these equations, does not fail to make use of division wherever possible, he will surely reach the simplest terms to which the problem can be reduced. And if it can be solved by ordinary geometry, that is, by the use of straight lines and circles traced on a plane surface, when the last equation shall have been entirely solved, there will remain, at most, only the square of an unknown quantity, equal to the product of its root by some known quantity, increased or diminished by some other quantity also known. Then this root or unknown line can easily be found. For example, if I have z squared equals az plus b squared, I construct a straight line and blah blah blah, and off we go again. Okay. So there's various Latin Okay, and this is more of Descartes' Geometry Book 2 on the nature of curved lines. The ancients were familiar with the fact that the problems of geometry may be divided into 3 classes, namely plane, solid, and linear problems. This is equivalent to saying that some problems require only circles and straight lines for their construction, while others require a conic section, and still others require more complex curves. I am surprised, however, that they did not go further and distinguish between different degrees of these more complex curves, nor do I see why they call the latter mechanical rather than geometrical. If we say that they are called mechanical because some sort of instrument has to be used to describe them, then we must, to be consistent, reject circles and straight lines, since these cannot be described on paper without the use of compasses and a ruler, which may also be termed instruments. It is not because of the other instruments being more complicated than the ruler and compasses are therefore less accurate, for if this were so, they would have to be excluded from mechanics, in which case accuracy of construction is even more important than in geometry. In the latter, exactness of reasoning alone is sought, and this can surely be thorough with reference to such lines as to simpler ones. I cannot believe, either, that it was because they did not wish to make more than two postulates, namely, 1. A straight line can be drawn between any 2 points, and 2. About a given centre, a circle can be described passing through a given point. In their treatment of the conic sections, they did not hesitate to introduce the assumption that any given cone can be cut by a given plane. Now, to treat all the curves which I mean to introduce here, only one additional assumption is necessary, namely, 2 or more lines can be moved, one upon the other, determining by their intersection other curves. This seems to me in no way more difficult. It is true that the conic sections were never freely received into ancient geometry, and I do not care to undertake to change names confirmed by usage. Nevertheless, it seems very clear to me that if we make the usual assumption that geometry is precise and exact, while mechanics is not, and if we think of geometry as the science which furnishes a general knowledge of the measurement of all bodies, then we have no more right to exclude the more complex curves than the simpler ones, provided they can be conceived of as described by a continuous motion or by several successive motions, each motion being completely determined by those which precede, for in this way an exact knowledge of the magnitude of each is always obtainable. Probably the real explanation of the refusal of ancient geometers to accept curves more complex than the conic section lies in the fact that the first curves to which their attention was attracted happened to be the spiral, the quadratics, and similar curves, which really do belong only to mechanics, and are not among those curves that I think should be included here, since they may be conceived of as described by two separate movements whose relation does not admit of exact determination. Yet they afterwards examine the conchoid, the cissoid, and a few others which should be accepted. But not knowing much about their properties, they took no more account of these than of the others. Again, it must have been that, knowing as they did only a little about the conic sections, and being still ignorant of many of the possibilities of the ruler and compass, they dared not yet attack a matter of still greater difficulty. I hope that hereafter those who are clever enough to make use of the geometric methods herein suggested will find no greater difficulty in applying them to plain or solid problems. I therefore think it proper to suggest to such a more extended line of investigation which will furnish abundant opportunities for practice. Okay, and off we go. I have shown, further, that what I have termed the first class of curves contains no others besides the circle, the parabola, the hyperbola, and the ellipse. This is what I undertook to prove. To show that a consideration of these curves is not without its use, and that they have diverse properties of no less importance than those of the conic sections, I shall add a discussion of certain ovals, which you will find very useful in the theory of catopretics and dioptrics. Never heard those words before. They may be described in the following way. Off we go again. And here's still more from Descartes, Geometry Book 3, on the construction of solid and supersolid problems. While it is true that every curve which can be described by a continuous motion should be recognized in geometry, this does not mean that we should use at random the first one that we meet in the construction of a given problem. We should always choose with care the simplest curve that can be used in the solution of a problem, but it should be noted that the simplest means not merely the one most easily described, nor the one that leads to the easiest demonstration or construction of the problem, but rather the one of the simplest class that can be used to determine the required quantity. For example, there is, I believe, no easier method of finding any number of mean proportionals, nor one whose demonstration is clearer, than the one which employs the curves described by the instrument x, y, z, previously explained. Thus, if two mean proportionals between YA and YE be required, it is only necessary to describe a circle upon YE as diameter, cutting the curve AD in D, and YD is then one of the required mean proportionals. The demonstration becomes obvious as soon as the instrument is applied to YD, since YA or YB is to YC as YC is to YD as YD is to YE. Similarly, to find 4 mean proportionals between YA and YG, or 6 between YA and YN, it is only necessary to draw the circle YFG, which determines by its intersection with AF the line YF, one of the 4 mean proportional blah blah blah. Wow. When the equation has been reduced to 3 dimensions, the value of y squared is found by the method already explained. If this cannot be done, it is useless to pursue the question further, for it follows inevitably that the problem is solid. If, however, the value of y squared can be found, we can by means of it separate the preceding equation into 2 others, each of the second degree, whose roots will be the same as those of the original equation. Okay. For example, grant that we may consider a root of the equation z cubed equals minus qz plus p known, because we know that it is the sum of 2 lines of which one is the side of a cube whose volume is half q, increased by the side of the square whose area is 1/4 q squared minus 1/27 p cubed, and the other is the side of another cube whose volume is the difference between half q and the side of the square whose area is blah blah blah. This is much knowledge of the root. This is as much knowledge of the roots as is furnished by Cardan's method. There is no doubt that the value of the root of the equation is quite as well known as clearly conceived when it is considered as the length of a chord inscribed by a circle of radius semtet blah blah blah. Okay. I hope that posterity will judge me kindly, not only as to the things which I have explained, but also as to those which I have intentionally omitted, so as to leave to others the pleasure of discovery. And now we're up to Isaac Newton, lived from 1642 to 1727. His life and work. Galileo died on January 8, 1642, exactly 300 years before the day I was born. Isaac Newton was born on Christmas Day of that year in the English industrial town of Woolsthorpe, Lincolnshire. He would later become Lucasian Professor of Mathematics at Cambridge University, the chair I now hold. Newton's mother did not expect him to live long, as he was born very prematurely. He would later describe himself as having been so small at birth he could fit into a quart pot. Newton's yeoman father, also named Isaac, had died 3 months earlier, and when Newton reached 2 years of age, his mother, Hannah Icecoff, remarried, wedding Barnabas Smith, a rich clergyman from New Witten. Apparently, there was no place in the new Smith family for the young Newton, and he was placed in the care of his grandmother, Margery Ascough. The spectre of this abandonment, coupled with the tragedy of never having known his father, haunted Newton for the rest of his life. He despised his stepfather. In journal entries for 1662, Newton recalled threatening my father and mother Smith to burn them and the house over them. Much like his adulthood, Newton's childhood was filled with episodes of harsh, vindictive attacks, not only against perceived enemies, but also against friends and family. He also displayed the kind of curiosity early on that would define his life's achievements, taking an interest in mechanical models and architectural drawing. Newton spent countless hours building clocks, flaming kites, sundials, and miniature mills powered by mice, as well as drawing elaborate sketches of animals and ships. At the age of 5, he attended schools at Skillington and Stoke, but was considered one of the poorest students, with his teachers' reports stating he was inattentive and idle. Despite his curiosity and demonstrable passion for learning, he was unable to apply himself to schoolwork. By the time Newton reached an age of 10, Barnabas Smith had passed away, and Hannah had come into a considerable sum from Smith's estate. Isaac and his grandmother began living with Hannah, a half-brother, and 2 half-sisters. Because his work at school was uninspiring, including his studies of mathematics, Hannah decided that Isaac would be better off managing the farm and estate, and she pulled him out of the free grammar school in Grantham. Unfortunately for her, Newton had even less skill or interest in managing the family estate than he had in schoolwork. Hannah's brother, William, a clergyman, decided that it would be best for the family if the absent-minded Isaac returned to school to finish his education. This time, Newton lived with the headmaster of the free grammar school, John Stokes, and he seemed to turn a corner in his education. One story has it that a blow to the head administered by a schoolyard bully somehow enlightened him, enabling the young Newton to reverse the negative course of his educational promise. Now demonstrating intellectual aptitude and curiosity, Newton began preparing for further study at a university. He decided to attend Trinity College, his Uncle William's alma mater, at Cambridge University. At Trinity, Newton became a subsizar, receiving an allowance towards the cost of his education in exchange for performing various chores, such as waiting tables and cleaning rooms for the faculty. By 1664, he was elected scholar, which status guaranteed him financial support and freed him from menial duties. When the university closed because of the bubonic plague in 1665, Newton retreated to Lincolnshire. In the 18 months he spent at home during the plague, he devoted himself to mechanics and mathematics and began to concentrate on optics and gravitation. His annus mirabilis, miraculous year, as Newton called it, was one of the most productive and fruitful periods of his life. It is also around this time that an apple, according to legend, fell onto Newton's head, awakening him from a nap under a tree and spurring him on to define the laws of gravity. However far-fetched the tale, Newton himself wrote that a falling apple had occasioned his foray into gravitational contemplation, and he is believed to have performed his pendulum experiments then. I was in the prime of my age for invention, Newton later recalled, and minded mathematics and philosophy more than at any time since. When he returned to Cambridge, Newton studied the philosophy of Aristotle and Descartes, as well as the science of Thomas Hobbes and Robert Boyle. He was taken by the mechanics of Copernicus and Galileo's astronomy, in addition to Kepler's optics. We have little direct information on Newton's mathematical education prior to his matriculation at Cambridge. Newton's first tutor at Cambridge was Benjamin Pullian, who later became Regius Professor of Greek. All words I don't know how to pronounce again. Newton soon came under the tutelage of Isaac Barrow, an outstanding mathematician and one of the founders of the Royal Society, who tutored Newton as young Isaac sped through Euclid's Elements. Following this, Newton soon mastered works on algebra by William Outred, 1574 to 1660, Francois Viet, 1540 to 1603, and most importantly, Descartes' geometry. Interesting. Spelled differently there. Around this time, Newton began his prism experiments in light, refraction, and dispersion, possibly in his room at Trinity or at home in Woolsthorpe. A development at the university that clearly had a profound influence on Newton's future was the arrival of Isaac Barrow, who had been named the Lucasian Professor of Mathematics. Barrow recognized Newton's extraordinary mathematical talents, and when he resigned his professorship in 1669 to pursue technology, he recommended the 27-year-old Newton as his replacement. Newton's first studies as Lucasian professor were centered in the field of optics. He set out to prove that white light was composed of a mixture of various types of light, each producing a different color of the spectrum when refracted by a prism. His series of elaborate and precise experiments to prove that light was composed of minute particles drew the ire of scientists such as Hooke, who contended that light traveled in waves. Hooke challenged Newton to offer further proof of his eccentric optical theories. Newton's way of responding was one he did not outgrow as he matured. He withdrew, set out to humiliate Hooke at every opportunity, and refused to publish his book, Optics, until after Hooke's death in 1703. There we go. Early in his tenure as Lucasian professor, Newton was well along in his study of pure mathematics, but he shared his work with few of his colleagues. Already by 1666, he had discovered general methods of solving problems of curvature, what he termed theories of fluxions and inverse fluxions. The discovery set off a dramatic feud with supporters of the German mathematician and philosopher Gottfried Wilhelm Leibniz, who more than a decade later published his findings on differential and integral calculus. Both men arrived at roughly the same mathematical principles, but Leibniz published his work before Newton. Newton's supporters claimed that Leibniz had seen Lucasian professor's papers years before, and a heated argument between the two camps, known as the calculus priority dispute, did not end until Leibniz died in 1716. Newton's vicious attacks, which often spilled over to touch on views about God and the universe, as well as his accusations of plagiarism, left Leibniz impoverished and disgraced. Most historians of science believe that the two men in fact arrived at their ideas independently, and that the dispute was pointless. Newton's vitriolic aggression towards Leibniz took a physical and emotional toll on Newton as well. He soon found himself involved in another battle, this time over his theory of colour, and with the English Jesuits. And in 1678, he suffered a severe mental breakdown. The next year, his mother passed away, and Newton began to distance himself from others. In secret, he delved into alchemy, a field widely regarded already in Newton's time as fruitless. This episode in the scientist's life has been a source of embarrassment to many Newton scholars. Only long after Newton died did it become apparent that his interest in chemical experiments was related to his later research in celestial mechanics and gravitation. Newton had already begun forming theories about motion by 1666, but he was as yet unable to adequately explain the mechanics of circular motion. Some 50 years earlier, the German mathematician and astronomer Johann Kepler had proposed 3 laws of planetary motion, which accurately described how the planets moved in relation to the Sun, but he could not explain why the planets moved as they did. The closest Kepler came to understanding the forces involved was to say that the Sun and the planets were magnetically related. Newton set out to discover the cause of the planet's elliptical orbits. By applying his own law of centripetal force to Kepler's third law of planetary motion, the law of harmonies, he deduced the inverse square law, which states that the force of gravity between any two objects is inversely proportional to the square of the distance between the object's centers. Newton was thereby coming to recognize that gravitation is universal, that one and the same force causes an apple to fall to the ground and the moon to race around the earth. He then set out to test the inverse square relation against known data. He accepted Galileo's estimate that the moon's distance from the Earth is 60 Earth radii, but the inaccuracy of his own estimate of the Earth's diameter made it impossible to complete the test to his satisfaction. Ironically, it was an exchange of letters in 1679 with his old adversary Hooke that renewed his interest in the problem. This time he turned his attention to Kepler's second law, the law of equal areas, which Newton was able to prove held true because of centripetal force. Hooke, too, was attempting to explain the planetary orbits, and some of his letters on that account were of particular interest to Newton. At an infamous gathering in 1684, 3 members of the Royal Society, Robert Hooke, Edmund Halley, and Christopher Wren, the noted architect of St. Paul's Cathedral, engaged in a heated discussion about the inverse square relation governing the motions of the planets. In the early 1670s, the talk in the coffee houses of London and other intellectual centres was that gravity emanated from the sun in all directions and fell off at a rate inverse to the square of the distance, thus becoming more and more diluted over the surface of the sphere as that surface expands. In 1684, the 1684 meeting was, in effect, the birth of Principia. Hooke declared that he had derived from Kepler's law of ellipses the proof that gravity was an emanating force, but would withhold it from Halley and Wren until he was ready to make it public. Furious, Halley went to Cambridge, told Newton Hooke's claim, and proposed the following problem. What would be the form of a planet's orbit about the sun if it were drawn towards the sun by a force that varied inversely as the square of the distance? Newton's response was staggering. It would be an ellipse, he answered immediately, and then told Halley that he had solved the problem 4 years earlier, but had misplaced the proof in his office. That's great. At Halley's request, Newton spent 3 months reconstituting and improving the proof. Then, in a burst of energy sustained for 18 months, during which he was so caught up in his work that he often forgot to eat, Newton further developed these ideas until their presentation filled 3 volumes. He chose to title the work Philosophiae Naturalis Principia Mathematica, in deliberate contrast with Descartes' Principia Philosophiae. The 3 books of Newton's Principia provided the link between Kepler's laws and the physical world. Halley reacted with joy and amazement to Newton's discoveries. To Halley, it seemed the Lucasian professor had succeeded where all others had failed, and he personally financed publication of the massive work as a masterpiece and a gift to humanity. Where Galileo had shown that objects were pulled towards the center of the Earth, Newton was able to prove that this same force, gravity, affected the orbits of the planets. He was also familiar with Galileo's work on the motion of projectiles, and he asserted that the moon's orbit around the Earth adhered to the same principles. Newton demonstrated that gravity explained predicted the moon's motions, as well as the rising and falling of the tides. Book 1 of Principia encompasses Newton's 3 laws of motion. 1. Every body perseveres in its state of resting or uniformly moving in a right line unless it is compelled to change the state by forces impressed upon it. 2. The change of motion is proportional to the motive force impressed and is made in the direction of the right line in which the force is impressed. 3. To every action there is always opposed an equal reaction, or the mutual actions of 2 bodies upon each other are always equal and directed to contrary directions. Book 2 began for Newton as something of an afterthought to Book 1. It was not included in the original outline of the work. It is essentially a treatise on fluid mechanics, and it allowed Newton room to display his mathematical ingenuity. Toward the end of the book, Newton concludes that the vortices invoked by Descartes to explain the motions of planets do not hold up to scrutiny, for the motions could be performed in free space without vortices. How that is so, Newton wrote, may be understood by the first book, and I shall now more fully treat of it in the following book. In Book 3, subtitled System of the World, by applying the laws of motion from Book 1 to the physical world, Newton concluded, there is a power of gravity tending to all bodies, proportional to the several quantities of matter which they contain. He thus demonstrated that that his law of universal gravitation could explain the motions of the 6 known planets, as well as moons, comets, equinoxes, and tides. The law states that all matter is mutually attracted with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Newton, by a single set of laws, had united the Earth with all that could be seen in the skies. In the first 2 rules of reasoning from Book 3, Newton wrote, "We are to admit no more causes of natural things than such as are both true and sufficient to explain their appearances. Therefore, to the same natural effects we must, as far as possible, assign the same causes." It is the second rule that actually unifies heaven and earth. An Aristotelian would have asserted that heavenly motions and terrestrial motions are manifestly not the same natural effects, and that Newton's second rule could not therefore be applied. Newton saw things otherwise. Principia was moderately praised on its publication in 1687, but only about 500 copies of the first edition were printed. However, Newton's nemesis, Robert Hooke, had threatened to spoil any coronation Newton might have enjoyed. After Book 2 appeared, Hooke publicly claimed that the letters he had written in 1679 had provided scientific ideas that were vital to Newton's discoveries. His claims, though not without merit, were abhorrent to Newton, who vowed to delay or even abandon publication of Book 3. Newton ultimately relented and published the final book of Principia, but not before painstakingly removing from it every mention of Hooke's name. Newton's work on integral and differential calculus can be found in his notebooks from the mid-1660s. However, Newton never published a purely mathematical text on his own. Only in the second half of the 20th century have an extensive proportion of his mathematical papers been published. Newton gave his contemporaries a glimpse of his discoveries in the Calculus Book 1, Section 1 of the Principia. He titled this section, "The Method of First and Last Ratios of Quantities," by the help of which we demonstrate the propositions that follow. In this section, included in the present volume, Newton presents 11 lemmas, the Greek term for subsidiary proposition, on first and last ratios that will allow him to make interchangeable use of figures constructed with curves and corresponding figures constructed from straight lines. In the first lemma, Newton proves that quantities and the ratio of quantities, which in any finite time converge continually to equality and before the end of that time approach nearer to each other than by any given difference, become ultimately equal. He proves this in a very straightforward manner that anticipates Weierstrass's epsilon delta method 2 centuries later. If the quantities and the ratios do not ultimately become equal, then they will have some finite ultimate difference d, and they cannot ultimately approach each closer than the difference d. Notice that Newton frames this statement in terms of change over time. Given the setting in Principia, a work on physical science, this is hardly surprising. 2 millennia before Newton, Archimedes had proven theorems about the area of particular geometric objects, such as the circle, by inscribing and circumscribing polygons about the object. In the second lemma, Newton takes a cue from Archimedes and extends this method to an arbitrary curve by inscribing and circumscribing rectangles about portions of the curve and demonstrating that the inscribed and circumscribed figures composed of these inscribed and circumscribed rectangles have areas that have an ultimate ratio of equality. Newton has the reader consider an arbitrary curve in relation to the straight line represented here by AE that he divides into equal parts AB, BC, CD, and so forth. That will be diminished ad infinitum. He then constructs the rectangles such as AKDB inscribed within a segment of the curve AAIB, circumscribed about the same segment of the curve. He notes that the difference in the areas of these rectangles is the area of the rectangle AKBL, or AKBL, yeah, and that the sum of the areas of these difference rectangles is simply the area of the first circumscribed rectangle AALB. And then Newton clinches the proof, noting that the length of the base AB of the rectangle AALB is being diminished ad infinitum, so that the area of the rectangle AALB becomes less than any given space. Hence, the areas of the inscribed and circumscribed figures ultimately become ultimately equal to one another, and the area described by the curvilinear figure as well. Newton put his lemmas to immediate use in the first proposition he demonstrates in Principia, Kepler's area law. In a scholium, I don't know what that means, at the end of section 1, Newton addresses concerns that would soon be voiced by critics, and quantities that themselves vanish to zero cannot have an ultimate proportion as they vanish to zero. He responds by comparing ultimate ratios to a body's velocity at a particular point in space. In an argument having its roots in the ancient Greeks, Newton points out that the body is certainly not at rest for the moment that it is at the particular place. In contrast, it has a definite ultimate velocity for the moment that it is at the particular place, just as quantities that vanish to zero can have an ultimate ratio to each other as it says as they vanish to zero. It's probably supposed to say as they vanish to zero. For those ultimate ratios with which quantities vanish are not truly the ratios of ultimate quantities, but limits towards which they approach nearer than by any given difference, but never go beyond, nor in effect attain to, till the quantities are diminished in infinitum. Yeah. Newton began the 18th century in a government post as Warden of the Royal Mint, where he utilized his work in alchemy to determine methods for re-establishing the integrity of the English currency. As president of the Royal Society, he continued to battle perceived enemies with inexorable determination, in particular carrying on his long-standing feud with Leibniz over their competing claims to have invented calculus. He was knighted by Queen Anne in 1705 and lived to see publication of the second and third editions of Principia. Newton occasionally claimed that he had derived many of the major propositions of the Principia using his discoveries in the calculus. He made one such claim in an unpublished preface to the Principia that he drafted around 1715, and finally went into print with such a claim in an anonymously published 1722 review of a book assessing his and Leibniz's claims to have invented calculus. He wrote, "By the help of the new analysis, Mr. Newton found out most of the propositions of his Principia philosophy, but because the ancients for making things certain admitted nothing into geometry before it was demonstrated synthetically, he demonstrated the proposition synthetically, that the system of the heavens might be founded upon good geometry, and this makes it difficult now for unskillful men to see the analysis by which the propositions were found out." Recent scholarly analysis of Newton's notebooks have revealed that there is not a shred of evidence for his extravagant claims made to secure priority for discovering the calculus for himself and not for his arch-rival Leibniz. Isaac Newton died in March 1727 after bouts of pulmonary inflammation and gout. As was his wish, Newton had no rival in the field of science. The man who apparently formed no romantic attachments with women, some historians have speculated on possible relationships with men, such as the Swiss natural philosopher Nicolas Fecio de Dulier, cannot, however, be accused of a lack of passion for his work. The poet Alexander Pope, a contemporary of Newton's, most elegantly described the great thinker's gift to humanity. "Nature and nature's laws lay hid in night. God said, 'Let Newton be,' and all was light." For all the petty arguments and undeniable arrogance that marked his life, towards its end, Isaac Newton was remarkably poignant in assessing his accomplishments. "I do not know how I may appear to the world, but to myself I seem to have been only like a boy, playing on the seashore and diverting myself, in now and then finding a smoother pebble or prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me." Okay. Selections from Principia, Book 1 of the Motion of Bodies, Section 1. Of the method of first and last ratios of quantities, by the help whereof we demonstrate the propositions that follow. Lemma 1. Quantities and the ratios of quantities which in any finite time converge continually to equality and before the end of that time approach nearer the one to the other than by any given difference become ultimately equal. If you deny it, suppose them to be ultimately unequal and let D be their ultimate significance, therefore they cannot approach their ultimate difference, therefore they cannot approach nearer to equality than by that given difference D, which is against the supposition. And off we go. So you would have seen this before if you've done calculus. I don't know what schoolium means. I could go look it up. I'll do that. I'm back. So scholium just means comment. It's like a explanatory note. Oh, that section on Newton wasn't very long, was it? Not compared to the others. Just this one little excerpt from Principia. There we go. Let's read the last paragraph. It may also be objected that if the ultimate ratios of evanescent quantities are given, their ultimate magnitudes will also be given, and so all quantities will consist of indivisibles, which is contrary to what Euclid has demonstrated concerning incommensurables in the 10th book of his Elements. But this objection is founded on a false supposition, for those ultimate ratios with which quantities vanish are not truly the ratios of ultimate quantities, but limits towards which the ratios of quantities decreasing without limit do always converge, and to which they approach nearer than any given difference, but never go beyond, nor in effect attain to, till the quantities are diminished in infinitum. This thing will appear more evident in quantities infinitely great. If two quantities whose difference is given be augmented in infinitum, the ultimate ratio of these quantities will be given, to wit, the ratio of equality. But it does not from thence follow that the ultimate or greatest quantities themselves, whose ratio that is, will be given. Therefore, if in what follows, for the sake of being more easily understood, I should happen to mention quantities as least, or evanescent, or ultimate, you are not to suppose that quantities of any determinate magnitude are meant, but such as are conceived to be always diminished without end. I'm just going to take a quick break. I'm back. On we go. So up next is Leonhard Euler. Lived 1707 to 1783. And this is his life and work. How long does it take to compare a life's work? How long does it take to compose a life's work? That's an easy question to answer. A lifetime, of course. And how long does it take to publish a life's work? For Leonhard Euler, the answer is a century or more. The Swiss Academy of Science began to publish his collected works in 1911. Okay. To date, over 6 dozen volumes have been published. More remain. This should come as no surprise. A prominent historian of science has estimated that Euler produced nearly a quarter of all the works in mathematics, physics, mechanics, astronomy, and navigation written in the 18th century. He was the most prolific mathematician of all time. Like many of the mathematicians profiled in this book, Euler's genius cannot readily be traced back through his family tree. His mother, the former Margaretha Brucker, I don't know how to pronounce it, came from a long line of well-educated clergymen. His father, Paulus Euler, also a clergyman, had been the first member of the Euler family to be well-educated. Paulus' grandfather, Hans Georg Euler, had been a comb maker when he settled in Basel in 1594. Paulus did have the distinction of having attended mathematics lectures given in Basel by the great Jacob Bernoulli, 1654-1705, the first of 8 great mathematicians from a family of hereditary genius. Margarita and Paulus married in 1701, and 6 years later, Leonhard Euler was born in the Swiss city of Basel on April 15. At that time, Basel was one of the 13 Swiss republics. Its population of 17,000 consisted mostly of Calvinists, many of whom had immigrated from more orthodox Catholic environments across Europe. Among these immigrants were Jacob Bernoulli's forebears, who had fled from Belgium in the late 16th century. Shortly after his son's birth, Paulus took up a pulpit in the town of Ryan, 5 miles outside of Basel, where I don't know how to pronounce these place names, where 3 more children were born to the family. Paulus served as his son's teacher, perhaps imparting some mathematical insights that had been gleaned at Jacob Bernoulli's lectures. At age 8, Leonhard went to Basel to live with his widowed maternal grandmother, Maria Magdalena Brucker Faber, so that he could attend the Basel Gymnasium. Although the gymnasium offered excellent instruction in Latin and Greek, it had no lectures in mathematics. The local citizenry thought mathematics too difficult for such young students. To fill this hole in the curriculum, Paulus hired the young theologian Johann Burckhardt as a special tutor in mathematics for his son. 5 years later, Euler enrolled at the University of Basel at the age of 13. He pursued a theology degree while an undergraduate. The university's records from this period reveal that he showed unusual proficiency in the classics, being able to recite Virgil's 12,000-line Aeneid by heart. No record survives of any mathematical accomplishments from this time, although there must have been some. When Leonhard received his master's degree in 1723, he dutifully followed his father's wishes and continued on at the university to pursue a doctorate in theology. That was not to be. Euler soon became friends with Johann II Bernoulli, 1710 to 1790, and together they attended the lectures of Johann I Bernoulli, 1667 to 1748, the father of Johann II and brother of Jacob, whose lectures Paulus had attended. Under the influence of both Bernoullis, the young Euler immersed himself in mathematics. Johann I Bernoulli soon recognized Euler's immense talents and offered him private lectures. Johann I would soon write that Euler was a young man of the most fortunate talents, from whose cleverness and acuteness we promise ourselves the greatest, having seen the ease and adroitness with which he has penetrated the most secret fields of higher mathematics under our auspices. Euler had many opportunities to exhibit the adroitness Bernoulli mentioned. In 1726, the Paris Academy sponsored a prize competition to determine the best way of setting up the masts on a sailing ship. Even though he had had no experience with sailing ships in landlocked Switzerland, his mathematical approach was so good that he came in second. That same year, Euler completed his dissertation on the theory of sound under the supervision of Bernoulli. This qualified him to apply for the vacant professorship of physics at the university. In spite of Bernoulli's ardent support for Euler, the university employed its standard method of drawing lots to reduce the field of applicants to just 3. Euler's was not among the 3 lots drawn. Switzerland's loss would be Russia's gain. In 1724, a year before his death, Tsar Peter the Great signed a decree founding a scientific academy in the new Russian capital, St. Petersburg. Peter invited the most distinguished scholars across Europe to his new academy. Among them were Nicholas II Bernoulli, 1695 to 1726, and Daniel Bernoulli, 1700 to 1782. As soon as they arrived in St. Petersburg, they recommended that the Academy invite Euler, their father's most brilliant student. Although Euler would never return to Switzerland, he retained his Swiss citizenship for the rest of his life. The Petersburg Academy offered Euler its chair in physiology. Euler quickly accepted and prepared for his new position by enrolling in Basel's medical faculty 3 days before he embarked for Russia. In reality, Euler chose to ignore the details of his initial appointment. Instead, he lectured in mathematics, physics, and logic. Euler would not be misplaced in the physiology chair for long. Daniel Bernoulli relinquished the physics chair to take up the mathematics chair when Jacob Hermann, its first holder, returned to Basel in 1730. That allowed Euler to take the vacant physics professorship. 2 years later, Bernoulli himself returned to Basel, thereby allowing Euler to take the mathematics chair. Peter the Great also had a practical end in mind when he founded the St. Petersburg Academy. He intended it to help modernize Russia. To that end, Euler made contributions in practical areas such as surveying, map-making, navigation, and once again, naval construction. Euler's income from these duties and his professorship allowed him to consider the prospect of marriage. He soon focused his attentions on Catherine Giselle, the daughter of a Swiss artist who also held an appointment at the Academy. Leonard and Catherine married just after Christmas 1733. Their first son, Johann Albert, was born not quite a year later. The Eulers would have 12 more children born to them over the next 17 years. Only 5 of them survived past early childhood. Euler often commented that he made many of his greatest mathematical discoveries while holding a baby in one arm and with other children playing at his feet. Perhaps those were the circumstances when he hit upon the first of his discoveries presented in this chapter. It dates from the middle of 1730s, shortly after he became a father for the first time. The analysis of infinite series goes back to the ancient Greeks' consideration of Zeno's paradoxes, most notably in Book 5 of Aristotle's Physics. The new mathematics of the 17th century provided an arsenal of new tools to inaugurate a new age of analysis of infinite series. Oh, dear me. In the late 17th century, Jacob Bernoulli proved that the harmonic series, sum of k equals 1 to infinity of 1 on k, diverges. Oh, I didn't know that diverged. Okay. He then raised the question of whether the sum of the inverse squares diverges or converges. Bernoulli turned his attention to another infinite series in order to answer this question. Triangular numbers are the numbers formed by the sum of the positive integers from 1 to n. For example, 1 equals 1, 3 equals 1 plus 2, 6 equals 1 plus 2 plus 3. More generally, n squared plus n on 2 equals 1 plus 2 plus blah, blah, blah. Okay. Bernoulli then proved that the series of inverse triangular numbers converges to the value 2, recognizing that 1 on n squared is less than or equal to 2 divided by n squared plus n. He easily proved that the sum of the inverse squares converges to a value no greater than 2. However, he was unable to determine that value. Bernoulli remarked, "If someone should succeed in finding what till now has withstood our efforts and communicate it to us, we shall be much obliged to him." This became known as the Basel problem in honor of Bernoulli. There is no record of Euler having studied number theory in Basel with his teacher Johann von Bernoulli, Jacob's younger brother. His interest in the subject seems to have been sparked in 1729 by Christian Goldbach, the first permanent secretary of the St. Petersburg Academy, and the person after whom Goldbach's conjecture that every even number greater than 2 can be expressed as the sum of 2 primes is named. Euler began to attack the Basel problem in 1731. By 1735 he had solved it. Now, however, against all expectation, I have found an elegant expression for the sum of the series 1 plus 1 on 4 plus 1 on 9 plus 1 on 16, etc., which depends on the quadrature of the circle. I have found that 6 times the sum of this series is equal to the square of the circumference of a circle whose diameter is 1. The series summed to pi squared on 6. Here is an outline of his proof. In 1715, the English mathematician Brooke Taylor had demonstrated that the trigonometric sine function can be expressed as the infinite series sine x equals x minus x cubed on 3 factorial plus x5 on 5 factorial minus x to the power of 7 on 7 factorial. Euler divided both sides of this equation by x, resulting in this expression. Notice that minus 1/3 factorial is the coefficient of the term in x squared. Okay, since the sine function takes the value 0 for all values plus or minus n pi, the equation just given has non-zero roots at plus or minus m pi for n equals 1, 2, 3, etc. Now Euler makes a daring leap. An nth degree polynomial, px, having non-zero roots a1, a2, a3 to an, and p0 equals 1, can be factored as follows. He leaps from this property of polynomials of finite degree to apply the property to the infinite degree polynomial just given with the sine function on the left-hand side to boot. Having done that, he arrives at sine x on x equals that monster. Okay, multiplying out the right side of this equation and collecting just the terms in x squared yields minus 1 on pi squared plus the sum from n equals 1 to infinity on 1 on n squared as the coefficient of x squared in sine x on x. Recalling that minus 1 on 3 factorial is the coefficient of the term in x squared, the left-hand side can be replaced by producing minus 1 on 6 equals minus 1 on pi squared times the sum of 1 on n squared for n equals 1 to infinity, or pi squared on 6. Quod erat demonstratum. Which is, that's the Latin for QED. Quod erat demonstrandum. Which means, thus ends the demonstration. Using the same methods, Euler also proved that the inverse fourth powers sum to pi to the power of 4 on 90, the sum of the inverse 6 powers sum to pi to the 6 on 945, and so on up to the sum of the inverse 26th powers, which equals this really big number. Interestingly, none of the sums of the inverse odd powers is yet known. Alright. Euler fell ill with what he described as a fiery fever in 1735, shortly after finishing the work just described. He recovered to full health after a long recuperation. Neither the fever nor the long recuperation slowed Euler's mathematical output. In 1736, Euler presented one of the first results in what he called the geometry of position, geometria situs. the study of relations dependent on position and not magnitude. Today, this is the branch of mathematics known as topology. The two branches of the Pregel River met in the Prussian city of Königsberg, 600 miles southwest of St. Petersburg, and Nienhof Island. Several bridges crossed the river. The people of Königsberg wondered if someone could take a walk crossing all of the bridges once and only once. This became known as the 7 Bridges of Königsberg problem. Most people doubted that such a walk was possible, but no one could prove it. Euler did. Our second Euler selection presents his analysis of this very problem. Euler realized that he could solve the problem of the bridges simply by enumerating all possible walks that crossed bridges no more than once. However, that approach held no interest for him. Instead, he generalized the problem to consider any configuration of the river and the branches into which it divides, as well as any number of bridges to determine whether or not it is possible to consider each bridge exactly once. Euler commented that he would first consider the sequence of land areas traversed without considering which bridges are used. If A, B, C, and D are the land areas in the 7 bridges problem, then A, B, D, C represents a sequence of crossing from A to B, B to D, and D to C. Euler begins his analysis by considering an extremely simple case: 2 land areas, A and B, connected by an arbitrary number of bridges. If one bridge connects a land area to A, then A can appear in a crossing sequence only once if that bridge is to be crossed only once. If 2 bridges connect to A, then A can appear in a crossing sequence only twice if each of those bridges is to be crossed only once. Generally, if an odd number n of bridges connect to A, then A can appear in a crossing sequence only n plus 1 divided by 2 times if each of the bridges is to be crossed only once. Returning to the particular details of the Königsberg problem, Euler noted that an odd number of bridges connected to each of the land areas, 5 to A, 3 to B, C, and D each. Given the result just described, the crossing must contain A 3 times, B, C, and D twice each, for a total of 9 letters in the crossing sequence. However, if each of the 7 bridges is to be crossed only once, such a crossing sequence can only contain A, B, C, and D a total of 8 times. Although Euler had solved the Königsberg problem, he did not stop there. He continued by noting that if an even number n of bridges connected to A, then A can appear in a crossing sequence only half n plus 1 times if A is a starting point for the journey, and only half n times if A is not a starting point for the journey, if each of the bridges is to be crossed only once. Having established that, Euler recognizes that every route must, of course, start in some region. Thus, from the number of bridges that lead to each region, I determine the number of times the corresponding letter will occur in the expression for the entire route as follows. When the number of bridges is odd, I increase it by 1 and divide by 2. When the number is, it says when the number if even, but it's probably when the number is even, I simply divide it by 2. Then, if the sum of the resulting numbers is equal to the actual number of bridges plus 1, the journey can be accomplished, though it must start in a region approached by an odd number of bridges. But if the sum is 1 less than a number of bridges plus 1, the journey is feasible if starting from a region approached by an even number of bridges, for in that case the sum is again increased by 1. Modern topology now treats land areas and bridges as vertices and edges connecting vertices. Euler's fever returned shortly after he finished his work on the 7 bridges problem. By 1738, he had lost vision in his right eye. Meanwhile, Peter the Great's widow, the Empress Catherine I, was continuing her husband's liberalizing from the Russian throne. However, she died in 1727, the year Euler arrived in Russia, and was followed by a rapid succession of weak rulers who were dominated by the old Russian nobility. As the years passed, the nobles, who wished to put the nation back on a path of Russification, became ever more suspicious of foreigners. The Holy Synod of the Russian Orthodox Church weighed in against the Academy because of its teaching of the new sciences in general and Copernican astronomy in particular. As Russia was pursuing a path of deliberalization, a new king to the west ascended his throne, planning on liberalizing his country. Frederick II, also known as the Great, ascended the Prussian throne in 1740 and immediately made plans to resurrect the Scientific Academy in his capital, Berlin, to be the equal of the academies in Paris, London, and St. Petersburg. Euler received one of the first invitations to join the new academy. Euler quickly accepted the invitation. The new director of the St. Petersburg Academy, Johann Schumacher, was a bureaucrat whose main goal seemed to be the suppression of talent wherever it might rear its inconvenient head, according to Euler. In his words, Russia had become a country where any person who speaks is hanged. Euler's wife was also eager to leave St. Petersburg for fear of the frequent fires that might consume their wooden house. Euler left St. Petersburg in June 1741, having published over 50 books and articles during his 14 years in the new Russian capital. He arrived in Berlin a month later and would remain in Berlin for a quarter century. While in Berlin, he continued his outpouring of work. He was so prolific that his new papers, about 380 of them, filled the pages of the journals of the academies in both Berlin, in French, and St. Petersburg, in Latin. During this period, Euler also wrote a number of popular textbooks. His Mechanica was the first work to present Newton's laws of motion using the framework of the new infinitesimal calculus. Euler's Introduction to Analysis of the Infinite, first published in 1748, is the best known textbook from this period. In this two-volume work, Euler presented the sum of the inverse squares as well as virtually every other result in mathematical analysis then known without using the techniques of the new and still controversial infinitesimal calculus. This text introduced generations of readers to the symbols cos and sine for the trigonometric functions, pi to represent the ratio of a circle's circumference to its diameter, I for the square root of -1, and finally the eponymous, I didn't know it was eponymous E, for the base of the integral logarithms. So it's E for Euler. I didn't know that. That's cool. It is no wonder that many historians of mathematics consider the introduction to be the equal of Euclid's Elements in terms of its impact. Euler's best-selling book from this period arose from his providing instruction in elementary science to the young princess of Anhalt-Dessau. Euler published these lessons as Letters of Euler on different subjects in natural philosophy addressed to a German princess. It contains over 200 letters on fields as diverse as logic, language, astronomy, gravity, light, sound, and magnetism. In addition, there are letters on particular questions, such as why the sky is blue, why the moon looks larger when it rises, and why it is cold at the top of a mountain in the tropics. Finally, because Euler was also responsible for providing moral training to the princess, the letters include his thoughts on the origins of evil and the conversion of sinners. In addition to his writing, Euler also found time to perform many other, more practical works. The king assigned Euler many tasks for the kingdom's benefit. These included correcting the level of the Finnow Canal, a major conduit for commerce in eastern Prussia, organizing state lotteries, and advising the government on issues concerning insurance, annuities, and widows' pensions. Euler also supervised the Academy's observatory and its botanical gardens. Frederick even asked Euler to supervise work on the plumbing system at Sans Souci, the royal summer residence. Euler hoped to be named the Academy's president after its first president, Pierre de Maupertuis, died in 1759. After all, he was the greatest scientist in Europe at mid-century. However, Euler lacked several key qualifications required by the king. He was Swiss rather than French. Moreover, by then Euler and his family were living on a farm outside of Berlin, hardly a sign of the worldly polish that Frederick greatly valued. In the end, King Frederick named another Frenchman, Jean Le Rond de l'Amber, to be the Academy's new president. The disappointed Euler immediately determined to leave Berlin. Euler had remained on extremely cordial terms with his former colleagues in St. Petersburg throughout his quarter century in Berlin. In recognition of the services he had previously rendered, the Academy in St. Petersburg sent him a regular stipend, even while Russia and Prussia were engaged in the 7 Years' War. By the mid-1760s, the ascent of Empress Catherine the Great had restored enough political order to Russia that Euler gladly accepted an offer to return to St. Petersburg. Of course, Euler needed Frederick's assent to leave Berlin. When he first wrote the king asking for his release, the king simply refused to answer. After 2 more letters of resignation, the king wrote back that Euler should withdraw his resignation and stop bothering him. Only Catherine the Great's intervention persuaded Frederick to release Euler. The king did this by sending a terse note that read, "With reference to your letter of April 30, I am giving you permission to resign in order to go to Russia." The Eulers returned to St. Petersburg in the summer of 1766 and moved into a house on the embankment of the river Neva, not far from the Academy. Back in St. Petersburg, the Eulers' life would not be easy. Leonard had developed a cataract in his good left eye during his last years in Berlin. It became much more severe after he returned to Russia and decided to have the occluded lens removed surgically. At first it appeared as though the surgery had been a success. However, complications arose and Euler soon lost the use of his left eye, leaving him with only the most meagre vision for the rest of his life. Shortly afterwards, Catherine's worst fears would be realized. In May 1771, a terrible fire swept through St. Petersburg, destroying over 500 houses along the Neva, including the Eulers. Only the efforts of Peter Grimm, a brave craftsman from Basel, saved the nearly blind Euler and his manuscripts from perishing as his house went up in flames. 2.5 years later, Euler became a widow when, in November 1773, his wife suddenly died at the age of 66. Euler persevered in his work in spite of the loss of his sight and his wife. In 1775, he wrote an average of 1 mathematics paper per week, dictating them to a scribe. No doubt Euler's prodigious memory, which had enabled him to memorize Aeneid in his teens, made it possible for him to continue his research. The second example of Euler's work presented here, his proof that every integer can be expressed as the sum of no more than 4 squares, dates from this period. In 1621, the French mathematician Claude Bachet, don't know how to pronounce that, conjectured that every positive integer can be expressed as the sum of no more than 4 squares. The great mathematical amateur Pierre de Fermat made some progress on this problem but was unable to provide a satisfactory proof. Euler did. In his proof, Euler. In his proof, Euler makes use of modular arithmetic. This proof depends critically on the fact that if k is not divisible by n, then am plus k squared and am minus k squared have the same remainder when divided by n. Therefore, if n is an odd prime, then half of the numbers of the form am plus b for b equals 1, 2 to n minus 1 are squares modulo n, and half are not. At about the same time that Euler published this proof, the English mathematician Edward Waring extended Bechet's original conjecture and asserted without proof that every positive integer can also be expressed as the sum of no more than 9 cubes, no more than 19 fourth powers, and that in general, for any power k, there is a value s such that every positive integer can be expressed as the sum of no more than s to the kth powers. In 1909, the German mathematician David Hilbert proved Waring's conjecture. Euler lived another decade following his wife's death, marrying her half-sister in July 1776. During early September 1783, he began to suffer from bouts of dizziness. The 7th of that month began as a normal day for Euler, spending the morning tutoring one of his grandchildren and then working out calculations for the orbit of the recently discovered planet Uranus. Later in the day, while taking tea and smoking a pipe, the pipe fell out of his hands. When he tried to pick it up, his pipe failed, and when he tried to pick up his pipe, he failed and soon collapsed, crying, "I am dying." He had suffered a stroke. He died later that night without regaining consciousness. It took the Academy's journal over 20 years to publish all of his remaining manuscripts. Wow. So, here's Leonhard Euler's on the sums of series of reciprocals. And here's the 7 bridges of Königsberg. And here's his proof that every integer is a sum of 4 squares, translated from the Latin by Professor E.T. Bell, California Institute of Technology, Pasadena, California. Fascinating. From this theorem, combined with the preceding, it follows obviously that every number is a sum of 4 or fewer squares. Pierre-Simon de Laplace, 1749 to 1827, his life and work. Critics of contemporary Darwinian biology often point to highly complex biological systems such as blood clotting that they describe as irreducibly complex, so complex that their evolution cannot be explained by Darwinian evolution. They cite this as evidence of intelligent design and, therefore, an intelligent designer. They would do well to cast their glance back 2 centuries to the accomplishments of Pierre-Simon de Laplace, perhaps the greatest mathematical physicist of all time. Isaac Newton's Principia unified and simplified all the physical science as it was then known to man, but it still left many questions unanswered, perhaps even unanswerable by physical science. Shortly after its publication in 1687, the Reverend Richard Bentley, one of Newton's earliest supporters and popularizers, presented the master with a question not considered in the Principia. Could the solar system, with the planets all revolving around the sun in the same direction in almost the same plane, be formed out of an initial uniform distribution of matter by the action of only natural causes, or was it evidence of design? Well, Newton believed that his system could in no way explain these obvious regularities in the heavens. He replied that most definitely they could not result from the action of only natural causes. The cause had to be not blind and fortuitous, but very skilled in mechanics and geometry. And so matters stood for nearly the entire 18th century until Pierre-Simon de Laplace blazed his way across the firmament of French science. Pierre-Simon de Laplace was born in a small town in Normandy in 1749. It is entirely possible that some of his distant uncles were among the Normans that invaded England in 1066 with William the Conqueror, but we can never know for sure. We do know that Laplace's father was a successful cider trader and that his mother came from a prosperous farming family. A comfortable background, to be sure, but one that might have suited a son to a career in the clergy or the military. That indeed is the educational path on which Laplace embarked, studying first at local Benedictine schools. At age 16, he matriculated at the nearby University of Caen, as my ignorance showing, intending to pursue a theology degree. However, Laplace soon discovered the joys of mathematics. After 2 years, he left Caen for Paris, the centre of French science. In Paris, Laplace quickly impressed the mathematician Jean de la Ronde-Lambert, who obtained a teaching position for his young protege at the École Militaire. In that position, Laplace taught geometry and trigonometry to cadets from good families, but with little interest in the subject. Nevertheless, the position allowed Laplace to remain in Paris, the centre of French, indeed global, mathematics. In 1770, Laplace began a rapid outpouring of papers on a wide variety of topics in pure and applied mathematics, drawing wide attention to himself. The most important papers focused on outstanding problems in planetary theory. The orbits of the two largest planets, Jupiter and Saturn, sometimes lag behind and sometimes ran ahead of their predicted position. Laplace sought to explain how the planets influenced each other in their orbits. This is a more difficult problem than the three-body problem, which even today can only be solved by successive approximations. Laplace demonstrated that perturbations were not cumulative, as Newton feared, but periodic. God did not need to intervene to keep the solar system from collapsing. Given this heady success, Laplace first sought election from the prestigious Académie des Sciences at the tender age of 22. Undismayed by his initial failure in 1771, he tried again the next year with the same result, losing the election to someone he considered to be a mediocre candidate who surpassed Laplace in only one dimension: age. Laplace never hesitated to let anyone know the high opinion he held of himself. Even in his early 20s, he considered himself the best mathematician in France. His mentors may not have held quite such a high opinion of the young Laplace, but they certainly recognized his talent. In 1773, D'Alembert and Lagrange conspired to have Laplace elected first to the Berlin Academy of Science and then as a special adjunct to the Paris Academy. With a place in the French scientific establishment secured, Laplace continued publishing profusely and teaching as necessary. In 1784, the army appointed him an examiner for the Royal Artillery Corps. This appointment secured Laplace an additional income and also gave him visibility to high government officials. But perhaps the most important relationship Laplace made from this appointment was with one of his first students, a 16-year-old from Corsica named Napoleon Bonaparte. In 1788, at the age of 39, Laplace married Marie Charlotte de Corti de Romanges. I don't know how to pronounce it. The daughter of a well-to-do squire from Besançon in the French Alps. She was not much more than half his age. Within a year, their marriage was blessed with the arrival of a son, Charles Emile, who went on who went on to have a distinguished military career, but died childless in 1874. Madame Laplace gave birth to a daughter, Sophie Suzanne, in 1792. Sophie married the Marquis de Parte, a minor Napoleonic noble. She died giving birth to Laplace's only grandchild, a child also named Sophie. Young Sophie later married the Comte de Cobot Cabernet, the scion of a major aristocratic family. Man, this book is making me feel like I don't know anything. They had many children, and Laplace's male descendants now bear the family name, Colbert Laplace. Engrossed as he was in science, Laplace had little time for the tumult of politics in the late 1780s and 1790s. He took no part in the affairs of the French Revolution during its most radical phase in the early 1790s, except to participate in the committee that devised the metric system, part of a systematic attempt to overthrow the shackles of the old regime. One camp argued that the fundamental unit of length should be defined in terms of the Earth's equatorial circumference. Laplace argued instead that given the role of the right angle in geometry, the fundamental unit of length should be based on the length of the quadrant from the North Pole to the equator. Thanks to Laplace's successful argument, the meter was defined as 1/10,000th of the distance from the pole to the equator. By the end of 1793, the political atmosphere in Paris became too intemperate for Laplace. Along with many other leading scientists, including Lavoisier and Coulomb, Laplace was purged from the committee devising the metric system. The radical Republicans loudly announced that such responsibilities could only be entrusted to men known for their Republican virtues and hatred of kings. Literally fearing for his neck, Laplace and his family fled from Paris to the country town of Melun, 30 miles away. In retrospect, Laplace had correctly judged the probabilities of the possible outcomes. His friend and colleague, the chemist Antoine Lavoisier, chose to remain in Paris, where he lost his head to the guillotine in the spring of 1794. Brutal. A semblance of order returned to Paris in July 1794 following the overthrow of the Jacobean dictatorship and its lead henchman, Robespierre. Shortly thereafter, the new government recalled Laplace to Paris to help French science recover from the radical excesses of the revolution. Laplace zestfully attended to his new role, naturally gravitating to a leadership role in the refounding of the great schools of learning, the École Normale Polytechnique and Centrale des Travaux Publics. I don't know how to pronounce it, sorry. The new government also reincarnated the Academy of Sciences as the Institute of France, which elected Laplace its vice president in December 1795, and then in April 1796, its president. The years following his 50th birthday saw the publication of Laplace's greatest work. In 1799, he published the first of what would eventually be 5 volumes of his epoch work, Mechanic Celesti, Celestial Mechanics. The last volume was published in 1825. During the course of the 18th century, astronomers discovered the planet Uranus as well as several additional moons of Saturn. All of the known planets and moons revolved in the same direction and almost in the Sun's equatorial plane. The Sun, planets, and the moons all rotated in the same direction as the Earth. If the commonality in all 29 motions was merely the result of chance, then the probability of that chance would be exceedingly small, 1/2 to the power of 29, about 1 in 100 billion. Laplace recognized that the regularity in the heavens had to have a physical cause, and he found it. He achieved what Newton had thought impossible. In the Celestial Mechanics, Laplace demonstrated how the solar system could have arisen from a whirling solar atmosphere with planets whose moons formed as rotating balls of gas that cooled and condensed, with the revolutions necessarily in the same direction in almost the same plane about the Sun. Laplace's work on probability began as early as 1780. In 1812, he published the first edition of his masterpiece in that area, Analytical Theory of Probabilities. Prior to Laplace, all mathematicians working in the area of probability had presumed that one could have knowledge of absolute probabilities of chance events. Laplace disagreed. Laplace had held that because the world is determined, there can be no probabilities in things. Probability results from our lack of knowledge. Laplace wrote that probability consists in reducing all events of the same kind to a certain number of equally possible cases, that is to say, those such that we are equally undecided about their existence. In so doing, Laplace expanded the scope of probability theory to include the probability of past causes of known events, as well as future outcomes. In the analytical theory, Laplace developed formula for assigning degrees of rational belief to propositions about past events. I'm going to take a break. In fact, I might be coming back to this tomorrow because I'm really weary. I'm back. So, this is the first time I've done a book teardown video that's taken more than one sitting to record. So I've done. I'm up to page 415, and this is the second recording session. I was working on this yesterday. I've been to bed. I've been asleep all night. I had a few things to do today. So now it's the next day, and we're going to continue. And I'm going to try and get this book finished today. So let's do that now. On we go. We're learning about Laplace, of course, as we were when I just left you. So let's pick up here. Laplace wrote, this is just recapping a little bit for my edification. Laplace wrote that probability consists in reducing all events of the same kind to a certain number of equally possible cases, that is to say, those such that we are equally undecided about their existence. In doing so, Laplace extended the scope of probability theory to include the probability of past causes of known events, as well as future outcomes. In the analytical theory, Laplace developed formula for assigning degrees of rational belief to propositions about past events. The concluding problem from the first chapter is a good example of the sort of problem that attracted Laplace. In this problem, Laplace begins with a ring of urns. One urn contains only black balls. Another urn contains only white balls. All of the other urns contain widely varied mixtures of black and white balls. Laplace considers the following process. Withdraw a ball from one urn, place it in the next urn. Shake that urn well. Withdraw a ball from that urn and place it in the next urn. Laplace demonstrated that eventually there would be the same ratio of black to white balls on all of the urns. In doing so, Laplace actually gave an example of the tendency of natural forces to impose order on even the most chaotic of systems, akin to his demonstration of the solar system's order. The critical success of the analytical theory of probabilities inspired Laplace to compose a popular version, the a philosophical essay on probabilities. First published in 1814 and reproduced here. Many commentators consider this essay the most complete, perfect argument ever made for a deterministic interpretation of the universe. The essay begins with the statement of 7 principles. 1. Probability is the ratio of the number of favorable cases to the number of all possible cases. 2. If the cases are not all equally possible, we must first determine their respective possibilities. 3. If events are independent of one another, the probability of their combined existence is the product of their respective possibilities. 4. When two events depend on each other, the probability of the compound event is the product of the first event and the probability that this event having occurred, the second one will occur. 5. If we calculate a priori the probability of the occurred event and the probability of an event composed of that one and a second one that is expected, the second probability divided by the first will be the probability of the event expected, drawn from the observed event. 6. Each of the causes to which an observed event may be attributed is indicated with just as much likelihood as there is probability that the event will take place, supposing the event to be constant. 7. The probability of a future event is the sum of the probabilities of the The probability of a future event is the sum of the products of the probability of each cause drawn from the event observed by the probability that, this cause existing, the future event will occur. Not surprisingly, the essay includes many problems involving coin tossing. Laplace wrote, "One regards two events as equally probable when one can see no reason that would make one more probable than the other, because, even though there is an unequal possibility between them, we know not which way, and this uncertainty makes us look on each as if it were as probable as the other." Thus, even if we are told that a coin is biased, we have no way of knowing the bias. That is, if we are ignorant of the bias, we begin with the assumption that it is a fair cause. When considering a run of 20 successive heads during a much longer run of coin tosses, Laplace asks whether the 20 successive heads are to be considered a chance event or the result of a cause. During the analysis, Laplace writes, "We look upon a thing as the effect of chance when we see nothing regular in it, nothing that manifests design, and when furthermore we are ignorant of the causes that brought it about. Thus, chance has no reality in itself. It is nothing but a term for expressing our ignorance of the way in which the various aspects of a phenomenon are interconnected and related to the rest of nature." Is the run of 20 heads a matter of chance or a manifestation of design? To the common person, it appears to be a regularity, but is it? Consider how this problem appears when playing the lottery, in which 6 numbers get picked out of 50. Many people avoid playing the set 1, 2, 3, 4, 5, 6, supposing that the set of 6 numbers shows much more regularity than the recent winning set of numbers. 6, 13, 15, 15, 32, 36. I don't know why you'd have a duplicate lotto number. That's quite odd. Okay, but Laplace would argue a thorough analysis of the lottery process would reveal the independence of each number's selection. Thus, the set 1, 2, 3, 4, 5, 6 shows neither more nor less regularity than the other set. Given the fact that a lottery payout depends on the number of winners, the very fact that many people would avoid playing 1, 2, 3, 4, 5, 6 is, in fact, a very good reason to play it. There would be less likelihood of anyone else having the same winning set of numbers. I'm a bit disappointed that Hawking just made that claim, because he doesn't have any evidence of that at all. It might be that lots and lots of people pick 1, 2, 3, 4, 5, 6 on the basis that it's just as likely as anything else. So I have to say, I will go as far to say that this statement from Hawking is disappointing. He doesn't have any evidence for this claim at all. He's just invented it. So, and it hasn't been tested. He doesn't know. So he shouldn't have made that claim, in my view. Anyway, on we go. In his later years, Laplace directed his focus to a wide variety of topics in mathematical physics: capillary action, double refraction, the velocity of sound, the shape and heat of the Earth, and elastic fluids. Laplace had no firm political views, other than making sure to keep his head firmly connected to the rest of his body so that he could pursue his scientific work. Napoleon had made him a member of the Senate, but in 1814 Laplace voted in favour of restoring the monarchy and exiling his former pupil and patron Napoleon to exile in Elba. When Napoleon briefly returned to power in 1815, Laplace once again exited himself from Paris. After Napoleon's defeat at Waterloo and exile to St. Helena, Laplace became a staunch supporter of the Bourbon monarchy. In return, Louis XVIII elevated Laplace to a peerage, making him a marquis in 1817. Shortly before his 78th birthday in 1827, Laplace died following 2 years of enfeeblement. In his funeral elegy, Fourier remarked that Laplace retained his extraordinary powers of memory and critical thinking until almost the end of his life. Fourier also remarked, Laplace was born to perfect everything, to deepen everything, to push back all the boundaries, to solve what was thought to be insoluble. In his funeral elegy, the mathematical Simon Denis Poisson remarked, for Laplace, mathematical analysis was an instrument that he bent to his purposes for the most varied applications, but always subordinating the method itself to the content of each question. Surely the Mécanique Céleste was Laplace's supreme achievement in the application of mathematical analysis. Laplace dedicated the third volume of his Mécanique Céleste to Napoleon. After browsing through the vast volume, Napoleon commented that he saw no mention of God. On hearing this, Laplace responded, Sire, there is no need of that hypothesis. Darwin's modern critics might do well to remember that. And here we are. I've read this before. I've actually got this in a book form, this essay, a philosophical essay on probabilities. It's a bit odd for an essay to have chapters, wouldn't you say? Fair enough. Now, I don't think we're going to read the whole thing, are we? It's pretty long. Well, let's just read chapter 1, and let's see how it finishes as well. Oh, it's an essay in parts and chapters. Oh my. Wow, it's long, isn't it? I should say I'm not surprised. The book that I have is, it's a book, not just an essay. I might just call out the chapters. We'll go over this again. This is really long. Wasn't expecting it to be this long. Okay, so it's 100 pages long. Look at that. A bit more, in fact. 101 pages, or not quite. Yeah, call it 100. Okay. Well, I'm not going to read the whole thing, but I will read the introduction, and then I'll call out the chapter headings, so we have an idea of what's covered in these 100 pages. So this is a philosophical essay on probabilities by Pierre-Simon de Laplace. Okay, Chapter 1, Introduction. This philosophical essay is the development of a lecture on probabilities which I delivered in 1795 to the normal schools whither I had been called by a decree of the National Convention as Professor of Mathematics with Lagrange. I have recently published upon the same subject a work entitled The Analytical Theory of Probabilities. I present here, without the aid of analysis, the principles and general results of this theory, applying them to the most important questions of life, which are indeed for the most part only problems of probability. Strictly speaking, it may even be said that nearly all our knowledge is problematical, and in the small number of things which we are able to know with certainty, even in the mathematical sciences themselves, the principal means for ascertaining truth, induction and analogy, are based on probabilities, so that the entire system of human knowledge is connected with the theory set forth in this essay. Doubtless it will be seen here with interest that in considering, even in the eternal disciplines of reason, justice, and humanity, only the favourable chances which are constantly attached to them, there is a great advantage in following these principles, and serious inconvenience in departing from them. Their chances, like those favourable to lotteries, always end by prevailing in the midst of the vacillations of hazard. I hope that the reflections given in this essay may merit the attention of philosophers and direct it to a subject so worthy of engaging their minds. Chapter 2, Concerning Probability. Chapter 3, The General Principles of the Calculus of Probabilities. Chapter 4, Concerning Hope. Chapter 5, Concerning the Analytical Methods of the Calculus of Probabilities. Actually, let's read the chapter concerning hope. Who doesn't want to know about hope? Let's hear about hope. The probability of events serves to determine the hope or the fear of persons interested in their existence. The word hope has various acceptations. It expresses generally the advantage of that one who expects a certain benefit in suppositions which are only probable. This advantage in the theory of chance is a product of the sum hoped for by the probability of obtaining it. It is the partial sum which ought to result when we do not wish to run the risks of the event in supposing that the division is made proportional to the probabilities. This division is the only equitable one when all strange circumstances are eliminated, because an equal degree of probability gives an equal right to the sum hoped for. We will call this advantage mathematical hope. Eighth principle. When the advantage depends on several events, it is obtained by taking the sum of the products of the probability of each event by the benefit attached to its occurrence. Let us apply this principle to some examples. Let us suppose that at the play of heads and tails, Paul receives 2 francs if he throws heads at the first throw, and 5 francs if he throws it only at the second. Multiplying 2 francs by the probability half of the first case, and 5 francs by the probability 1/4 of the second case, the sum of the products, or 2 1/4 francs, will be Paul's advantage. It is the sum which he ought to give in advance to that one who has given him this advantage, for, in order to maintain the equality of the play, the throw ought to be equal to the advantage which it procures. If Paul receives 2 francs by throwing heads at the first and 5 francs by throwing it at the second throw, whether he has thrown it or not at the first, the probability of throwing heads at the second throw being 1 on 2, multiplying 2 francs and 5 francs by half the sum of these products will give 3 1/2 francs for Paul's advantage, and consequently for his stake at the game. Ninth principle. In a series of probable events, of which the ones produce a benefit and the others a loss, we shall have the advantage which results from it being from it by making a sum of the products of the probability of each favorable event by the benefit which it produces, and subtracting from this sum that of the products of the probability of each unfavorable event by the loss which is attached to it. If the second sum is greater than the first, the benefit becomes a loss and hope is changed to fear. Consequently, we ought always, in the conduct of life, to make the product of the benefit hoped for by its probability at least equal to the similar product relative to the loss. But it is necessary, in order to attain this, to appreciate exactly the advantages, the losses, and their respective probabilities. For this a great accuracy of mind, a delicate judgment, and a great experience in affairs is necessary. It is necessary to know how to guard oneself against prejudices, illusions of fear or hope, and erroneous ideas of fortune and happiness, with which the majority of people feed their self-love. The application of the preceding principles to the following question has greatly exercised the geometricians. Paul plays at heads and tails with the condition of receiving 2 francs if he throws heads at the first throw, and 4 francs if he throws it only at the second throw. 8 francs if he throws it only at the third, and so on. His stake at the play ought to be, according to the 8th principle, equal to the number of throws, so that if the game continues to infinity, the stake ought to be infinite. However, no reasonable man would wish to risk at this game even a small sum, for example 5 francs. Whence comes this difference between the result of calculation and the indication of common sense? We soon realize that it amounts to this, that the moral advantage which a benefit procures for us is not proportional to this benefit, and that it depends upon 1,000 circumstances, often very difficult to define, but of which the most general and most important is that of fortune. Indeed, it is apparent that 1 franc has much greater value for him who possesses only 100 than for a millionaire. We ought then to distinguish in the hoped-for benefit its absolute from its relative value. But the latter is regulated by the motives which make it desirable, whereas the first is independent of them. The general principle for appreciating this relative value cannot be given, but here is one proposed by Daniel Benoli, which will serve in many cases. The 10th principle. The relative value of an infinitely small sum is equal to its absolute value divided by the total benefit of the person interested. This supposes that every one has a certain benefit whose value can never be estimated as 0. Indeed, even that one who possesses nothing always gives to the product of his labor and to his hopes a value at least equal to that which is absolutely necessary to sustain him. If we apply analysis to the principle just propounded, we obtain the following rule. Let us designate by unity the part of the fortune of an individual independent of his expectations. If we determine the different values that his fortune may have by virtue of these expectations and their probabilities, the product of these values raised respectively to the powers indicated by their probabilities will be the physical fortune pardon me, which would procure for the individual the same moral advantage which he receives from the part of his fortune taken as unity and from his expectations. Excuse me for a sec. I'm back. By subtracting unity from the product, the difference will be the increase of the physical fortune due to expectations. We will call this increased moral hope. It is easy to see that it coincides with mathematical hope when the fortune taken as unity becomes infinite in reference to the variation which it receives from the expectations. But when these variations are an appreciable part of this unity, the two hopes may differ very materially among themselves. This rule conduces to results conformable to the indications of common sense, which can by this means be appreciated with some exactitude. Thus, in the preceding question, it is found that if the fortune of Paul is 200 francs, he ought not reasonably to stake more than 9 francs. The same rule leads us again to distribute the danger over several parts of a benefit expected, rather than to expose the entire benefit to this danger. It results similarly that at the fairest game, the loss is always greater than the gain. Let us suppose, for example, that a player having a fortune of 100 francs risks 50 at the play of heads and tails. His fortune after his stake at the play will be reduced to 87 francs. That is to say, his last sum would procure for the player the same moral advantage as the state of his fortune after the stake. The play is then disadvantageous, even in the case where the stake is equal to the product of the sum hoped for by its probability. We can judge this of the immorality of games in which the sum hoped for is below this product. They subsist only by false reasonings and by the cupidity which they excite, and which, leading the people to sacrifice their necessaries to chimerical hopes, whose improbability they are not in condition to appreciate, are the source of an infinity of evils. Fair enough. The disadvantage of games of chance, the advantage of not exposing to the same danger the whole benefit that is expected, and all the similar results indicated by common sense, subsist, whatever may be the function of the physical fortune which for each individual expresses his moral fortune. It is enough that the proportion of the increase of this function to the increase of the physical fortune diminishes in the measure that the latter increases. Interesting. All right, chapter 5, concerning the analytical methods of the calculus of probability. Okay, now we're up to part 2, applications of the calculus of probabilities. Chapter 6, games of chance. Chapter 7, concerning the unknown inequalities which may exist among chances which are supposed equal. Chapter 8, concerning the laws of probability which result from the indefinite multiplication of events. Chapter 9, the application of the calculus of probabilities to natural philosophy. This is a long chapter. Chapter 10, application of the calculus of probabilities to the moral sciences. Chapter 11, concerning the probabilities of testimonies. Chapter 12, concerning the selections and the decisions of assemblies. Chapter 13, concerning the probability of the judgment of tribunals. Chapter 14, concerning tables of mortality and of mean durations of life, of marriages and of associations. Chapter 15, concerning the benefits of institutions which depend upon the probability of events. Chapter 16, concerning illusions in the estimation of probabilities. Chapter 17, concerning the various means of approaching certainty. Chapter 18, historical notice concerning the calculus of probabilities. And that's it. Let's read the final paragraph. It is seen in this essay that the theory of probabilities is at bottom only common sense reduced to calculus. It makes us appreciate with exactitude that which exact minds feel by a sort of instinct without being able oft times to give a reason for it. It leaves no arbitrariness in the choice of opinions and sides to be taken, and by its use can always be determined the most advantageous choice. Thereby it supplements most happily the ignorance and the weakness of the human mind. If we consider the analytical methods to which this theory has given birth, the truth of the principles which serve as a basis, the fine and delicate logic which their employment in the solution of problems requires, the establishments of public utility which rest upon it, the extension which it has received and which it can still receive by its application to the most important questions of natural philosophy and the moral science, if we consider that, again, that, even in the things which cannot be submitted to calculus, it gives the surest hints which can guide us in our judgments, and that it teaches us to avoid the illusions which ofttimes confuse us, then we shall see that there is no science more worthy of our meditations, and that no more useful one could be incorporated in the system of public instruction. Good one. All right, now we're up to Jean-Baptiste Joseph Fourier. Now, I'm pretty sure that we call it Fourier because you got the Fourier transform, but I would have thought the French would call it Fourier. But I don't know. I'm going to call him Fourier because that's how I've heard, Fourier transforms just pronounced. So he was born 1768 and he died in 1830. And this is what Stephen Hawking had to say about his life and work. Introduction of a new tool into a field of intellectual endeavour often sparks a spate of remarkable results in that field. Jean-Francois Champollion's decipherment of the Rosetta Stone in 1822 proved such a spark to the field of Egyptology. Researchers were suddenly able to translate the hieroglyphs found in Egyptian antiquities. In that same year, Jean-Baptiste Joseph Fourier published his groundbreaking work, The Analytical Theory of Heat, which paved the way for significant breakthroughs in mathematics and mathematical physics during the remainder of the 19th century. It is no coincidence that these new tools appeared at the same time. Champollion was a protege of Fourier, who was the leader of the French scientific expedition that discovered the Rosetta Stone in 1799. During his lifetime, Fourier was better known as a serious Egyptologist and able government official than as a mathematical physicist. Today, we remember him by the mathematical tools that bear his name. The vernal equinox of 1768 heralded the arrival of another spring season in France. It also marked the birth of Jean-Baptiste Joseph Fourier in the town of Auxerre, about 100 miles southeast of Paris. Fourier was the 9th of 12 surviving children born to the tailor Joseph Fourier and his second wife, the former Edme Germaine Lebig. Sorry about the pronunciation. Monsieur Fourier Sr. had also sired 3 children by his first wife. Little is known of Fourier's early childhood beyond the fact that his father and mother died in quick succession before his 9th birthday. A Madame Moiton rescued the orphan Fourier from total misfortune by paying his tuition to the École Royale Militaire, I don't know what that is, local military school run by the Benedictine order. It was there that Fourier first discovered the joys of mathematics, devoting all of his spare time to his newfound joy as he prepared for a career as a military officer. After graduating from the local military school in 1787, Fourier hoped to continue his education at the Benedictine College de Montiagu in Paris. But for some reason, his application was rejected. Finding his way to a military career blocked, Fourier pursued another calling common to bright young Frenchmen without other prospects, the priesthood. He became a novice at the Benedictine Abbey of Saint Benet-sur-Loire in the town of Fleury, near the city of Orleans. In short time, the head abbot recognized Fourier's intellectual brilliance and put him in charge of the abbey's teaching program, a heavy load for someone also studying for the priesthood. Soon, however, Fourier began to doubt whether he truly had a vocation to the priesthood. He yearned to work more intensely with mathematics and physics, and as is evidenced by this note to a friend. Yesterday was my 21st birthday. At that age, Newton and Pascal had already acquired many claims to immortality. Fourier's first significant mathematical research was conducted at the Abbey. In 1789, he submitted a paper on a problem in the theory of equations to the Academy of Sciences in Paris. The noted mathematicians Adrien-Marie Legendre and Gaspard Monge recommended the paper for publication in the fall. However, the paper's publication was thwarted when, on July 14, 1789, a mob stormed the Bastille and the French Revolution began. The cancelled publication was the least of the impacts the French Revolution would have on Fourier. Shortly after the storming of the Bastille, Fourier left the Abbey. He returned to his hometown where he began teaching philosophy, history, rhetoric, and mathematics for the École Royale Militaire. The revolutionary milieu worked its effects on the young Fourier, who, in his later years, wrote, "As the natural ideas of equality developed, it was possible to conceive the sublime hope of establishing among us a free government, exempt from kings and priests, and to free from this double yoke the long usurped soil of Europe. I readily became enamored of this cause, in my opinion the greatest and most beautiful which any nation has ever undertaken." Oh wow. Fourier matched his actions with his passions and joined Auxerre's Municipal Committee on Surveillance, which was charged with enforcing government decrees. More ominously, Fourier also joined the local Popular Society, which had aligned itself with the revolutionary Jacobin Party. The leading Jacobins, most notably Robespierre, believed that an energetic, centralized state was essential to consolidate the advances achieved by the revolution. By the middle of 1793, the Jacobins purged members of the more tolerant Girondist party from the National Convention. Fourier became known as a prominent speaker at the meetings of Auxerre's Popular Society. At one meeting, he spoke so persuasively on the need for men to serve in the French army that the area's quota was filled exclusively by volunteers. He also strove to protect Auxerre's citizens from the reign of terror that Robespierre and his Committee of Public Safety inflicted on France. In 1794, Fourier's stinging criticism of corruption among his fellow officials led the committee to issue a decree for his arrest and execution by the guillotine. Fourier went to Paris to plead his case, but it was to no avail. When he returned home, the local surveillance committee issued the order for his arrest and execution, but the public outcry in his support was so great that the order was repealed. 8 days later, however, Fourier was arrested and imprisoned after the order was reinstated under pressure from the Committee of the Public Safety in Paris. Once again, Auxerre's citizenry rallied to Fourier's support. They sent a delegation to Paris to meet with Claude Louis Saint-Just, Robespierre's colleague on the Committee of Public Safety. After much effort, Fourier's supporters convinced Saint-Just to order his release. Soon, however, none of this would matter. The reign of terror suddenly ended when Robespierre, Saint-Just, and other leading Jacobins were arrested and sent to the guillotine. A general amnesty followed, and Fourier was released. The Jacobin-controlled National Convention left a legacy in the area of higher education that had a profoundly positive impact on Fourier's career. In 1794, it decreed that the establishment of the École Normale in Paris to teach university-level courses appropriate to the new revolutionary environment. The convention intended the École Normale to be different from the specialized institutions of higher learning, such as the School of Mines, which the monarchy had established. In sharp contrast, the École Normale offered a wide range of courses taught by the best scholars in France. Its mathematics faculty included the renowned mathematicians Joseph Louis Lagrange, Pierre-Simon Laplace, and Mong. Fourier's home district quickly chose him to be a student at the École Normale. The École Normale, I have no idea how to pronounce it. The École Normale had an even shorter life than did many of the French Revolution's creations. It opened its doors on January 1795 and closed them that May. Wow. Fortunately for Fourier, this was long enough for him to make a very significant impression on Mong. In 1794, the convention established the École Polytechnique to provide training in engineering and applied sciences for students who would be directed towards the military. When the École Normale closed its doors, many science and engineering students transferred to the École Polytechnique. Although Fourier wished to do so as well, the École Polytechnique had an upper age limit of 20 for entering students, and he was 25. Thanks to Mong's assistance, Fourier overcame this hurdle. At first, Mong tried to secure a teaching position for Fourier, but the school had no budget for additional teaching staff. Mong then secured Fourier an appointment as Administrateur de Police, which made him responsible for maintaining discipline in the lecture hall. Fourier's diary reveals that he assisted Mong in a course on the use of science and mathematics in military contexts. Fourier's earlier Jacobin connections haunted him one final time while he was at the Polytechnic. The government that replaced Robespierre was, in many respects, no better than its predecessor. It suspected conspiracies around every corner. It arrested Fourier because of his Jacobin connections and connections with the Robespierre, even though Robespierre himself had ordered Fourier's arrest. By August, the government agreed to release Fourier after hearing pleas from Lagrange, Laplace, Mong, and Fourier's students. In 1797, Fourier succeeded Laplace as professor of analysis and mechanics, even though he had completed hardly any original research in science or mathematics. This would soon change. He published his first mathematical result in 1798, a new proof of Descartes' rule of signs. In the polynomial fx equals x to the power of m plus a1 x to the power of m minus 1 plus ... plus am, two successive coefficients are called combinations. If they have the same sign, the combination is called a permanence. If they have different signs, the combination is called a variation. Descartes' rule says that the number of positive roots does not exceed the number of variations, and the number of negative roots does not exceed the number of permanences. Fourier gave a vastly simplified proof. Fourier was flush with the success of his first publication when his research and teaching career soon received an unanticipated interruption. In early 1798, the French government named Napoleon Bonaparte to head a military expedition into Egypt. Napoleon asked Mong and the chemist Claude Louis Berthollet to choose the scientific members of the expedition. In May, Mong chose his pupil and colleague Fourier. 3 months later, Fourier was named perpetual secretary of the Institute of Egypt. Napoleon took the expedition to Egypt in late July 1798 and then left in August 1799 to return to Paris to seize power as first consul. A few months before he left, Napoleon named Fourier leader of one of two scientific expeditions that spent the autumn of 1799 investigating the monuments and inscriptions in Upper Egypt. Fourier's expedition team discovered the Rosetta Stone in July 1799. There you go. Fourier remained in Egypt with the expedition for 2 more years until the Anglo-French Peace Treaty of 1801 forced the French to withdraw and relinquish the Rosetta Stone to the English. With the Egyptian expedition drawing to an end, Fourier hoped to secure his teaching post at the Polytechnic. Napoleon had other plans for him. In the few months they had spent together on the expedition, Napoleon had become impressed with Fourier's diplomatic and military talents. By 1801, Napoleon had assumed absolute power in France and needed no one else's approval to appoint Fourier to the post of prefect of the Isère department, which was based in the city of Grenoble near the Italian border. The post carried a heavy load. The prefecture had to carry out the orders of the central government while at the same time being responsive to the needs of its own citizens. Fourier carried out his appointment with intensity and integrity. While many prefects used their position to place cronies from Paris or their home district into positions of local power, Fourier did just the opposite. He made sure to appoint deserving local citizens to important posts, among them Jean-Francois Champollion, who would later decipher the Rosetta Stone. When Napoleon made a grand visit to Grenoble in February 1804, just 3 months before crowning himself emperor, he made Fourier a chevalier of the newly formed Legion of Honor. 5 years later, Napoleon elevated Fourier to the title of baron. While diligently acting as prefect, Fourier yearned to be free of governmental responsibilities so that he could pursue his scientific interests. In 1807, Mong and Berthollet tried to persuade Napoleon to release Fourier from his duties, but Napoleon would hear nothing of the kind. Fourier toiled on with his governmental duties even as he began to suffer bad attacks of rheumatism in Grenoble's chilling winds. He briefly considered going into exile as a way to rid himself of his onerous governmental duties and find a healthier climate. Somehow, Fourier found enough time in 1807 to work out his theory of heat diffusion. At the very end of the year, he presented an essay entitled On the Propagation of Heat in Solid Bodies to the Institut de France. This essay was a precursor to the analytical theory of heat that would appear 15 years later. The Institute appointed the mathematicians Sylvestre Francois Lacroix, Mong, Laplace, and Lagrange to a committee to determine whether the work was worthy of publication. The first 3 members approved publication. Lagrange withheld his approval because he objected to Fourier's expansion of functions by the trigonometrical series known as the Fourier series, the very piece of mathematics produced here, for which Fourier is best remembered. Finding few rewards to his scientific researches, Fourier turned his attention to the multi-volume Description of Egypt, for which he was the general editor. It ultimately ran to 20 volumes and took 20 years, between 1808 and 1827, to complete. On New Year's Day, 1810, the Institute of France announced that it would offer a prize for the best work on the mathematical theory of heat and its conformation. In addition, the Institute pledged to publish the work in its house journal or independently if the reviewers found the winning entry deserving. On September 23, 1811, a week before the close of entries, the Institute received an entry from Monsieur Antoine Cardon Michels of Bourges, I don't know how to pronounce it, who submitted a 21-page essay describing heat as a symbol of man's return to the fire. Fourier's 215-page manuscript arrived 5 days later. It was a revision of his 1807 memoir. Lagrange, Laplace, and Monge served on the review committee along with Etienne Louis Malus and René Jashuet. Once again, Lagrange objected to Fourier's work, but he had to agree that Fourier's work was the best entry submitted. Lagrange was able to block independent publication of Fourier's essay and force its publication to a regular issue of the Institute's House Journal. As it turned out, no issues of the House Journal, the Memoir Presents Par divers Savants, I don't know what that is, were published between 1811 and 1827. Oh wow. Even though Lagrange and his opposition to Fourier's mathematics died in April 1813, Fourier realized that the only way to guarantee publication of his work would be to revise it into book form and publish it on his own. During his period of revising, Napoleon abdicated in April 1814. Although Fourier's allegiance to Napoleon put him at risk of prosecution by the newly restored monarchy, the new government recognized that he had always acted with integrity while prefect of Vizier. Because of this, he was asked to continue in that office. I'm just going to take a break. Back. Napoleon's return from exile in Elba a year later severely tested Fourier's allegiance. He prepared the city's defenses against Napoleon. Fourier fled Grenoble just before Napoleon forced open its gates on March 7, 1815. The next day, Napoleon issued a decree removing Fourier from the prefecture, about 8 years too late for Fourier's liking. However, the two old comrades met the very next day outside the gates of Grenoble, and Napoleon immediately named Fourier prefect of the nearby Rhone department, based in its capital, the city of Lyon. Fourier had little choice but to accept the appointment, otherwise Napoleon might have imprisoned him. Fourier soon resigned when he received an order from Paris that would have forced him to remove all officials who had expressed royalist sympathies. Fourier doubted Napoleon's prospects of remaining in power. Sure enough, on June 18th, the combined English and Prussian armies defeated Napoleon at the Battle of Waterloo. 4 days later, Napoleon abdicated and was exiled to St. Helena in the South Atlantic. On July 8, King Louis XVIII re-entered Paris, and the Bourbon monarchy was re-established. Fourier's flip-flop between the monarchy and Napoleon put him in a bad light with the new government. He was finally free of his governmental duties, but had very few prospects for an income. He applied to the new government for a pension. At first, the government was inclined to grant the pension, but it ended up refusing to do so. Once again, a former student and colleague came to Fourier's aid. The Comte de Chabrol de Volvic, a former student and a former colleague on the Egyptian expedition, had become the new government's prefect of the sign department, which included the capital city of Paris. He offered Fourier the directorship of the Bureau of Statistics for the department, a position that could provide him with a reasonable income. Fourier remained in this position for the rest of his life. Initially, the new king refused to approve Fourier's election to the scientific section of the Institute of France. The king had Monge expelled because of his ties to Napoleon. In 1817, however, the king relented and Fourier was elected to the Academy of Sciences. In 1822, Fourier became one of its perpetual secretaries. The year 1822 also marked the publication of the crowning achievement of Fourier's career, the analytical theory of heat. Fourier's main concern in this work is the diffusion of heat in solid bodies. Our main interest in chapter 3 presented in this chapter 3 presented in this volume. In this chapter, Fourier demonstrates that an arbitrary function fx can be expressed in the interval from negative pi to positive pi as the infinite trigonometric series half a0 plus the sum of a n cos nx Oh, it's this monster. I'm not going to try and pronounce that. The great Swiss mathematician Daniel Bernoulli first suggested such an infinite series representation in the late 1740s as he was developing a mathematical analysis of vibrating musical strings. However, Bernoulli was unable to determine the values of the coefficients of the series. Determining their values was Fourier's greatest accomplishment. As early as his 1807 essay, Fourier had demonstrated the following. So we've got A0, AN, and BN. Briefly, Fourier determines these values as follows. He begins by supposing this and proceeds as follows. To determine the value of the coefficient A0, Fourier integrates both sides of the equation over the interval -pi to +pi. To determine the values of the coefficients an, Fourier multiplies both sides of the equations by cos mx and then integrates over the interval -pi to +pi. To determine the value of the coefficient bn, Fourier multiplies both sides of the equation by sine mx and then integrates over the interval -pi, +pi. Fourier made two key assumptions. First, he assumed the integrability of the function fx. Second, he assumed that the integral of the infinite sums, for example, this monster, was identical to the infinite sum of the integrals, for example. Okay. This is a distributive property of definite integrals over infinite sums. Okay. During the rest of the 19th century, mathematicians spent a good deal of effort determining the range of functions for which these assumptions are valid. Fourier was in his mid-50s when he finally published the analytical theory of heat. He was beginning to suffer from ill health, especially chronic rheumatism. He might also have been suffering from malaria, which he might have caught during his time in Egypt. He never married, although his acquaintances said he was extremely fond of the company of intelligent women, among them Sophie Germain, one of the most prominent female mathematicians. One of the first prominent female mathematicians. On May 4, 1830, Fourier was stricken with a severe attack of rheumatism. He died on May 16, 1830, of nervous angina and heart problems, according to his doctors. Fourier's accomplishment in physics revolved around his solution of the problem of heat diffusion in solid bodies. This problem stood outside the scope of rational and celestial mechanics that had dominated physics since the days of Isaac Newton. From this perspective, Fourier's work formed a major achievement in the field of mathematical physics. In the course of his work, he developed a new mathematical technique that would not likely have arisen otherwise. It paved the way for many advances in both mathematical physics and pure mathematics during the remainder of the 19th century and remains a primary analytical tool in both areas. The great British mathematical physicist Lord Kelvin would later write of him. Fourier's theorem is not only one of the most beautiful results of modern analysis, but it is said to furnish an indispensable instrument in the treatment of nearly every recondite question in modern physics. Fourier is a mathematical poem. There you go. So this is a selection from The Analytical Theory of Heat, Chapter 3, Propagation of Heat in an Infinite Rectangular Solid. Fascinating. It's infinite and rectangular. Alright. So let's read the introduction. Section 1. Statement of the problem. Problems relative to the uniform propagation or to the varied movement of heat in the interior of solids are reduced by the foregoing methods to problems of pure analysis, and the progress of this part of physics will depend in consequence upon the advance which may be made in the art of analysis. The differential equations which we have proved contain the chief results of the theory. They express, in the most general and most concise manner, the necessary relations of numerical analysis to a very extensive class of phenomena, and they connect forever with mathematical science, one of the most important branches of natural philosophy. It remains now to discover the proper treatment of these equations in order to derive their complete solutions and an easy application of them. The following problem offers the first example of analysis which leads to such solutions. It appeared to us better adapted than any other to illustrate the elements of the method which we have followed. And off we go. Section 2. First example of the use of trigonometric series in the theory of heat. Section 3. Remarks on these series. Section 4. General solution. Section 5. Finite expression of the result of the solution. Section 6. Development of an arbitrary function in trigonometric series. Section 7, application to the actual problem. And there it is. It is easy to ascertain the relations of this integral to the general integral, which has two arbitrary functions. These functions are by the very nature of the problem determinate, and nothing arbitrary remains but the function f alpha, considered between the limits alpha is 0 and alpha is pi. Equation A represents, under a simple form, suitable for numeric applications, the same value of V reduced to a convergent series. If we wished to determine the quantity of heat which the solid contains when it is arrived at its permanent state, we should take the integral of dx dy v from x equals 0 to x equals pi, and from y equals 0 to y equals infinity. The result would be proportional to the quantity required. In general, there is no property of the uniform movement of heat in a rectangular plate, which is not exactly represented by this solution. We shall next regard problems of this kind from another point of view and determine the varied movement of heat in different bodies. There you go. So we're about halfway through this book now, and we're up to Carl Friedrich Gauss, 1777 to 1855, his life and work. In 1940, the eminent British mathematician G.H. Hardy, wrote, 317 is a prime, not because we think so, or because our minds are shaped in one way rather than another, but because it is so, because mathematical reality is built that way. Could this attitude towards mathematics explain why Carl Friedrich Gauss, unquestionably the greatest mathematician of all time, withheld from publication his work in non-Euclidean geometry while seeking an empirical verification he would never find? Perhaps, but we will never know with certainty. What we do know with certainty is the enormity of Gauss's mathematical gifts and his accomplishments. Gauss's talents were obvious as soon as he stepped into a classroom at the age of 7. When the class began to be unruly, the teacher, J.G. Butner, assigned them the task of adding up all the integers from 1 to 100. As his classmates struggled to fit their calculations on their individual slates, Gauss wrote the answer immediately, 5,050. As soon as the problem was stated, Gauss recognized that the set of integers from 1 to 100 was identical to 50 pairs of integers, such each adding up to 101. 1 in 100, 2 in 99, so on through to 50 and 51. Herr Butner approached Gauss's parents to persuade them to let their son stay after school for special math instruction. Gauss's parents were at first skeptical. They had recognized their son's calculating ability when, at the age of 3, he corrected a mistake his father made in paying out wages to men who worked him. However, the elder Gausses had very limited horizons. Gauss's father, Gebhard, born in 1744, was a gardener, labourer, and foreman who came from a long line of poor, unlettered workmen who had had little success escaping their peasant roots in the lower middle class. His mother, born Dorothy Benz in 1743, was a maid before becoming Gebhard's second wife in 1776. Their only son, Carl Friedrich, was born a year later in the city of Brunswick, the capital of a duchy of the same name. In one respect, Gauss was very fortunate that his parents had such limited horizons and did not abuse his talents. Otherwise, they might have taken him on tour and exhibited him as a calculating prodigy, in much the same way that Mozart's father had taken young Wolfgang on tour as a musical prodigy. By his early teens, Gauss had worked out 2 methods to compute square roots to as many as 50 decimal places. He is reputed to have read tables of logarithms and found slight errors many places to the right of the decimal point. This computational facility would serve Gauss very well later in life. Fortunately, he was to have as close to a regular education as possible for someone of his gifts. At the age of 11, Gauss entered the local gymnasium and received a thorough education in the classics. His real math education came in one-on-one instruction after school and on his own as he devoured the contents of works like Newton's Principia and Bernoulli's Ars Conjectandi in his spare time. Gauss achieved such a distinguished record at the gymnasium that at the age of 15, Karl Wilhelm Ferdinand, Duke of Brunswick, gave Gauss a stipend to continue his education at the Brunswick Collegium Carolinum. Gauss entered the Collegium already possessed of a scientific and classical education worthy of a graduate. 3 years later, he left the Collegium in 1795, having done enough mathematics to fill a career. During these years, Gauss gave the first proposals for approximations for pi n, the function counting the number of primes less than n. Gauss first proposed the following. Pi n is approximately n divided by ln n. ln n is the natural logarithm of n. And then refined this to pi n equals lin, where lin is the integral between 2 and n of dx ln x. Ever the calculator, Gauss computed the number of primes and tested the formula up to 3 million. Wow. Gauss sped through the curriculum at the Collegium and enrolled at the University of Göttingen, 60 miles from Brunswick, rather than the duchy's official university in nearby Helmstedt, most likely due to Göttingen's superior mathematics library. Surprisingly, Göttingen's records show that Gauss borrowed far more books in the humanities than in mathematics. Gauss's notebooks tell us that he had a much higher regard for his classics professor than for his mathematics professor. However, mathematical accomplishment quickly won out. The Greeks had known that regular polygons with 3 or 5 or 15 sides could be constructed with a straight edge and a compass. So could any regular polygon having a number of sides that was a power of 2 times 3 or 5 or 15. and that is where the boundary of the field stood for 2 millennia, until 1796, when Gauss discovered that a 17-sided regular polygon could also be constructed with the classical geometrical tools, the straight edge and compass. He quickly generalized his result to any regular polygon with a number of sides that is a product of a power of 2 and any number of Fermat primes. A Fermat prime is a prime number of the form 2 to the power of n plus 1, where n is itself a power of 2. Fermat between 1601 and 1665, I hope I'm pronouncing that right, anyway, thought that all numbers of the form 2 to the power of n plus 1, where n is a power of 2, are prime numbers, and it is easy to see that 3, 5, 17, and 257 have this property. With only a little bit of brute force, you can demonstrate, as Fermat must have done, that 65,537, which is 2 to the power of 16 plus 1, is a prime. The next candidate Fermat prime is over 4 billion, 2 to the power of 32 plus 1. We cannot fault Fermat for not finding 641 as its smallest prime divisor. It took a century for the great mathematician Leonhard Euler to find that. In his notebooks, Gauss speculated that there are no other Fermat primes. To date, none have been found to exist. Gauss was so overjoyed at this result that it convinced him to pursue a career in mathematics. After 2 years at Göttingen, he realized that no one on the faculty could really be of any assistance to him, so he went home to Brunswick to write his doctoral dissertation. For his topic, he chose the fundamental theorem of algebra that every polynomial equation of degree n with complex coefficients has exactly n roots in the complex numbers. His dissertation was the first of what would be 4 proofs throughout his career. Freed of the need to write a set piece, Gauss turned his attention to number theory. Number theory goes back to the Greeks with Euclid's proof of the infinity of prime numbers and the form of even perfect numbers being 2 of the earliest results in the field. From time to time, new results were added or new conjectures made. In the 17th century, the French mathematician Pierre de Fermat, a contemporary of Descartes, made his famous conjecture that the equation x to the power of n plus y to the power of n equals z to the power of n has no non-trivial solutions in integers for n greater than 2. The Arabs made some progress for the cases n equals 3 and n equals 4. However, the complete proof of Fermat's last theorem did not come until 1995. In the 50 years before Gauss, Lagrange had provided the first proof that every integer can be expressed as the sum of no more than 4 squares, and Goldbach had conjectured that every even number other than 2 can be expressed as the sum of 2 primes. In 1770, the English mathematician published the statement of a theorem that had first been proposed by his former student John Wilson. The integer p is a prime if and only if p evenly divides p minus 1 factorial plus 1. Recall that n factorial is 1 times 2 times 3 times 4 times ... times n. Given the speed with which n factorial grows, Waring despaired of ever having a notation that would enable a proof of the conjecture whose truth could barely be established in particular cases. When Gauss began work on his epochal arithmetic disquisitions, excerpted here, number theory was merely a collection of isolated results. Upon hearing of Waring's despair, Gauss is supposed to have remarked that mathematics is concerned with notions rather than with notations. In the disquisitions, he introduced the notion of congruence, and in so doing unified number theory. 2 integers x and y are said to be congruent modulo the integer z if and only if x minus y is evenly divisible by z. Following Gauss, we would express this congruence relationship as x is congruent to y mod z. This powerful analytical method was the foundation of the arithmetic disquisitions, a compendium of Gauss's result in number theory, which he published at the age of 24. It is divided into 7 sections: congruences in general, congruences of the first degree, residues of powers, congruences of the second degree, quadratic forms, applications, division of the circle. I'm just going to take a quick break. I'm back. With the notion of congruence and Gauss's compact notation for it, he could easily state Wilson's theorem as the integer p is a prime if and only if p minus 1 factorial is congruent to minus 1 mod p. And he could also state and prove the complement to Wilson's theorem. If n is a composite number other than 4, then n minus 1 factorial is congruent to 0 mod n. These results only hinted at the power of congruence as a mathematical tool. In 1795, while still at the Collegium, Gauss had discovered the law of quadratic reciprocity, which had only been stated and incompletely proven a decade earlier by the 33-year-old French mathematician Adrien Marie Legendre. I wish I knew how to pronounce it. In the language of congruences, the law of quadratic reciprocity states, if p and q are primes not both congruent to 3 modulo 4, then either both x squared is congruent to p mod q and x squared is congruent to q mod p are solvable, or neither x squared is congruent to p mod q nor x squared congruent to q mod p is solvable. If p and q are primes, both congruent to 3 modulo 4, then exactly one of the equations okay, I didn't quite understand that. Notice that this theorem comes nowhere close to resolving the question of whether p is in fact a quadratic residue modulo q in isolation. It merely allows one difficult numerical calculation, such as whether 257 is a prime modulo 65,537, to be replaced by the easier numeric calculation of whether 65,537 is a prime modulo 257. The first step is to reduce 65,537 to its residue modulo 257, which is 2, and then determine whether 2 is a quadratic residue modulo 257. Gauss considered the law of quadratic reciprocity to be the theorem Orem, the golden theorem, or the gemma arithmeticae, the gem of arithmetic. He considered arithmetic itself, as he called number theory, to be the queen of mathematics, which he called the queen of sciences. Early in 1801, the Duke of Brunswick raised Gauss's stipend. However, Gauss felt as though he had done little to merit the raise. With the arithmetic disquisitions in press, Gauss sought a new challenge and turned his attention to planetary theory. In January 1801, the Italian astronomer Joseph Piazzi had briefly observed what he thought to be a new planet before losing track of it. Gauss spent much of 1801 improving the theory of planetary perturbation to utilize true ellipses rather than circular approximations. Gauss predicted the mysterious body was an asteroid rather than a new planet. At the end of the year, astronomers found the asteroid Ceres, exactly where Gauss's improved method said it should be. The discovery of Ceres earned Gauss genuine international fame. In January 1802, the Academy of Sciences in the Russian capital of St. Petersburg elected him a corresponding member. Gauss felt as though he had indeed merited the increase in the Duke's stipend. The Duke raised Gauss's stipend again in 1803. The increased income may have prompted Gauss to think about his personal situation. In 1805, Gauss surprised everyone around him by announcing his engagement to Joanna Osthoff after a year-long courtship. He wrote his friend Boullier, For 3 days now, this angel, almost too heavenly for our earth, has been my fiancée. Life lies before me like an eternal spring with radiant colours. They married on October 9th, 1805. For a brief time, Gauss did seem to be in the spring of his life. His patron rewarded him with a hefty increase following his marriage, perhaps motivated by an offer of position in St. Petersburg. The Gauss's first child, Joseph, named for the discoverer of Ceres, was born on August 21, 1806. A daughter christened Wilhelmina followed a year and a half later on February 29th, 1808. Unfortunately for Gauss, his blissful spring would not last long. In November 1806, Duke Ferdinand died from a wound he suffered losing the Battle of Auerstadt to Napoleon the previous month. Following Napoleon's victories in Germany, Göttingen found itself in the Kingdom of Westphalia, a French vassal state. As a professor, Gauss had to pay 2,000 francs tax, a small fortune in those days. The astronomer Olbers sent Gauss the necessary funds to pay the tax. However, Gauss refused his benevolence. Then Gauss received a letter from the French mathematician Laplace, who said he considered it an honor to pay the tax and lift the obligation from Gauss. Once again, Gauss declined the offer, but not out of any animosity for the Frenchman. Gauss had a great respect for Laplace, and Laplace for Gauss. When Laplace was once asked who was the greatest mathematician in Germany, he immediately replied with the name of Pfaff, who had nominally supervised Gauss's doctoral dissertation. When asked why he hadn't named Gauss, Laplace immediately replied, "Gauss is the greatest mathematician in the whole world." In the end, an anonymous donor sent Gauss the money to pay the tax. Unable to repay the donor, Gauss made regular donations to charity with interest, as if paying off a loan for the amount donated. Gauss would not have a long marriage to Johanna. She died a month after giving birth to their third child, Ludwig, in 1809. Sadly, Ludwig died 5 months later. Within a year of Johanna's death, Gauss married Minna Waldick, Johanna's best friend. We can only guess that Gauss may have been motivated by a need to find a stepmother for his 3 children. Gauss had 3 more children by Minna before she became ill, first with tuberculosis and then with what was diagnosed as hysterical neurosis. Gauss and Minna were perpetually unhappy until her death in 1831. At the beginning of the 19th century, Paris remained the center of the mathematical world. Göttingen was at best a remote outpost. Gauss had occasional correspondence with the mathematical giants in France, but he never troubled himself to visit Paris. There were no mathematicians in Germany who came close to him in stature during the prime of his career, and few worthy of correspondence. Given the mediocre state of affairs in the German mathematics community, it was not surprising that Gauss chose to serve as professor of astronomy and director of the observatory at Göttingen. Had he been professor of mathematics, he would have been required to spend his time teaching mathematics to indifferent undergraduates. Not having mathematics classes to teach may have given Gauss the free time to pursue the consequences of denying Euclid's parallel postulate, research he had begun in his student days and then put aside. He seems to have done this work almost against his will, hardly bearing the thought that the parallel postulate might not be true. He was never able to allow himself to publish this work. We know it only through his notebooks. Gauss's contemporaries considered him to be a mathematical scientist with strong interest in applied and even empirical mathematics. His interest in geodesy, the mathematics of surveying and representing the land, is a good example of his strong empirical leanings. He initially worked on surveying problems in his early 20s, then set that interest aside for nearly 2 decades. In 1817, at the age of 40, he returned to this subject, taking responsibility for a survey of the state of Hanover. For several years, Gauss spent his summers surveying the land and spending much of the rest of the year analysing the data. Dissatisfied with the standard geodetic measurement techniques used on sighting lamps or flares, Gauss invented a new method using a device called a heliotrope. It employed mirrors to deflect light rays to small aperture telescopes. Gauss employed his geodetic work to find empirical support for non-Euclidean geometry. As part of one of his surveys, he measured the angles of the triangle formed by the mountain tops of the northern German peaks Hohenhagen, Bocken, and Inselberg. The measurement of this triangle, with sides between 45 and 70 miles long, proved inconclusive. Gauss calculated the sum of the angles of the triangle to be 180 degrees, 0 minutes, and 15 seconds. 1 part in 43,200, close enough to 180 degrees, to be due to measuring error. Thanks to Einstein's theory of general relativity, we know that the sum of the angles of such a triangle exceeds 180 degrees by 10 to the power of minus 17 n, 1 part in 10 to the power of 21. And I'm not sure if that's supposed to be 10 to the power of 21 factorial. I suppose not. No, it's just an exclamation mark. 10 to the power of 21. The 10 to the power of 21 factorial, that would be a very, very silly big number. Without any empirical data, Gauss chose not to publish any of his work on non-Euclidean geometry. However, when Gauss received word in 1831 that the Hungarian mathematician János Bolyai had published work demonstrating the consistency of a non-Euclidean geometry, he responded to János' father Farkas, an old friend. To praise it would amount to praising myself, for the entire content of the work coincides almost exactly with my own meditations, which have occupied my mind for the past 30 or 35 years. Well, Gauss thought that he was merely reporting a fact. Both Bolyais took it as a great offence and as an attempt to seal priority. Ah, how sad. In 1824, Gauss received a substantial salary increase, his first raise since 1807. A year later, he received a large bonus for the surveying work. His newfound financial bounty came at a very fortunate point in his life, just as Gauss was beginning to suffer from asthma and a heart ailment. By 1825, the physical burden of the summer surveys became too much for him to bear, and he satisfied himself with supervising the surveys and doing all of the calculations. It has been estimated that he handled more than 1 million pieces of numeric data by himself. Given his computational talents, it is hardly surprising that even late in his life, Gauss would find new fields for his talents. In the 1840s, he took on the task of putting the university's pension fund on a sound actuarial basis. He must have been especially good at investments. When he died, his estate was equal to 200 times his annual income. Wow. Over the years, Gauss began to attract a handful of students to his occasional mathematical lectures. Anyone who attended his lectures on number theory in 1809, the theory of curved surfaces in 1827, or the method of least squares in 1851, should have considered himself exceptionally fortunate. Bernard Riemann and Richard Dedekind, each included in this book, were among the fortunate. Their generation established Göttingen as the center of the mathematical universe. Gauss resisted his physical ailments until he was well into his 70s. He finally died on February 23, 1855, 2 months short of his 78th birthday. In his will, Gauss stipulated that a 17-sided regular polygon be carved into his gravestone. However, that was not to be. The mason charged with the task thought that viewers would confuse a 17-sided regular polygon with a circle, so he carved a 17-pointed star. Although the mason may not have followed Gauss's instructions, he did mark Gauss as a star, the greatest star in the mathematical firmament. I'm going to take a break. I'm back. So we're reading about Carl Friedrich Gauss, and this is selections from his work Arithmetic Disquisitions, Section 3, Residues of Powers. Theorem 45. In any geometric progression, 1, a cubed, etc., outside of the first term 1, there is still another term, at, which is congruent to unity relative to the modulus p when p is prime relative to a, and the exponent t is less than p. Oh wow, and off we go. So these are a bunch of theorems from Gauss, who Hawking has said is the greatest mathematician of all time. That was unqualified, wasn't it? He really just gave it to Gauss. I heard Gauss was a bit of a calculator. He liked to run the numbers and actually do the computations and add things up and calculate. Of course, these days we get machines to do that sort of thing for us. This is section 4, congruence of the second degree. Sorry, that's congruences of the second degree. That's theorem 94. Both -3 and +3 are non-residues of all prime numbers of the form 12m plus 5. -3 is a non-residue, +3 a residue, of any prime number of the form 12m plus 11. Since every number of the form 6m plus 5 is necessarily contained among those of the form 12m plus 5 or 12m plus 11, and since the first of these is contained among numbers of the form 4m plus 1, the second among numbers of the form 4m plus 3, we have these theorems. There we go. And there's a big table of numbers at the end here. I'm going to look up how to pronounce this name. Alright, so it's Augustin Louis Cauchy. Lived 1789 to 1857. His life and work. Euclid earned an income in teaching. Okay, talking about Euclid again. Among his students was Ptolemy I, king of Egypt. King Ptolemy once asked his teacher for a shortcut to geometric knowledge, to which Euclid replied, "Sire, there is no royal road to geometry. Perhaps there is no royal road to mathematics in general and geometry in particular. However, if any mathematician rode with the royals, it was Augustin Louis Cauchy." Augustin Louis Cauchy was born was born during the infancy of the French Revolution on August 21, 1789. His parents, Louis-Francois Cauchy and Marie-Madeleine Cauchy née Desetre, named him for the month of his birth and his father. Louis-Francois had been born to a Rouen metalsmith in 1760. Marie-Madeleine had been born to a family of Paris bureaucrats in 1767. They married in 1787. So she was 20 when she got married. Louis-Francois Cauchy had trained as a lawyer and was a commissioner of the Paris police under the royal regime. He lost that position as a result of the storming of the Bastille and had to take a position with the Bureau of Charities in order to make any kind of living. As the Reign of Terror began to descend on Paris in 1792, Louis-Francois feared that his royalist ties might cost him his neck, and he fled to a country house in Orsel with his family that by now included a second son. This would be the first of Augustin Louis Cauchy's flights from political upheaval. The Cauchy's exile in Orsel may have been hard at times, but it had its benefits. Principal among them may have been the fact that their neighbours in Orsel included the great mathematicians Simon Pierre Laplace and Joseph Louis Lagrange, the latter of whom is said to have predicted the young boy's scientific genius and warned his father about letting him see a mathematics text before the age of 17. Whether it was due to his own education in the classics or Lagrange's warning, Louis-Francois used his ample free time in Orsel to begin the education of his eldest son, giving him a sound foundation in the study of Greek and Latin. Louis-Francois continued his teaching of his son when the family was able to move back to Paris in July 1794 after the fall of Robespierre and the end of the Reign of Terror. Louis-Francois' fortunes rose with those of Napoleon, and when Napoleon became first consul in January 1, 1800, Louis-Francois was elected Secretary General of the newly created Senate, whose membership included Laplace and Lagrange. At Lagrange's suggestion, Louis-Francois enrolled his son at the École. I'm going to have to look it up. Hang on. Okay, the word is école. It's pronounced école, and it means school. So there you go. So he was enrolled at the school. Central du Panthéon. Just after his 13th birthday, at the École, young Cauchy spent 2 years studying ancient languages, drawing, and natural history. He excelled at ancient languages, earning first-place prizes in Latin composition and Greek poetry competitions. Even though he had developed a distinguished record studying classic languages, Augustin Louis Cauchy had his heart set on studying engineering at the École Polytechnique. That's the technical school. Cauchy ranked second among all of the applicants to the École Polytechnique in 1805. When he enrolled in the fall, he had to choose the field of public service he would enter once he graduated. He chose civil engineering with a specific interest in highways and bridges. Cauchy soon rose to the top of his class, graduated with honours in 1807, and then enrolled for advanced study at the École des Ponts at the School of Highways and Bridges. There you go. At this school, students were in the classroom from December through March and spent the rest of the year on fieldwork. In 1810, after once again graduating at the top of his class, Cauchy became a field engineer for the Department of Highways and Bridges in Cherbourg to work on a naval base from which Napoleon planned to invade England. In a letter to his father, Cauchy wrote that he had just 4 books in his possession when he left for Cherbourg: a collection of Virgil's poetry, Thomas A. Kempis' Imitation of Christ, Laplace's Mécanique Céleste, and Lagrange's Traité des Fonctions Analytiques. Okay. We know little of Cauchy's time in Cherbourg other than the fact that he was introduced to Napoleon when the emperor visited in May 1811. In 1812, Cauchy returned to Paris to seek an academic appointment that would allow him the income and time to pursue his mathematical pursuits. He failed in this attempt in large part due to a protracted illness and had to be satisfied with an appointment as a member of the technical staff building the Ourcq Canal. When his former mentor Lagrange died in 1813, Cauchy sought election as Lagrange's replacement on the mathematics faculty at the Institut de France. Not only did he fail to win election to the post, but he was also eliminated on the first ballot. For the next 2 years, Cauchy sought every available position at the Institute, but never succeeded. Finally, at the very end of 1814, he received a bit of consolation with election to the Philomathic Society of Paris. 3 months later, just as Cauchy was preparing to begin his teaching, France would once again be torn asunder following Napoleon's return to Paris from his exile in Elba. Following the restoration of the Bourbon monarchy in 1814, many of France's leading institutions were purged of radical supporters of Napoleon. Cauchy tried and failed to win the chair in mechanics that had been held by Simon Denis Poisson. He finally won an appointment to a teaching post at the École Polytechnique, first as the substitute professor of analysis for the mathematician Louis Poinsot, whose ill health had rendered him unable to teach for 3 years, and then a full appointment as professor of analysis and mechanics in his own right. Having finally obtained a permanent position, Cauchy's parents urged him to marry. In fact, they did more than urge him to marry. His father chose the bride, Alice de Bourg, daughter of the owner of a publishing company bearing the family's name. She came with a considerable dowry, and they had a wedding ceremony to suit their social position. Louis XVIII and the entire royal family signed the marriage contract. All the evidence make it seem as though Cauchy treated his wife and daughters as little more than adornments that could be left behind when necessary. He probably married just to satisfy the bourgeois demands of his parents. He and Alice, I don't know how to pronounce her name, had 2 daughters, Marie-Françoise Alicia, born in 1819, and Marie Mathilda, born in 1823. They would each marry into the nobility. Following his appointment, Cauchy sent about to reorganize the mathematics curriculum at the École Polytechnique, giving much more emphasis to pure mathematics. He initially focused on the calculus, the subject matter of the excerpts in this chapter. Newton and Leibniz had invented the calculus to solve particular mathematical problems. Newton, for example, needed to be able to solve problems in celestial dynamics involving ellipses and parabolas. As calculus evolved in the 18th century, it did so on uncertain foundations. The derivative of a function was considered to be a means to express the formula for the tangent to a curve at a particular point P. The integral of a function was considered to be an infinite sum of the values of an infinite number of infinitesimally thin rectangles whose heights were the value of the function and whose widths were the infinitesimal quantity expressed as dx. Indeed, Leibniz introduced the integral sign in this integral expression here from a to b fx dx, precisely because of its similarity to the letter S, the first letter of summation. So long as particular well-behaved functions were considered, for example fx equals x squared, the problem of determining the integral of a function was reduced to finding the limit of a particular series. For the function fx equals x squared, the integral is considered to be the sum of the rectangles of height x squared and width dx, as shown here in this diagram. Consequently, the problem of finding the integral of the function fx equals x squared between 0 and 1 is nothing more than the problem of finding the limit of 1 on n squared plus 2 on n squared plus 3 on n squared unto n minus 1 on n squared as n approaches infinity, which is given as that expression up there. Early 18th century mathematicians soon discovered that the integral and derivatives were inverses of each other. By the middle of the 18th century, Leonhard Euler and Johann Bernoulli, I'm going to have to look that up. Hang on. Okay, so that's Johann Bernoulli. So where were we? By the middle of the 18th century, Leonhard Euler and Johann Bernoulli considered the integral to be nothing more than the inverse of the derivative. In fact, Euler used Leibniz's concept of the integral as a summation only when making an approximate evaluation of an integral. Finding the formula for the integral of a function fx entailed searching for another function gx whose derivative was everywhere equal to fx. Thus, the formula for the integral of the function fx equals x squared was gx equals x cubed on 3, simply because fx equals x squared is the derivative of gx equals x cubed on 3. These were the foundations on which the calculus stood when Cauchy began to teach at the École Polytechnique in 1818. There were methods of integrating well-behaved functions, but there was no theory of the integral, perhaps spurred on by Fourier's demonstration that an arbitrary function could be represented by an infinite trigonometric series. Cauchy developed the first theory of the integral, independent of the particular function and independent of the differential calculus, for which he also laid new foundations, independent of geometric intuitions. In the introduction to his Cours d'Analyse of 1821, Cauchy explained that he sought to bring the same degree of rigor found in Euclid's Elements to the field of mathematical analysis. He was particularly concerned to banish infinitesimals. A new definition of continuity was required. Cauchy gave the following as his definition of the continuity of a real function of one variable. Let fx be a function of the variable x, and suppose that, for each value of x between two given bounds, this function constantly takes one finite value. If, from the value of x between those bounds, one attributes to the variable x an infinitely small increment alpha, alpha the function itself will receive as an increment the difference, f of x plus alpha minus f of x, which will depend on the same time on the new variable and on the value of x. This being granted, the function fx will be a continuous function of the variable x between the two assigned bounds if, for each value of x between those bounds, the numerical value of the difference f of x plus alpha minus fx decreases indefinitely with alpha. In other words, the function fx remains continuous with respect to x between the given bounds if, between these bounds, an infinitely small increment in the variable always produces an infinitely small increment in the function itself. Cauchy devoted the first part of his resume, is it? I'm not really sure. Some sort of paper. The first part of his paper of 1823 to differential calculus, focusing on the derivative of a function y equals fx. He took the term derivative and the notion f prime x from his mentor Lagrange. However, or is it Lagrange? I'm not sure. Lagrange had continued to speak of the derivative in general terms, a tangent to a curve, finding formula for particular derivatives as necessary. Cauchy went far beyond Lagrange and defined the derivative of f at x as the limit of the difference quotient delta y divided by delta x equals f of x plus I minus fx on I, as I tends to 0, our modern non-geometric definition of the derivative. The second part of his Calcul Infinitesimal focused on the concept of the integral, as we saw earlier. It's pretty standard. Of a function fx continuous between a and b. Cauchy divided the interval ab at n points, x1, x2 to xn, such that a is less than x1, is less than x2, is less than xn, is less than b. He called the largest value of xi minus 1 the norm of the partition, and considered a sum s as this expression here. Okay, now called the Cauchy sum of the partition. Using his definition of continuity, Cauchy showed that for a continuous function fx on a fixed interval ab, the sums s and s prime must be arbitrarily close to each other, provided that the norms of p and p prime are sufficiently small. This observation allowed Cauchy to define the integral of fx dx between a and b, to be the limit of s as the norm of p goes to 0. Using his definition of continuity, Cauchy showed that for any two partitions P and P', the corresponding sums S and S' could be made arbitrarily close to each other, provided that the norms of P and P' are sufficiently small. By defining a theory of the integral, Cauchy was then able to demonstrate the intimate relationships between the integral and the derivative as a theorem that has come to be known as the fundamental theorem of calculus. It states that if f is an integrable function in the interval ab, and if gx is the integral of ft from a to x less than or equal to b, then the derivative gx is identical to fx, that is, g prime x is fx. Although Cauchy was able to inspire his most gifted students, he never learned to adapt his courses to suit the level of the average student who came to the école seeking to augment their rudimentary knowledge of mathematics to suit the needs of, say, an engineering career. Because Cauchy's lectures were too ambitious to be presented in the allotted time, they often ran over. In April 1821, just before the end of a lecture that had run into overtime, several students booed and hissed Cauchy and then walked out on him. Dear me. Far from pleasing the faculty councils at the école, Cauchy's calcul infinitesimal incurred their wrath for being too theoretical and not sufficiently practical. In fact, in late 1823, the Minister of the Interior appointed a commission, including Laplace and Poisson, to ensure that the instruction in mathematics was attuned to the needs of engineering students. For the rest of the decade, the École administration continually monitored Cauchy's lectures to guarantee their suitability for engineering students. France experienced a period of relative peace and stability during the reign of the restored monarch Louis XVIII. When Louis XVIII died in 1824, he was succeeded by his younger brother Charles X, who attempted to restore the monarchy to the power it had prior to the Revolution. As pockets of Republican sympathy arose throughout France, the government sought to restrain them and enlisted the aid of organizations supporting the monarchy. An ardent royalist and Catholic, Cauchy was one of the founders of one of them, the Association for the Protection of the Catholic Religion. After the July Revolution of 1830 overthrew Charles X in favour of his cousin Louis Philippe, Duke of Orleans, academics, like all government officials, were required to take an oath of allegiance. Cauchy not only refused to do so, he went into exile of his own volition, perhaps concerned that the new regime would persecute devout Catholics like himself. Not surprisingly, Cauchy lost his appointments. Leaving his wife and children in France, Cauchy first went to live with a group of Jesuits in the town of Fribourg, just over the Swiss border. The Jesuits soon recommended him to the King of Sardinia, one of their benefactors, and he offered Cauchy a chair at the University of Turin. However, Cauchy stayed there for little more than 3 years when he received an offer to join Charles X in Prague and teach the exiled king's grandson, the Crown Prince. Only then did Cauchy send for his family to join him after a 4-year separation. Charles X rewarded Cauchy by making him a baron. By 1838, Charles X had died and the Crown Prince's education completed on his 18th birthday. With his work for the court done, Cauchy returned to Paris, no doubt impelled by his mother's declining health. Having lost his academic positions after going into exile, the only position Cauchy could resume was his membership in the Academy of Science. Fortunately for him, his old teacher Prony died within a year of his return, and Cauchy was elected to succeed his old mentor as Professor of Geometry at the Bureau of Longitudes. Political conditions had eased, and academics no longer had to swear an oath of allegiance. Although Cauchy's coolness to the new regime may not have jeopardized his life, it did hinder his career, costing Cauchy comfortable appointments at several government-sponsored institutions. In 1843, he was one of 3 candidates for a chair of mathematics that had become vacant at the College of France. Although clearly the most eminent of the candidates, Cauchy's ultra-monarchist and Jesuit sympathies swayed many of the electors away from him. In the end, he received only 3 votes from the 24-member committee. Feeling humiliated by the result, Cauchy announced that he would no longer allow himself to be nominated for any position if there were even the slightest chance of his defeat. He had no teaching post from 1838 to 1848. He only had his appointment to the Academy of Sciences to provide him a forum for presenting his scientific work, and that he did in earnest, presenting 240 notes and studies to the Academy during this 10-year interval. When the Revolution of February 1848 overthrew Louis Philippe, Cauchy hoped that his former pupil, the Duke of Bordeaux, now Count of Chambord, would take the throne. That would not be the case. The Second Republic replaced Louis Philippe. Although hardly a Republican, Cauchy benefited from the Republic's abolition of loyalty oaths. He soon won election to a chair at the University of Paris. When Napoleon III became emperor in 1852, he exempted Cauchy from taking the oath. Cauchy worked at a furious pace his entire life, publishing 789 mathematical and scientific papers. Publication of, Ovar Complete, I don't know how to pronounce that, began in 1882 and only ended in 1970. That's a lot longer later, with the publication of the 27th and final volume. His prodigious output only came to an end with his death on May 23, 1857, following a short bout with rheumatism. So here's his work on calculus. It doesn't say when it was published. This is a lecture. Derivatives of function of only one variable. I'm going to take a quick break. I'm back. So this lecture was translated by John Anders. Doesn't say when. Doesn't say when it was written. Doesn't say when it was translated. The derivative of a function of only one variable. Whenever the function y equals fx remains continuous between 2 given limits of the variable x and a value contained between 2 given limits is assigned to this variable, an infinitely small increase made to the variable produces an infinitely small increase in the function itself. Consequently, if we set delta x equals I, the 2 terms of the ratio of the difference will be infinitely small quantities. But while the 2 terms, viz. The differences, simultaneously approach the limit 0, the ratio itself will be able to converge to another limit, be it positive or negative. This limit, if it exists, has a determinate value for each particular value of x, but it varies with x. For example, if we set f equals x to the power of n, m designating a whole number, the ratio between the infinitely small differences will be given as this expression here, and at its limit, this ratio will be the quantity mx to the power of m minus 1. That is a new function of the variable x. This will hold in general. So this is about the fundamental theorem of calculus. There we go. Here's his 4th lecture. Differentials of functions of a single variable. So that was differentials. What was the first one? Derivatives, of course. Okay. There's the 21st lecture, integral calculus. Start with definite integrals. Definite integrals are, of course, where the bounds are given. And this is 22nd lecture, formulas for the determination of exact values or values approaching definite integrals. Then the 23rd lecture, decomposition of a definite integral into many others. imaginary definite integrals, geometric representation of definite real integrals, composition of a function under the sign integral sign into two factors, one of which always conserves the same sign. Uh, 24th lecture. Some definite integrals whose values are infinite or indeterminate. Principal values of indeterminate integrals. There we go. Whenever the integrals in 14 become indeterminate, equations 15 and 16 furnish for each of them a unique particular value which we will call the principal value. If we take integral 8 as an example, we will recognize that its principal value reduces to 0, though in general its value is indeterminate. There we go. So this is Nikolai Ivanovich Lobachevsky, 1792 to 1856, his life and work. In the Sherlock Holmes stories, The Sign of Four, Arthur Conan Doyle has the great detective make the following pronouncement: when you have eliminated the impossible, whatever remains, however improbable, must be the truth. Thus it was with geometry at the dawn of the 19th century. After 2 millennia of trying to prove Euclid's parallel postulate, it was time for geometers to demonstrate that it could not be proved and that other geometries were possible, however improbable that might be. This is the nearly concurrent accomplishment of the Russian mathematician Nikolai Ivanovich Lobachevsky and the Hungarian mathematician János Bolyai, presented in this and the next chapter, respectively. Nikolai Ivanovich Lobachevsky was born on December 1, 1792, in the little town of Makariv, about 40 miles north of the city of Nizhny Novgorod, in the Volga River in the heart of Russia. He was the second of 3 sons born to Ivan Maximovich and Praskovia Alexandrovna Lobachevsky, a couple who had emigrated from Poland a few years earlier. Little is known of Lobachevsky's father except that he was barely able to support his family on his income as a clerk in the government land surveying office. Ivan died when Nikolai was 7. Hoping to make a living teaching young children, the newly widowed Praskovia moved her family 200 miles east to the city of Kazan, almost on the edge of Siberia. Nikolai would spend the rest of his life in this new hometown. Praskovia's 3 sons were her first students, and they turned out to be prize students. Each of them won a government scholarship to pay for their attendance at the local gymnasium in Kazan. Nikolai entered in 1802 and graduated with highest honors 5 years later, winning a government scholarship to attend the local university. Kazan University first opened its classroom doors in 1805, the result of one of the many educational reforms that marked the early years of the reign of Tsar Alexander I. The very newness of the university, coupled with its remoteness, meant that it did not have an entrenched faculty. Instead, it hired young faculty from all over Eastern and Central Europe. Indeed, when Lobachevsky was a student, Kazan University was able to boast of more accomplished scholars than all but the very best German universities. These young scholars brought the latest ideas in mathematics, physics, astronomy, philosophy, and pedagogy to Kazan. The most important of these for Lobachevsky was Martin Barrels, 1769 to 1833, who had only been able to find employment in German teaching mathematics in a school. However, Bartels had had the good fortune to have had the great Gauss as one of his students, and they continued to correspond with each other over the years. Bartel's lectures soon persuaded Lobachevsky to abandon his plans to study medicine. Bartels lectured on Euler's treatment of differential and integral calculus, Lagrange's analytical mechanics, Gauss's arithmetic disquisitions, Monge's work on the application of mathematical analysis to geometry, and Montucla. I guess I'm gonna have to look up these names. Hang on. Okay, so that's Mon's work on the application of mathematical analysis to geometry, and Montucla 4-volume history of mathematics. Montucla's detailed coverage of the history of attempts to prove Euclid's parallel postulate may well have been the source of Lobachevsky's interest in the problem. In many ways, Lobachevsky did not display model behavior as a student. From time to time, university administrators accused him of being obstinate, overly self-centered, and having atheistic tendencies. In August 1811, the curator of the Kazan School District recommended to the University Council that it should express to Lobachevsky, the leader in bad conduct, our regrets about his unbecoming actions, which becloud his superior abilities. Fortunately for Nikolai, Bartels and his other professors knew better than the administrators. They recommended that he be granted a master's degree in recognition of his extraordinary gifts in mathematical and physical sciences, which he received at the end of the year. In those days, it was no easy matter finding a teaching job in Kazan. Nikolai must have considered it a stroke of good fortune when his elder brother Alexis took sick leave and was unable to continue teaching courses in elementary mathematics to government employees in need of a college degree to secure promotion to a higher position. The authorities at the university must have been impressed by the former troublemaker's teaching abilities. In 1814, they appointed him to a lectureship. 2 years later, they promoted him to assistant professor, and in 1822 to full professor. Throughout the course of his teaching career at the university, Lobachevsky lectured on physics and astronomy as well as mathematics. However, he always felt most comfortable teaching plane and spherical trigonometry. Lobachevsky lectured from his own notes, hoping to turn them into a textbook that would eventually supplement his income. The manuscripts for these notes reveal that up until the early 1820s, Lobachevsky, like many before him, tried to prove Euclid's parallel postulate. These manuscripts included 3 attempted proofs of the postulate, but elsewhere in the notes, Lobachevsky admitted that none of them were conclusive. We cannot be sure what motivated Lobachevsky to discard his attempts to prove the parallel postulate. His colleague, Bartels, may have passed on hints received from the great Gauss. Alternatively, he may have been inspired by the philosopher A.S. Lubkin, who took up his post in Kazan in 1812 and taught a strict form of empiricism that rejected Immanuel Kant's treatment of space as a category that is synthetic and a priori, that organizes our experience rather than being an experience derived from them. Lobachevsky would later write, "The fruitlessness of the attempts made since Euclid's time for the space of 2,000 years aroused in me the suspicion that the truth, which it was desired to prove, was not contained in the data themselves, that to establish it the aid of experiment would be needed, for example, of astronomical observations, as in the case of the laws of nature." Here is a brief recapitulation of Lobachevsky's 1840 essay, Geometrical Researches on the Theory of Parallels, his most mature exposition and the work reproduced here. He begins by considering a point P and a straight line L in the same plane as P, but not containing P. He lets PB be the line through P perpendicular to L. He next considers the line through P perpendicular to PB. In Euclidean geometry, this is the only line through P that does not intersect the line L. That is precisely the assumption that Lobachevsky abandons in his construction of a non-Euclidean geometry when he postulates that there are other lines through P that do not intersect the line L. These non-intersecting lines are separated from the lines through P that do intersect the line L by the 2 lines X and Y shown in the figure below. The lines X and Y do not intersect the line L either. Lobachevsky defines them as the parallels to the line L. Each is said to have definite direction of parallelism. X is the parallel to the right and Y is the parallel to the left. The angle theta that any perpendicular PB makes with each of the two parallels is called the angle of parallelism for the length PB. In ordinary Euclidean geometry, theta is 90 degrees. I'll be back in a minute. I'm back. That was dinner time around here. We had rice with curried sausages and coleslaw. So on we go. This is non-Euclidean geometry from Lobachevsky. In Lobachevsky's geometry, theta is a function of the distance from P to B. It approaches 0 degrees as the distance becomes infinitely larger, and approaches 90 degrees as the distance becomes infinitesimally small. Having made this alternate postulate, Lobachevsky goes on to prove that in this alternate geometry, if line L1 is parallel to line L2 for a given point on L1, then L1 is parallel to L2 for every point of L, the property called permanency. If line L1 is parallel to line 2, then line L2 is parallel to line 1. Reciprocity. Reciprocity. If line L1 is parallel to line L0, and if L2 is parallel to line L0 in the same direction, then the line L1 is parallel to line 2. Transitivity. So far, none of these conclusions is startling. Each one has a direct analogue in Euclidean geometry. However, the next conclusion is quite startling, having no analogue in Euclidean geometry. If line L1 is parallel to line L2, then L1 is asymptotic to L2. That is, L1 and L2 come arbitrarily close to each other. In contrast, in Euclidean geometry, two parallel lines remain equidistant from each other. Lobachevsky completed his first treatment of non-Euclidean geometry in 1823 in a manuscript he titled Geometria. It was not published until 1909. In this manuscript, Lobachevsky often used the phrase imaginary geometry for the new geometry he had discovered. The manuscript makes it clear that he considered Euclidean geometry to be a special case of this more general imaginary geometry, just as the real numbers are a special case of the imaginary, i.e. complex numbers. For some reason, Lobachevsky chose not to communicate his results for over 2 years, when in February 1826 he read a paper that no longer survives, titled A Concise Outline of the Foundations of Geometry, to his colleagues in Kazan. Encouraged by his colleagues' reception, Lobachevsky incorporated his results in his lecture series, Elements of Geometry, being published in installments in the Kazan Messenger during the academic year 1829 to 1830. The first quarter of the 19th century saw the first significant contribution made by Russian mathematicians. Under the Francophone influence of the Russian court, most mathematicians based in St. Petersburg and Moscow published in French. A few published in German. In far-off Kazan, Lobachevsky did not share this view. He submitted his Elements of Geometry to the St. Petersburg Academy of Sciences for publication in one of their scholarly journals. The referee Mikhail Ostrogradsky, a vocal proponent of the view that complex mathematical arguments simply could not be presented in Russian, judged the work to be unworthy of publication by the Academy. However, someone in St. Petersburg, most likely Ostrogradsky, paid some attention to Lobachevsky. Shortly after the rejection, the St. Petersburg journal, Son of the Fatherhood, carried a scathing unsigned review of Elements of Geometry. The review severely criticized Lobachevsky for not making a sufficient effort to present his ideas clearly. Certainly, this criticism would have been no surprise coming from someone who thought Russian too crude a language for mathematics. Lobachevsky might have fared better with the initial reception of his Lobachevsky might have fared better with the initial reception of his work had Kazan University been able to retain its cosmopolitan faculty when they could have most come to his assistance. Unfortunately, in 1826, the government of the new Tsar Nicholas I forced the university to dismiss many of its foreign faculty, including, especially, Bartels. When Lobachevsky revised his work in new elements of geometry, he chose not to communicate it to the Academy in St. Petersburg. Instead, he merely published it in the Scientific Journal of Kazan University between 1835 and 1838. Bypassing the Academy in St. Petersburg, Lobachevsky also submitted a short paper written in French titled Geometrie Imaginaire, so imaginary geometry, providing an overview of his work to the Journal of Pure and Applied Mathematics. This journal, published by August Krell in Berlin, had quickly established itself as Europe's leading mathematics journal since its founding in 1826. This paper undoubtedly reached a wide audience, but only the great Gauss seemed to notice it. The astronomer Otto Wilhelm Struve reports that when he visited Gauss in 1843, he found the great man reading one of Lobachevsky's works in its original Russian language, a language Gauss did not conquer until he was well into his 60s. At Gauss's suggestion, perhaps, Lobachevsky published a German version of his work in 1840 in the essay Geometrical Researches on the Theory of Parallels. In addition to his great work in geometry, Lobachevsky also performed great works on behalf of his university. He was put in charge of the library in 1825 and made rector in 1827, a post he held for 19 years. In this position, he supervised the expansion of the university's scientific teaching, both in terms of buildings and curriculum. In 1828, he delivered a famous speech on the role of science in education. Influenced by the spirit of the 18th century Enlightenment, he argued that education should be the primary path to honor and glory in Russian society, in contrast to nobility of blood, which dominated much of Russia. Lobachevsky's concern for his university often manifested itself in surprising fashions. When a cholera epidemic erupted in Kazan in 1830, Lobachevsky invited faculty, students and their families to move into the university campus. He closed the gates to everyone except doctors, and he forced strict sanitary regulations. This helped save many in the university community. In 1842, a disastrous fire swept through the city, destroying half of it. The university lost many of its buildings, including the recently completed library. Fortunately, Lobachevsky had the presence of mind to save the instruments and the books housed in the library. In 2 years, they had a new home thanks to his efforts. In 1837, Tsar Nicholas I made Lobachevsky a boyar, a member of the hereditary nobility, in recognition of his many contributions to higher education. This recognition was mostly forgotten nearly a decade later when, in 1846, as he was suffering from arteriosclerosis, a new local administration abruptly stripped Lobachevsky of his professorship and rectorship, thinking him too old and sick at age 53. Lobachevsky retired to family life on his estate. Lobachevsky did not marry until he was nearly 40. When he died in 1832, when he did marry in 1832, he married the lady Varvara Alexeyevna Moiseva, a much younger woman who came from a wealthy family from Kazan. Together they had 7 children. Their oldest son became Nikolai's pride and joy. Tragically, this son died shortly after his father's forced retirement, putting Nikolai into a deep depression. Soon afterwards, Lobachevsky's illness worsened and he lost his eyesight. He died on February 4, 1856. Lobachevsky died having made a significant impression on only a few of his contemporaries. Gauss was one of those on whom he did make an impression. In 1842, Gauss persuaded the Royal Society of Sciences in Göttingen to make Lobachevsky a corresponding member. At about the same time, he was also made an honorary professor of Moscow University. Further recognition outside of Kazan would have to wait until after Lobachevsky's death. This came first when the French mathematician Jules Hoel published a French translation of the theory of parallels in 1865. 3 years later, the Italian mathematician Eugenio Beltrami demonstrated that Lobachevsky's geometry could be realized as the surface of a pseudosphere in Euclidean space. Beltrami demonstrated that in Lobachevsky's geometry, the sum of the angles of a triangle is less than 2 right angles. Most importantly, Beltrami's techniques demonstrated that a contradiction in Lobachevsky's geometry would manifest itself as a contradiction in Euclidean geometry. By 1870, the eminent German mathematician Karl Weierstrass offered a seminar in Lobachevsky's geometry at the prestigious University of Berlin. A few years later, the English geometer William Kingdom Clifford described Lobachevsky as the Copernicus of geometry. What more fitting recognition could there be? So this is Lobachevsky's Geometrical Researches on the Theory of Parallels, translated by Dr. George Bruce Halstead. Translator's preface. And this is translated in May 1891. I'm not sure what language it was written in. Lobachevsky was the first man ever to publish a non-Euclidean geometry. Of the immortal essay now first appearing in English, Gauss said, "The author has treated the matter with a master hand and in the true geometer's spirit. I think I ought to call your attention to this book, whose perusal cannot fail to give you the most vivid pleasure." Clifford says, "It is quite simple, merely Euclid without the vicious assumption, but the way things came out of one another is quite lovely. What Vesali was to Galen, what Copernicus was to Ptolemy, that was Lobachevsky to Euclid." Says Sylvester, "In Quaternions, the example has been given of algebra released from the yoke of the commutative principle of multiplication, an emancipation somewhat akin to Lobachevsky's of geometry from Euclid's noted empirical axiom." Cayley says, "It is well known that Euclid's 12th axiom, even in Playfair's form of it, has been considered as needing demonstration, and that Lobachevsky constructed a perfectly consistent theory, wherein this axiom was assumed not to hold good, or say a system of non-Euclidean plane geometry. There is a like system of non-Euclidean solid geometry." Translator's introduction. Prove all things, hold fast that which is good, does not mean demonstrate everything. From nothing assumed, nothing can be proved. Geometry Without Axioms was a book which went through several editions and still has historical value. But now a volume with such a title would, without opening it, be set down as simply the work of a paradoxer. The set of axioms for the most influential in the intellectual history of the world was put together in Egypt, but really it owed nothing to the Egyptian race, drew nothing from the boasted law of Egypt's priests. The Papyrus of the Rhine, belonging to the British Museum, but given to the world by the erudition of German Egyptologist Eisenhower, or Eisenlohr, and a German historian of mathematics, Cantor, gives us more knowledge of the state of mathematics in ancient Egypt than all else previously accessible to the modern world. Its whole testimony confirms with overwhelming force the position that geometry as a science strict and self-conscious deductive reasoning, was created by the subtle intellect of the same race whose bloom in art still overawes us in the Venus of Milo, the Apollo Belvedere, and Laocoon. In a geometry occur the most noted set of axioms, the geometry of Euclid, a pure Greek professor at the University of Alexandria. Not only at its very birth did this typical product of the Greek genius assume sway as ruler in the pure sciences, not only does its first efflorescence carry us through the splendid days of Theon and Hypatia, but unlike the latter, fanatics cannot murder it. That dismal flood, the Dark Ages, cannot drown it. Like the phoenix of its native Egypt, it rises with the new birth of culture. An Anglo-Saxon, Alderard Bath, finds it clothed in Arabic vestments in the land of Alhambra. Then clothed in Latin, it and the newborn printing press confer honour on each other. Finally, back again in its original Greek, it is published first in queenly Basel, then in stately Oxford. The latest edition in Greek is from Leipzig's learned presses. How the first translation into our cut-and-thrust survival of the fittest English was made from the Greek and Latin by Henricus Billingsley, Lord Mayor of London, and published with a preface by John Doe, the magician, may be studied in the library of our own Princeton, where they have, by some strange chance, Billingsley's own copy of the Arabic-Latin version of Campanus's bound with the Editio Princeps in Greek and enriched with his autograph emendations. Even today, in the vast system of examinations set by Cambridge, Oxford, and the British government, no proof will be accepted which infringes Euclid's order, a sequence found upon his set of axioms. The American ideal is success. In 20 years, the American maker expects to be improved upon, superseded. The Greek ideal was perfection. The Greek epic and lyric poets, the Greek sculptors, remain unmatched. The axioms of the Greek geometer remained unquestioned for centuries, for 20 centuries. How and where doubt came to look toward them is of no ordinary interest, for this doubt was epoch-making in the history of mind. Among Euclid's axiom was one differing from the others in prolixity, whose place fluctuates in the manuscripts, and which is not used in Euclid's first 27 propositions. Moreover, it is only then brought in to prove the inverse of one of these already demonstrated. All this suggested, at Europe's Renaissance, not a doubt of the axiom, but the possibility of getting along without it, of deducing it from the other axioms and the 27 propositions already proved. Euclid demonstrates things more axiomatic by far. He proves what every dog knows, that any two sides of a triangle are together greater than the third. Yet when he has perfectly proved that lines making without a transversal equal alternate angles are parallel, in order to prove their inverse, that parallels cut by a transversal make equal alternate angles, he brings in the unwieldy postulate or axiom. If a straight line meet two straight lines, so as to make the two interior angles on the same side of it taken together less than two right angles, these straight lines, being continually produced, shall at length meet on that side on which the angles which are less than the two right angles. Do you wonder that succeeding geometers wished by demonstration to push this unwieldy thing from the set of fundamental axioms? Numerous and desperate were the attempts to deduce it from the reasonings about the nature of the straight line and plane angle. In the Encyclopädie der Wissenschaften und Kunst, von Oesch und Gruber. Leipzig, 1838. Under parallel, Schnocki says that in mathematics there is nothing over which so much has been spoken, written, and striven as over the theory of parallels, and all, so far up to this time, without reaching a definite result and decision. Some acknowledge defeat by taking a new definition of parallels, as for example the stupid one. Parallel lines are everywhere equally distant. This still given on page 33 of Schuyler's Geometry, which that author, like many of his unfortunate prototypes, then attempts to identify with Euclid's definition by pseudo-reasoning, which tacitly assumes Euclid's postulate. That is, he says on page 35, for, if not parallel, they are not everywhere equally distant. And since they lie in the same plane, must approach when produced one way or the other, and then since straight lines continue in the same direction, must continue to approach if produced farther, and if sufficiently produced, must meet. This is nothing but Euclid's assumption, diseased and contaminated by the introduction of the indefinite term direction. How much better to have followed the third class of his predecessors, who honestly assume a new axiom, differing from Euclid's in form, if not in essence. Of these, the best is called Playfair's. Two lines which intersect cannot both be parallel to the same line. The German article mentioned is followed by a carefully prepared list of 92 authors on the subject. In English, an account of like attempts was given by Perronet Thompson, Cambridge, 1833, and is brought up to date in the charming volume Euclid and His Modern Rivals by C.L. Dodgson, late mathematical lecturer of Christ Church, Oxford, the Lewis Carroll author of Alice in Wonderland. All this shows how ready the world was for the extraordinary flaming forth of genius from different parts of the world, which was at once to overturn, explain, and remake not only all this subject, but as consequence all philosophy, all Ken law, as was the case with the discovery of the conservation of energy, the independent interruptions of genius, whether in Russia, Hungary, Germany, or even in Canada, gave everywhere the same results. At first these results were not fully understood even by the brightest intellects. 30 years after the publication of the book he mentions, we see the brilliant Clifford writing from Trinity College, Cambridge, April 2, 1870. Several new ideas have come to me lately. First, I have procured Lobachevsky. A paper that it's the one that we saw. A small tract of which Gauss, therein quoted, says, okay, I'm not even going to try some really long French statement. Then Clifford says, it is quite simple, merely Euclid without the vicious assumption, but the way the things come out of the other is quite lovely. Cool. The first axiom doubted is called a vicious assumption. Soon no man sees more clearly than Clifford that all the assumptions and none vicious. He had been reading the French translation by Huel, published in 1866, of a little book of 61 pages published in 1840 in Berlin under the title I don't know, some German thing that I can't say. It's Lobachevsky's book. The first public expression of whose discoveries, however, dates back to a discourse on at Kazan on February 12, 1826. Under this commonplace title, Who would have suspected the discovery of a new space in which to hold our universe and ourselves? A new kind of universal space. The idea is a hard one. To name it, all the space in which we think the world and stars live and move and have their being was ceded to Euclid as his by right of preemption, description, and occupancy. Then the new space and its quick following fellows could be called non-Euclidean. Gauss, in a letter to Schumacher, dated November 28, 1846, mentions that as far back as 1792 he had started on this path to a new universe. Again he says something in French which is beyond me. But here we see in the last word the same imperfection of view as in Clifford's letter. The perception has not yet come to that, though the non-Euclidean geometry is rigorous, Euclid is not one whit less so. A former friend of Gauss at Göttingen was the Hungarian Wolfgang Bullier. His principal work, published by subscription, has the following title, which looks like it's in Latin. In the first volume with special numbering appeared the celebrated appendix of his son János Bullier with the following title. Okay. This has got too much foreign language in it for me to tell you what it's about. Then we're on to here with the theory of parallels, which is an excerpted work of Lobachevsky's. In geometry, I find certain imperfections which I hold to be the reason why this science, apart from transition into analytics, can as yet make no advance from that state in which it has come to us from Euclid. As belonging to these imperfections, I consider the obscurity of the fundamental concepts of the geometrical magnitudes and in manner and method of representing the measuring of these magnitudes, and finally the momentous gap in the theory of parallels, to fill which all efforts of mathematicians have been so far in vain. For this theory, Legendre endeavours have done nothing, since he was forced to leave the only rigid way to turn into a side path and take refuge in auxiliary theorems which he illogically strove to exhibit as necessary axioms. My first essay on the foundations of geometry I published in the Kazan Messenger for the year 1829. In the hope of having satisfied all requirements, I undertook hereupon a treatment of the whole of this science, and published my work in separate parts in some sort of something. Oh, okay. So something from the Kazan University. For the years 1836, 1837, 1838, under the title New Elements of Geometry, with a complete theory of parallels. The extent of this work perhaps hindered my countrymen from following such a subject, which since Legendre had lost its interest. Yet I am of the opinion that the theory of parallels should not lose its claim to the attention of geometers, and therefore I aim to give here the substance of my investigations, remarking beforehand that contrary to the opinion of Legendre, all other imperfections, for example, the definition of a straight line, show themselves foreign here and without any real influence on the theory of parallels. In order not to fatigue my reader with the multitude of those theorems whose proofs present no difficulties, I prefix here only those of which a knowledge is necessary for what follows. And then we're off. Pretty serious business. There you go. And there's a translator's appendix. Elliptic geometry. Gauss himself never published aught upon this fascinating subject, geometry non-Euclidean. But when the most extraordinary pupil of his young teaching life came to read his inaugural dissertation before the philosophical faculty of the University of Göttingen, from the 3 themes submitted, it was the choice of Gauss which fixed upon the one, über die Hypothesen will do, something about geometry. Gauss was then recognized as the most powerful mathematician in the world. I wonder if he saw that here his pupil was already beyond him, when in his 6th sentence Riemann says, therefore space is only a special case of a 3-fold extensive magnitude, and continues, from this, however, it follows of necessity that the propositions of geometry cannot be deduced from general magnitude ideas, but that those peculiarities through which space distinguishes itself from other thinkable 3-fold extended magnitudes can only be gotten from experience. Hence arises the problem to find the simplest facts from which the metrical relations of space are determinable, a problem which from the nature of the thing is not fully determinate. For there may be obtained several systems of simple facts which suffice to determine the metrics of space. That of Euclid, as weightiest, is for the present aim made fundamental. These facts are, as all facts, not necessary, but only of empirical certainty. They are hypotheses. Therefore, one can investigate their probability, which, within the limits of observation, of course, is very great, and after this judge of the allowability of their extension beyond the bounds of observation, as well on the side of the immeasurably great as on the side of the immeasurably small. Riemann extends to this idea of curvature to space of 3 and more dimensions. The curvature of the space is constant and positive, and on it figures can freely move without deformation. The curvature of the plane is constant and 0, and on it figures slide without stretching. The curvature of the 2-dimensional space of Lobachevsky and Bolyai completes the group, being constant and negative, and in it figures can move without stretching or squeezing. As thus corresponding to the sphere, it is called the pseudosphere. In the space in which we live, we suppose we can move without deformation. It would then, according to Riemann, be a special case of a space of constant curvature. We presume its curvature null. At once, the supposed fact that our space does not interfere to squeeze us or stretch us when we move is envisaged as a peculiar property of our space. But is it not absurd to speak of space as interfering with anything? If you think so, take a knife and a raw potato and try to cut it into a 7-edged solid. I'm not sure what they were getting at there. Further on in this astonishing course comes the epoch-making idea that though space be unbounded, it is not therefore infinitely great. Riemann says, in the extension of space constructions to the immeasurably great, the unbounded is to be distinguished from the infinite. The first pertains to the relations of extension, the latter to the size relations. That our space is an unbounded 3-fold extensive manifoldness is a hypothesis, which is applied in each apprehension of the outer world, according to which, in each moment, the domain of actual perception is filled out, and the possible places of a sought object constructed, and which in these applications is continually confirmed. The unboundedness of space possesses, therefore, a greater empirical certainty than any outer experience. From this, however, the infinity in no way follows. Rather would space, if one presumes bodies independent of place, that is ascribed to it a constant curvature, necessarily be finite, so soon as this curvature had ever so small a positive value. One would, by extending the beginnings of the geodesics lying in a surface element, obtain an unbounded surface with constant positive curvature, therefore a surface which in a homoloidal, threefold extensive manifoldness would take the form of a sphere, and so is finite. Here we have for the first time in human thought the marvelous perception that universal space may yet be only finite. Assume that a straight line is uniquely determined by 2 points, but take the contradictory of the axiom that a straight line is of infinite size, then the straight line returns into itself, and two having intersected get back to that intersection point. On we go. So we're up to János Bolyai, 1802 to 1860. His life and work. In the Odyssey, Homer wrote, "Few sons are the equals of their fathers. Most fall short, all too few surpass them." None of the other mathematicians featured in this book were the sons of mathematicians. János Bolyai is the exception. His father, Farkas Wolfgang Bolyai, from 1775 to 1856, was a mathematician of some note. Both worked on the problem of Euclid's parallel postulate. The elder Bolyai tried and failed to prove the parallel postulate. When he learned that his son was pursuing the same problem, he advised his son to give it up, essentially giving the age-old advice, "Do as I say, not as I do." János ignored his father's advice and ultimately devised a non-Euclidean geometry. To understand the achievement of the son, we must first learn the work of the father. This essay is about both of them. The Bolyais descended from the ancient Hungarian noble family of Bolya de Bolyai, which had been known for their heroic participation defending their homeland against the Turks as far back as the 13th and 14th centuries. The family had once been wealthy, but by the middle of the 18th century was no longer so. Farkas Wolfgang Bolyai was born to Gaspar Bolyai and his wife Kristina on the greatly diminished Bolyai estate in the village of Domald near the town of Marsovonagashle. At that time, Transylvania was part of the Kingdom of Hungary in the Austro-Hungarian Empire. Since the end of World War I, Transylvania has been part of Romania, and Marsovonagashle has been known as Târgu Mureș. Gaspar taught Farkas his first lessons until he enrolled Farkas at the age of 6 at the Calvinist Evangelical Reform School in the nearby city of Nagyszeben. The school's faculty immediately recognized Farkas's talents in language, music, and of course mathematics. At age 12, his talents earned him the appointment as tutor to Simon Kameni, the 8-year-old son of a member of an important local baron. This appointment enabled Farkas to pursue an education that his family probably could not have afforded. After finishing at the local school, Farkas and Simon enrolled at the Calvinist college in nearby Kolozsvár. Hungary had won its freedom from the Ottoman Empire in 1699, only to find itself 90 years later under the thumb of the Habsburg Austro-Hungarian Empire. Kolozsvár was a hotbed of liberalism and Hungarian nationalism when Farkas arrived in 1790. No doubt he was greatly influenced by the view that reason rather than faith lay at the heart of understanding the cosmos and improving the lot of humankind. In particular, it lay at the heart of developing a truly Hungarian culture. When Farkas and Simon graduated in 1796, they chose not to pursue their education in Vienna, the imperial capital. Instead, they matriculated first at the University of Jena in Prussia, before moving on to the prestigious University of Göttingen. At Göttingen, they were exposed to the very newest results in mathematics and the sciences. Most importantly for Farkas, he had the good fortune to be at Göttingen at the same time as Carl Friedrich Gauss, the greatest mathematician of all time. They became close friends and corresponded with each other for the rest of their lives. Farkas and Simon lived the good life in Göttingen for the 2 years it took them to complete their studies. Then Simon's father ran into financial difficulties, their credit evaporated, and Farkas could not even afford to return home. For a year he had to borrow and beg for money in order to eke out a meagre existence, until a friend from Hungary sent him enough money to pay off his debts and allow him to return home by foot. Back in Kolosvar, he found employment as a tutor. Thinking his income sufficient to support a family, Farkas married Susanna von Arcos, the daughter of a local surgeon. A year later, on December 15, Susanna gave birth to their firstborn, a son named János. The financial demands of his new family soon forced Farkas to accede to his father's wishes that he return home to Maroskoshule to take up a job teaching mathematics, physics, and chemistry at the local Calvinist college. Once again, the job paid very little, but Farkas was able to supplement his income by writing and producing his own plays, running the college tavern, and even designing tiles and cast iron stoves. János turned out to be Farkas and Susanna's only child to live past infancy. As his marriage to Susanna soured, Farkas turned his attention more and more to János. By the age of 4, János was already able to point out the most prominent constellations in the night sky. He also demonstrated an easy facility with mathematics at an early age, being able to identify a number of geometric figures and even the sine function. He taught himself how to read by the age of 5, and by the age of 7 was giving violin recitals. János was tutored at home until the age of 9. His father taught him mathematics, and the best students at the local college tutored him in other subjects. János entered the local college in 1812, shortly before his 10th birthday. Not surprisingly, he flew through his studies, often taking classes intended for students several years older. Noting that János mastered calculus by the age of 13, Farkas thought that his son could be best educated under Gauss's wing at Göttingen. No doubt this would have been the best plan for János. Unfortunately, Gauss rejected his old friend's suggestion, and the Bolyais needed to turn elsewhere for János's continuing education. When János graduated from the local college in 1818, neither the university at Vienna nor the one in Pest offered an attractive course in mathematics. Going to a foreign university was out of the question, being beyond Farkas's financial means. In the end, János decided to study military engineering at the Imperial Academy of Engineering in Vienna. He took only 4 years to complete a course that normally took 7. While in Vienna, János became close friends with Carl Saz, who was enrolled for a law degree. They spent many hours together working on the parallel postulate. János began to work on Euclid's parallel postulate when he attended the Imperial Academy, in spite of his father's warning that he not do so. You should not tempt the parallels in this way. I know this way until its end. I have also measured its bottomless night. I have lost in it every light, every joy of my life. You should shy away from it as if from lewd intercourse. It can deprive you of all your leisure, your health, your peace of mind, and your entire happiness. This infinite darkness might perhaps absorb 1,000 giant Newtonian towers. It will never be light on earth, and the miserable human race will never have something absolutely pure, not even geometry. Farkas had begun his own attacks on the parallel postulate while still in Göttingen, and made his greatest progress while János was still a very young child. Farkas pursued a path that had been trodden by many mathematicians before him, trying to prove Euclid's parallel postulate. He attempted to prove that the distance line of a straight line is itself a straight line. Farkas began by considering the segment BD and the segment CH, perpendicular to it at C, its midpoint. He considers T to be the geometrically movable rigid figure BCDH, shaped like a T upside down, and moves T along me. It says me. I think it means the line AE in either direction, plus or minus infinity. Farkas attempted to prove that the curve G described the point H there's some word missing there. Farkas attempted to prove that the curve G described the point H is a straight line. That's not grammatical. I'm not sure what he meant exactly. He first accused that G is not a straight He first assumed that G is not a straight line, noting that G would be symmetric with respect to the line including the segment CH. Farkas laboriously argued that G would intersect CH again at a point other than H. Farkas sent this proof to Gauss in late 1804. Gauss quickly spotted the error in Farkas's proof, namely the argument that G would intersect CH again at a point other than H, and wrote back informing his friend. It would later be shown that the assertion that G is a straight line is equivalent to Euclid's parallel postulate. Gauss's response deflated Farkas so much that he gave up further attempts to prove the parallel postulate and spent the rest of his career trying to find simpler and more plausible equivalents to Euclid's parallel postulate. Thus, Farkas's 1820 warning to János should come as no surprise. It was simply a piece of fatherly advice. János paid it no heed and began his own attempts first to prove the parallel postulate and then to develop a non-Euclidean geometry. Upon his graduation from the Imperial Engineering Academy in 1822, János was immediately commissioned as a sub-lieutenant in the Imperial Army and posted to the city of Lvov, now part of the Ukraine. It was from Lvov that on November 3, 1823, János wrote to his father that, "From nothing I have another entirely new world." János considered a line G, a point O not on G, and constructs the perpendicular from O to G that intersects G at the point N. He further supposes the points A and B to lie on G on either side of N. Then, perhaps owing to his training as an engineer, or perhaps due to a suggestion of Saz, he rotates the half line OA counterclockwise about O and notes that there will be a position, OA star, at which the half line rebounds from G and no longer intersects it. He considers the same rotation of OB clockwise about O, rebounding from G at OB star. János then asks a very interesting question. Are the half lines OA star and OB star extensions of each other or not? If they are, standard Euclidean geometry results. If they are not extensions of each other, then a non-Euclidean geometry results in which the parallel postulate does not hold. Notice that in this case there is a positive angle between OA star and OB star. As a result, the sum of the angles NOB star and ONB star is less than two right angles. From this, János easily deduces that in this geometry, the sum of the angles of a triangle is less than two right angles. It would be more than a year until János could actually show his new geometry to his father. Farkas remained cautious at first. After all, he had once thought that he had made a significant breakthrough, only to be disappointed severely. This mattered little to János, who had little time to think about publishing his work owing to his frequent reassignments that took him to different parts of the eastern provinces of the empire. By 1831, however, Farkas had become enthusiastic about his son's work, describing it in his diary as an original and great work, the greatest yet written by a Hungarian. When János visited in 1831, Farkas urged János to allow him to include his Science of Absolute Space in the great mathematical compendium, the Tentamen, that he was publishing after a decade of effort. János agreed. Thinking of his son's accomplishment, Farkas sent a copy of János's essay to Gauss as soon as it was published. After reading János's work, Gauss wrote to one correspondent, "I regard this young geometer Bolyai as a genius of the first order." His response to Farkas was less complimentary and more matter-of-fact. "Now something about the work of your son. You will probably be shocked for a moment when I begin by saying I cannot praise it, but I cannot do anything else, since to praise it would be to praise myself. The whole content of the paper, the path that your son has taken, and the results to which he has been led, agree almost everywhere with my own meditation, which have occupied me in part already for 30 to 35 years. Farkas was stunned. János was dismayed as well. Unaware of Lobachevsky's simultaneous discovery of non-Euclidean geometry, Gauss's response seemed to have robbed János of priority. Even after he became convinced of the veracity of Gauss's claim, János remained bitter that the great man had chosen to remain silent about his earlier discoveries. Gauss's response no doubt contributed to János's growing irritability and declining health. Having been plagued by a fever for several months, János was forced to retire from the army in June 1833 at the age of 30. János first went to live with his father in Moravia. However, he did not get along with his stepmother Teresa, whom Farkas had married in 1824, 3 years after the death of János's mother. After a year, János left for Domald, where he lived on the old Bolyai estate. It was there that he met Rosalie von Orban, who would become his common-law wife. His pension was so minuscule that he could not afford to make the deposit required for a proper marriage. János continued to work on mathematics for the rest of his life, especially on the geometric representation of complex numbers. In 1837, the Jablonski Society of Leipzig issued a call for papers on the topic. János was chagrined when he learned that his father had also submitted a paper to the society. Neither Bolyai's paper was published. Indeed, even though he wrote an additional 20,000 notebook pages, now housed in a library in Târgu Mureș, János published nothing but the Science of Absolute Space during his lifetime. By 1846, Rosalie had borne János 3 children, 2 of whom survived. For some reason, perhaps wanting to be closer to his widowed father, János moved his family from Domald back to Maroskovile that year. Moving closer to his father did not work out well. Relations between Farkas and János worsened. One consequence of their proximity was that Farkas easily passed a copy of Lobachevsky's theory of parallel lines onto János when a copy arrived in 1848. János studied Lobachevsky's work in great detail, recording his observations in a notebook labeled Geometrical Examination. At first he thought that Lobachevsky might be a fictional character made up by Gauss, perhaps. In the end, János recognized that he and Lobachevsky had independently discovered non-Euclidean geometry, with the Russian being equally deserving of credit. János and Rosalie finally had a proper marriage in 1849 after a change in the law no longer required him to make an onerous deposit. Unhappily, he left her 3 years later. Farkas finally retired from his college post in 1851 and died on November 20, 1856, after suffering a series of strokes. By that time, János was already in the throes of a protracted illness. He died a little more than 3 years later on January 27, 1860. János was so little known when he died that no portrait remains of him. When the Hungarian post office issued a stamp reproduced at the opening of this chapter to honor the centenary of his death, it had to have an imaginary portrait of him painted. The science of absolute space lay forgotten until Richard Balzer discussed it along with Lobachevsky's theory of parallel lines in the second edition of his Element de Mathématiques in 1867. Further recognition came when the French mathematician Jules Hoel published a French translation a year later. The ultimate tribute came at the end of the 19th century when the French mathematician Henri Poincaré used the title Bolyai-Lobachevsky geometry to describe the non-Euclidean geometry these mathematicians had discovered coincidentally. This is The Science of Absolute Space, translated by Dr. George Bruce Halstead, and then there's a translator's introduction. So this is the notes from the translator. The year 1799 finds two extraordinary young men striving thus: to gild refined gold, to paint the lily, to cast a perfume over the violet. Okay, I didn't really understand that. A little bit too poetic for me. So that was a lot of notes from the translator, and the notes have an appendix. There you go. And then here we go into János Bolyai. János Bolyai. And this is Science of Absolute Space, which is a fascinating title. Wow. Section 1. If the ray AM is not cut by the ray BN, situated in the same plane, but is cut by every other ray BP, comprised in the angle ABN, we will call ray BN parallel to ray AM. This is designated by BN, and then there's double pipes AM. I'm not sure what the double pipes mean. I probably should know. Oh, of course, parallel. BN is parallel to AM. That's BN and AM parallel. Okay. They're in the same plane, and the angle okay. Well, okay. So, I mean, my amateur thing is that the ABN in those circumstances is a right angle 90 degrees. It is evident that there is one such ray BN and only one passing through any point B taken outside of the straight AM, and that the sum of angles BAM and ABN cannot exceed a ST angle, for in moving BC around B until BAM plus ABC equals ST angle. Well, ST angle must be 180 degrees. I've never heard that notation before. Somewhere ray BC first does not cut ray AM, and it is then BC is parallel to AM. It is clear that BN parallel to EM, wherever the point E be taken on the straight AM, supposing in all such cases that AM is greater than AE. Right. Okay. So that's pretty basic beginnings, and on we go. So this is, as he said, the science of absolute space. Actually, it's funny. It's the science absolute of space. Do you think that's a mistranslation? The science absolute of space. Isn't it? Wouldn't it be the absolute science of space? I'm not sure. They've gone to a lot of trouble to reproduce these papers, and all the typesetting and diagrams must have taken a long time. I wonder how many mistakes there are in there. There'd be more than one. Okay, and this from János Bolyai has an appendix, number 1, remarks on the preceding treaty by Bolyai Farkas. Just a sec. So, yes, appendix 1, remarks on the preceding treatise by Bolyai Farkas. There we go. Okay. Appendix 2. Some points in John Bolyai's appendix compared with Lobachevsky by Wolfgang Bolyai. So I don't know who these other Bolyais are. Maybe they're brothers or parents, I'm not sure. And then there's appendix 3. Light from Non-Euclidean Spaces on the Teaching of Elementary Geometry by G.B. Halstead. As foreshadowed by Bolyai and Riemann, founded by Cayley, extended and interpreted for hyperbolic, parabolic, elliptic spaces by Klein, recast and applied to mechanics by Sir Robert Ball, proactive metrics may be looked upon as characteristic of what is highest and most peculiarly modern in all the bewildering range of mathematical achievement. Mathematicians hold that number is wholly a creation of the human intellect, while on the contrary our space has an empirical element. Of possible geometries we cannot say a priori which shall be that of our actual space, the space in which we move. Of course, an advance so important, not only for mathematics but for philosophy, has had some metaphysical opponents, and as long ago as 1878 I mentioned in my Bibliography of Hyperspace and Non-Euclidean Geometry, published in the American Journal of Mathematics, Volume 1, 1878, and Volume 2, 1879. Of these, Schmerz-Dumont as a sad paradoxer, and another J.C. Becker, both of whom would ere have shared the oblivion of still more antiquated fighters against the light, but that Dr. Schotten, praiseworthy for the very attempt at a comparative planimetry, happens to be himself a believer in the a priori founding of geometry, while his American reviewer, Mr. Zewett, was then also an anti-non-Euclidean, though since converted. Okay. He says, we find that some of the best German textbooks do not try at all to define what is space, or what is a point, or even what is a straight line. Do any German geometries define space? I never remember to have met one that does. In experience, what comes first is a bounded surface, with its boundaries, lines, and their boundaries, points. Are the points those definitions are omitted anything different or better? Are the points whose definitions are omitted anything different or better? Dr. Schotten regards the two ideas, direction and distance, as intuitively given in the mind, and as so simple as to not require definition. When we read of two jockeys speeding around a track in opposite directions, and also on page 87 of Richardson's Euclid, 1891, read, the sides of the figure must be produced in the same direction of rotation, going round the figure always in the same direction. We do not wonder that when Mr. Zewett had written, he therefore bases the definition of the straight line on these two ideas, he stops, modifies, and rubs that out as follows, or rather recommends to elucidate the intuitive idea of the straight line possessed by any well-balanced mind by means of the still simpler ideas of direction in a circle and distance on a curve. But when we come to geometry as a science, as foundation for work like that of Cayley and Ball, I think with Professor Crystal It is essential to be careful with our definition of a straight line, for it will be found that virtually the properties of the straight line determine the nature of space. Our definition shall be that 2 points in general determine a straight line. We presume that Mr. Zigwet glories in that unfortunate expression, a straight line is the shortest distance between 2 points. Still, occurring in Wentworth, New Plane Geometry, page 33, even after he has said, page 5, the length of the straight line is called the distance between 2 points. If the length of the one straight line between 2 points is the distance between those points, how can the straight line itself be the shortest distance? If there is only one distance, it is the longest as much as the shortest distance, and if it is the length of this shorter longest distance, which is the distance, then it is not the straight line itself, which is the longer shortest distance. But Wentworth also says, of all lines joining 2 points, the shortest is the straight line. This general comparison involves the measurement of curves, which involves the theory of limits, to say nothing of ratio. The very ascription of length to a curve involves the idea of a limit. And then to introduce this general axiom, as does Wentworth, only to prove a very special case of itself, that 2 sides of a triangle are together greater than the third, is surely bad logic, bad pedagogy, and bad mathematics. This latter theorem, according to the first of Pascal's rules for demonstrations, should not be proved at all, since every dog knows it. But to this objection, as old as the sophists, Simpson long ago answered for the science of geometry that the number of assumptions ought not to be increased without necessity, or as Dedekind has it, something in German. I'm not even going to try, I don't speak German. I have no idea what that says. Professor W.D. Smith, Ph.D., Göttingen, has written, nothing could be more unfortunate than the attempt to lay the notion of direction at the bottom of geometry. Was it not this notion which led so good a mathematician as John Casey to give as a demonstration of a triangle's angle sum the procedure called a practical demonstration on page 87 of Richardson's Euclid, and there described as laying a straight edge along one of the sides of the figure and then turning it around so as to coincide with each side in turn. This assumes that a segment of a straight line, a sect, may be translated without rotation, with which assumption readily comes to view when you try the procedure in two-dimensional spherics. Though this fallacy was exposed by so eminent a geometer as Olaus Henrici, and so public a place as the pages of Nature, yet it has just been solemnly reproduced by Professor G.C. Edwards of the University of California in his Elements of Geometry, Macmillan, 1895. It is of the greatest importance for every teacher to know and connect the commonest forms of assumption equivalent to Euclid's axiom 11. If in a plane 2 straight lines perpendicular to a third nowhere meet, are there others, not both perpendicular to any third, which nowhere meet? Euclid's axiom 11 is the assumption no. Playfair's answer no. Playfair's answers no more simply. But the very same answer is given by the common assumption of our geometries, usually unnoticed, that a circle may be passed through by any 3 points not co-straight. This equivalence was pointed out by Farkas, who took upon this as the simplest form of the assumption. Other equivalents are the existence of any finite triangle whose angle sum is a straight angle, or the existence of a plane rectangle, or that in triangles the angle sum is constant. Okay. This is going to go on for a fair bit, so we won't read all of it. Now we're up to Évariste Galois. What do we know about it's Évariste Galois. Évariste Galois. Born in 1877. No, that's 1811. And died 1832. Didn't live very long. 20 years old. Shocking. His life and work. When you are young, your world knows no bounds. Everything is possible. Solutions for the world's ills, no matter how complex, lie within your grasp, no matter how radical those solutions may be. How ironic that Évariste Galois, the shortest-lived mathematician chronicled in this book, made his mark by proving that there is no general solution by radicals for polynomial equations of the fifth degree or higher. I'm going to read that again. What did he prove? Proving that there is no general solution by radicals for polynomial equations of the fifth degree or higher. Okay, well, I know what fifth degree polynomials are, but I don't yet know what solution by radicals refers to. Perhaps that'll be covered in this chapter. On October 25, 1811, Nicolas Gabriel Galois and his wife Adelaide Marie Niedemante became parents of a son, Évariste, perhaps the most precocious mathematician of all time. We have no record of mathematical talent on either side of Évariste's family. Nevertheless, he came from good intellectual stock. His maternal grandfather and an uncle on that side of his family were juries at the Faculty of Law in Paris. His father and paternal grandfather were headmasters of a school. Galois grew up in his birthplace of Bouches-la-Reine, a town about 5 miles outside of Paris, which his father served as mayor when Napoleon returned to power during the 100 Days in 1815. Adelaide Marie, which is his mother, served as her son's only teacher until he turned 12. She gave him a good foundation in Greek and Latin and passed on the religious skepticism she shared with her husband. In 1823, at age 12, Galois' parents enrolled him as a boarder in the 4th class at the prestigious Lycée of Louis le Grand in Paris. This famous preparatory school, which still exists, already numbered both Robespierre and Victor Hugo amongst its alumni. It is likely that Galois' parents thought that Louis le Grand would be a liberal environment in which their son would be nurtured amidst a country that was becoming more royalist and more conservative. They turned out to be very mistaken. During Galois' first few months at Louis le Grand, a large number of students rebelled against the headmaster's plan to bring a conservative Jesuit faculty back to the school. Some students refused to recite in class. Some refused to sing at mandatory chapel service. Many refused to toast the dying King Louis XVIII. Although this behaviour was characteristic of Galois' later teenage years, we have no way of knowing whether he was among the rebels. In any case, Galois was not one of the 40 students the headmaster summarily expelled in response to the rebellion. Perhaps Galois did not participate in the rebellious activities after all. He had a sterling record during his first 2 years at Louis le Grand, earning a first prize and several honourable mentions for his academic work. But then Galois became bored with his studies, performed poorly in his 3rd year, and had to repeat it. Fortunately, he took his first mathematics course when he repeated his 3rd year and then flourished. This class introduced him to Legendre. I don't know how to pronounce that. Is it going to be in my notes? Okay, Legendre. Sorry about that. Where are we? A first prize and several honourable mentions for his academic work. But then Galois became bored, blah, blah, blah. Where were we up to? This class introduced him to Legendre. Legendre. Sorry. This class introduced him to Legendre's textbook in geometry, which Galois is said to have read with the speed of someone reading a novel. Galois did not merely flourish, he engulfed himself in mathematics, doing this at the cost of his other work. Soon he was receiving poor marks in all of his courses except mathematics. His rhetoric instructor described him as dissipated. Only his mathematics instructor, Vernier, recognized Galois' burning genius. He wrote, "Mathematics is the passion that dominates him. I think it would be best for him if his parents allowed him to study nothing else. He is wasting his time here and does nothing but torment his teachers and overwhelm himself with punishments." Vernier also wrote that his pupil needed to acquire more method, but Galois would have none of that. Against Vernier's advice, Galois took the entrance examination to the prestigious École Polytechnique a year earlier, and without even taking the usual preparatory course for the exam. Not surprisingly, Galois failed to gain admission because he lacked mastery in several basic areas of mathematics. To Galois, this was a great injustice, even when Vernier tried to explain that he should not be surprised. Nevertheless, Vernier encouraged Galois to enroll in a special mathematics class provided by the great teacher Louis-Paul Émile Richard. Richard soon recognized Galois' genius and tried to get his star admitted to the Polytechnic without taking their entrance examination. Not surprisingly, École, I don't know how you pronounce it, refused to consider that approach. Okay. In response, Galois drifted more and more from the work in Richard's course and began work on a short paper on continued fractions that he published in the Annales de Mathématiques in March 1829 at the age of 17. Galois spent the spring of 1829 working on his first paper on the resolution of algebraic equations to the Academy of Sciences, and getting ready to retake the entrance examination for École Polytechnique in July. Once again, matters did not go smoothly. Sometime in June of that year, a priest forged Galois' father's name on a number of scurrilous notes that greatly offended many members of the larger Galois family. Shamed by the scandal that followed, Galois' father committed suicide. Holy shit. What happened? A priest forged Galois' father's name on a number of scurrilous notes that greatly offended many members of the larger Galois family. And then he killed himself. Shamed by the scandal that followed, Galois' father committed suicide on July 2. Not surprisingly, Galois disastrously failed the entrance examination for the École Polytechnique. Consequently, he had to settle for École Normale, a school for training secondary school teachers. All right. The paper fared little better. The Academy appointed the great mathematician Cauchy to review the paper. However, Cauchy, absorbed as always in his own researches, took his time reviewing it. In January 1830, Cauchy wrote to a colleague that he had been too ill to present to the Academy his report on Galois' paper, as well as a paper of his own. A month later, Cauchy presented his own paper, but not his report on Galois' paper. Instead, it appears as though Cauchy encouraged Galois to revise his paper and resubmit it for the Academy's grand prize in mathematics to the mathematician Fourier. What did we make in our notes? It's Fourier, but I'm pretty sure everyone talks about Fourier transform. So I think the correct pronunciation is Fourier. So the Academy's perpetual secretary for mathematics and physics. Alas, Fourier died in April 1830, and there is no record of his having distributed Galois' paper to other members of the prize committee. Galois and France experienced a momentous year in 1830. King Charles X, who had ascended to the throne in 1824, was in many ways even more autocratic than the French kings of the 18th century who had preceded the Revolution of 1789. On July 26, 1830, Charles and his ministers issued ordinances suspending freedom of the press and greatly curtailing the powers of the legislature. By the end of the day, the citizens of Paris rose in revolt. 3 days later, they had deposed Charles and replaced him with his cousin, Louis Philippe, the Duke of Orleans. As revolutionary anti-monarchist sentiments formed in Paris during June and July, the director of L'École Normale locked his students inside to prevent them from taking to the streets. Galois became so angry with this that he tried to escape from the école by climbing over its walls. When he failed, there was nothing left to do but take his examinations in calculus and physics. On July 22, Galois placed 4th out of 9 students who took the calculus exam. 2.5 weeks later, on August 9th, he placed 3rd out of 8 students who took the physics examination. One can only presume that Galois was rather distracted by the events going on outside the walls of the school. With examinations finished and the July Revolution over, the director could no longer keep his students locked inside the school. Galois quickly took advantage of the new atmosphere and joined the Society of Friends of the People, an extremist Republican secret society that sought the abolishment of the monarchy altogether. His political activities soon got Galois in deep trouble with the school, so deep that he quit the school in early December before the director's expulsion notice became effective. On leaving the school, Galois immediately joined the artillery of the National Guard, a branch of the militia composed mostly of rabidly anti-monarchist Republicans. On December 21, a Paris court was scheduled to pronounce sentence on 4 former ministers of Charles X who had been convicted of treason under the state treason against the state. Radical Republicans thought that the ministers deserved nothing less than the death sentence. The artillery of the National Guard, including Galois, stationed themselves in front of the Louvre, planning to start a revolt in case the court handed down a life sentence. Fearful of the mayhem that might ensue, the new king's minister moved the more regular troops near the Louvre. Both sides eyed each other suspiciously when a distant cannon shot indicated that life sentences had been pronounced. Fighting did not erupt, even though tensions ran high. When the Marquis de Lafayette, hero of both the American and French revolutions, called for peace, the crowd seemed to be placated. Nevertheless, fearing a threat to the throne, a royal decree abolished the artillery of the National Guard on December 31. Having dropped out of school, Galois decided to offer a weekly mathematics course of his own. The announcement in the Gazette stated that the course would cover mathematical topics that were new, some so new that they had never before been presented in public lectures. When the class met for the first time on January 13th, 1831, in a bookshop near the Sorbonne, nearly 40 students attended. Perhaps some of them wanted to see the fiery radical at the front of the class rather than at the back. In any case, the class only met a few times. Galois' political activities occupied him anew. During the unrest of December 1830, 19 officers of the artillery of the National Guard had been arrested on a charge that they had conspired to give their cannons to the mob. Their imprisonment and trial consumed Galois. Following their acquittal in April 1831, Galois was one of the organisers of a celebration banquet to be held on May 9 at the restaurant of the Vendanges Le Bourgogne. I don't know what that is. Alexandre Dumas, author of The Count of Monte Cristo and The Three Musketeers, wrote in his diary, "It would be difficult to find in all of Paris 200 persons more hostile to the government than those to be found reunited at 5 o'clock in the afternoon in the long hall on the ground floor above the garden." During the banquet, Galois took out a pocket knife, raised a wine glass, and made a toast that invoked the name of the new king, Louis Philippe. Some people at the banquet thought they heard Galois make a threatening remark about the king. Others thought that someone else had made the remark while Galois was making his toast. The authorities chose to believe the worst of Galois and arrested him. The next day, while he was visiting his mother, he was jailed at Saint-Pélagie prison in Paris to await his trial. The trial began on June 15. Galois' lawyer told the jury that Galois had said to Louis Philippe, "If he betrays," as he was wielding his knife, and that many in the crowd had not heard him say, "If he betrays," because of the noise. Galois became his own worst witness when the prosecutor interrogated him. When the prosecutor asked him if he really meant to kill the king, Galois responded, "Yes, if he betrays." Dear me. He went on to predict that the king would, in fact, betray the people if he had not done so already. Fortunately for Galois, the judge charged the jury to decide what Galois had said and meant at the feverish banquet, not what he had said under oath in the more sedate courtroom. The jury may have been moved by Galois' tender years. They acquitted him after only a few minutes of deliberation. Galois could not keep himself out of trouble. Many years later, celebrating Bastille Day would have been considered an ordinary act of French patriotism. In 1831, celebrating it by wearing the uniform of the outlawed artillery guard, as Galois and his Republican friend Duchatelet chose to do, was an extremely seditious act. The two friends were imprisoned in Saint-Pélagie prison for their behaviour. The end of July marked the first anniversary of the July Revolution of 1830. To commemorate the fallen heroes, the warden of Saint-Pélagie arranged for a mass to be held in their memory. Not surprisingly, the atmosphere at the mass was very tense. As the prisoners were being locked in their cells, cries of "Help! Murder!" were heard. A shot rang out from the garret of the prison guard who lived across the street. One of the prisoners fell wounded. Enraged, Galois accused the warden of having arranged the shooting. The warden responded by throwing Galois into the dungeon. Holy cow. Galois languished there for more than 3 months until he was formally charged and then sentenced to an additional 6 months in prison. While in prison, he learned that the Academy had rejected his latest manuscript. Its secretary, Francois Arago, wrote that the mathematician Poisson had reported, "We have made every effort to understand Galois' proofs. His argument is neither sufficiently clear nor developed sufficiently to allow us to judge its rigour. It is not even possible for us to give an idea of his paper." The author claims that the manuscript contains propositions that are part of a general theory having rich applications. Quite often, different parts of a theory clarify each other and can be understood more easily when taken together than when taken in isolation. We would prefer to wait for the author to publish a more complete account of his work before forming a more definite opinion. Okay. Reading this crushed Galois. He decided to publish the papers himself with the help of his friend Auguste Chevalier. Two of them are presented here. Here is a brief description of the mathematics they cover. Okay, so we're going to have a look at polynomials, quadratic equations. This is, I forget what they call this one, minus b plus or minus the square root of b squared minus 4ac over 2a. I wonder, did you see the guy who figured that out? No, we must have known that earlier. So that was just all notes. Who said this? To one Republican friend he wrote, okay, Galois died on the morning of May 30 as a result of a duel with a man named Péchu de Herbenville. Little remains of the last month of Galois' life, aside from letters he wrote the night before the duel. To one Republican friend, he wrote, "I die the victim of an infamous coquette and her 2 dupes. It is in a miserable piece of slander that I end my life." To another he wrote, "I have been provoked by 2 patriots. It is impossible for me to refuse." For many years, historians conjectured the reason for Galois' fatal duel. Possible reasons include a royalist plot, a government conspiracy, a female agent provocateur, or a prostitute. In the 1960s, an historian looked at the original copy of the letters Galois wrote and noticed that Galois had erased the name Stephanie Dumotel from one of them. Further investigation revealed that Stephanie Felice Potterin du Motel was the daughter of the doctor who had treated Galois at Sierre Fautrier. Perchot was one of the 19 Republicans who had been acquitted of conspiring to give cannons to the mob. Finally, here was conclusive evidence that Galois had died for love. The night before he died, Galois also wrote a final letter to his friend, Chevalier, printed here, in which he gave an overview of his works. Galois asked his friend to publish it in the Revue Encyclopédique, which Chevalier did. In the letter, Galois wrote, "Ask Jacobi or Gauss to give their opinion, not as to the truth, but as to the importance of the theorems." Neither of the 2 mathematicians seems to have taken notice. A decade later, the French mathematician Joseph Louis Ville did take notice. In 1843, Liouville announced to the Academy that he had found in Galois' work a solution as correct as it was deep of a lovely problem, given an irreducible equation of prime degree to determine whether or not it is solvable in radicals. In 1846, Liouville published Galois' complete works in the Journal of Mathematics. Pure Mathematics with Applications, I think, which he edited. Galois died in obscurity, with hardly anyone having read or understood his work. He is now recognized by the greatest accolade that mathematics can bestow. A branch of mathematics is named for him, Galois theory. Cool. I was going to take a quick break. So, this is Memoir on the Conditions for the Solvability of Equations by Radicals by Évariste Galois. The memoir given here is taken from a work that I had the privilege of presenting to the Academy 1 year ago. Because this work has not been included and the propositions that it held are again doubtful, I ought to be content to give the general principles of the theory in a synthetic form and give only one application of my theory. I implore my judges to read at least these few pages with care. Here we will find a general condition which is satisfied by every equation that is soluble by radicals, and that, conversely, assures their solvability, resolubility. Okay. We apply the condition only to equations the degree of which is a prime number. Here is the theorem given by our analysis. For an equation of a prime degree that does not have commensurable divisors to be soluble by radicals, it is necessary and sufficient that all the roots be rational functions of any 2 of the roots. The other applications of the theory are themselves particulars theories in their own right. Moreover, they need to use number theory and a particular algorithm. Let us save them for another occasion. In part, they have a relationship to the modular equations of the theory of elliptical functions, which we will demonstrate are not able to be resolved by radicals. January 16, 1831. Nice work, Évariste. So there he goes. He's off and away on his paper here. Proposition 1, Proposition 2, 3, 4. 5 and 6 and 7. And there we go. There's proposition 8. Seems to be quite a lot of prose with this proof compared to some of the other ones. Oh, here we go. On groups and equations and abelian integrals. Translated from the French by Dr. Louis Wisner, Hunter College of the City of New York. All right. Évariste Galois, 1811 to 1832, was born in Paris, was educated at the Lycée Louis le Grand and the École Normale. Sorry, I don't know how to pronounce it. Was a rabid Republican, was twice imprisoned for his political views, and lost his life in a stupid, boyish duel before he had reached the age of 21. His most important paper, Memoires sur les conditions blah blah blah, was not published until 1846, when his works appeared in the Louisville's Journal de Mathématiques. The night before the duel in which Galois was killed, he wrote a letter to his friend Auguste Chevalier, in which he set forth briefly his discovery of the connection of the theory of groups with the solution of equations by radicals. In this letter, written apparently under the impression that the result of the duel would be fatal to himself, he asked that it be published in the Revue Encyclopédique, which I wish that was carried out the same year, 1832, page 568. His works were republished in 1897 under the auspices of La Société Mathématique de France, with an introduction by E. Picard. Further writings of Galois were published by J. Tannery in the Bulletin des Scientific and Mathematics, 1906 to 1907, and reprinted the following year in book form. It being impossible to include in a source book of this kind the memoir above mentioned, the letter to M. Chevalier is here given in translation. Okay. There we go. So that's Évariste Galois' letter to his friend. Now we're up to George Boole, 1815 to 1864. He didn't live very long, did he? Still, he lived longer than Évariste Galois. His life and work. The class of people drenched in rain is identical to the class of people drenched in rain and drenched in rain. This is an example of the principle of idempotency, literally self-power. George Boole discovered its full power. His wife's misunderstanding of it would lead to his premature death. Dear me. George Boole was born in Lincoln, in the north of England, not far from the birthplace of the greatest English scientist of all time, Sir Isaac Newton. Boole's father, John Boole, came from a family that had lived in Lincolnshire for many centuries, but never flourished. Although trained as a shoemaker, John Boole developed a lively interest in scientific instruments, especially telescopes. In 1800, at the age of 23, he went to London to seek his fortune. London held no fortune for John, only a bride. In 1806, he met Mary Ann Joyce, a younger daughter from an old Berkshire family who was working in London as a lady's maid. They married after a short courtship, but had to live apart at their places of employment for 6 months. Then, as now, London was by far the most expensive place to live in England. Realizing that he would never make his fortune in London, John Boole moved back to Lincoln in 1807 and set up a shoemaker's business. The northern English air might not have suited Mary Ann Boole at first. For years she tried and failed to conceive a much hoped-for child. She and her husband were overjoyed when at the age of 34, after more than 8 years of marriage, she became pregnant with their first child. On November 2, 1815, she gave birth to a son, George, who was named after his recently deceased paternal grandfather. Motherhood must have agreed with Mary Ann Boole. In short order, she gave birth to a daughter and 2 more sons. Wow, at the age of 34. George Boole had a distinguished record at the local schools in spite of the shy and retiring character he would display his whole life. He supplemented his education in the classroom with much learning outside of it. As the firstborn, Boole was the apple of his parents' eye. His father spent many evenings with him building cameras, kaleidoscopes, microscopes, telescopes, and sundials. However, Boole first achieved notoriety thanks to his interest in classical languages. After learning Latin from a local bookseller, Boole taught himself classical Greek. At the age of 14, he made a metrical translation of an ode written by the Greek poet Melegia. The translation so impressed Boole's father that he persuaded the local Lincoln Herald to print it along with the translator's age. A local schoolmaster wrote to the editor that the translation far exceeded the powers of any 14-year-old. No doubt his schoolmaster would have been skeptical of Boole's mathematical genius. Even in his teens, Boole had become a religious nonconformist. Although raised in the Orthodox Church of England, his ability in languages allowed him to read a wide range of Christian theology. In some early notebooks, Boole compared the Christian Trinity with the three dimensions of space. At an early age, Boole developed an attraction to the ancient Hebrew conception of God as an absolute entity. For a while, Boole even considered the idea of converting to Judaism. In the end, he became a nonconformist Unitarian. He had come from a more well-to-do family. He certainly would have gone to Oxford or Cambridge, but that would never be his lot in life. As the son of a struggling shoemaker, there was no way that Boole could even contemplate a university education, much less the issues that his religious unorthodoxy might raise. So, rather than taking instruction, young George Boole decided to give instruction. At the age of 17, he became a schoolteacher in Doncaster. His nonconformist religious views made for a short stay there, and within a year, Boole moved to a post in Liverpool. Convinced of his abilities as a teacher and an administrator, he left his Liverpool position after just 6 months to return to Lincoln, where, in the fall of 1834, he opened a classical, commercial, and mathematical academy, a day school for young boys and girls. Boole's headmastership of the school must have been a success. In 1838, he took complete charge of a much larger academy in Waddington. With Waddington just 4 miles from Lincoln, Boole was able to maintain his ties with charitable and educational institutions in Lincoln. If Boole received his scientific tutelage from his father, he must have learned of the importance of good works from his mother. At the age of 20, he became a co-founder and trustee of the Female Penitence Home in Lincoln, a center for the rehabilitation of wayward women. He was also an officer of the named Early Closing Association. This was not a temperance union, but instead an organization seeking reasonable limits on working hours. Boole's most important civic association in London was with the Mechanics' Institution, whose founding coincided with his return in 1834. It was a combination trade school and lending library for the betterment of the working class. John Boole was its first curator, and he made sure that the library was well stocked with Royal Society publications and the great English and continental works such as Newton's Principia, Laplace's Mécanique Céleste, and Lagrange's Mechanic Analytic. George Boole devoured this material, reading it not once but again and again, if necessary, in order to master it. Perhaps I should do the same with this book. Boole also benefited greatly from his acquaintance with one of the patrons of the Mechanics' Institution, Sir Edward Bromhead, a fellow of the Royal Society. Bromhead was a Cambridge graduate and a talented amateur mathematician who had an eye for mathematical genius. He had recently been a sponsor of the Nottingham mathematician George Green. Boole must have spent many hours visiting Bromhead at his family manor, Thirlby Hall, just outside Lincoln, and borrowing volumes from Bromhead's library. The environment in and around Lincoln must have suited Boole. In 1838, he published his first paper on certain theorems in the calculus of variations. His early papers covered a wide range of topics: differential equations, integration, logic, probability, geometry, and linear transformations. These papers all appeared in the recently founded Cambridge Mathematical Journal. By 1843, Boole had the confidence to submit his paper on a general method in analysis to the Royal Society, the apex of British science. The Royal Society almost failed to consider Boole's paper because no one on the Society's council knew Boole. Fortunately, the head of the Society's Mathematics Committee suggested that two specialists review the paper. One of the specialists wanted to reject the paper. His opinion did not prevail. The other specialist not only recommended the publication, but also nominated the paper for the gold medal that the Society was offering for the best paper submitted between 1841 and 1844. His recommendation carried the day, earning Boole the acclaim of the British mathematics community. In spite of this award, Boole continued his habit of often refusing introductions to eminent mathematicians, feeling that his work was inferior to theirs. In fact, as late as 1845, at almost the age of 30, he considered taking an undergraduate degree at Cambridge. When he realized that he could not shirk his continuing financial responsibility for his parents, Boole reversed course, and instead of seeking to enroll in a university, he decided to seek a university professorship. Fortunately for Boole, the government of Sir Robert Peel passed a bill establishing 3 new Queen's Colleges in Ireland in 1846. Boole quickly applied for a professorship at these new colleges and hoped that he would be appointed within a year. That did not happen. The Great Irish Potato Famine diverted the government's attention away from the colleges to more important matters. Boole finally received his appointment to Queen's College, Cork, in southwest Ireland in August 1849, shortly after the death of his father. Boole's paper on a general method in analysis was a precursor to his groundbreaking work in logic. It focused on the structure and form of the objects of mathematical analysis, thereby laying the foundation for his attention to the structure and form of logic itself. In a postscript to his paper, Boole wrote, "The position which I am most anxious to establish is that any great advance in the higher analysis must be sought for by an increased attention to the laws of the combination of symbols. The value of this principle can scarcely be overrated." At Queen's, Boole quickly earned appointment to be Dean of Faculty. In this position, he gave an annual address to the college faculty at the start of every college session. His 1851 address, titled "The Claims of Science, especially as founded in its relations to human nature," contains hints of what he would address 3 years later in The Laws of Thought. In this address, he asked, first, whether there exist, with reference to our mental faculties, such general laws as are necessary to constitute a science. For we have seen that it is essentially in recognition of general laws, not of particular facts, that science consists. Secondly, supposing that such general laws are discoverable, what is the nature of the relation between the mind, which the mind sustains towards them? Is it like that of external nature, a relation of necessary obedience, or is it a relation of some distinct kind having no example and no parallel in the material system? If it is asked whether, out of these common principles of the reason, we are able to deduce the actual expression of its fundamental laws, I reply that this is possible, and that the results constitute the true basis of mathematics. I speak here not of the mathematics of number and quantity alone, but of mathematics in its larger, and I believe, truer sense, as universal reasoning expressed in symbolic forms, and conducted by laws, which have their ultimate abode in the human mind. Aristotle and Leibniz, the greatest logicians of all time prior to Boole, believed that it should be possible to express the fundamental laws of logic in a mathematical form. Prior to Boole, many mathematicians had tried to do just that. Indeed, Leibniz had developed a scheme in which the expression all x are y was expressed as x/y. By analogy to arithmetic, x/y times y/z equals x/z, thereby representing that if all x are y and all y are z, then all x are z. But this was about the limit to all attempts prior to Boole. All of the previous attempts to render logic in algebraic form had tried to force it into the algebra of real numbers. Boole realized that another algebra was needed. In the laws of thought, he progressed along the road to abstraction by performing algebraic operations on symbols representing entities not previously considered mathematical objects at all. The intersection of two classes was represented by a multiplication-like operation, and the union of two classes was represented by an addition operation. Classical logic had concentrated on the four forms statement: all x are y, no x are y, some x are y, some x are not y. Boole began by focusing on the first of these forms, all x are y. He represented the assertion that all x are y as xy equals y. Thus, if all x are y, then all y are x. Then xy equals yx. In particular, xx equals x. That is, x squared equals x. The principle of idempotency for all classes x, not just for two particular values in numeric algebra. With plus representing class intersection, Boole demonstrated a distributive law of class intersection over class union, namely zx plus y equals zx plus zy. For example, the intersection of z, the class of left-handed people, with the union of x, the class of Englishmen, and y, the class of Irishmen, is identical to the union of the class of left-handed Englishmen with the class of left-handed Irishmen. Boole then demonstrated how purely symbolic manipulation of class representations could be used to represent classical schemes of implications without making reference to the schemes themselves in the argument. Here is how Boole proved that if all x are y and all y are z, then all x are z. By supposition, all x are y and all y are z. Put symbolically, this is x equals xy and y equals yz. Substituting y equals yz in x equals xy produces x equals xy equals x outside of yz equals xy out of z equals xz, or x equals xz, which is the representation of all x are z. Boole achieved even more powerful results when he introduced the symbol 1 for the universal class, the symbol 0 for the empty class, and the operator dash for complementation. The class P minus Q is the set of elements in P, not in Q. By doing this, that's not negation, it's complementation, okay. By doing this, he was able to prove that for all x, x1 minus x equals 0, the principle of non-contradiction. Nothing has a property and the negation of that property. And here it is, x equals x squared, x minus x squared equals 0, x1 minus x squared equals 0, x out of 1 minus x equals 0. Aristotle had considered the principles of non-contradiction and idempotency to be of equal stature, both necessary postulates for logical reasoning. With his Algebra of Logic, George Boole had proven that the principle of non-contradiction could be deduced from the more intuitive principle of idempotency, that the class of objects with the property x and the property x, as many times as you like, in fact, is identical to the class of objects with the property x just once. Half a century after it was written, Bertrand Russell described the laws of thought as the work in which pure mathematics was discovered. Nice one. If Cork was the scene of Boole's greatest mathematical accomplishment, it was also the site of the happiest time in his life. When he arrived at Cork, Boole soon became a close friend of John Ryle, professor of Greek and a vice president of the college. By 1850, Boole met Ryle's 18-year-old niece, Mary Everest. Mary Everest came from a family in country gentry in Gloucestershire. Her father, Thomas, was a reverend in the Anglican Church. His older brother, Sir John Everest, had been Surveyor General of India and was the first man to survey the world's tallest mountain, which he named after himself, Mount Everest. There you go. Unlike Boole, who had only known the harshness of the north of England as a child, Mary Everest had seen something of the world. Her father suffered from consumption and for several years took a leave in the healthier climate of France, where he received homeopathic treatment. Homeopathy, literally like the ailment, stress treating an ailment by administration of small doses of drugs that, if given to a healthy patient, would induce symptoms of the very ailment being treated. Reverend Everest also believed in long walks and ice-cold baths before breakfast as invigorating morning constitutionals. The treatments worked well enough to allow the Everest family to return home to his parsonage. In his diary, Bull confessed to being a hopeless romantic who had fallen in and out of love quite often. He yet appeared to have little romantic interest in Mary Everest when they first met. He contented himself with teaching her mathematics during the summers between 1850 and 1852. Between 1852 and 1855, George and Mary contented themselves with a correspondence on mathematical topics, never once meeting. That came to an end in June 1855 when Thomas Everest died suddenly, leaving Mary destitute. Ever the romantic, George Bull immediately proposed marriage. Mary accepted, and they married on September 11 of that year. For the first 2 years after their marriage, they lived in a house called College View, which was about a 10-minute walk to the college. It was convenient, but soon became too crowded for the Bulls, whose first daughter, Mary Ellen, born in 1856, would soon be followed by another daughter named Margaret, born to them in 1858. Shortly before Margaret's birth, they moved to a rented house in the village of Blackrock, 4 miles from the college but only half a mile from the railway station. The Bulls loved this house. It had a wonderful view of Cork's magnificent harbour. But this house soon became too small for their ever-expanding family, now blessed with 2 more daughters, Alicia, born in 1860, and Lucy, born in 1862. In anticipation of yet another child, once again a daughter named Ethel, born in 1864, the Bulls moved to a house named Litchfield Cottage in the village of Ballintemple, a mile closer to the college but much further from the railway station. Mary Bull saw this as an opportunity for George to take long walks of the sort that her father had encouraged to help with the rheumatic affliction of which he often complained. But the long walks did not cure Bull. One of them killed him. On November 24, 1864, Bull made the long walk from Ballintemple to the college in a torrential rain. After lecturing in his soaked clothes, he made the long walk back to Ballintemple. When he got home, he collapsed into bed and became feverishly ill. Still convinced of the correctness of homeopathy, Mary Bull proceeded to pour buckets and buckets of cold water over her husband as a means of curing him. But, of course, the bronchial pneumonia Bull developed was not idempotent. The cold water therapy only made him worse. Mary Bull finally agreed to call a medical doctor on December 5, but it was already too late. By then, Bull was in a deep, feverish coma. 3 days later, he died. Bull achieved many honours in his life. Trinity College, Dublin, and Oxford universities awarded him honorary doctorates. In 1857, he was made a Fellow of the Royal Society. But perhaps posterity had bestowed the greatest honour on Bull. Many computer languages have objects that take the value true or false. They are called booleans. Wonderful. So that's all about George Bull, and this is his An Investigation of the Laws of Thought, Chapter 1. Should I have a quick flip through this? That's pretty long. We're going to read all this. Let's read the first chapter, shall we? Wow. Chapter 4. What did that say? General rule for the symbolical expression of primary propositions. Chapter 5. Of the fundamental principles of symbolical reasoning and of the expansion or development of expressions involving logical symbols. Chapter 7, on elimination. 8 on the reduction of systems of propositions. Wow, this is a real monster, this thing. Chapter 9 on certain methods of abbreviation. Chapter 10 of the conditions of a perfect method. Chapter 11 of secondary propositions and of the principles of their symbolical expression. Chapter 12 of the methods and processes to be adopted in the treatment of secondary propositions. Wow. So that's from 842 to 979. It's a monster. Anyway, let's have a read of the first chapter. It's a pretty big chapter anyway. So let's see how he introduces his investigation of the laws of thought. This is chapter 1, Nature and Design of This Work. Alright, I'm going to take a quick break, get myself a coffee, and we'll continue. So this is chapter 1 of An Investigation of the Laws of Thought by George Bull, The Nature and Design of This Work. It's 16 pages, the introductory chapter, so I thought we'd have a quick read of that, then we'll flip through the rest of the work and hopefully get this book finished soon. 1. The design of the following treatise is to investigate the fundamental laws of those operations of the mind by which reasoning is performed, to give expression to them in the symbolical language of a calculus, and upon this foundation to establish the science of logic and construct its method, to make that method itself the basis of a general method for the application of the mathematical doctrine of probabilities, and, finally, to collect from the various elements of truth brought to view in the course of these inquiries some probable intimations concerning the nature and constitution of the human mind. 2. That this design is not altogether a novel one. That this design is not altogether a novel one, it is almost needless to remark, and it is well known that that its two main practical divisions of logic and probabilities are very considerable. Sorry, let me try this whole sentence again. That this design is not altogether a novel one, it is almost needless to remark, and it is well known that to its two main practical divisions of logic and probabilities a very considerable share of the attention of philosophers has been directed. In its ancient and scholastic form, indeed, the subject of logic stands almost exclusively associated with the great name of Aristotle. As it was presented to ancient Greece in the partly technical, partly metaphysical disquisitions of the Organon, such, with scarcely any essential change, it has continued to the present day. The stream of original inquiry has rather been directed towards questions of general philosophy, which, though they have arisen among the disputes of the logicians, have outgrown their origin, and given to successive ages of speculation their peculiar bent and character. The eras of Porphyry and Proclus, of Anselm and Abelard, of Ramus and of Descartes, together with the final protests of Bacon and Locke, rise up before the mind as examples of the remoter influences of the study upon the course of human thought, partly in suggesting topics fertile of discussion, partly in provoking remonstrance against its own undue pretensions. The history of the theory of probabilities, on the other hand, has presented far more of that character of steady growth which belongs to science. In its origins, the early genius of Pascal; in its maturer stages of development, the most recondite of all the mathematical speculations of Laplace, were directed to its improvement. To omit here the mention of other names scarcely less distinguished than these. As the study of logic has been remarkable for the kindred questions of metaphysics to which it has given occasion, so that of probabilities also has been remarkable for the impulse which it has bestowed upon the higher departments of mathematical science. Each of these subjects has, moreover, been justly regarded as having relation to a speculative as well as to a practical end. To enable us to deduce correct inferences from given premises is not the only object of logic, nor is it the sole claim of the theory of probabilities that it teaches us how to establish the business of life assurance on a secure basis, and how to condense whatever is valuable in the records of innumerable observations in astronomy, in physics, or in that field of social inquiry which is fast assuming a character of great importance. Both these studies have also an interest of another kind, derived from the light by which they shed upon the intellectual powers. They instruct us concerning the mode in which language and number serve as instrumental aids to the processes of reasoning. They reveal to us in some degree the connection between different powers of our common intellect. They set before us what, in the two domains of demonstrative and of probable knowledge, are the essential standards of truth and correctness. Standards not derived from without, but deeply founded in the constitution of the human faculties. These ends of speculation yield neither in interest nor in dignity, nor yet, it may be added, in importance, to the practical objects with the pursuit of which they have been historically associated. To unfold the secret laws and relations of those high faculties of thought by which all beyond the merely perceptive knowledge of the world and of ourselves is attained or matured, is an object which does not stand in need of commendation to a rational mind. 3. But although certain parts of the design of this work have been entertained by others, its general conception, its method, and to a considerable extent its results, are believed to be original. For this reason, I shall offer in the present chapter some preparatory remarks and explanations in order that the real aim of this treatise may be understood and the treatment of its subject facilitated. It is designed, in the first place, to investigate the fundamental laws of those operations of the mind by which reasoning is performed. It is unnecessary to enter here into any argument to prove that the operations of the mind are in a certain real sense subject to laws, and that a science of the mind is therefore possible. If these are questions which admit of doubt, that doubt is not to be met by an endeavour to settle the point of dispute a priori, but by directing the attention of the objector to the evidence of actual laws by referring him to an actual science. And thus the solution of that doubt would belong not to the introduction to this treatise, but to the treatise itself. Let the assumption be granted that a science of the intellectual powers is possible, and let us for a moment consider how the knowledge of it is to be obtained. 4. Like any other sciences, that of the intellectual operations must primarily rest upon observation, the subject of such observation being the very operations and processes of which we desire to determine the laws. But while the necessity of a foundation in experience is thus a condition common to all sciences, there are some special differences between the modes in which this principle becomes available for the determination of general truths when the subject of inquiry is the mind, and when the subject is external nature. To these it is necessary to direct attention. The general laws of nature are not, for the most part, immediate objects of perception. They are either inductive inferences from a large body of facts, the common truth in which they express, or in their origin at least, physical hypotheses of a causal nature, serving to explain phenomena with undeviating precision and to enable us to predict new combinations of them. They are, in all cases, and in the strictest sense of the term, probable conclusions, approaching, indeed, ever and ever nearer to certainty as they receive more and more of the confirmation of experience. But of the character of probability, in the strict and proper sense of that term, they are never wholly divested. On the other hand, the knowledge of the laws of the mind does not require as its basis any extensive collection of observations. The general truth is seen in the particular instance, and it is not confirmed by the repetition of instances. We may illustrate this proposition by an obvious example. It may be a question whether that formula of reasoning, which is called the dictum of Aristotle, de omni et nullo, expresses a primary law of human reasoning or not, but it is no question that it expresses a general truth in logic. Now, that truth is made manifest in all its generality by reflection upon a single instance of its application. And this is both an evidence that the particular principle or formula in question is founded upon some general law or laws of the mind, and an illustration of the doctrine that the perception of such general truths is not derived from an induction from many instances, but is involved in the clear apprehension of a single instance. In connection with this truth is seen the not less important one, that our knowledge of the laws upon which the science of the intellectual powers rests, whatever may be its extent or its deficiency, is not probable knowledge. For we not only see in the particular example of the general truth, but we see it also as a certain truth. A truth, our confidence in which will not continue to increase with increasing experience of its practical verifications. 5. But if the general truths of logic are of such a nature that when presented to the mind they are at once command assent, wherein consists the difficulty of constructing the science of logic? Not, it might be answered, in collecting the materials of knowledge, but in discriminating their nature and determining their mutual place and relation. All sciences consist of general truths, but of those truths some only are primary and fundamental, others are secondary and derived. The laws of elliptic motion, discovered by Kepler, are general truths in astronomy, but they are not its fundamental truths. And it is also in the purely mathematical sciences. An almost boundless diversity of theorems which are known, and an infinite possibility of others, as yet unknown, rest together upon the foundation of a few simple axioms, and yet these are all general truths. It may be added that they are truths which to an intelligence sufficiently refined would shine forth in their own unborrowed light, without the need of those connecting links of thought, those steps of wearisome and often painful deduction, by which the knowledge of them is actually acquired. Let us define as fundamental those laws and principles from which all other general truths of science may be deduced, and into which they may all be again resolved. Shall we then err in regarding that as the true science of logic which, laying down certain elementary laws, confirmed by the very testimony of the mind, permits us thence to deduce, by uniform processes, the entire chain of its secondary consequences, and furnishes, for its practical applications, methods of perfect generality? Let it be considered whether in any science, viewed together as a system of truth or as the foundation of a practical art, there can properly be any other test of the completeness and the fundamental character of its laws than the completeness of its system of derived truths and the generality of the methods which it serves to establish. Other questions may indeed present themselves. Convenience, prescription, individual preference may urge their claims and deserve attention. But as respects the question of what constitutes science in its abstract integrity, I apprehend that no other considerations than the above are properly of any value. 6. It is designed, in the next place, to give expression in this treatise to the fundamental law of reasoning in the symbolical language of calculus. Upon this head it will suffice to say that those laws are such as to suggest this mode of expression, and to give it a peculiar and exclusive fitness for the ends in view. There is not only a close analogy between the operations of the mind in general reasoning and its operations in the particular science of algebra, but there is to a considerable extent an exact agreement in the laws by which the two classes of operations are conducted. Of course, the laws must in both cases be determined independently. Any formal agreement between them can only be established a posteriori by actual comparison. To borrow the notation of the science of number and then assume that in its new application the laws by which its use is governed will remain unchanged would be mere hypothesis. There exist, indeed, certain general principles founded in the very nature of language, by which the use of symbols, which are but the elements of scientific language, is determined. To a certain extent these elements are arbitrary. Their interpretation is purely conventional, but we are permitted to employ them in whatever sense we please. But this permission is limited by two indispensable conditions. First, that from the sense one conventionally established, we never, in the same process of reasoning, depart. Secondly, that the laws by which the process is conducted be founded exclusively upon the above fixed sense or meaning of the symbols employed. In accordance with these principles, any agreement which may be established between the laws of the symbols of logic and those of algebra can but issue in an agreement of process. The two provinces of interpretation remain apart and independent, each subject to its own laws and conditions. Now the actual investigations of the following pages exhibit logic, in its practical aspect, as a system of processes carried out by the aid of symbols, having a definite interpretation and subject to laws founded upon that interpretation alone. But at the same time, they exhibit those laws as identical in form with the laws of the general symbols of algebra, with this single addition, viz., that the symbols of logic are further subject to a special law, as seen in chapter 2, to which the symbols of quantity, as such, are not subject. Upon the nature and evidence of this law, it is not purposed here to dwell. These questions will be fully discussed in a future page. But as constituting the essential ground of difference between those forms of inference with which logic is conversant and those which present themselves in that particular science of number, the law in question is deserving of more than a passing notice. It may be said that it lies at the very foundation of general reasoning, that it governs those intellectual acts of conception or of imagination which are preliminary to the processes of logical deduction, and that it gives to the processes themselves much of their actual form and expression. It may hence be affirmed that this law constitutes the germ or seminal principle of which every approximation to a general method in logic is the more or less perfect development. 7. The principle has already been laid down in 5, that the sufficiency and truly fundamental character of any assumed system of laws in the science of logic must partly be seen in the perfection of the methods to which they conduct us. It remains, then, to consider what the requirements of a general method in logic are, and how far they are fulfilled in the system of the present work. Logic is conversant with two kinds of relations among things and relations among facts. But as facts are expressed by propositions, the latter species of relation may, at least for the purposes of logic, be resolved into a relation among propositions. The assertion that the fact or event A is an invariable consequence of the fact or event B may, to this extent at least, be regarded as equivalent to the assertion that the truth of the proposition affirming the occurrence of the event B always implies the truth of the proposition affirming the occurrence of the event A. Instead, then, of saying that logic is conversant with relations among things and relation among facts, we are permitted to say that it is concerned with the relation among things and relations among propositions. Of the former kind of relations, we have an example in the proposition, all men are mortal. Of the latter kind in the proposition, if the sun is totally eclipsed, the stars will become visible. The one expresses a relation between men and mortal beings, the other between elementary proposition. The sun is totally eclipsed, the stars will become visible. Among such relations, I suppose to be included those which affirm or deny existence with respect to things, and those which affirm or deny truth with respect to propositions. Now let those things or those propositions among which relation is expressed be termed the elements of the propositions by which such relation is expressed. Proceeding from this definition, we may then say the premises of any logical argument given relations among certain elements, that the conclusion must express an implied relation among those elements, or among a part of them, that is, a relation implied by or inferentially involved in the premises. 8. Now, this being premised, the requirements of a general method in logic seem to be the following. First, as the conclusion must express a relation among the whole or among a part of the elements involved in the premises, it is requisite that we should possess the means of eliminating those elements which we desire not to appear in the conclusion, and of determining the whole amount of relation implied by the premises among the elements which we wish to retain. Those elements which do not present themselves in the conclusion are, in the language of common logic, called middle terms, and the species of elimination exemplified in treatises on logic consist in deducing from two propositions containing a common element or middle term a conclusion connecting the two remaining terms. But the problem of elimination, as contemplated in this work, possesses a much wider scope. It proposes not merely the elimination of the middle term from two propositions, but the elimination generally of middle terms from propositions, without regard to the number of either of them, or to the nature of their connection. To this object, neither of the processes of logic nor those of algebra, in their actual state, present any strict parallel. In the latter science, the problem of elimination is known to be limited in the following manner. From two equations, we can eliminate one symbol of quantity. From three equations, two symbols, and, generally, from n equations to n-1 symbols. But though this condition, necessary in algebra, seems to prevail in the existing logic also, it has no essential place in logic as a science. There, no relation whatever can be proved to prevail between the number of terms to be eliminated and the number of propositions from which the elimination is to be effected. From the equation representing a single proposition, any number of symbols representing terms or elements in logic may be eliminated. And from any number of equations representing propositions, one or any other number of symbols of this kind may be eliminated in a similar manner. For such elimination, there exists one general process applicable to all cases. This is one of the many remarkable consequences of that distinguishing law of the symbols of logic to which attention has already been directed. Secondly, it should be within the province of a general method in logic to express the final relation among the elements of the conclusion by any admissible kind of proposition, or in any selected order of terms. Among varieties of kind, we may reckon those which logicians have designated by the terms categorical, hypothetical, disjunctive, and so on. To a choice or selection in the order of the terms, we may refer whatsoever is dependent upon the appearance of particular elements in the subject or in the predicate, in the antecedent or in the consequent of that proposition which forms the conclusion. But waiving the language of the schools, let us consider what really distinct species of problems may present themselves to our notice. We have seen that the elements of the final or inferred relation may either be things or propositions. Suppose the former case, then it might be required to deduce from the premises a definition or description of some one thing, or class of things, constituting an element of the conclusion in terms of the other things involved in it. Or we might form the conception of some thing or class of things involving more than one of the elements of the conclusion, and require its expression in terms of the other elements. Again, suppose the elements retained in the conclusion to be propositions. We might desire to ascertain such points as the following, viz., whether, in virtue of the premises, any of those propositions, taken singly, are true or false, whether particular combinations of them are true or false, whether, assuming a particular proposition to be true, any consequences will follow, and if so, what consequences with respect to the other propositions, whether, any particular condition being assumed with reference to certain of the propositions, any consequences, and what consequences will follow with respect to the others, and so on. I say that these are general questions which should fall within the scope or province of the general method in logic to solve. Perhaps we might include them under this one statement of the final problem of practical logic. Given a set of premises expressing relations among certain elements, whether things or propositions, required explicitly the whole relation consequent among any of those elements under the proposed conditions and in any proposed form. That this problem, under all its aspects, is resolvable will hereafter appear. But it is not for the sake of noticing this fact that the above inquiry into the nature and the functions of a general method in logic has been introduced. It is necessary that the reader should apprehend what are the specific ends of the investigation upon which we are entering, as well as the principles which are to guide us to the attainment of them. 9. Possibly it may here be said that the logic of Aristotle, in its rules of syllogism and conversion, sets forth the elementary process of which all reasoning consists, and that beyond these there is neither scope nor occasion for a general method. I have no desire to point out the defects of the common logic, nor do I wish to refer to it any further than is necessary in order to place in its true light the nature of the present treatise. With this end alone in view, I would remark, first, that syllogism, conversion, and so on, are not the ultimate processes of logic. It will be shown in this treatise that they are founded upon and are resolvable into ulterior and more simple processes which constitute the real elements of method in logic. Nor is it true, in fact, that all inference is reducible to the particular forms of syllogism and conversion. Vida, chapter 15. Okay. Secondly, if all inference were reducible to these two processes, and it has been maintained that it is reducible to syllogism alone, there would exist the same necessity for a general method, for it would still be requisite to determine in what order the processes should succeed each other, as well as their particular nature, in order that the desired relation should be obtained. By the desired relation, I mean that full relation which, in virtue of the premises, connects any element selected out of the premises at will, and which, moreover, expresses that relation in any desired form and order. If we may judge from the mathematical sciences, which are the most perfect examples of method known, this directive function of method constitutes its chief office and distinction. The fundamental processes of arithmetic, for instance, are in themselves but the elements of a possible science. To assign their nature is the first business of its method, but to arrange their succession is its subsequent and higher function. In the more complex examples of logical deduction, and especially in those which form a basis for the solution of difficult questions in the theory of probabilities, the aid of a directive method, such as a calculus alone can supply, is indispensable. 10. Whence it is that the ultimate laws of logic are mathematical in their form, why they are, except in a single point, identical with general laws of number, and why in that particular point they differ, are questions upon which it might not be very remote from presumption to endeavour to pronounce a positive judgment. Probably they lie beyond the reach of our limited faculties. It may, perhaps, be permitted to the mind to attain a knowledge of the laws to which it is itself subject, without its being also given to it to understand their ground and origin, or even, except in a very limited degree, to comprehend their fitness for their end, as compared with other inconceivable systems of law. Such knowledge is, indeed, unnecessary for the ends of science, which properly concerns itself with what is, and seeks not for grounds of preference or reasons of appointment. These considerations furnish a sufficient answer to all protests against the exhibition of logic in the form of a calculus. It is not because we choose to assign to it such a mode of manifestation, but because the ultimate laws of thought render that mode possible, and prescribe its character, and forbid, as it would seem, the perfect manifestation of the science in any other form, that such a mode demands adoption. It is to be remembered that it is the business of science not to create laws, but to discover them. We do not originate the constitution of our own minds, greatly as it may be in our power to modify their character. And as the laws of the human intellect do not depend upon our will, so the forms of the science, of which they constitute the basis, are in all essential regards independent of individual choice. 11. Beside the general statement of the principles of the above method, this treatise will exhibit its application to the analysis of a considerable variety of propositions, and of trains of propositions constituting the premises of demonstrative arguments. These examples have been selected from various writers. They differ greatly in complexity, and they embrace a wide range of subjects. Though in this particular respect it may appear to some that too great a latitude of choice has been exercised, I do not deem it necessary to offer any apology upon this account. That logic, as a science, is susceptible of very wide applications is admitted, but it is equally certain that its ultimate forms and processes are mathematical. Any objection a priori, which may therefore be supposed to lie against the adoption of such forms and processes in the discussion of a problem of morals or of a general philosophy, must be founded upon misapprehension or false analogy. It is not of the essence of mathematics to be conversant with the ideas of number and quantity. Whether as a general habit of mind it would be desirable to apply symbolical processes to moral argument is another question. Possibly, as I've elsewhere observed, the perfection of the method of logic may be chiefly valuable as an evidence of the speculative truth of its principles. To supersede the employment of common reasoning, or to subject it to the rigour of technical forms, would be the last desire of one who knows the value of that intellectual toil and warfare which imparts to the mind an athletic vigour, and teaches it to contend with difficulties, and to rely upon itself in emergencies. Nevertheless, cases may arise in which the value of a scientific procedure, even in those things which fall confessedly under the ordinary dominion of the reason, may be felt and acknowledged. Some examples of this kind will be found in the present work. 12. The general doctrine and method of logic above explained. Let me start again. 12. The general doctrine and method of logic above explain. I'm going to take a quick break. I'm back. On we go. 12. The general doctrine and method of logic above explained form also the basis of a theory and corresponding method of probabilities. Accordingly, the development of such a theory and method upon the above principles will constitute a distinct object of the present treatise. Of the nature of this application, it may be desirable to give here some account, more especially as regards the character of the solutions to which it leads. In connection with this object, some further detail will be requisite concerning the forms in which the results of the logical analysis are presented. The ground of this necessity of a prior method in logic as the basis of a theory of probabilities may be stated in a few words. Before we can determine the model in which the expected frequency of occurrence of a particular event is dependent upon the known frequency of occurrence of any other events, we may be acquainted with the mutual dependence of the events themselves. Speaking technically, we must be able to express the event whose probability is sought as a function of the events whose probabilities are given. Now, this explicit determination belongs in all instances to the department of logic. Probability, however, in its mathematical acceptation, admits of numerical measurement. Hence, the subject of probabilities belongs equally to the science of number and to that of logic. In recognizing the coordinate existence of both these elements, the present treatise differs from all previous ones. And as this difference not only affects the question of the possibility of the solution of problems in a large number of instances, but also introduces new and important elements into the solutions obtained, I deem it necessary to state here, at some length, the peculiar consequences of the theory developed in the following pages. 13. The measure of the probability of an event is usually defined as a fraction of which the numerator represents the number of cases favorable to the event, and the denominator the whole number of cases favorable and unfavorable, all cases being supposed equally likely to happen. That definition is adopted in the present work. At the same time, it is shown that there is another aspect of the subject, shortly to be referred to, which might equally be regarded as fundamental, and which would actually lead to the same system of methods and conclusions. It may be added that so far as the received conclusions of the theory of probabilities extend, and so far as they are consequences of its fundamental definitions, they do not differ from the results, supposed to be equally correct in inference, of the method of this work. Again, although questions in the theory of probabilities present themselves under various aspects and may be variously modified by algebraical and other conditions, there seems to be one general type to which all such questions, or so much of each of them as truly belongs to the theory of probabilities, may be referred. Considered with reference to the data and the Q-ostum. I don't know what that word is. It's Q-U-O-E-S-I-T-U-M. Considered with reference to the data, that type may be described as follows. First, the data are the probabilities of one or more given events, each probability being either that of the absolute fulfillment of the event to which it relates, or the probability of its fulfillment under given supposed conditions. 2. The quositum, or object sort. So it's the sort object, okay? The object sort is the probability of the fulfillment, absolutely or conditionally, of some other event differing in expression from those in the data, but more or less involving the same elements. As concerned the data, they are either causally given, as when the probability of a particular throw of a die is deduced from a knowledge of the constitution of the piece, or they are derived from observation of repeated instances of the success or failure of events. In the latter case, the probability of an event may be defined as the limit towards which the ratio of the favorable to the whole number of observed cases approaches, the uniformity of nature being presupposed, as the observations are indefinitely continued. Lastly, as concerns the nature or relation of the events in question, an important distinction remains. Those events are either simple or compound. By a compound event is meant one of which the expression in language, or the conception in thought, depends upon the expression or the conception of other events which, in relation to it, may be regarded as simple events. To say it rains, or to say it thunders, is to express the occurrence of simple event, but to say it rains and thunders, or to say it neither rains or thunders, is to express that of a compound event. For the expression of that event depends upon the elementary expression, it rains, it thunders. The criterion of simple events is not, therefore, any supposed simplicity in their nature. It is found solely on the mode of their expression in language or conception in thought. 14. Now one general problem, which the existing theory of probabilities enables us to solve, is the following, viz. Given the probabilities of any simple events, Given the probabilities of any simple events, required the probability of a given compound event, that is, of an event compounded in a given manner out of the given simple events. The problem can also be solved when the compound event, whose probability is required, is subjected to given conditions, that is, to conditions dependent also in a given manner on the given simple events. Besides this general problem, there exist also particular problems of which the principle of solution is known, Various questions relating to causes and effects can be solved by known methods under the particular hypothesis that the causes are mutually exclusive, but apparently not otherwise. Beyond this, it is not clear that any advance has been made toward the solution. Excuse me. Sorry about that, I had a phone call. On we go. Beyond this, it is not clear that any advance has been made toward the solution of what may be regarded as the general problem of the science, viz., given the probability of any events, simple or compound, conditioned or unconditioned, required the probability of any other event equally arbitrary in expression and conception. In the statement of this question, it is not even postulated that the events whose probabilities are given and the one whose probability is sought should involve some common elements, because it is the office of a method to determine whether the data of a problem are sufficient for the end in view, and to indicate, when they are not so, wherein the deficiency consists. This problem, in the most unrestricted form of its statement, is solvable by the method of the present treatise. Or, to speak more precisely, its theoretical solution is completely given, and its practical solution is brought to depend only upon processes purely mathematical, such as the resolution and analysis of equations. The order and character of the general solution may be thus described. 15. In the first place, it is always possible, by the preliminary method of the calculus of logic, to express the event whose probability is sought as a logical function of the events whose probabilities are given. The result is of the following character. Suppose that X represents the event whose probability is sought, A, B, C, and so on, the events whose probabilities are given, those events being either simple or compound. Then the whole relation of the event X to the events A, B, C, and so on, is deduced in the form of what mathematicians term a development, consisting, in the most general case, of 4 distinct classes of terms. By the first class are expressed those combinations of the events A, B, C, which both necessarily accompany and necessarily indicate the occurrence of the event X. By the second class, those combinations which necessarily accompany but do not necessarily imply the occurrence of the event X. By the third class, those combinations whose occurrence in connection with the event X is impossible, but not otherwise impossible. By the fourth class, those combinations whose occurrence is impossible under any circumstances. I shall not dwell upon this statement of the result of the logical analysis of the problem, further than to remark that the elements which it presents are precisely those by which the expectation of the event X, as dependent upon our knowledge of the events A, B, C, is, or alone can be, affected. General reasoning would verify this conclusion, but general reasoning would not usually avail to disentangle the complicated web of events and circumstances from which the solution above described may be evolved. The attainment of this object constitutes the first step towards the complete solution of the question proposed. It is to be noted that thus far the process of solution is logical, that is, conducted by symbols of logical significance and resulting in an equation interpretable into a proposition. Let this result be termed the final logical equation. The second step of the process deserves attentive remark. From the final logical equation to which the previous step has conducted us, are deduced by inspection a series of algebraic equations implicitly involving the complete solution of the problem proposed. Of the mode in which this transition is effected, let it suffice to say that there exists a definite relation between the laws by which the probabilities of events are expressed as algebraic functions of the probabilities of other events upon which they depend, and the laws by which the logical connection of the event is itself expressed. This relation, like other coincidences of formal law which have been referred to, is not founded upon hypothesis, but is made known to us by observation and reflection. If, however, its reality were assumed a priori as the basis of the very definition of probability, such deduction would thence lead us to the received numerical definition as a necessary consequence. The theory of probability stands, as it has already been remarked, in equally close relation to logic and to arithmetic, and it is indifferent, so far as results are concerned, whether we regard it as springing out of the latter of these sciences or as founded in the mutual relations which connect the two together. 16. There are some circumstances, interesting perhaps to the mathematician, attending the general solutions deduced by the above method, which it may be desirable to notice. First, as the method is independent of the number and the nature of the data, it continues to be applicable when the latter are insufficient to render determinate the value sought. When such is the case, the final expression of the solution will contain terms with arbitrary constant coefficients. To such terms there will correspond terms in the final logical equation, the interpretation of which will inform us what new data are requisite in order to determine the values of those constants, and thus render the numerical solution complete. If such data are not to be obtained, we can still, by giving to the constants their limiting values 0 and 1, determine the limits within which the probability sought must lie, independently of all future experience. When the event whose probability is sought is quite independent of those whose probabilities are given, the limits thus obtained for its value will be 0 and 1, and it is evident that they ought to be, and the interpretation of the constants will only lead to a restatement of the original problem. Secondly, the expression of the final solution will in all cases involve a particular element of quantity determinable by the solution of an algebraic equation. Now, when that equation is of an elevated degree, a difficulty may seem to arise as to the selection of the proper root. There are, indeed, cases in which both the elements given and the elements sought are so obviously restricted by necessary conditions that no choice remains. But in complex instances, the discovery of such conditions, by unassisted force of reasoning, would be hopeless. A distinct method is requisite for this end, a method which might not appropriately be termed the calculus of statistical conditions. Into the nature of this method I shall not here further enter than to say that, like the previous method, it is based upon the employment of the final logical equation, and that it definitely assigns, first, the conditions which must be fulfilled among the numerical elements of the data in order that the problem may be real, that is, derived from possible experience. Secondly, the numerical limits within which the probability sought must have been confined if, instead of being determined by theory, it had been deduced directly by observation from the same system of phenomena from which the data were derived. It is clear that these limits will be actual limits of the probability sought. Now, on supporting the data subject to the conditions above assigned to them, it appears in every instance which I have examined that there exists one root, and only one root, of the final algebraic equation which is subject to the required limitations. Every source of ambiguity is thus removed. It would even seem that new truths relating to the theory of algebraic equations are thus incidentally brought to light. It is remarkable that the special element of quantity, to which the previous discussion relates, depends only upon the data, and not at all upon the object sought of the problem proposed. Hence the solution of each particular problem unties the knot of difficulty for a system of problems, viz., for that system of problems which is marked by the possession of common data, independently of the nature of their object sought. This circumstance is important whenever from a particular system of data it is required to deduce a series of connected conclusions, and it further gives to the solutions of particular problems that character of relationship derived from their dependence upon the central and fundamental unity, which not unfrequently marks the application of general methods. 17. But though the above considerations, with others of a like nature, justify the assertion that the method of this treatise For the solution of questions in the theory of probabilities is a general method, it does not thence follow that we are relieved in all cases from the necessity of recourse to hypothetical grounds. It has been observed that a solution may consist entirely of terms affected by arbitrary constant coefficients, may in fact be wholly indefinite. The application of the method of this work to some of the most important questions within its range would, were the data of experience alone employed, present results of this character. To obtain a definite solution, it is necessary, in such cases, to have recourse to hypotheses possessing more or less of independent probability, but incapable of exact verification. Generally speaking, such hypotheses will differ from the immediate results of experience in partaking of a logical rather than of a numerical character, in prescribing the conditions under which phenomena occur rather than assigning the relative frequency of their occurrence. This circumstance is, however, unimportant. Whatever their nature may be, the hypotheses assumed must therefore be regarded as belonging to the actual data, although tending, as is obvious, to give the solution itself somewhat of a hypothetical character. With this understanding as to the possible sources of the data actually employed, the method is perfectly general, but for the correctness of the hypothetical elements introduced, it is of course no more responsible than for the correctness of the numerical data derived from experience. In illustration of these remarks, we may observe that the theory of the reduction of astronomical observations rests in part upon hypothetical grounds. It assumes certain positions as to the nature of error, the equal probabilities of its occurrence in the form of excess or defect, and so on, without which it would be impossible to obtain any definite conclusions from a system of conflicting observations. But granting such positions as the above, the residue of the investigation falls strictly within the province of the theory of probabilities. Similar observations apply to the important problems which proposes Similar observations apply to the important problem which proposes to deduce from the records of the majorities of a deliberative assembly the mean probability of correct judgment in one of its members. If the method of this treatise be applied to the mere numerical data, the solution obtained is of that wholly indefinite kind above described. And to show in a more eminent degree the insufficiency of those data by themselves, the interpretation of the arbitrary constants which appear in the solution merely produces a restatement of the original problem. Admitting, however, the hypothesis of the independent formation of opinion in the individual mind, either absolutely, as in the speculations of Laplace and Poisson, or under limitations imposed by the actual data, as will be seen in this treatise, chapter 21, the problem assumes a far more definite character. It will be manifest that the ulterior value of the theory of probabilities must depend very much upon the correct formation of such mediate hypotheses, which the purely experimental data are insufficient for definite solution, and where that further experience indicated by the interpretation of the final logical equation is unattainable. Upon the other hand, an undue readiness to form hypotheses in subjects which from their very nature are placed beyond human ken must react upon the credit of the theory of probabilities and tend to throw doubt in the general mind over its most legitimate conclusions. 18. It would perhaps be premature to speculate here upon the question whether the methods of abstract science are likely at any future day to render service in the investigation of social problems at all commensurate with those which they have rendered in various departments of physical inquiry. An attempt to resolve this question upon a pure a priori grounds of reasoning would be very likely to mislead us. For example, the consideration of human free agency would seem at first sight to preclude the idea that the movements of the social system should ever manifest that character of orderly evolution which we are prepared to expect under the reign of a physical necessity. Yet already do the researchers of the statist reveal to us facts at variance with such an anticipation. Thus the records of crime and pauperism present a degree of regularity unknown in regions in which the disturbing influence of human wants and passions is unfelt. On the other hand, the distemperature of seasons, the eruption of volcanoes, the spread of blight in the vegetable, or of epidemic maladies in the animal kingdom, things apparently or chiefly the product of natural causes, refuse to be submitted to regular and apprehensible laws. Fickle as the wind is a proverbial expression. Reflection upon these points teaches us in some degree to correct our earlier judgments. We learn that we are not to expect, under the dominion of necessity, an order perceptible to human observation, unless the play of its producing causes is sufficiently simple, nor, on the other hand, to deem that free agency in the individual is inconsistent with regularity in the motions of the system of which he forms a component unit. Human freedom stands out as an apparent fact of our consciousness, while it is also, I conceive, a highly probable deduction of analogy. See chapter 22. From the nature of that portion of the mind whose scientific constitution we are able to investigate. But whether accepted as a fact reposing on consciousness or as a conclusion sanctioned by the reason, it must be so interpreted as not to conflict with an established result of observation, viz., that phenomena, in the production of which large masses of men are concerned, do actually exhibit a very remarkable degree of regularity, enabling us to collect in each succeeding age the elements upon which the estimate of its state and progress, so far as manifested in outward results, must depend. There is thus no sound objection a priori against the possibility of that species of data which is requisite for the experimental foundation of a science of social statistics. Again, whatever other object this treatise may accomplish, it is presumed that it will leave no doubt as to the existence of a system of abstract principles and of methods founded upon those principles, by which any collective body of social data may be made to yield, in an explicit form, whatever information they implicitly involve. There may, where the data are exceedingly complex, be very great difficulty in obtaining this information, difficulty due not to any imperfection of the theory, but to the laborious character of the analytical processes to which it points. It is quite conceivable that in many instances that difficulty may be such as only united effort could overcome. But that we possess theoretically in all cases, and practically, so far as the records the seeds of general truths, but that we possess theoretically in all cases, and practically, so far as the requisite labour of calculation may be supplied, the means of evolving from statistical records the seeds of general truths which lie buried amid the mass of figures, is a position which may, I conceive, with perfect safety be affirmed. 19. But beyond these general positions I do not venture to speak in terms of assurance. Whether the results which might be expected from the application of scientific methods to statistical records, over and above those the discovery of which requires no such aid, would be so far compensate for the labour involved as to render it worthwhile to institute such investigations upon a proper scale of magnitude, is a point which could, perhaps, only be determined by experience. It is to be desired, and it might without great presumption be expected, that in this, as in other instances, the abstract doctrines of science should minister to more than intellectual gratification. Nor, viewing the apparent order in which the sciences have been evolved, and have successfully contributed their aid to the service of mankind, does it seem very improbable that a day may arrive in which similar aid may accrue from departments of the field of knowledge yet more intimately allied with the elements of human welfare. Let the speculation of this treatise, however, rest at present simply upon their claim to be regarded as true. 20. I design, in the last place, to endeavour to educe from the scientifical results of the previous inquiries some general intimations respecting the nature and constitution of the human mind. Into the grounds of the possibility of this species of inference it is not necessary to enter here. One or two general observations may serve to indicate the track which I shall endeavour to follow. It cannot but be admitted that our views on the science of logic must materially influence, perhaps mainly determine, our opinions upon the nature of the intellectual faculties. For example, the question whether reasoning consists merely in the application of certain first or necessary truths with which the mind has been originally imprinted, or whether the mind is itself a seat of law, whose operation is as manifest and as conclusive in the particular as in the general formula, or whether, as some not undistinguished writers seem to maintain, all reasoning is of particulars. This question, I say, is one which not merely affects the science of logic, but also concerns the formation of just views of the constitution of the intellectual faculties. Again, if it is concluded that the mind is by original constitution a seat of law, the question of the nature of its subjection to this law, whether, for instance, it is an obedience founded upon necessity, like that which sustains the revolution of the heavens, and preserves the order of nature, or whether it is subjection of some quite distinct kind, is also a matter of deep speculative interest. Further, if the mind is truly determined to be a subject of law, and if its laws also are truly assigned, the question of their probable or necessary influence upon the course of human thought in different ages is one invested with great importance, and well deserving a patient investigation, as matter both of philosophy and of history. These and other questions I propose, however imperfectly, to discuss in the concluding portion of the present work. They belong, perhaps, to the domain of probable or conjectural, rather than to that of positive knowledge. But it may happen that where there is not sufficient warrant for the certainties of science, there may be grounds of analogy adequate for the suggestion of highly probable opinions. It has seemed to me better that this discussion should be entirely reserved for the sequel of the main business of this treatise, which is the investigation of scientific truths and laws. Experience sufficiently instructs us that the proper order of advancement in all inquiries after truth is to proceed from the known to the unknown. There are parts, even of the philosophy and constitution of the human mind, which have been placed fully within the reach of our investigation. To make a due acquaintance with those portions of our nature, the basis of all endeavours to penetrate amid the shadows and uncertainties of that conjectural realm which lies beyond and above them, is the course most accordant with the limitations of our present condition. Holy cow, that guy can put some sentences together, can't he? That last one was a monster. To make a due acquaintance with those portions of our nature, the basis of all endeavours to penetrate amid the shadows and uncertainties of that conjectural realm which lies beyond and above them, is the course most accordant with the limitations of our present condition. Holy cow. Alright, so then we've got chapter 2. Of signs in general, and of the signs appropriate to the science of logic in particular, also of the laws to which that class of signs are subject. Proposition 1, Class 1. Chapter 3. Derivation of the laws of the symbols of logic from the laws of the operations of the human mind. Chapter 4. Of the division of propositions into the two classes of primary and secondary, of the characteristic properties of those classes, and of the laws of the expression of primary propositions. Chapter 5. Of the fundamental principles of symbolical reasoning and of the expansion or development of expressions involving logical symbols. Chapter 6. Of the general interpretation of logical equations and the resulting analysis of proportions, also of the condition of interpretability of logical functions. Chapter 7. On elimination. Chapter 8. On the reduction of systems of propositions. Chapter 9. On certain methods of abbreviation. Chapter 10. Of the conditions of a perfect method. Chapter 11. Of secondary propositions and of the principles of their symbolical expression. Chapter 12. Of the methods and processes to be adopted in the treatment of secondary propositions. All right. I'll just read the last couple of paragraphs here. We thus reach by a different route the same conclusion. Though as an exhibition of the power of the method, the above examples are of slight value, they serve as well as more complicated instances would do to illustrate its nature and character. 7. It may be remarked, as a final instance of analogy between the system of primary and that of secondary propositions, that in the latter system also the fundamental equation, x1 minus x equals 0, admits of interpretation. It expresses an axiom. A proposition cannot at the same time be true and false. Okay. Let this be compared with the corresponding interpretation solved under the form x equals 0 over 1 minus x equals 0 divided by 0 x by development. Well, that's a divided by 0 error there. It furnishes the respective axioms. A thing is what it is. Okay. If a proposition is true, it is true. Forms of what has been termed the principle of identity. Upon the nature and value of these axioms, the most opposite opinions have been entertained. Some have regarded them as the very pith and marrow of philosophy. Locke devoted to them a chapter headed On Trifling Propositions. In both these views, there seems to have been a mixture of truth and error. Regarded as supplanting experience, or as furnishing materials for the vain and wordy janglings of the schools, such propositions are worse than trifling. Viewed, on the other hand, as intimately allied with the very laws and conditions of thought, they rise into at least a speculative importance. Okay, there you go. I'm going to take a quick break and then we're going to go on with Riemann. Here we are. Georg Friedrich Bernhard Riemann, 1826 to 1866. His life and work. Boston and Chicago were two great seats of mathematical research located in major American cities. Until they won in 2004, if you asked a baseball fan in Boston what they most hoped to see in their lifetime, they would have answered a World Series win for the Boston Red Sox. Chicago Cub fans are still waiting. Ask a mathematician in either of these cities, or anywhere else in the world, what they would most hope to see in their lifetime, and they would most likely answer a proof of the Riemann hypothesis. Perhaps mathematicians, like Red Sox fans, will have their prayers answered in our lifetimes, or at least before the Cubs win the World Series. Bernhard Riemann's life spanned just under 40 years, a lifespan that produced only a single volume of collected works. Some of these works were not published until after Riemann's early death in 1866. In spite of, or perhaps because of, the slimness of his collected works, everything he touched revolutionized mathematics. Georg Friedrich Bernhard Riemann was born on September 17, 1826, in the town of Berselenz in northern Germany, the second of 6 children born to Friedrich Bernhard Riemann and his wife, the former Charlotte Ebel. A year later, the family moved to the town of Quickborn. Nothing in his family foreshadowed Riemann's mathematical genius. His father came from a long line of Lutheran ministers. His maternal grandfather was a councillor at the Hanoverian court. Nevertheless, Riemann's genius soon became readily apparent to all, in spite of a lifelong shyness that made it hard for him to engage with people. Riemann so excelled at the local school in Quickborn that the school's administration provided him with an individual tutor to teach him advanced arithmetic and geometry. Before long, the teacher realized that he was learning more from Riemann's sophisticated solution than he was teaching Riemann. Mindful of his son's talents, Riemann's father insisted that young Bernhard enroll at the prestigious gymnasium in Hanover when he turned 14. Being away from his parents for the first time was a great hardship for Riemann, who soon wrote home of his overwhelming loneliness. Only the fact that he was able to live with his maternal grandmother made it possible for the painfully shy boy to bear the separation from his parents. When Riemann's grandmother died 2 years later, his parents reluctantly allowed him transfer to the gymnasium in near Lauenburg. Lunenburg to complete his secondary education. The gymnasium at Lunenburg proved to be a most fortunate choice for Riemann. Recognizing the new student's gift, Lunenburg's director allowed Riemann access to his private library, which contained many advanced mathematical works. When Riemann asked him to recommend a book that was not too easy, the director suggested Legende's massive theory of numbers. A week later, when Riemann returned the book, the director asked him if it had been too much of a challenge, to which Riemann had responded that he was glad to have been given a book that took him a whole week to master. All 859 pages of it. Legende's theory of numbers undoubtedly provided Riemann with his first introduction to the study of the distribution of prime numbers, the subject of the third selection included here. 2 years later, Riemann asked that he be examined on Legende's book as part of his graduation examination. Not surprisingly, he answered every question perfectly, in spite of not having looked at the work in 2 years. Ever dutiful to his parents, Riemann enrolled at the University of Göttingen, planning to take a degree in theology and philosophy so that he could follow his father into the ministry. Much as he tried to satisfy his family's wishes, Riemann could not resist the attraction of Göttingen's one and only star mathematician, Carl Friedrich Gauss. Riemann was enthralled by Gauss's lectures on the method of least squares and decided to make mathematics his career. By this time, Gauss was past 70 and ailing. He suggested that Riemann transfer to the University of Berlin, where he could study under a new generation of German mathematicians, Steiner, Jacobi, Eisenstein, and especially Dirichlet. Riemann's concern about Berlin's distance from Quickborn was partially relieved when his parents provided their blessing that he follow Gauss's advice. After receiving his baccalaureate degree in 1849, Riemann returned to Göttingen to pursue a doctorate under Gauss. In November 1851, Riemann submitted to Gauss his doctoral thesis, entitled Foundations of a General Theory of Functions of a Complex Variable. Near to the end of his career, at Göttingen, Gauss realized that he had finally found a worthy successor and lavished praise on Riemann's dissertation. The dissertation submitted by Herr Riemann offers convincing evidence of the author's thorough and penetrating investigations in those parts of the subject treated in the dissertation, of a creative, active, truly mathematical mind, and of a gloriously fertile originality. The presentation is perspicuous and concise and, in places, beautiful. The majority of readers would have preferred a greater clarity of arrangement. The whole is a substantial, valuable work, which not only satisfies the standards demanded for doctoral dissertations, but far exceeds them. A month later, Riemann passed his dissertation defense with flying colors. Because of the few teaching jobs available in German universities, freshly minted PhDs had to take unpaid positions and then write a second dissertation called an habilitation paper, and then give an habilitation lecture to demonstrate their ability to hold a paid teaching post. For his habilitation paper, Riemann chose to write on the representability of a function by means of trigonometric series, to respond to his teacher Dirichlet's query about the meaning of the integrals in Fourier's formula. Riemann wrote this paper, the first selection presented here, while working as an unpaid assistant to Wilhelm Weber's seminar in mathematical physics. For Leibniz, the definite integral yx dx was the sum of infinitely many small summons, sigma y I x delta I x. However, as a matter of practice, mathematicians preferred to use antiderivatives and the fundamental theorem of calculus to evaluate integrals rather than computing sums. Fourier's work on the representation of functions by trigonometric series forced mathematicians to deal with integrals of functions without elementary antiderivatives. It forced them to find a method of integration that applies when antiderivatives could not be found. Following Cauchy's approach to integration, Dirichlet in 1829 established that piecewise continuous functions are integrable. Dirichlet left the task of integrating a wider class of functions to his successors, and Riemann was the one who found a solution. Cauchy had taken the value of the function at one of the two endpoints of each subinterval when evaluating Cauchy sums, and then refined the petition to approach the definite integral. Cauchy sum evaluated at left endpoints. There we go. In contrast, Riemann required that any value in each subinterval could be chosen to evaluate the Riemann sums that must converge to a limit as the norm of the petition decreases to zero. Riemann sum evaluated at arbitrary points. There we go. The existence of the Cauchy integral for a function fx in the interval ab had depended on the continuity of fx in the interval ab. The existence of the Riemann integral for a function fx depended on a related but radically different conception, variation. Pardon me. Riemann, like Cauchy, begins his theory of the integral by partitioning the interval ab with the set of points x1, x2, x3, xn minus 1, xn, such that a equals x0 is less than x1, is less than x2, is less than x3, so is equal to b. Okay. He then considers the variation of the function fx in each subinterval xk minus 1 xk, that is, the maximum value of the difference of the value of the function in the subinterval xk minus 1 xk, where dk equals the maximum of fs minus ft for any s and t, such that xk minus 1 is less than or equal to s and t is less than xk. The variation of the function fx in the interval ab is the sum of the products of each of the dk times the corresponding width of the subinterval xk minus 1. That is, the sum of dk times xk minus 1. Riemann recognized that this sum had to approach zero as the norm of the partition, that is, the greatest value of xk minus 1 approach zero. Informally, this can be described as being continuous, except in intervals of arbitrarily small size. Thus, for example, the Dirichlet function dx, which takes the following values, equals 1 on b if x is rational and can be expressed in lowest terms as the fraction a on b, or equals 0 if x is irrational, can be integrated because the values of dx at rational values of x are all less than 1, and the rational values of x can be enumerated and the nth such value enclosed in an interval of size epsilon on 2 to the power of n, so that they sum to epsilon, a value chosen to be arbitrarily small. Some intervals about rational values of x equals a on b with dx equals 1 on b. Riemann never bothered to publish this paper during his lifetime. His friend and colleague Richard Dedekind published it in 1868, 2 years after Riemann's death. In these few pages, Riemann provided the impetus for the vigorous development of theories of measure and the integral for 50 years, culminating with Lebesgue's theory of measure and the integral in 1904, presented later in this volume. With his habilitation paper done, Riemann had one final hurdle to clear before he could take up a paid teaching post, his habilitation lecture. Gauss asked Riemann to suggest 3 topics for his lecture. Riemann responded with the following topics: the history of the question of the representability of a function as a trigonometric series, solutions of 2 quadratic equations in 2 unknowns, on the hypothesis that underlie the foundations of geometry. Expecting that Gauss would choose the first topic and allowing him to present the results of his habilitation paper, to Riemann's great surprise, Gauss chose the third topic. Dedekind thought that it was because Gauss was so curious to hear how such a young person would handle so difficult a topic. After overcoming his initial surprise, Riemann realized that he now had the opportunity to write an essay that could be intelligible to a wider audience at the university, and strove to make it so. Riemann begins his analysis by distinguishing discrete manifolds from continuous manifolds. He notes that for discrete manifolds, such as the natural numbers, comparison is done by counting. In contrast, for continuous manifolds, such as space, comparison is done by measuring. Measuring is done by superposition using one chosen magnitude as a standard. Until the standard magnitude is chosen, the most we can do is compare 2 magnitudes to each other when one is a part of the other, in which case we can tell which is greater and which is less, qualitatively, but not quantitatively. Riemann asks the reader to consider a one-dimensional manifold as one in which continuous progress from a point is possible only on 2 sides, forwards or backwards. Riemann then suggests, if one now supposes that this manifoldness in its turn passes over into another entirely different and again in a definite way, namely so that each point passes over into a definite point of the other, then all the specializations so obtained form a doubly extended manifoldness. In a similar manner, one obtains a triply extended manifoldness if one imagines a doubly extended one passing over in a definite way to another entirely different, and it is easy to see how this construction may be continued. If one regards the variable object instead of the determinable notion of it, this construction may be described as a composition of a variability of n plus 1 dimensions out of a variability of n dimensions and a variability of 1 dimension. Riemann explains that in a similar fashion, fixing the value of 1 dimension of an n-dimensional manifold results in a manifold of n minus 1 dimensions. And then Riemann makes his crucial move. Having constructed the notion of a manifoldness of n dimensions and found that its true character consists of the property that the determination of position in it may be reduced to n determinations of magnitude, we come to the second of the problems proposed above, viz., the study of the measure relations of which such a manifoldness is capable, and of the conditions which suffice to determine them. These measure relations can only be studied in abstract notions of quantity, and their dependence on one another can only be represented by formulae. The measure of interest to Riemann is, of course, the distance between 2 points, which is, equivalently, the length of the line between them. Position fixing being reduced to quantity finding, and the position of a point in the n-dimensional manifoldness being consequently expressed by means of n variables, x1, x2, x3 to xn, the determination of a line comes to the giving of these quantities as functions of one variable. The problem consists then in establishing a mathematical expression for the length of a line, and to this and we must consider the quantities x as expressible in terms of certain units. Riemann considers a very general class of metrics for which the distance ds between points is close together, say less than x, x1, x2, x3, xn, and these are okay. Okay, so you have to read that. Can be expressed as this, and the sum, that is the integral of the ds, gives the length of the line between two arbitrary points. Riemann notes that the Euclidean distance from the origin to the point defined by the n variables, namely the square root of the sum of the squares of the variables, is just one of many particular forms of manifoldness. Gij equals 1 if I equals j, Gij equals 0 otherwise. the one for which space is flat. Riemann recognized that in spaces of constant curvature, bodies may move about without stretching. He also demonstrated that if the sum of the angles of a triangle is always greater than two right angles, then the space must be a space of positive curvature. If the sum is always less than two right angles, then the space must be a space of negative curvature. And if the sum is always identical to two right angles, then the space must be everywhere flat. Of course, space need not be flat. It need not even be of constant curvature. Aware of Gauss's futile attempts to survey triangles whose angles added up to a value different than two right angles, Riemann wrote, "If we suppose that bodies exist independently of position, the curvature is everywhere constant, and it then results from astronomical measurements that it cannot be different from zero, or at any rate its reciprocal must be an area in comparison with which the range of our telescopes may be neglected. But if this independence of bodies from position does not exist, we cannot draw conclusions from metric relations of the great to those of the infinitely small. In that case, the curvature at each point may have an arbitrary value in three directions, provided that the total curvature of every measurable portion of space does not differ sensibly from zero. Still more complicated relations may exist if we no longer suppose the linear element expressible as the square of a quadratic differential. Now it seems that the empirical notions on which the metrical determinations of space are founded, the notion of a solid body and of a ray of light, cease to be valid for the infinitely small. We are therefore quite at liberty to suppose that the metric relations of space in the infinitely small do not conform to the hypotheses of geometry, and we ought in fact to support it if we can thereby obtain a simpler explanation of the phenomena. The question of the validity of the hypotheses of geometry in the infinitely small is bound up with the question of the ground of the metric relations of space." Riemann had begun his lecture by noting that the physical space of our experience is one of several forms of three-dimensional space. The metrical properties of our three-dimensional space, he says, must be derived from experience. They cannot be derived solely from the axioms and postulates of geometry. Riemann closed his lecture by stating, "Either, therefore, the reality which underlies space must form a discrete manifoldness, or we must seek the ground of its metric relations outside it, in binding forces which act upon it. The answer to these questions can only be got by starting from the conception of phenomena which has hitherto been justified by experience and which Newton assumed as a foundation, and by making in this conception the successive changes required by facts which it cannot explain. Researchers starting from general notions, like the investigation we have just made, can only be useful in preventing this work from being hampered by too narrow views, and progress in knowledge of the interdependence of things from being checked by traditional prejudices. This leads us into the domain of another science, of physics, into which the object of this work does not allow us to go today. Little did Riemann know that 50 years after his death, this work would provide the mathematical foundation on which Einstein constructed the general theory of relativity. Riemann's lecture, the second selection presented in this volume, must have met with success because Gauss and Weber each responded with great praise. Having passed the final hurdle, Riemann finally began his teaching career in the fall of 1854, giving a lecture series on partial differential equations to a grand total of 8 students, more than double the number he had expected. However, this was hardly a way to make a living. When Riemann's father died in 1855, his 3 surviving sisters had to seek financial support from their older brother, a postal clerk, who earned far more than the economically destitute mathematician. When Gauss died in the same year, Riemann's friend knew that Gauss's chair would go to Riemann's former Berlin professor, P.J.L. Dirichlet. They tried to persuade the university to appoint Riemann to an assistant professorship, but that effort came to naught. The loss of his father and the mounting financial strain proved to be too much for Riemann's weak disposition and led to a nervous breakdown in late 1855. To relieve the strain, Riemann retreated to the mountains, where he refreshed himself by taking long hikes with his colleague Richard Dedekind. Good fortune seemed to strike Riemann in 1857 when the university offered him an assistant professorship. In 1858, the Italian mathematicians Enrico Betti, Felice Casarati, and Francesco Brioschi visited Riemann in Göttingen to discuss his mathematical works. As soon as Riemann began to feel financially secure, his brother died, leaving him to support his 3 unmarried sisters. Whether coincidence or not, Riemann first began to suffer from consumption during this most troubling of financial circumstances. Within a year, Riemann's burdens eased somewhat with the premature death of his sister Marie, and then a year later, in 1859, Riemann finally achieved the professional success of which he was so worthy when he succeeded Dirichlet to the chair of mathematics at Göttingen, following his former teacher's untimely death. The year 1859 also marked Riemann's election to the Berlin Academy of Science. To commemorate his appointment, Riemann wrote his only paper on number theory, entitled On the Number of Prime Numbers Less Than a Given Magnitude. Undoubtedly, his interest in the subject grew out of his reading Lesonder's Theory of Numbers while a student at the gymnasium in Leuenberg 15 years earlier. Lesonder and Gauss had each conjectured that pi x, the function counting all the primes less than x, asymptotically approached Lix, i.e., or that is, the ratio of pi x divided by Lix approaches 1, where Lin equals integral of 2 to n dx ln x as x grows large. In this epochal paper, which I consider mathematical virtuosity of the highest order, Riemann introduced radically new methods to attack this problem. He begins by introducing the infinite series of inverse S powers, a series first studied by Euler in the mid-18th century, who proved that for S equals 2, the series sums to the limit pi squared on 6. Riemann names this the zeta function after the Greek letter zeta. More formally, the zeta function is represented as zeta s equals the sum from n equals 1 to infinity of 1 over n to the power of s. At first glance, it appears from At first glance, it appears far from obvious how an infinite series involving all of the positive integers can relate to the primes. However, Euler had provided the connection by first noticing that thanks to the unique factorization of the integers, the infinite sum of inverse s powers of the positive integers can be written as the infinite products of the infinite geometric series for each prime number p, and then applying a basic property of infinite geometries geometric series that this sums to 1 over 1 minus p to the power of negative s, to restate the zeta function as the infinite product zeta s equals the product for p, 1 over 1 minus p to the power of negative s. These are just the initial steps in this mathematical tour de force, as defined by these infinite sum and product representations. The zeta function only converges for complex numbers with real parts greater than 1. Drawing on breakthrough results from his doctoral dissertation, he extends the zeta function to all complex numbers having an infinite singularity only for s equals 1. During the course of the paper, Riemann makes the casual remark that it is very probable that all roots of a related function are real. Certainly one would wish for a stricter proof here. Meanwhile, I have temporarily put aside the search for this after some fleeting futile attempts. A value x is a root of the function fx if fx equals 0. A root of the function, is that zeta, capital Zeta? I'm not sure what that's. Anyway, a root of this function is real if and only if a root of the zeta function is a complex number with real part equal to 1/2. Making this assumption about the roots of the zeta function, Riemann concludes, the well-known approximation formula fx equals Lix fx is also called pi x. It is the function that counts the primes less than x. Thus correct only up to values of the order of magnitude x to the power of 1/2, or the square root of x. The values of the roots of the zeta function determine the magnitude of the difference between pi x and Lix. The hypothesis that all the roots of the zeta function have real part equal to 1/2 has come to be known as the Riemann hypothesis. The hypothesis that all the roots of the zeta function have real part equal to 1/2 has come to be known as the Riemann hypothesis. After a few years, Riemann's prospects brightened briefly, and in June 1862 he married Elise Koch, a friend of his sister's. However, within a month of his marriage, Riemann once again fell ill with pleurisy, followed by consumption. Influential friends persuaded the university authorities to allow Riemann the funds to travel to Italy for the winter to convalesce. Thinking himself recovered, Riemann left Italy in the spring and foolishly walked in deep snow while travelling through the Alpine passes in Switzerland. Following a relapse, he returned to Italy once again in August 1863, stopping first in Pisa, where his wife gave birth to their one and only child, Ida. While in Pisa, Riemann occasionally attended lectures at its university, which soon offered him a professorship at the urging of Betti and Casarati, members of his mathematics faculty, and Brioschi, Minister of Education. Although the terms of his contract at Göttingen prevented him from accepting the offer, the German university allowed him to make an extended stay in Pisa in the hope that he would regain his health. Unfortunately, that was not to be. Riemann died on July 20, 1866, in the village of Salesco, on the shores of Lake Maggiore, 2 months short of his 40th birthday. For several decades after the publication of Riemann's paper on the distribution of primes, mathematicians wondered how he arrived at his conjecture that all of the zeros of the zeta function have a real part of a half. The paper not only gives no clue how Riemann arrived at this conjecture, but also doesn't even provide grounds for knowing that any zero of the zeta function has a real part of 1/2. Some mathematicians simply suppose that Riemann possessed some wonderful insights. In fact, Riemann gained his knowledge of the behavior of the zeta function with great computational effort. When he died, his wife rescued most of his private papers from an overzealous housemaid who had begun to burn them in the furnace. Having saved them from destruction, Elise Riemann kept them locked away for the rest of her life. They only became public in the 1920s, and when they did, they provided a treasure trove to their editor, the mathematician C.L. Siegel. Siegel saw that Riemann had discovered several high-powered computational techniques that other mathematicians had rediscovered over the intervening 60 years. Ever the perfectionist, Riemann left unpublished these methods because he lacked proofs to demonstrate their effectiveness. We can only imagine what Riemann might have done had he been fortunate enough to enjoy 2 or 3 more decades of life. For 30 years following Riemann's death, virtually no progress was made on the problem of prime number distribution. Then in the 1890s, Hadamard, von Mangold, and de la Vallée-Poussin exploited ideas in Riemann's paper, proving his main formula for pi x and the prime number theorem that pi x equals Lix or is proportional to Lix, where Lin is the integral of dx ln x. Originally conjectured by Gauss and Lasonder a century earlier. David Hilbert made the Riemann hypothesis the 8th of his 23 problems presented to the International Congress of Mathematicians in 1900. Hilbert confidently expected the Riemann hypothesis to be proven in a decade or so. Hilbert revised his estimate as the Riemann hypothesis resisted all attempts to crack it. Shortly before his death in 1943, someone asked Hilbert what his first question would be if he were revived in 500 years. The great mathematician immediately responded, "I would ask, has someone proved the Riemann hypothesis?" A century later, it remains unproven, and there is now $1 million prize for whoever proves or disproves the hypothesis. No one expects it to be disproved. Mathematicians have proven that at least 40% of the solutions must have a real part equal to 1/2. Indeed, the first 1.5 billion known solutions all have real part equal to 1/2, yet it remains unproven. Riemann died at far too early an age. We can only ask whether he would have rigorously proved his eponymous hypothesis had he been granted the biblical lifespan of 70 years. Perhaps we will live long enough to see Riemann's hypothesis proved. If we are fortunate for that to happen, we shouldn't be surprised if the roots of that proof lie in Riemann's epochal paper itself. And then we're away. On the representability of a function by means of a trigonometric series, from Essays of the Royal Society of Sciences, Göttingen, Volume 13. Alright, Chapter 12. The concept of a definite integral and the scope of its validity. Investigation of whether a function can be represented by a trigonometric series with no particular assumptions about the nature of the function. On the hypotheses which lie at the bases of geometry. One, notion of an n-ply extended magnitude. 2. Measure relations of which a manifoldness of n dimensions is capable on the assumption that lines have a length independent of position, and consequently that every line may be measured by every other. Three, application to space. On the number of prime numbers less than a given quantity. Monthly reports of the Berlin Academy, November 1859. Chapter 7. Alright, we're going to take a break. On we go. Karl Weierstrass, 1815 to 1879. Sorry, 1897. His life and work. Imagine what it would be like to be a mathematician whose name would be destined to live on forever. Not bad as fantasies go. Now imagine what it would be like if you had to spend the first 12 years of your career teaching in a high school, not just teaching mathematics, but calligraphy and even physical education. That is the part of Karl Weierstrass' autobiography that even Weierstrass could only remember as a time of unending dreariness and boredom. For every epsilon, there is a delta. Karl Weierstrass was born in Ostenfeld, Westphalia, now part of Germany, on October 31, 1815, 4.5 months after Wellington's defeat of Napoleon at the Battle of Waterloo. There is little in Weierstrass's forebears to suggest intellectual achievement, but much less mathematical greatness. He was the eldest child of Wilhelm and Theodora, née von der Forst. We know nothing of his mother's family except that they, like the Weierstrass family, were moderate Catholics. We know that his father was reasonably well educated in arts and sciences. Wilhelm Weierstrass had a career as a petty bureaucrat in the Westphalian and then the Prussian government. At age 8, he entered the tax service and began to transfer frequently. Karl's already tumultuous home life took a more serious turn for the worse when his mother died suddenly in 1827, after she had given Wilhelm 2 daughters and another son. The elder Weierstrass remarried within 2 years, adding yet one more upset into young Karl's life. In 1828, Karl entered the Catholic Gymnasium, high school, in the Westphalian town of Paderborn, yet another new hometown necessitated by his father's move to yet another new job, Assistant Tax Commissioner of Paderborn. Home finances must have been very difficult for the Weierstrass family. At the age of 14, young Karl went to work as a bookkeeper for a local merchant's wife. His father thought that it would give Karl a chance to use his prowess at arithmetic. Little could Father Weierstrass imagine that it would give Karl the spare time to read the gymnasium's copies of the Journal of Pure and Applied Mathematics, the leading mathematics journal in all of Europe. Devouring these copies, Karl Weierstrass made up his mind that he was going to be a mathematician. But Wilhelm Weierstrass had other ideas. In spite of the many mathematics prizes that his son won on his gymnasium graduation in 1834, Wilhelm insisted that Karl enroll in a public finance and administration program at the nearby University of Bonn. Young Karl very grudgingly agreed. Great physical and mental strain filled the 4 years he spent at Bonn. Weierstrass often indulged himself in bouts of drinking and fencing as a means of rebellion. Several times he barely avoided serious injury in a fencing duel. After 4 long years, young Weierstrass left Bonn without sitting for the degree examinations. His father was distraught. 4 years at university and still Karl was no closer to a position as a petty bureaucrat. Within a year, a family friend suggested a reasonable compromise. Karl could enroll at the nearby Theological and Philosophical Academy in nearby Munster and sit an examination for a teaching degree in just a year. Weierstrass did sit the examination just a year later in 1840 and asked for a particular challenging problem on the mathematics exam. Little did Weierstrass know how well he had answered the problem. The school authorities merely told him that he had passed the mathematics exam along with the other portions of the exam. They didn't bother to tell him that the external examiner for the mathematics exam was the mathematician Christoph Gutermann, who had been a student of the great Gauss. Gutermann recognized that Weierstrass's examination answer had made important advances in the branch of mathematics called elliptical function theory, but Weierstrass wasn't to learn of this praise for almost a decade. Thus, Weierstrass embarked on a 15-year career of teaching mathematics to disinterested students and lacking colleagues possessing even a fraction of his gift. Amazingly, Weierstrass published his first research papers in the gymnasium's prospectus, designed to interest fathers looking to place their sons in school. We can only imagine what the fathers' reactions must have been to reading mathematics that was completely incomprehensible to them because it was groundbreaking. To maintain his sanity in the midst of the dreary monotony of the gymnasium years, Weierstrass immersed himself in whatever contemporary mathematics he could find. Years of such stress took its toll. By 1850, Weierstrass began to suffer persistent attacks of vertigo that could last as long as an hour and would only come to a halt with a violent bout of vomiting. But success lay just around the corner. In 1854, Weierstrass finally submitted his paper on the theory of abelian functions to the Journal of Pure and Applied Mathematics. It was the watershed event of his life. Weierstrass finally began to receive the attention he deserved. The University of Königsberg, now Danzig, offered him an honorary doctorate. Hoping to keep him, the gymnasium at Brandsburg promoted him to senior lecturer and offered a year-long sabbatical in 1855. But Weierstrass hoped for something greater, a true university appointment. In 1855, at nearly 40 years of age, Weierstrass sought his first university appointment as professor of mathematics at the University of Breslau in East Prussia, now Wrocław in Poland. He failed to secure that post, but then the offers began to pour in. Shortly after he published a second paper on abelian functions in 1856, he attended a conference in Vienna and was offered a chair at the Austrian university of his choice. At the time, Austria was something of a mathematical backwater, so Weierstrass remained unsure of what to do. Then the Industrial Institute of Berlin offered him a full professorship. Weierstrass knew that it wasn't the most prestigious of institutions, but was better than Austria. However, it was not better than the prestigious University of Berlin. As fate would have it, the University of Berlin offered Weierstrass an associate professorship just after he accepted the offer from the Industrial Institute. Much as he wanted to accept the offer from the University of Berlin, Weierstrass knew that he had to honor his 7-year commitment to the Industrial Institute. Although not among the most prestigious institutions of higher learning in Germany, the Industrial Institute finally provided Weierstrass the opportunity to pursue his research and present it to students eager to learn them. Weierstrass is best known for his development of what is now known as the epsilon method, after the Greek letter epsilon, the contribution presented in this chapter. Weierstrass began developing the epsilon method in his class titled Introduction to Analysis during the academic year in 1859 to 1860. The epsilon method provided a rigorous way for mathematicians to work with the notion of an infinite sequence or series reaching a limit. A few examples will help to illustrate the power of Weierstrass's epsilon method. Consider the geometric series that begins with 1 and continues with successive powers of 1/2. Continued on to infinity, many readers will remember the formula for the sum of a finite number of terms of a geometric progression. This formula can be applied to any infinite number This formula can be applied to any finite number n of terms in the series given above by setting a equals 1 and r equals 1/2, yielding 1 minus a half to the power of n over 1 minus 1/2. Mathematicians argued, intuitively, that the numerator of this expression reached 1 in the limit as n reached infinity, since 1/2 to the power of n reached 0 as n reached infinity. But what did it mean for n to reach infinity? That had puzzled mathematicians and philosophers since the days of the ancient Greek mathematician and philosopher Zeno of Elea, died about 425 BC. Weierstrass's epsilon method provided a solution. N no longer had to reach infinity. Instead, the limit was defined for n being in the process of reaching infinity. Weierstrass defined an infinite sequence as having a limit if, for any epsilon e, you could find an integer n, so that for all integers m is greater than or equal to n, the mth term of the sequence was always within epsilon of the limit. Consider how easily the epsilon method can be applied to the problem of proving that the limit of 1/2 to the power of n reaches 0 as n reaches infinity. For any epsilon, just find the power of 1/2 that is less than epsilon, and it is obvious that all greater powers will also be less than epsilon. The epsilon method had an even greater impact in the theory of functions. Prior to the middle of the 19th century, mathematicians had concentrated on functions that, like the sine wave, could be drawn, at least in parts, without lifting a pencil from the paper, or perhaps lifting it, at most, occasionally. This was a very geometric notion of continuity. The epsilon method freed mathematicians from thinking about continuity in such a geometric manner. Weierstrass defined continuity of a function f at a point xo as follows. If for every epsilon a sigma could be found so that fx is written epsilon of fx0 whenever x is within sigma of x0, then f is continuous at x0. This definition certainly fit the intuitive notion that as you drew a continuous function near a point, you had to be getting closer to the value of the function at that point, but it could do much more. Earlier in the 19th century, the German mathematician Gustav Dirichlet had defined two rather strange functions. The first, I'm not sure what that letter is. Let's call it x, but it's not x, is it? The first xx is called the characteristic function of the rationals in the reals. It takes the following values. Xx equals 1 if x is rational and 0 if x is irrational. Okay. The second function, not surprisingly, called the Dirichlet function, dx, is even stranger. It takes the following values. Dx equals 1 on b if x is rational and can be expressed in lowest terms as a fraction a on b. Otherwise it equals 0 if x is irrational. Neither of these functions can be drawn the way a sine curve may be drawn. That's not surprising for the first of them, since it is discontinuous at every point. Just take epsilon less than 1. There will always be another point nearby whose value differs by 1, since the rationals and the irrationals are intermixed with each other everywhere. Not all mathematicians initially found much value in monstrous functions such as these. Very early in the 20th century, the great French mathematician Henri Poincaré, let me check. Very early in the 20th century, the great French mathematician Henri Poincaré complained of this and other functions. Logic sometimes makes monsters. Since half a century we have seen arise a crown of bizarre functions which seem to try to resemble as little as possible the honest functions which serve some purpose. In 1861, within 2 years of first formulating the epsilon method, Weierstrass proved that the Dirichlet function dx was continuous at any irrational value of x. Suppose that we want to apply the epsilon delta method for x equals the square root of 2 with epsilon equals 0.1. That is, epsilon equals 1 on 10. We know that d square root of 2 equals 0. What value can sigma take so that all values of dx for x within sigma of root 2 are not more than 0.1? Our choice for epsilon, away from 0.0, the value of dx for x equals the square root of 2. The demonstration is remarkably straightforward once you realize that the only rational numbers for which dx is greater than 0.1, our epsilon, must have a denominator no greater than 10. All of these rational numbers near root 2 can be listed out and the one closest to root 2 determined. We have the benefit of using a spreadsheet. Here is a chart of the values for dx for all the rational numbers between 1 and 2 having a denominator no greater than 10. It turns out that the rational number with a value of dx closest to 0 is x equals 1.3 or 13 on 10. The initial space of mathematical activity in Berlin greatly wearied Weierstrass. Sorry, I read that wrong. The initial spate of mathematical activity in Berlin greatly wearied Weierstrass. Shortly after the groundbreaking researches of 1859 to 1861, he suffered a complete collapse from what was termed brain spasms. Ultimately, he had to take a year's sabbatical, not just from teaching, but from mathematical research. When he returned to teaching in 1863, he always lectured from a seating position. An advanced student dealt with the physical labor of writing the mathematics on a blackboard. Finally, after 8 long years, he was able to move to a position at the esteemed University of Berlin. Ever the perfectionist and always careful of his physical exertions, Weierstrass refrained from publishing his epsilon method until the middle of the 1880s. Perhaps not surprisingly, the best of a generation of German mathematics students matriculated at Weierstrass's footsteps at the University of Berlin, the only source for learning the epsilon method firsthand. Georg Cantor, whose work appears later in this book, was perhaps the greatest of all of Weierstrass's students. Cantor's work also became the cause of friction between Weierstrass and one of his oldest and best friends, Leopold Kronecker, who left us with the quotation, "God created integers, all else is the work of man," used as the title of this book. Kronecker could abide all sorts of numbers, rational numbers, real numbers, even imaginary numbers. However, Kronecker could not abide the infinite, the focus of Cantor's work. Kronecker simply thought that Cantor's infinite mathematical objects could not exist and that Cantor's work was meaningless and useless. Aside from his mathematics, Weierstrass's later years were not very happy. Like many mathematicians, Weierstrass never married, and neither did his brother nor either of his 2 sisters. Weierstrass spent the last 3 years of his life confined to a wheelchair, completely dependent on others and immobile. He died in Berlin in early 1897, several months after his 81st birthday. The great French mathematician Henri Poincaré, who had earlier complained of the surge of monstrous mathematical objects such as the Dirichlet function, had high praise for Weierstrass. Poincaré considered Weierstrass to be Germany's 3rd greatest mathematician of the 19th century, surpassed only by the incomparable Gauss and the inestimable Riemann. And then we're away. A theory of functions. 7. Uniform continuity. Oh, that was only a short one. Richard Julius Wilhelm Dedekind, 1831 to 1916. His life and work. Richard Julius Wilhelm Dedekind was born on October 6, 1831 in Brunswick, Germany, which was also the birthplace of Carl Friedrich Gauss. Dedekind was the youngest of the 4 children of Julius Levin Aldrich Dedekind and Caroline Marie Henriette Dedekind, née Imperius. He grew up in the intellectually stimulating home one would expect of an academically accomplished family. His father was a professor of law at the Collegium Carolinum in Brunswick, whose own father had been a distinguished chemist and physician. His maternal grandfather had also been a professor at the Collegium. The other Dedekind son became a court judge, and his sister Julie published several novels. Dedekind followed in his brother's footsteps and began his formal education at the Gymnasium Martino Catholiceum in Brunswick. At first, chemistry and physics were his favourite subjects, with mathematics just a useful tool in their service. However, by the time he enrolled at the local Collegium Carolinum in 1848, Dedekind had turned away from chemistry and physics because of what seemed to him to be their chaotic logical structure in favour of mathematics. During his 2 years at the Collegium, Dedekind studied nothing but mathematics and the most abstract of the physical sciences. In short order, he mastered analytic geometry, differential and integral calculus, and the foundations of analysis. When Dedekind enrolled at the nearby University of Göttingen in 1850, he was by far the best prepared student of his entering class. Dedekind sped through Göttingen's mathematics offerings. He attended Gauss's lectures on the theory of least squares. 50 years later, he would remember them as the most beautiful and logical exposition of mathematics he ever encountered. While at Göttingen, he attended a seminar in number theory, the most advanced offering of the mathematics department. At this seminar, he met the slightly older Bernhard Riemann, whose champion he would become. In the spring of 1852, Dedekind wrote his doctoral dissertation on the theory of Eulerian integrals under Gauss's supervision. He would be the last of the great Gauss's 6 doctoral students. In spite of having received his doctorate, Dedekind considered his mathematical education to be incomplete. He spent 2 years attending classes to fill in what he considered to be the gaps in his knowledge before he took the examination that would allow him to be a university lecturer. Of course, he passed with flying colours, enabling him to take a lowly teaching post at Göttingen as a Privatdozent, lecturing undergraduates on geometry and probability. Dedekind felt a particularly great loss when Gauss died in 1855. However, Dedekind's loss was soon followed by the great satisfaction of working with Gauss's successor, Peter Gustav Lejeune Dirichlet. Although a member of the faculty himself, Dedekind had no compunction about attending Dirichlet's courses on a wide variety of topics, including number theory, potential theory, definite integrals, and partial differential equations. The two men were so close that many members of the Göttingen mathematics community joked that they were inseparable twins. But if anyone were Dedekind's twin, it was Riemann. They were truly inseparable, spending long hours together, walking in the woods near Göttingen, discussing mathematical topics. When Dedekind received an offer of a better post at the Zurich Polytechnic, he agonized over leaving Göttingen and Riemann. In the end, Dedekind accepted the offer in far-off Zurich. Although physically in Switzerland, Dedekind remained spiritually in Germany. When Riemann was elected to the Berlin Academy in 1859, Dedekind leapt at the chance to accompany his friend on his visit to Berlin. It turned out to be a wise decision. When in Berlin, he met the leading figures of the German mathematical community, Kramer, Brockart, Kronecker, and especially Weierstrass. These contacts soon bore fruit. In 1862, they arranged for Dedekind to receive an offer at the Brunswick Polytechnic, the successor of the Carolinum Collegium. Dedekind returned to his alma mater, where his father had taught. Although more prestigious appointments would be offered in later years, Dedekind felt very much at home in his birthplace and never took another position. A course on differential calculus that Dedekind taught his first year in Zurich kindled his interest in the foundations of mathematics. As the course unfolded, he realized that he was unable to present his students with a sound theoretical foundation for the continuum of real numbers comprising the real line. He set to work to remedy this situation. 14 years later, he published his classic work, Continuity and Irrational Numbers, 1872, that gave the first rigorous foundation for the continuum of real numbers. It is included in this volume along with his essay, The Nature and Meaning of Numbers, published in 1887. The nature of the real line had bedeviled mathematics ever since the Pythagoreans discovered the irrationality of the square root of 2 in the 5th century BC. Surveying the developments of mathematics, Dedekind recognized the successive extension of one class of numbers into a larger class of which they were a part. First, the whole numbers, 1, 2, 3, were extended to the entire class of integers, positive, 0, and negative. Mathematical operations on negative integers could be expressed in terms of whole numbers. Then the integers were extended to the rational numbers of which they were a part. Most recently, Dedekind's mentor, Gauss, had extended the real numbers to the complex numbers having real and imaginary parts. Dedekind employed the concept of a cut to ground the whole of the real line, rational and irrational numbers, in the rational numbers. He began by noticing that every rational number A divides the set of rational numbers into two classes, A1, the set of rational numbers less than A, and A2, the set of rational numbers greater than A. Moreover, every rational number belonging to A1 is less than every rational number belonging to A2. Thus, the rational number A cuts the rational numbers into two distinct classes of numbers separated by the order relationship less than / greater than. Dedekind realized that many other cuts could be created among the rational numbers. For example, square root of 2 cuts the rational numbers into two classes. The A1, the set of positive rational numbers whose square is less than the square root of 2, plus 0 and all the negative rational numbers. And A2, the set of positive rational numbers whose square greater than the square root of 2. Once again, every rational number belonging to A1 is less than every rational number belonging to A2. Similarly, pi can be defined as cutting the rational numbers into two classes. A1, the set of positive rational numbers of the form A on B, whose ratio is less than the ration of a circle's circumference to its diameter. I think it's supposed to say ratio. Plus 0 and all the negative rational numbers. And A2, the set of positive rational numbers of the form A on B, whose ratio is greater than ration of a circle's circumference to its diameter. Here too, every rational number belonging to A1 is less than every rational number belonging to A2. Having given examples of cuts, Dedekind generalized the concept so that any exhaustive division of the rational numbers into two sets, A1 and A2, such that every member of A1 is less than every member of A2, defines a cut that is identified with a real number. If the real number identified is not a rational number, as in the case of the cut that defines the square root of 2, then it must be an irrational number. After defining the real numbers in terms of cuts, Dedekind went on to show that arithmetic on the real numbers is just as we would expect it to be precisely because of the basic arithmetic operations of addition and subtraction preserve the less than greater than relationship among positive rational numbers. Consider, for example, the cuts created by root 2 and root 3 into sets A1 and A2 and B1 and B2 respectively. Take any rational number in A1 and any rational number in B1, their product will be less than the product of any rational number in A2 and any rational number in B2, and the cut corresponds to square root of 6, just as one would expect. Dedekind frequently spent his summers in Switzerland or the Tyrolean Alps. During his 1874 holiday, he met Georg Cantor for the first time at the city of Interlaken. Dedekind's groundbreaking analysis of the continuum served as one of Cantor's major sources of inspiration for his own revolutionary work on transfinite numbers presented later in this volume. It is through Cantor's correspondence with Dedekind in the 1870s and 1880s that historians have come to understand the development of Cantor's ideas. As Göttingen rose to the prominence in of Berlin in mathematics, Brunswick remained a backwater. Dedekind never had any doctoral students at Brunswick. The light demands at Brunswick afforded Dedekind the opportunity to oversee the publication of 2 mathematical masterpieces. In 1863, Dedekind published Dirichlet's lectures on number theory, mostly from notes he had taken. By 1894, 3 more editions had appeared. When Riemann died prematurely in 1866, Dedekind took it on himself to publish his friend's collected works. The classic volume appeared 10 years after his friend's early death. He also supervised the publication of the collected works of his mentor, Carl Friedrich Gauss. The light demands at Brunswick also allowed Dedekind to become the Polytechnic's director from 1872 to 1875. Although he disliked administrative duties, Dedekind did enjoy the fact that he had taken on a position that had previously been his father's and his maternal grandfather's. Dedekind retired from his university post in 1894. Even though retired, he continued to lecture until well into his 70s. Unlike many mathematicians, he enjoyed lecturing. Dedekind received many honours over the course of his career. The first came from Göttingen, which elected him a corresponding member of its academy in 1862. In 1880, he received a similar honour from the Academy of Science in Berlin, in 1900 from the Academy of Sciences in Paris, and the Academy in Rome. In 1902, Dedekind received many honorary doctorates on the 50th anniversary of his doctorate at Göttingen. Content with his life in Brunswick, Dedekind never married and lived with his sister Julie until her death in 1914. He died after a short illness on February 12, 1916. Even though Europe was in the midst of the Great War, mathematicians in France and England mourned his passing, knowing that the last direct link to the great Gauss had been lost. And then we're on to the essay on the theory of numbers. Shall we read the preface to the first edition? Actually, I won't, because we're running out of time for this video. It's going to go over 2 hours, 12 hours, I think, at the moment. So let's just skip ahead, because we've got to get this thing finished. Continuity and irrational numbers, properties of rational numbers, comparison of the rational numbers with the points of a straight line, continuity of the straight line, creation of irrational numbers, operations with real numbers, infinitesimal analysis, nature and meaning of numbers, systems of elements, transformation of a system, similarity of a transformation, similar systems, transformation of a system in itself, the finite and the infinite, simple infinite systems, series of natural numbers, greater and less numbers, finite and infinite parts of the number series, definition of a transformation of the number series by induction, the class of simply infinite systems, addition of numbers, multiplication of numbers, involution of numbers, number of the elements of a finite system, there we go. Now we're up to Georg Cantor, 1845 to 1918, his life and work. Georg Cantor scaled the peaks of infinity and then plunged into the deepest abyss of the mind, mental depression. Georg Ferdinand Ludwig Philipp Cantor was the firstborn son and namesake of a Protestant father and a Catholic mother. His father, Georg Waldemar Cantor, was a German-born Protestant who moved to St. Petersburg, the capital of Tsarist Russia, to become a stockbroker. Cantor ultimately became famous because of the mathematical talent on his father's side. However, he first achieved notoriety for his fine violin playing, no doubt a talent derived from his mother, Marie Bohm, a native Russian who came from a musical family renowned for its violin virtuosi. Any records of Cantor's early schooling in St. Petersburg must have been lost when the family moved back to Germany and settled in Frankfurt so that his father would no longer have to endure the harsh Russian winters. Cantor had a distinguished record at gymnasia in Frankfurt and nearby Wiesbaden. Cantor's father thought that young Georg's love of mathematics could enable him to be a shining star in the engineer firmament. Cantor acquiesced to his father's firm suggestion that the Polytechnic School in Zurich would be a good school for studying engineering. After a semester, young Georg finally summoned up the courage to ask his father's permission to transfer to the University of Berlin, where he could study pure mathematics. Much to Cantor's surprise, his father agreed to the change. In June 1863, as he was finishing his year in Zurich, Cantor learned of his father's sudden death. The elder Cantor would never know of even his son's first accomplishment as a shining star in the mathematical firmament. Cantor sped through the mathematics curriculum at Berlin, where he was a pupil of the great Weierstrass, newly resident in the chair of mathematics. Within 4 years, he had both his undergraduate and doctoral degrees. After teaching at a local girls' school for 2 years, Cantor received his first university teaching appointment at the University of Halle, the birthplace of the composer George Friedrich Handel, about 100 miles south of Berlin. 10 years later, he received a full professorship. He would remain there for the rest of his career. When Cantor arrived at Halle, his new colleague, the mathematician Heinrich Hein, challenged him to prove the uniqueness of a function's representation by a trigonometric series, a generalization of Fourier series. This was the research that led Cantor to his study of the infinite in the 1870s. Cantor was not the first mathematician to formalize the concept of the infinite. Prior to Cantor, Richard Dedekind, 1831 to 1916, made the first giant step by deciding how to recognize the infinite rather than construct it, thereby avoiding objections such as the following one made by the great Gauss. I protest against the use of infinite magnitude as something completed, which in mathematics is never permissible. Infinity is merely a facon de parler, the real meaning behind a limit, which certain ratios approach indefinitely near, while others are permitted to increase without restriction. Dedekind looked at the natural numbers 0, 1, 2, 3, 4 as the paradigm example of an infinite set and defined a set as infinite if the natural numbers could be put into a one-to-one correspondence with that set or a subset of it. Thus, the natural numbers are infinite by definition, and so are the integers, the rational numbers, and the real numbers, because every natural number is also an integer, a rational number, and a real number. With Dedekind having accomplished that, Cantor asked two interesting questions. First, can infinity be recognized without making reference to the natural numbers? Second, are there different degrees of infinity? Cantor answered his first question by defining a set as being infinite if it could be put into a one-to-one correspondence with Cantor. I think there's a typo here. With Cantor answered his first question by defining a set to be infinite if it could be put into a one-to-one correspondence with the set of natural numbers 0, 1, 2, etc. The set of natural numbers trivially satisfy this condition. The set of natural numbers can be put into a one-to-one mapping with a subset of itself. Consider, for example, the mapping that takes 0 to 1, 1 to 2, 2 to 3, 3 to 4. Therefore, any set that satisfies Cantor's definition of the infinite automatically satisfied Dedekind's definition. To show the opposite requires a piece of 20th century mathematics called the axiom of choice. The bulk of Cantor's groundbreaking work concerned his second question, and it builds on his answer to the first question. By making the infinite more general than the natural numbers, Cantor opened the possibility of there being different degrees of the infinite. Cantor defined two sets as being equinumerous if they could be put into a one-to-one correspondence with each other. Thus, the positive integers are equinumerous with the negative integers by the mapping n to negative n for a positive integer n. Similarly, the positive real numbers are equinumerous with the real numbers by a similar mapping. Try proving to yourself that the positive integers are equinumerous with all of the integers. As he made these proofs, Cantor introduced the distinction between a set's cardinality, that is, how many members it has, and its order type. He noted that although the positive and the negative integers have the same cardinality, they have a different order type. There is a first positive integer, but no last one, using the standard greater than less than ordering. In contrast, there is a last negative integer, but no first one, using the standard greater than less than ordering. Cantor used Hebrew letters to denote cardinal numbers. Aleph null, the Hebrew letter Aleph with a subscript of 0, denotes the first infinite cardinal. Greek letters denote order types. The Greek letter omega, denotes the order type of a set, like the positive integers with the first element but no last element. Just going to take a quick break. Where are we up to? The Greek letter omega denotes the order type of a set, like the positive integers with the first element but no last element, and omega star, omega with an asterisk as a superscript, denotes a set like the negative integers with a last element but no first element. The order type, omega plus 1, describes a set like the positive integers plus a single element greater than all of the positive integers. The integers as a whole have order type omega star plus omega. Can you guess what kind of set the order type omega plus omega star describes? It's not hard, it is just not one you're used to dealing with. Then Cantor demonstrated the power of his definition based on equinumerosity. First, he demonstrated that the positive rational numbers are equinumerous with the positive integers. Cantor realized that the positive rational numbers couldn't be put into greater than less than, so he rearranged. Okay, so we've got 1, 2, 3, 4 divided by 1, you got 1, 2, 3, 4 divided by 2, okay. Okay, cool. He rearranged them by the sum of their numerator and denominator, and then started enumerating them as follows, thereby demonstrating that the positive rational numbers are equinumerous with the positive integers. Cantor then tackled the real numbers and proved that they are not equinumerous with the integers. There are strictly more real numbers than integers. Here is the gist of Cantor's proof for real numbers greater than 0 and less than 1. If the positive real numbers greater than 0 and less than 1 are equinumerous with positive integers, then they can all be listed out in a sequence such as this. Now comes Cantor's great insight. He considers the highlighted digits on the diagonal and he changes all of their values, adding 1 if the value is 0 through 8 and changing 9 to a 0. This constructs the real number 0.32319527777682 that cannot be in the table because it differs from every real number listed in the table. Cantor used a particular form of a reduction ad absurdum proof called a diagonalization argument, which to demonstrate that there are strictly more real numbers than there are integers. We will see diagonalization arguments reappear with gusto in the works of Kurt Gödel and Alan Turing. Because the word infinity had a long history with much baggage attached, Cantor introduced the term transfinite numbers to denote all of his infinite numbers, both the cardinal numbers and the ordinal numbers, or order types. Then Cantor asked a question that remains open to this day. Given that there are strictly more real numbers than integers, how many different types of infinite subsets of the real numbers are there? Are there only two types of infinite subsets of the real numbers, those equinumerous to the real numbers and those equinumerous to the integers? Or are there more types of subsets in between these two types? Cantor believed that there are only two types of infinite subsets of the real numbers, but he could not prove it. The resolution of this conjecture, now known as the continuum hypothesis, would have surprised Cantor. In 1940, Kurt Gödel showed that the continuum hypothesis cannot be disproved using the standard axioms of set theory. Then in 1963, Paul Cohen proved that it cannot be proved using those axioms either. Cantor's early years in Halle must have been filled with joy. In 1874, he married Valley Gutman, a friend of his sister. They honeymooned in Switzerland and returned to a house Cantor had built with the inheritance from his father. It would be the birthplace of their 5 children over the next 12 years. Cantor's growing family must have made financial demands on a professor paid at relatively meagre provincial standards. Hoping to alleviate these problems, Cantor sought a professorship at his alma mater in Berlin. Cantor's work on transfinite numbers had drawn wide praise in the world of mathematics, praise that he hoped would win him an appointment at a prestigious university such as Berlin. Weierstrass, his old mentor, had been particularly full of praise for Cantor's work, but there were pockets of those opposed to any talk of actual infinities. Among them was Leopold Kronecker, a high-ranking professor in Berlin. Mathematics, according to Kronecker, dealt with constructions, precisely what Cantor and Dedekind had avoided in their treatment of the infinite. In spite of Weierstrass' efforts, Kronecker was able to block all attempts to get Cantor a mathematics professorship at Berlin. Just before turning 40, the combination of personal and professional stresses became too much for Cantor to bear. He had his first bout of deep mental depression, spending a few weeks in a sanitarium. After his release, Cantor wrote to a fellow mathematician, "I don't know when I shall return to the continuation of my scientific work. At the moment I can do absolutely nothing with it, and limit myself to the most necessary duty of my lectures. How much happier I would be to be scientifically active, if only I had the necessary mental freshness." Indeed, Cantor's best years as a mathematician had ended. Perhaps recognizing this, Cantor devoted significant energy to building an association of mathematicians across the newly unified Germany. He served as its first president from its founding in 1890 until 1893, when he had his next round of depression. Cantor would be in and out of mental hospitals for the last 25 years of his life, fighting depression. In 1894, he published an exceptionally strange paper for a mathematician of his renown. While in the mental hospital, he had become fascinated by Goldbach's famous conjecture that every even number could be expressed as the sum of 2 primes. In 1894, he published a paper demonstrating all of the ways that even numbers up to 1,000 could be written as the sum of 2 primes. 40 years after, an obscure mathematician had done the same for all of the even numbers up to 10,000. As the years went on, Cantor's mental state got worse and worse. In these later years, he devoted himself to the study of Shakespeare. He even attempted to prove that the bard and the philosopher Francis Bacon were one and the same person. The German mathematical community had planned to have a major celebration in 1915 in honor of Cantor's 70th birthday. However, the privations of World War I made that impossible. Cantor entered a mental hospital for the last time in June 1917. On January 6, 1918, he died, unaware that Imperial Germany would also perish by the end of the same year. And then we're off. Selections from contributions to the founding of the theory of transfinite numbers. First article. The conception of power or cardinal number. Greater and less with powers. The addition and multiplication of powers. Exponentiation of powers. The finite cardinal numbers. The smallest transfinite cardinal number, Aleph 0. Ordinal types of simply ordered aggregates. Addition and multiplication of ordinal types. The ordinate type, what is that, n? I'm not sure what that number is. The ordinal type of the aggregate R of all rational numbers which are greater than 0 and smaller than 1 in their natural order of precedence. The fundamental series contained in a transfinite ordered aggregate. The ordinal type theta of the linear continuum X. Contributions to the founding of the theory of transfinite numbers, second article. Well-ordered aggregates. The segments of well-ordered aggregates. The ordinal numbers of a well-ordered aggregates. The numbers of the second number class Z, Aleph null. The power of the second number class is equal to the second greatest transfinite cardinal number, Aleph 1. The numbers of the form. The powers gamma to the power of alpha in the domain of the second number class. The normal form of the numbers of the second number class. The epsilon numbers of the second number class. Alright, so now we're up to Henri Lebesgue, 1875 to 1941, his life and work. I remember once hearing a story about a historian of Babylonian astronomy whose colleagues asked him for help interpreting an ancient astronomical manuscript. He stroked his beard for a while and pondered the odd symbols on the manuscript his colleagues had placed in front of him. Then suddenly he began to explain the manuscript to his colleagues as he rotated it 90 degrees from portrait mode to landscape mode. Henri Lebesgue made just such a change in perspective for the theory of the integral. On June 28, 1875, Henri Lebesgue was born into a middle-class family in the town of Beauvais, some 50 miles north of Paris. Henri grew up in a home that encouraged intellectual pursuit. Although his father was a typesetter and his mother an elementary school teacher, they had a remarkable library that allowed young Henri to read widely. The local schools soon recognized his brilliance and arranged for local philanthropies to finance his education when his father died of tuberculosis. Lebesgue had an outstanding academic record, first at the local Collège de Beauvais, and then in Paris at the Lycée Saint Louis, and then at the Louis le Grand. In 1894, at the age of 19, he entered the prestigious École Normale Supérieure in Paris. While at the school, Lebesgue often indulged himself in his mathematical studies, neglecting other subjects that interested him less. His diary revealed that he only managed to pass a chemistry examination by speaking in hushed tones to his deaf examiner and not writing anything on the blackboard. Lebesgue graduated in 1897 for the 2 years following his graduation, Lebesgue worked at the school's library and began his attack on a new theory of measure and the integral as he pursued his graduate studies at the Sorbonne. Lebesgue secured a teaching position at the Lycée Central in Nancy, near the German border. While in Nancy, Lebesgue finished the development of the ideas that blossomed into the dissertation for which he received a doctorate from the Sorbonne in 1902. It was immediately published by the Annales de Mathematica of Milan and hailed as a revolutionary breakthrough. Prior to Lebesgue, mathematicians believed that Riemann had developed the theory of the integral as completely as possible. In previous selections, we have seen that Cauchy and then Riemann had based a theory of the integral on the process of partitioning the x-axis and taking a value of the function fx somewhere in each of the segments of the partition. Lebesgue's great insight was to partition the y-axis rather than the x-axis in much the same way that Cauchy and Riemann had partitioned the x-axis. Having partitioned the y-axis, Lebesgue then considered each element of the partition and proceeded to take the measure of the portion of the x-axis that the function being integrated mapped into the element of the partition. Here is an example. Consider the interval yn and yn plus 1, one element of a partition of the y-axis. In this example, the set of points on the x-axis that take a value in the interval yn plus 1 forms the set Mn. In order to determine the contribution of the interval yn plus 1 to the Lebesgue integral being evaluated, Lebesgue multiplies the measure of the set Mn and any value in the interval yn plus 1. Using Weierstrass's rigorous epsilon delta method, Lebesgue says that if a limit exists as the size of the widest element of the partition of the x-axis approaches 0, then that limit is the value of the Lebesgue interval being evaluated. By defining the integral in this manner, Lebesgue had reduced the theory of the integral to the theory of measure. If we consider the problem from a geometrical perspective, we see that Lebesgue had reduced the problem of determining the area of a two-dimensional object to the problem of determining the measure of a set of points embedded in the one-dimensional real line. Lebesgue's seminal paper, a large portion of which is presented here, he first addresses the topic of measuring a set of points embedded in the one-dimensional real line and then progresses to his theory of the integral. Lebesgue begins by enunciating properties a measure must have to satisfy our intuitions. The measure of the interval AB, that is, the set of real numbers x such that a is less than equal to x and x is less than equal to b, is simply the value b minus a. If the set of real numbers En are pairwise disjoint, i.e. no two sets have any points in common, then the measure of the union of En is equal to the sum of the measures of the interval En, of the individual En. If a set of real numbers E has measure m, then the set of points formed by adding the constant value a to every real number in E results in a set denoted by E plus a that also has measure m. Before defining a set's measure, Lebesgue first defined its outer measure and its inner measure. If a set has an outer measure and an inner measure, and if these values are identical, then the value is the measure of the set. A set's outer measure is defined in terms of coverings of intervals that form a superset of the set being measured. That is, the set in question is a subset of the union of the intervals that form the covering. Each interval in a covering has a measure, and the sum of these measures may be finite. Since a bounded set can always be covered by the entire bounded interval, Lebesgue recognized that the sum of the measures of the coverings of a bounded set always have a finite lower bound. This lower bound is the set's outer measure. Lebesgue demonstrated that the rationals have outer measure of 0 by employing Cantor's demonstration that the rationals can be enumerated and enclosing the nth rational number in a closed interval of width, that is, measure epsilon to the power of n. Summarizing the measures of all these intervals results in epsilon, which can be made as small as desired. Thus the rationals have an outer measure of 0, which makes them a measurable set of measure 0. Lebesgue defined the inner measure of the set E bounded by the interval AB in terms of the outer measure of the set of points contained in the interval AB less the set of points contained in the set E, to wit, the inner measure of the set E bounded by the interval AB is the measure of the interval AB minus the outer measure of the set of points contained in the interval AB less the set of points contained in the set E. This is written as shown, where measure of I is an inner measure and measure of E is an outer measure. Using Lebesgue's definition, it becomes readily apparent that the set of irrational numbers in the unit interval O1 has inner measure 1, and as a result of the rational numbers of the set of rational numbers in the unit interval O1 having outer measure 0. An immediate consequence is that the set of irrational numbers in the unit interval O1 has measure 1, and the set of rational numbers in the unit interval O1 has measure 0. With this radically different approach to the theory of the integral, a wide range of functions became integrable and fell within the embrace of mathematical analysis. The most obvious example of a function that is Lebesgue integrable but not Riemann integrable is xx. I'm still not sure what that symbol is. Give me a second. Okay, so that symbol there that looks like an italic capital X, it's actually a lowercase chi, which is a Greek letter. So chi x equals 1 if x is rational, chi x equals 0 if x is irrational. This function is not Riemann integrable because every element of a partition of the x-axis, no matter how fine-grained, will contain infinitely many rational numbers and infinitely many irrational numbers. Thus, the Riemann sums can never converge. On the other hand, the only elements of a partition of that matter for determining a Lebesgue integral are the elements including the values 0 and 1. As we have seen, the set of points on the x-axis that chi x maps to 1 has measure 0. The measure of the irrational in any interval considered is the width of the interval. Therefore, the Lebesgue integral of chi x over any interval AB is simply 0. With the publication of his dissertation, Lebesgue quickly had his choice of academic appointments. In 1902 to 1903, he taught at the University at Rennes. I don't know how to pronounce it. A year later, he moved to the Collège de France in Paris, where he remained for 3 years until he accepted a position at the University of Poitiers. In 1910, the mathematics faculty at the Sorbonne appointed him maître de conferences, lecture master. When France entered World War I, Lebesgue immediately offered his services to the Ministry of Defense, which put him to work determining how frequently troop trains should run to the front lines. Following the war, with Sorbonne promoted Lebesgue to a full professorship, which he held for only 3 years until he accepted a chaired professorship at the Collège of France. Lebesgue remained in this position for the rest of his career. Although his ideas revolutionized mathematical analysis, Lebesgue himself had very little personal influence on the mathematical community. Uninterested in politics, inside or out of the academy, Lebesgue seemed content to give his lectures, write his articles, and lead a solitary life. Oh man, I hear that. In spite of the prominence of his work, he supervised only one doctoral dissertation during his career. The French mathematical community had the good sense to recognize the importance of his contributions. Lebesgue received the Prix Hullovich, I don't know what that means, in 1912, another one in 1914, and another again in 1917, and then another one in 1919, some sort of award. His 1922 election to the Academy of Sciences topped the list of honours he received. Lebesgue lived such a modest life that very little is known of his family life. While at Rennes in 1903, he married Louise Marguerite Vallée, the sister of a fellow student at the École Normale Supérieure. They had a daughter named Suzanne and a son named Jacques, before they divorced in 1916 after little more than a dozen years of marriage. Lebesgue lived alone for the rest of his life, often suffering from ill health. Dispirited by the German occupation, he died on July 26, 1941, at the age of 66, following a short illness. And here we go, selections from Integral, Length and Area. Introduction. Chapter 1, Measure of a set. The elements of a set are points on a straight line. Chapter 2, Integrals. Definite integral of functions with one variable. Indefinite integrals and primitive functions of functions with one variable. Alright, now we're up to Kurt Gödel. I think it's just Gödel and Turing and we're done. So we're going for the finish line. I'm going to get this finished. I think it's going to go over 12 hours, so I'm going to have to do something about culling some of it. Maybe I'll just speed up the playback or something. Anyway, let's get these 2 chapters read and then I'll go and figure out how to turn it all into one video of 12 hours. So this is chapter on Kurt Gödel, 1906 to 1978, his life and work. Mathematicians are well known for their eccentricities. The film and book A Beautiful Mind portrays the eccentricities of the mathematician John Forbes Nash during his time at MIT and Princeton. Although Nash might have been the most eccentric mathematician during his days at MIT, he certainly was not the most eccentric mathematician at Princeton. That honour undoubtedly belongs to Kurt Gödel, the greatest mathematical logician of all time, and certainly the maddest. The very same mind, able to prove some of the deepest results of modern mathematics, was also a lifelong hypochondriac who saw conspiracies behind every door. Kurt Gödel was born on April 28, 1906 in Brno, Moravia, then a province of Austria-Hungary, now part of the Czech Republic. He was the second of 2 sons born to Rudolf and Marianne Gödel, Protestant ethnic Germans. No one on either side of Gödel's family had ever shown a significant aptitude for math or science. Kurt Gödel did. Gödel sped through the early years of his education, taking only 4 years to complete the equivalent of the first 8 years of schooling. He entered the Real Gymnasium, the equivalent high school, in 1918, just as Czechoslovakia became an independent nation following the end of World War I. Gödel almost always received top marks throughout his schooling. Ironically, the only time he received less than a top mark was in maths class. Nothing survives from those early years to indicate the greatness Gödel would achieve. Given the Gödel's German ethnicity, it is not surprising that in the fall of 1924, Kurt followed his older brother Rudolf to the University of Vienna, about 70 miles north from Brno, where Rudolf was studying medicine. Gödel originally intended to pursue a career in physics. From the collection of library slips he saved, he was an inveterate pack rat, we know that Gödel read many physics texts during his years at Vienna. Vienna hosted much intellectual ferment during the 1920s. A group of scientists and philosophers who called themselves the Vienna Circle met on a weekly basis, attempting to set both mathematics and the physical sciences on a firm philosophical foundation. In 1926, Gödel's mentor, the mathematician Hans Hahn, invited him to attend the Circle's meetings. Gödel did, and undoubtedly turned his attention from physics to logic. In 1900, David Hilbert, the world's most eminent mathematician, delivered an address to the Second International Congress of Mathematics in Paris, at which he presented 23 problems, from the discussion of which an advancement of science may be expected. Hilbert's first problem was to determine the cardinal number of the continuum of real numbers, that is, to solve Cantor's continuum problem, presented in chapter 14. Hilbert's second problem was to demonstrate the consistency of the axioms of arithmetic that form the foundations of mathematics. Gödel completely solved Hilbert's second problem with an entirely unexpected answer. He also achieved the first substantial result in response to Hilbert's first problem. Gödel's library slips show that his interest definitely turned from physics to logic between the summer and fall of 1928 as he was seeking a topic for his doctoral dissertation. Gödel chose the completeness of the predicate calculus as his topic. The predicate calculus introduces universal quantifiers for all x and existential quantifiers, there exists an x, into logic. This allows formalization of Aristotle's logic, for which the assertion all men are mortal is a typical example. In the predicate calculus, this is expressed as, for all x, if x is a man, then x is mortal. A typical theorem of the predicate calculus is, there exists an x such that property of A holds for x and property of B holds for x, implies that there exists an x that property A holds for x and there exists an x such that property B holds for x. Gödel's doctoral dissertation demonstrated a twofold result: the completeness of the predicate calculus, namely that all true propositions can be proven, and the consistency of the predicate calculus, namely that only true propositions can be proven, otherwise it would be inconsistent. Gödel worked on his doctoral dissertation for the first half of 1929, even when his mother and Aunt Anna moved in with his brother Rudolf and him following the sudden death of Gödel's father in February. Gödel's advisors approved his dissertation on July 6, 1929, and he received his PhD 7 months later in February 1930. Gödel's completeness theorem won him some recognition from the mathematical community. It solved a problem that had been posed by a prominent mathematician in the expected manner. In the Austro-German university environment of that era, a doctoral dissertation and PhD degree were not sufficient to take up a university position. An additional piece of research called a habilitation was needed. Gödel sought a more challenging problem for his habilitation: to demonstrate the consistency of the axioms of arithmetic, the foundations of mathematics. Gödel set out on the journey leading to his habilitation in early 1930 and finished by early fall of that year. Like Columbus, his journey led him far from his expected destination. Following Hilbert, Gödel took the axioms of the Italian mathematician Giuseppe Peano as his foundation for the formal arithmetic of the natural numbers. Axiom 1, 0 is a natural number. Axiom 2, every natural number n has a successor, informally n plus 1, that is also a natural number. Axiom 3, no natural number has 0 as its successor. Axiom 4, different natural numbers have different successors. 5, if for some property P holds for 0, and if it holds for a natural number n, then P also holds for n successor, and P holds for all natural numbers. In his habilitation, Gödel demonstrated the incompleteness of formal arithmetic. He showed that in any such formal system, there always exists a statement that cannot be proven within the system, even though its truth is apparent. If formal arithmetic is consistent, then that consistency cannot be proven within formal arithmetic itself, as Hilbert had sought. In the process, Gödel clearly distinguished provability from truth. This is the work of Gödel's presented in this volume. Gödel's remarkable results rests on two cornerstones. The first is Gödel numbering, the assignment of natural number values to each sequence of terms in the formal system. Consider the simple statement: 0 equals 0 prime, or 0 equals the successor of 0, that is 0 equals 0 plus 1. Suppose that the following odd numbers have been assigned to the three terms appearing in this statement. 0 is 23, equals is 15, and prime is 21. Then the number 2 to the power of 23 times 3 to the power of 15 times 5 to the power of 23 times 7 to the power of 21 uniquely expresses the sequence of terms 0 equals 0 prime. Literally, it says that the first and third terms are 0, the second term is equal, and the fourth term is prime. Gödel then shows how to recognize the Gödel numbers of valid proofs inside the formal system. The second cornerstone of Gödel's incompleteness theorem is a formalized version of the statement: this statement is unprovable, that asserts its own unprovability. This is a subtle variation of a form of the liar's paradox: this sentence is false, that goes back to ancient Greece. The sentence in the liar's paradox can neither be true nor false without leading to absurdity. By focusing on provability rather than on truth, Gödel's sentence avoids the paradox. If formal arithmetic is consistent, meaning that only true statements can be proven, then Gödel's statement must be true. But if it were false, then it could be proven, contrary to the consistency. Furthermore, it cannot be proven because that would demonstrate just the opposite of what it asserts, its unprovability. Moreover, Gödel showed that if the consistency of the formal system could be demonstrated inside the system itself, then the informal argument just given could be formalized, and the formalized version of the statement, this statement is unprovable, would itself be proven, thereby contradicting itself and demonstrating the inconsistency of the system. Gödel's two incompleteness theorems were published in March 1931. They made an immediate impact throughout the mathematical community. Hilbert was at first angry to learn that his grand scheme for securing the foundations of mathematics had been shown to be impossible. However, Hilbert's assistant, Paul Bernays, convinced him that Gödel had achieved a truly important advance. They also had an impact on Gödel's career. Gödel submitted this work as his habilitation a year later, allowing him to take up a paid position at the university. More importantly, his work drew attention in the American mathematical community that led to an invitation for Gödel to be a visiting scholar at the newly founded Institute for Advanced Studies at Princeton, New Jersey. Gödel was one of 24 visiting scholars at the institute during 1933 to 1934, its first year of operation. Albert Einstein was one of the Institute's 8 original permanent faculty members. Gödel and Einstein met during Gödel's first year at the Institute but did not become close friends for nearly another decade. Gödel returned to Vienna in tumult after an uneventful year in the peace and quiet of Princeton. Just a month after his return, a band of Nazis stormed the chancellery and assassinated the Austrian president. After his return, Gödel's physical health declined in parallel to Austria's political well-being. He suffered from a toothache all summer long. By October, he complained of mental exhaustion and needed to spend a week convalescing at a sanitarium outside of Vienna. Gödel regained some measure of health in September 1935. He returned to the Institute in Princeton for another year's visit. However, within 2 months' time, he once again fell into the throes of depression and in November decided to return to Vienna to recuperate. This time, he needed several months in a sanitarium to recover. After his recovery, Gödel began to work on the third great achievement mentioned earlier, a partial solution to Hilbert's first problem of determining the cardinal number of the continuum of real numbers. Cantor had conjectured that the power of the continuum, LF1, the second transfinite cardinal. By 1938, Gödel proved that if set theory is consistent, then adding the axiom that LF1 is the power of the continuum does not make it inconsistent. Gödel would visit America one more time before the start of World War II. He had a good reason for his inability to leave for America in September 1938, in time for the start of the academic year. In that month, Gödel finally married the only woman with whom he ever formed a romantic attachment, Adele Nimsberger, née Paquette. Kurt first met Adele in late 1928 or early 1929 while working on his dissertation. Both of his parents immediately objected to his relationship with Adele. Kurt was only 22 years old. She was 29, about to be divorced, a lower-class Catholic, and worst of all, in their eyes, she worked as a nightclub dancer. Little is known of their courtship. In contrast to the voluminous store of the most insignificant minutiae he saved during his life, not a single letter or card has been found from Gödel's nearly decade-long courtship. The marriage came as a complete surprise to Gödel's closest friends. They were completely unaware of Kurt and Adele's relationship. Adele was Kurt's protectress, putting up with his ways and taking care of as much of his personal life as she could. Unknown to Gödel's family, Adele had frequently visited him during his stay at the sanitarium in 1936, often tasting his food. Unfortunately for Kurt, Adele could only take care of domestic matters. Gödel's last visit to America before World War II reveals the manner in which Gödel often ignored his own affairs. He should have informed his dean of faculty at Vienna that he was taking a leave of absence before he left. Characteristically for the eccentric Gödel, he waited until the very end of October to do so. Gödel also let his authorization to teach at the University of Vienna lapse while he was in America. In June 1939, Gödel returned to a thoroughly Nazified Austria. Following Germany's annexation of Austria and the Anschluss of March 1938, Gödel and his wife had automatically become German citizens. Shortly after his return from America, the Reich served him with a notice to report to his draft board. The German army classified Gödel as unfit for combat, but fit for garrison duty behind the lines. Fortunately for Gödel, the Nazis never learned of his hospitalizations for depression. If they had, they might have sent him to a concentration camp rather than classify him as fit for garrison duty. Gödel, of course, no longer wanted any part of Austria or Germany and sought to leave permanently to reside in the United States. Throughout the fall of 1939, as the German army raced through Poland, the Institute for Advanced Study and Gödel attempted to negotiate American entry visas and German exit visas for both Gödel and his wife. The Institute director coyly wrote a letter to the German embassy in Washington urging that Gödel was an Aryan and one of the greatest mathematicians in the world, and that surely the German government would consider it more important for Gödel to continue his mathematical work than to serve in the army. The Gödels finally secured all of the necessary travel documents in January 1940. They feared taking the direct route to America across the North Atlantic. The British might attack and sink their ship. If the British captured them, they would be interned because they were German citizens. Consequently, the Gödels came to America the long way round. They took the Trans-Siberian Railway to Vladivostok, one ship to Yokohama, Japan, and finally an American flagship to San Francisco. All told, the journey took 7 weeks. When an American immigration official asked Gödel if he had ever been a patient in a mental institution, Gödel wisely and falsely replied no. Ironically, all of Gödel's great mathematical achievements had been accomplished by the time he took up permanent residence in the institute in 1940. One great scientific achievement remained. In the late 1940s, Gödel turned his attention to cosmology. In anticipation of a paper in a volume honoring Einstein, Gödel constructed a rotating model of the universe that satisfied Einstein's equation. Gödel showed that in such a rotating universe, there can be no privileged notion of universal time that can be regarded as absolute all throughout the cosmos. Indeed, in such a rotating universe, closed, time-like lines, that is, travel into the distant past, is theoretically possible. Like his incompleteness theorems, this result upsets previously held expectations. Gödel and Einstein became close friends when Gödel returned to Princeton. In many ways, they were polar opposites. Gödel was cold and aloof, very serious, and suspicious of common sense. Einstein was warm and affable. Perhaps Einstein recognized Gödel's need for someone to take care of him. Einstein may also have valued Gödel's willingness to help Einstein may also have valued Gödel's willingness to engage in intellectual disagreements with him. For example, Gödel doubted that a unified theory of quantum mechanics and gravitation could ever be achieved. This was the focus of Einstein's intellectual efforts in his later years. Einstein played a role in one of the strangest and most amusing incidents in Gödel's life. Gödel became an American citizen in December 1947. He studied diligently for his hearing, much more diligently than necessary. The economist Oscar Morgenstern, one of his closest friends, noticed Gödel becoming more and more upset as the hearing date approached. Morgenstern simply thought that Gödel was nervous in anticipation of the hearing. A few days before the hearing, Gödel confided to Morgenstern that he had found a serious flaw in the American Constitution. The president could fill vacancies without Senate approval while the Senate was in recess. This, Gödel reasoned, could lead to a dictatorship. Morgenstern realized that he and Einstein needed to persuade Gödel that pursuing this point during his citizenship hearing might well jeopardize his chances of being granted citizenship. Einstein joined Morgenstern, who drove Gödel to Trenton for the hearing. During the drive, Gödel's two friends tried to persuade him to stay away from this topic, but they failed. When Judge Philip Foreman asked Gödel whether a dictatorship similar to the one in Germany could arise in the US, Gödel, following his inclination to focus on the logical rather than the practical, answered in the affirmative and began to expound the supposed flaw in the Constitution. Fortunately for Gödel, Judge Foreman, who had also presided at Einstein's citizenship hearing, found Einstein's presence to be sufficient reference for Gödel and quickly steered him to other topics. Gödel's mental and physical well-being deteriorated significantly over the last 30 years of his life. He became even more reclusive and more of a hypochondriac. He began to eat even less. At times he would refuse to leave his home when distinguished European mathematicians visited Princeton, fearing that they might be intent on killing him. In his later years, Gödel would sometimes see visitors in his house during the afternoon. He always made sure to ask his wife to interrupt after 30 minutes to remind him that it was time to take his nap. I once heard a British philosopher repeat this story with a surprising twist. When Adele came in to tell Kurt that it was time to take his nap, Gödel replied, "But I like this man." Gödel gave his last public lecture in 1951. After 1952, he published nothing except revisions of earlier work. His notebooks show that he attempted to continue his work during the 1950s and 1960s, but failed to accomplish any finished results. He kept abreast of developments in logic and set theory through 1960s. Most notable among these was Paul J. Cohen's 1963 proof that the axioms of set theory could be consistently extended by supposing that the power of the continuum takes a power other than Aleph-1. In other words, the independence of Cantor's continuum hypothesis from the axioms of set theory. Gödel withdrew more and more from the life of the Institute during the last decade of his life. Most of the members who were there when he arrived had long since died. His notebooks reveal that he expended almost all of his intellectual energy on two problems. The first of these problems attempted to continue his earlier accomplishment on the continuum hypothesis. Gödel believed that the true power of the continuum was Aleph-2, the next cardinal number after Aleph-1. He tried in vain to find axioms for set theory from which this power of the continuum could be derived. The second problem, consuming Gödel, was completely different from anything else he had ever worked on. He attempted to formalize St. Anselm's ontological proof of the existence of God. Many mathematicians experience a decline in their mathematical output as they age, as Gödel did. Few experience deterioration in their mental and physical health as he did. Gödel was always obsessed with his diet and health, especially with his bowel movements. Starting in 1946, he recorded his daily consumption of laxatives. In 1951, Gödel needed to be hospitalized to treat bleeding ulcers. After his discharge, he put himself on a very strict diet that included 1/4 pound of butter, 3 whole eggs, and 2 egg whites a day. He hardly ever ate any meat. Late in 1954, Gödel suffered another serious bout of depression. Undoubtedly, his recovery from these episodes must be ascribed to Adele's tender loving care. Throughout the 1960s, Gödel's physical and mental health remained precarious but not life-threatening. All that changed again in early 1970 when he once again became paranoid about his health and ate even less than before. According to Morgenstern, Gödel looked like a living corpse. Unfortunately for Gödel, his wife Adele, who was 6 years older than him, began to suffer from her own serious health problems, including a series of small strokes. She was no longer able to take care of him. Gödel entered the hospital for the final time just after Christmas 1977. He died on January 11, 1978, weighing only 65 pounds. The death certificate testified to the fact that he had starved himself to death. Gödel took on only the biggest problems, made decisive breakthroughs, and then left further developments to others. He never directed a graduate student during his career, and he never had a teaching appointment once he settled in America. Nevertheless, Kurt Gödel left his unmistakable imprint on the foundations of mathematics. On formerly undecidable proposition of Principia Mathematica and related systems. This is Gödel's famous paper, and after that we're going to have our chapter on Alan Turing, and then we'll have finished this book. I'm annoyed because it's gone. I've run over 12 hours, I'm pretty sure, so I'm going to have to speed it up or something. I'm not sure what I'm going to do. Anyway, here we go. Alan Matheson Turing, 1912 to 1954. His life and work. As the American physicist J. Robert Oppenheimer waited to testify in front of a congressional committee about to strip him of his top-secret clearance, Oppenheimer's friend and colleague Isidore Rabi tried to console him. Rabi told him, "Oppie, if this were Britain, you would have been given a knighthood for your work on the atomic bomb." If Oppenheimer deserves the leading credit for bringing the war in the Pacific to a close thanks to his work leading the Manhattan Project, then Alan Matheson Turing deserves a similar leading credit for bringing the war in Europe to a close earlier than later thanks to his work in decoding Enigma, the Nazis' encryption machine. Turing received an honour below a knighthood following World War II. A knighthood would have required public acknowledgement of Turing's cracking of the Enigma code, something the British kept hidden from the public for well after 25 years, long after Turing's death. Ironically, this honour provided Turing no help when he was arrested for acts of gross indecency. Instead, it accentuated his violation of public morals. Not only had he committed acts of gross indecency, but he had done it with someone from the working class. Alan Turing came from a family of modest distinction. The Turings could trace their ancestry back to a 14th century family of Aberdeenshire in northern Scotland. They must have been supporters of the Stuart dynasty, who came south to England when James I ascended to the throne in 1603. Charles I awarded a baronetcy to Sir John Turing in 1638. Sir John nearly paid for the honour with his head during the English Civil War. Turing's mother, Ethel Stoney, came from a Protestant Irish family that received its land holdings from William of Orange in 1688. A distant cousin, George Johnston Stoney, coined the term electron in 1894, just as the atomic era dawned. Ethel's father, Edward Stoney, had a distinguished career building railways and bridges for the British Raj in India. She met Alan's father, Julius Matheson Turing, on a sea voyage from India in the spring of 1907. He had made a career in the Indian civil service after receiving his degree at Oxford. They married that October and returned to India in the new year, where their first child, John, was born in September. Alan, their second child, was born in London on June 23, 1912, while the whole family was on leave in England. Britons in the employ of the Indian civil service lived a life with benefits and costs. While in India they lived in near luxury, much better than they could back home. But India was not Britain, especially when it came to children who often spent long stretches back home without one or both parents. Such was the life of young Alan, whose father returned to India when he was 9 months old. His mother returned to India 6 months later, leaving her 2 sons with the Wards, an unrelated retired army couple in a small town near Hastings. The Wards had little time for the Turing boys. They had 4 daughters of their own. Colonel Ward was stiff and remote, and Alan disappointed Mrs. Ward when he failed to show an interest in military toys. And so it was for Turing growing up with his parents in faraway India during most of his formative years. As luck would have it, Julius Turing resigned from the Indian Civil Service in 1926, just as Alan entered Sherborne, one of the older public boarding schools in England. Alan never quite fit in at Sherborne. At the end of his first year, Alan's headmaster wrote to his parents, "He should do very well when he finds his métier, but meanwhile he would do much better if he would try to do his best as a member of this school. He should have more esprit de corps." Alan complimented his poor showing on the playing fields with equally poor showings in the classroom, ranking at the bottom of his non-science classes for his first year and a half. But mathematics and science were another matter. Alan soon began to excel in these classes, and a fortunate case of the mumps during the second half of his second year gave him the opportunity to pursue these subjects while paying much less attention to the others. While in the school sanitarium, he read Einstein's popularized accounts of his theories of special and general relativity. While at Sherborne, Turing developed a deep, intimate bond with Christopher Morcom, a student a year ahead of him. Morcom was everything that Turing was not. He excelled in all of classes and won many school prizes. They had a shared passion for mathematics, which they each hoped to pursue at Trinity College, Cambridge, in the College of Isaac Newton and Bertrand Russell, the very centre of English mathematics. In December 1929, they took the Trinity Scholarship exams. Christopher passed with flying colours. Alan did not. He was distraught at the thought of being at another Cambridge college, unable to share rooms with Christopher, but there would be no time together at Cambridge. In February 1930, Christopher suddenly became ill and died from complications of tuberculosis, a disease he had contracted as a young boy. Christopher Morcom's death left Alan Turing utterly alone. While his parents only abandoned him for a year or two at a time, Christopher had abandoned him forever. Turing resolved that he would have to go to Cambridge and, by himself, achieve enough for the two of them. He did. Turing finally won a scholarship to King's College, Cambridge, where he matriculated in the autumn of 1931. In many ways, King's was a much better match for Turing than Trinity would have been. The College of John Maynard Keynes and E.M. Forster, King's was not as hidebound to tradition as Trinity. Its dons even went out of their way to mix with the students. Doing mathematics at Cambridge was a joy to Turing. He was finally in an environment where the qualities stressed by Sherborne class, sports talent, or charm did not matter. The only thing that mattered was mathematical ability, and Alan Turing had that in trumps. For his undergraduate dissertation, Turing developed a new proof of the central limit theorem of probability, and he passed his baccalaureate examinations with marks of distinction. These accomplishments earned him a stipend to do postgraduate work at King's, and this led to his greatest mathematical achievement in 1936. His 1936 paper on computable numbers with an application to the Einstein problem, reproduced here. In 1928, the German mathematician David Hilbert, the greatest mathematician alive, repeated 3 challenges to the world of mathematics that he had first made at the Great Mathematical Congress held at Paris in 1900. 1. To prove that all true mathematical statements could be proven, that is, the completeness of mathematics. 2. To prove that only true mathematical statements could be proven, that is, the consistency of mathematics. 3. To prove the decidability of mathematics, that is, the existence of a decision procedure to which the truth or falsity of any given mathematical proposition. Late in 1934, Turing learned that Kurt Gödel had proven the first 2 of these challenges. The third challenge remained. Turing set out to answer it, working on it from the spring of 1935 to the spring of 1936. In order to do so, he needed to make precise the notion of a decision procedure. He needed to formalize it. Perhaps inspired by a childhood interest in typewriters, Turing did this by expressing the concept of a decision procedure in terms of machines now known as Turing machines. Turing recognized that typewriters can only write onto a sheet of paper. They have no ability to interpret the sheet of paper. That is left to the human typist. Turing realized that to eliminate the human component, the machine needed to be able to read input as well as write output. Abstracting and simplifying as much as possible, Turing supposed that his machine operated on a tape composed of a square that could either contain a mark or be blank. The tape extended indefinitely to the left and to the right. Turing gave the machine the ability to read the tape, to write a mark on the square, and to erase the mark on the square. In order to avoid human intervention and be purely mechanical, it was necessary for each combination of the machine's configuration and symbol scan, the machine's construction would determine whether to write a symbol in a blank square, erase a symbol found in a square, or neither write nor erase the square, whether to remain in the same configuration, i.e. set of rules, or to change to another configuration, and whether to move to the left, move to the right, or stay in place. Writing out all of this information, defining an automated machine, would create a table of behavior of a finite size that would completely define the machine's behavior. From the abstract perspective, the table was the machine. There could be many such tables, each defining a machine with different behavior. A fairly simple machine could mechanically emulate the process of adding 2 numbers. Suppose each number is represented as consecutively marked squares on the tape, and the 2 numbers are separated by an empty square. The machine starts on the leftmost marked square of the 2 numbers. It moves right, leaving symbols in place as they are found, and then writes a symbol when it encounters the first empty square, which represents the end of the first number and the start of the second. Now change the configuration to the following set of rules. Keep moving right, leaving symbols in place as they are found in marked squares until coming to an empty square. This marks the end of the second number. Move left and erase the symbol found. A Turing machine with a slightly more complicated table of behaviors can be defined to multiply 2 numbers. But these were simple processes. Turing realized that, in contrast, a decision-making machine of the sort required by Hilbert's decision problem could not be directly constructed. At most, its existence could only be inferred. And if no such machine existed, that could only be inferred, perhaps by taking an inventory of all such machines, and if no such machine existed that could only be inferred, perhaps by taking an inventory of all such machines, which is precisely what Turing did. I'm not sure if that sentence was grammatical. Anyway, we're almost finished. He supposed that all of the machines were put in some definite order. He then realized that a square with a symbol written on it could be interpreted as 1, and an empty square could be interpreted as 0. Having made these interpretations, the machine could be interpreted as generating tapes of 0s and 1s. Supposing these sequences of 0s and 1s to be preceded by a decimal point, Turing was able to interpret each of the machines as a real number in binary form between 0 and 1. Turing called these numbers computable numbers, and he turned to Cantor's diagonalization procedure to produce a real number that was not a computable number, a real number different from every number in the table. Such a number could not be the output of any of the machines that had been listed. It was an uncomputable number. But Turing was not done. Perhaps the very process of Cantor diagonalization was itself a mechanical procedure that was nothing more than computing the first square using the table for the first machine, and then changing its value. Then changing to the table for the second machine to compute the second square, and then changing its values, and so on, ad infinitum, using the table for the 2,241,985th machine to compute the 2,241,985th square and changing its value ad infinitum. But Turing realized this supposed that the nth machine actually got as far as the nth square, and there was no guarantee that the nth machine wouldn't get into a loop and never get to the nth square. In the absence of a decision procedure, whose very existence was in question, there was no way to examine the table for the machine and tell whether it would get into a loop or not. The only way to tell if a given machine had a loop would be to let the machine execute until it got to the nth square. However, that would need to be done for all of the machines that had been listed originally in order to show that the Cantor diagonalization procedure was itself mechanical. Doing this for all of the machines would require an infinite number of steps, not the finite number of steps required for the process to be mechanical in the sense defined by Turing. Therefore, the Cantor diagonalization procedure was not mechanical in the precise sense defined by Turing. Turing had shown that there was no decision procedure. In the space of 6 years, Gödel and Turing had shattered Hilbert's dream. Typically for Turing, this work on computable numbers was completely original rather than a derivative of someone else's groundbreaking result. In fact, it was so original that Turing didn't even know that the American logician Alonzo Church had arrived at the same result for Hilbert's decision problem by radically different means. Turing's proof was so revolutionary that the London Mathematical Society decided that only Church himself could referee the paper. Church not only refereed the paper, but also invited Turing to come to Princeton University to study with him. Turing's Cambridge mentor, Max Newman, approved. Princeton's mock Gothic architecture reminded Turing very much of his days at Cambridge. However, if Cambridge embodied class, then Princeton bespoke wealth, a wealth totally unfamiliar to Turing. The clock tower of its graduate college was an imitation of the clock tower at Magdalen, College, Oxford. Students jokingly called it the Ivory Tower, not because of the often ethereal intellectual activity it overlooked, but because it overlooked Proctor Hill, the graduate college's chief public room, built with a donation from William Cooper Proctor, a founder of the American company Procter & Gamble, the manufacturers of ivory soap. Within the confines of the mathematics department, Turing could pursue whatever he pleased. There was no need to conform. He felt at home in the department. Yet, in spite of John von Neumann's offer to stay on at the Institute for Advanced Study as a research assistant, Turing decided to return to England after receiving his PhD in 1938. He realized that America, in general, and Presbyterian Princeton, in particular, would not easily tolerate a nonconformist such as himself. In the summer of 1938, he returned to Europe on the brink of war. Before heading up to Cambridge, Turing stopped at the Government Code and Cipher School, GCCS, run by the Foreign Office to let them know that he had begun thinking about encryption and especially decryption techniques. When war broke out in September 1939, Turing left his Cambridge Fellowship and immediately reported to the faculty of GCCS and established in the small town of Bletchley Park, the town where the rail line from Oxford to Cambridge intersected the main rail line from London to the north. While at Bletchley Park, Turing had his only serious relationship with a woman. Joan Clark had been preparing for her final examinations for a Cambridge mathematics degree when she reported to Bletchley Park in June 1940. Her older brother had been at King's College, Cambridge, and she had once met Turing before the war. Turing began dating Joan in the spring of 1941. Working the same shift allowed them the opportunity to play chess or go to the movies together, even go on day-long cycling trips when they shared a day off. After a few months of dating, Turing proposed marriage and Joan immediately accepted.
Within a few days, Turing, already having second thoughts, told Joan of his homosexual tendency, expecting her to break off the engagement. To Turing's surprise, she did nothing of the sort and took him to London to meet her parents. Turing and Joan agreed to keep their engagement a secret from all but their closest confidants. She never wore her engagement ring at work, where they continued to address each other as Mr. Turing and Miss Clark. After several months, Turing realized that he could not go through with the marriage. He loved Joan, but it was in much the same way that he imagined he would love a sister, or perhaps in the same way that he loved Christopher Morcom's mother. There was deep affection, but not the same passion that he had felt towards Christopher. After breaking his engagement with Joan, Turing made sure that they never worked the same shifts. Turing could have resumed his Cambridge fellowship following the war and pursued a career in mathematics. However, the work on Enigma had given him a passion to build a brain. Cambridge was not the place to do this. The National Physical Laboratory in London was. After the war, von Neumann at Princeton and Turing each worked on projects to develop the first real computer. They each envisioned a computer containing stored instructions, but that is where their similarity ended. Von Neumann had intended that the instructions stored in the computer could not be modified. They could not be called as stored in a predetermined sequence. Turing went much further. He suggested that computers store a set of instruction tables that could be called as desired with the desired inputs. Turing had devised the art of programming an automatic electronic digital computer with internal program storage. While at the National Physical Lab, the British government awarded Turing the Order of the British Empire, OBE, for his war work. The OBE award had little impact on Turing. He was greatly relieved when the award ceremony was cancelled due to the King's illness. Having the letter painted on his office door only meant that he had to respond whenever someone asked him what he had done to win the award. In the end, he simply stashed the medal in a toolbox. Within 2 years of starting the computer project, Turing could see that it was running into bureaucratic quicksand. Realizing this was not for him, he fled London on an early sabbatical, retreating to the refuge of Cambridge, where he resumed his fellowship and taught mathematics for a year. While back at Cambridge, Turing began an erotic relationship with a third-year math undergraduate named Neville Johnson. At the end of the year, Neville graduated from Cambridge and moved away. So did Turing. Instead of going back to MPL at London, he accepted a position at Manchester University in the British Midlands, where his old mentor Max Newman was leading a team that had been making significant progress building a computer. Manchester's sheer shabbiness appealed to Turing. It lacked the airs of either Cambridge or Princeton. It also lacked Cambridge's tolerance for nonconformity. In 1952, Turing went to the Manchester police to report that he had been burgled in his home. The culprit was someone named Harry, an acquaintance of Turing's newly found homosexual partner. Being wiser in the ways of the world than Turing, Harry had assumed that Turing was an easy mark for robbery. As a homosexual, Turing had forfeited the protection of the law in the mid-20th century Britain, but Harry had miscalculated. Turing did go to the legal authorities. With Turing's naive help, the authorities identified Harry as the culprit and prosecuted him for burglary. Harry may have miscalculated, but Turing made a much more significant miscalculation. He fared far worse than Harry. The authorities charged him with the crime of gross indecency. Far worse, perhaps, was the fact that Turing had crossed class lines and become intimate with someone from the working classes. While he kept his sexual liaisons within the university, no one noticed outside its cloistered halls. Following his conviction, Turing chose to submit himself to estrogen therapy rather than a 2-year prison sentence. He preferred to give up his emotional desires rather than an environment conducive to intellectual pursuits. But he chose poorly. The estrogen therapy led to impotence, as intended, and severe depression. At one point, Turing remarked to a friend, "I'm growing breasts." Writing to another, he reformulated the liar's paradox as it applied to himself. Turing believes that machines think. Turing lies with men. Therefore, machines do not think. Turing committed suicide in 1954. We can only imagine what great works might have been in his future, and we can only imagine what the consequences for Britain and the free world would have been had Turing's ordeal occurred 15 years earlier, before he had led the effort that cracked the Nazi Enigma code in World War II. However, Turing had proven that no machine would ever be able to decide this question. On computable numbers with an application to the Einstein's problem. The Einstein's problem. Received May 28. 1936. Read 12th November 1936. Alright. Computing machines, definitions, automatic machines, computing machines, circular and circle-free machines, computable sequences and numbers, examples of computing machines, abbreviated tables, enumeration of computable sequences, the universal computing machine, detailed description of the universal machine, application of the diagonal process, the extent of the computable numbers, examples of large classes of numbers which are computable, application to the Einstein-Gun's problem, Lemma 1, Lemma 2, appendix, computability and effective calculability. The theorem that all effectively calculable, lambda definable sequences are computable and its converse are proved below in outline. It is assumed that the terms well-formed formula and conversion as used by Church and Kleene are understood. In the second of these proofs, the existence of several formulae is assumed without proof. These formulae may be constructed straightforwardly with the help of, e.g., the results of Kleene in A Theory of Positive Integers in Formal Logic. Okay. On computable numbers with an application to the Einstein-Gunn problem, a correction. So there was a correction. In a paper entitled On Computable Numbers with an Application to the Einstein-Gunn problem, the author gave a proof of the insolubility of the Einstein-Gunn problem of the Engere function. This proof contains some formal errors, which will be corrected here. There are also some other statements in the same paper which should be modified, although they are not actually false as they stand. There we go. There we go. So you had to fix some details. And here we are on page 1327 at the index. 1,327 pages. I started reading this book in October, and it is now the 1st of January the next year. This has taken me 2 or 3 months to get through this book. And the video is going to play longer than 12 hours, so I'm going to have to speed up some of it or something to get through it in one video's worth of size. There we go. So I might as well throw you over to the farewell cam and we'll wrap up.
That's a wrap. Man, that book took a long time to get through. And all I did was read the editor's notes about the various mathematicians. I didn't really engage with the actual papers themselves in very much detail at all. So, yeah, I mean, you would have to be a very impressive individual if you could read this book from cover to cover and engage with the material that's in there. Personally, I am not ready to read this book closely. I have to do a lot more work, particularly calculus, but even just trigonometry, algebra, these sorts of things. So I am not ready to read this book closely, but I do find that it helps me generally understand the scope of mathematics, and just try to get my head around what it is, what's in it, you know. So it helps me with some breadth and some perspective, but the details of it are well beyond me. So one thing that I found myself thinking about a lot, as I read through this book, is just the idea. They talk about dimensions as degrees of freedom, and like if you've got two dimensions, like an x-axis and a y-axis, and then you've got you've got a circumference. Like, say you have a radius, it's the circle at the origin, the unit circle at the origin. It goes through one on the y-axis, it goes through one on the x-axis, you know, like that. And we say that those are degrees of freedom, right? That's x and y, and and you've got this thing, and it can move through both dimensions. It moves through the Y dimension and it moves through the X dimension. But that thing, that one unit thing, what is that? When it's going through both of the dimensions at the same time, but it's bound by something that's sort of bigger. Anyway, I don't understand how like a radius, I don't know how it can move through two dimensions at the same time while keeping its length as a measure. Anyway, I just can't get my head around that. I don't understand it, and I think there might be something there. And I kind of think that's maybe, what was it, Weierstrass or one of the mathematicians in this book was looking at something along those lines. Anyway, I've obviously still got a very great deal to learn. So look, if you made it to the end of this video, well done. It took me a long time to to put it together, so you know, I'm very impressed if you managed to get through it. So I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.